to our machine learning full course from Simplilearn. Think of this as your step-by-step guide to mastering the world of machine learning, the technology that's changing how we solve problems and make smart decisions. So, what's machine learning all about? In simple terms, it's a tool that helps computers learn from data, make predictions, and make choices without needing specific instructions. It's like teaching them to recognize patterns and handle tasks automatically. So in this course, we'll start with the basics and work our way to more advanced topics like deep learning and linear algebra for machine learning. We'll also take a look at how AI and machine learning are evolving in 2024, plus go over key interview questions to help you break into this exciting field. By the end, you'll know how to use machine learning to create smart systems, analyze data, and open doors to new career paths. These skills are in high demand, so you'll be ready to make a mark in the tech world. Now, before we commence, if you want to enhance your career in AI, here's some quick info for you guys. Check out Simplilearn's postgraduate program in AI and machine learning with Purdue University and IBM. This program is perfect for aspiring AI enthusiasts and professionals looking to switch careers. Gain expertise in Gen AI, prompt engineering, ChatGPT, explainable AI, and many more. Hurry and enroll now. You can find the course link in the description box and pinned comments. Outro bhi.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify Song A. But when the choice became complicated, as in the case of Song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for Song B, if we draw a circle around the Song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called K-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of Song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro, and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams, and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency. Hence, supervised learning uses labeled data to train the model. Here the machine knew the features of the object and also the labels associated with those features. On this note, let's move to unsupervised learning and see the difference. Suppose you have cricket dataset of various players with their respective scores and the wickets taken. When we feed this dataset to the machine identifies the pattern of player performance. So it plots this data with the respective wickets on the x-axis while runs on the y-axis. While looking at the data, you will clearly see that there are 2 clusters. The one cluster are the players who scored high runs and took less wickets, while the other cluster is of the players who scored less runs but took many wickets. So here we interpret these 2 clusters as batsmen and bowlers. The important point to note here is that there were no labels of batsmen and bowlers. Hence, the learning with unlabeled data is unsupervised learning. So we saw supervised learning where the data was labeled and the unsupervised learning where the data was unlabeled. And then there is reinforcement learning, which is reward-based learning, or we can say that it works on the principle of feedback. Here, let's say you provide the system with an image of a dog and ask it to identify it. The system identifies it as a cat. So you give a negative feedback to the machine saying that it's a dog's image. The machine will learn from the feedback, and finally if it comes across any other image of a dog, it will be able to classify it correctly. That is reinforcement learning. To generalize machine learning model, let's see a flowchart. Input is given to a machine learning model, which then gives the output according to the algorithm applied. If it's right, we take the output as our final result. Else, we provide feedback to the training model and ask it to predict until it learns. I hope you've understood supervised and unsupervised learning. So let's have a quick quiz. You have to determine whether the given scenarios uses supervised or unsupervised learning. Simple, right? Scenario 1. Facebook recognizes your friend in a picture from an album of tagged photographs. Scenario 2. Netflix recommends new movies based on someone's past movie choices. Scenario 3. Analyzing bank data for suspicious transactions and flagging the fraud transactions. Think wisely and comment below your answers. Moving on, don't you sometimes wonder how is machine learning possible in today's era? Well, that's because today we have humongous data available. Everybody is online, either making a transaction or just surfing the internet, and that's generating a huge amount of data every minute. And that data, my friend, is the key to analysis. Also, the memory handling capabilities of computers have largely increased, which helps them to process such a huge amount of data at hand without any delay. And yes, computers now have great computational powers. So there are a lot of applications of machine learning out there. To name a few, machine learning is used in healthcare where diagnostics are predicted for doctors' review. The sentiment analysis that the tech giants are doing on social media is another interesting application of machine learning. Fraud detection in the finance sector and also to predict customer churn in the e-commerce sector. While booking a cab, you must have encountered surge pricing often, where it says the fare of your trip has been updated. Continue booking? Yes, please, I'm getting late for office. Well, that's an interesting machine learning model which is used by global taxi giant Uber and others, where they have differential pricing in real time based on demand, the number of cars available, bad weather, rush hour, etc. So they use the surge pricing model to ensure that those who need a cab can get one. Also, it uses predictive modeling to predict where the demand will be high, with the goal that drivers can take care of the demand and surge pricing can be minimized. Great! Hey Siri, can you remind me to book a cab at 6 p.m. today?
Okay, I'll remind you.
Thanks.
No problem.
What is machine learning? Machine learning is the science of making computers learn and act like humans by feeding data and information without being explicitly programmed. We see here we have a nice little diagram where we have our ordinary system. Your computer, nowadays you can even run a lot of this stuff on a cell phone because cell phones have advanced so much. And then with artificial intelligence and machine learning, it now takes the data and it learns from what happened before. And then it predicts what's going to come next. And then really the biggest part right now in machine learning that's going on is it improves on that. How do we find a new solution? So we go from descriptive, where it's learning about stuff and understanding how it fits together, to predicting what it's going to do, to post-scripting, coming up with a new solution. And when we're working on machine learning, there's a number of different diagrams that people have posted for what steps to go through. A lot of it might be very domain specific. So if you're working on photo identification versus language versus medical or physics, some of these are switched around a little bit or new things are put in. They're very specific to the domain. This is kind of a very general diagram. First, you want to define your objective. Very important to know what it is you're wanting to predict. Then you're going to be collecting the data. So once you've defined an objective, you need to collect the data that matches. You spend a lot of time in data science collecting data, and the next step, preparing the data. You got to make sure that your data is clean going in. There's the old saying, bad data in, bad answer out, or bad data out. And then once you've gone through and we've cleaned all this stuff coming in, then you're going to select the algorithm. Which algorithm are you going to use? You're going to train that algorithm. In this case, I think we're going to be working with SVM, the support vector machine. Then you have to test the model. Does this model work? Is this a valid model for what we're doing? And then once you've tested it, you want to run your prediction. You want to run your prediction or your choice or whatever output it's going to come up with. And then once everything is set and you've done lots of testing, then you want to go ahead and deploy the model. And remember I said domain specific. This is very general as far as the scope of doing something. A lot of models, you get halfway through and you realize that your data is missing something and you have to go collect new data because you've run a test in here someplace along the line. You're saying, hey, I'm not really getting the answers I need. So there's a lot of things that are domain specific that become part of this model. This is a very general model, but it's a very good model to start with. And we do have some basic divisions of what machine learning does that's important to know. For instance, do you want to predict a category? Well, if you're categorizing things, that's classification. For instance, whether the stock price will increase or decrease. So in other words, I'm looking for a yes-no answer. Is it going up or is it going down? And in that case, we'd actually say, is it going up? True. If it's not going up, it's false, meaning it's going down. This way, it's a yes-no, 0, 1. Do you want to predict a quantity? That's regression. So remember, we just did classification. Now we're looking at regression. These are the two major divisions in what data is doing. For instance, predicting the age of a person based on the height, weight, health, and other factors. So based on these different factors, you might guess how old a person is. And then there are a lot of domain-specific things, like do you want to detect an anomaly? That's anomaly detection. This is actually very popular right now. For instance, you want to detect money withdrawal anomalies. You want to know when someone's making a withdrawal that might not be their own account. We've actually brought this up because this is really big right now. If you're predicting the stock, whether to buy stock or not, you want to be able to know if what's going on in the stock market is an anomaly. Use a different prediction model because something else is going on. You got to pull out new information in there. Or is this just the norm? I'm going to get my normal return on my money invested. So being able to detect anomalies is very big in data science these days. Another question that comes up, which is on what we call untrained data, is do you want to discover structure in unexplored data? And that's called clustering. For instance, finding groups of customers with similar behavior given a large database of customer data containing their demographics and past buying records. And in this case, we might notice that anybody who's wearing a certain set of shoes goes shopping at certain stores, or whatever it is, they're going to make certain purchases. By having that information, it helps us to market or group people together so that we can now explore that group and find out what it is we want to market to them if you're in the marketing world. And that might also work in just about any arena. You might want to group people together, whether they're based on their different areas and investments and financial background, whether you're going to give them a loan or not. Before you even start looking at whether they're a valid customer for the bank, you might want to look at all these different areas and group them together based on unknown data. So you don't know what the data is going to tell you, but you want to cluster people together that come together. Let's take a quick detour for quiz time. Oh, my favorite. So we're going to have a couple questions here under our quiz time. And we'll be posting the answers in the part 2 of this tutorial. So let's go ahead and take a look at these quiz times questions, and hopefully you'll get them all right, and it'll get you thinking about how to process data and what's going on. Can you tell what's happening in the following cases? Of course, you're sitting there with your cup of coffee, and you have your checkbox and your pen trying to figure out what's your next step in your data science analysis. So the first one is grouping documents into different categories based on the topic and content of each document. Very big these days. You have legal documents, you have maybe it's a sports group documents, maybe you're analyzing newspaper postings. But certainly having that automated is a huge thing in today's world. B, identifying handwritten digits in images correctly. So we want to know whether they're writing an A or capital A, B, C. What are they writing out in their handwriting? C, behavior of a website indicating that the site is not working as designed. D, predicting salary of an individual based on his or her years of experience. HR hiring setup there. So stay tuned for part 2. We'll go ahead and answer these questions when we get to the part 2 of this tutorial. Or you can just simply write at the bottom and send a note to Simplilearn, and they'll follow up with you on it. Back to our regular content. And these last few bring us into the next topic, which is another way of dividing our types of machine learning, and that is with supervised, unsupervised, and reinforcement learning. Supervised learning is a method used to enable machines to classify, predict objects, problems, or situations based on labeled data fed to the machine. And in here you see we have a jumble of data with circles, triangles, and squares, and we label them. We have what's a circle, what's a triangle, what's a square, and we have our model training, and it trains it so we know the answer. Very important, when you're doing supervised learning, you already know the answer to a lot of your information coming in. So you have a huge group of data coming in, and then you have new data coming in. So we've trained our model. The model now knows the difference between a circle, a square, a triangle. And now that we've trained it, we can send in this case, a square and a circle goes in, and it predicts that the top one's a square and the next one's a circle. And you can see that this is being able to predict whether someone's going to default on a loan, because I was talking about banks earlier. Supervised learning on stock market, whether you're going to make money or not. That's always important. And if you are looking to make a fortune in the stock market, keep in mind it is very difficult to get all the data correct on the stock market. It is it fluctuates in ways really hard to predict. So it's quite a roller coaster ride. If you're running machine learning on the stock market, you start realizing you really have to dig for new data. So we have supervised learning, and if you have supervised, we should need unsupervised learning. In unsupervised learning, machine learning model finds the hidden pattern in an unlabeled data. So in this case, instead of telling it what the circle is, and what a triangle is, and what a square is, it goes in there, looks at them, and says, for whatever reason, it groups them together. Maybe it'll group it by the number of corners. And it notices that a number of them all have 3 corners, a number of them all have 4 corners, and a number of them all have no corners. And it's able to filter those through and group them together. We talked about that earlier with looking at a group of people who are out shopping. We want to group them together to find out what they have in common. And of course, once you understand what people have in common, maybe you have one of them who's a customer at your store, or you have 5 of them are customer at your store, and they have a lot in common with 5 others who are not customers at your store. How do you market to those 5 who aren't customers at your store yet? They fit the demographics of who's going to shop there, and you'd like them to shop at your store, not the one next door. Of course, this is a simplified version. You can see very easily the difference between a triangle and a circle, which might not be so easy in marketing. Reinforcement learning. Reinforcement learning is an important type of machine learning where an agent learns how to behave in an environment by performing actions and seeing the result. And we have here where in this case, a baby. It's actually great that they used an infant for this slide, because the reinforcement learning is very much in its infant stages. But it's also probably the biggest machine learning demand out there right now, or in the future. It's going to be coming up over the next few years, is reinforcement learning and how to make that work for us. And you can see here where we have our action. In the action in this one, it goes into the fire. Hopefully the baby it was just a little candle, not a giant fire pit like it looks like here. When the baby comes out, and the new state is the baby is sad and crying because they got burned on the fire. And then maybe they take another action. The baby's called the agent because it's the one taking the actions. And in this case, they didn't go into the fire. They went a different direction, and now the baby's happy and laughing and playing. Reinforcement learning is very easy to understand because that's how, as humans, that's one of the ways we learn. We learn whether it is, you burn yourself on the stove, don't do that anymore. Don't touch the stove. In the big picture, being able to have a machine learning program or an AI be able to do this is huge because now it's starting to learn how to learn. That's a big jump in the world of computer and machine learning. And we're going to go back and just kind of go back over supervised versus unsupervised learning. Understanding this is huge because this is going to come up in any project you're working on. We have in supervised learning, we have labeled data. We have direct feedback. So someone's already gone in there and said, yes, that's a triangle. No, that's not a triangle. And then you predict an outcome. So you have a nice prediction. This new set of data is coming in and we know what it's going to be. And then with unsupervised training, it's not labeled. So we really don't know what it is. There's no feedback. So we're not telling it whether it's right or wrong. We're not telling it whether it's a triangle or a square. We're not telling it to go left or right. All we do is we're finding hidden structure in the data, grouping the data together to find out what connects to each other. And then you can use these together. So imagine you have an image and you're not sure what you're looking for. So you go in and you have the unstructured data, find all these things that are connected together. And then somebody looks at those and labels them. Now you can take that labeled data and program something to predict what's in the picture. So you can see how they go back and forth, and you can start connecting all these different tools together to make a bigger picture. There are many interesting machine learning algorithms. Let's have a look at a few of them. Hopefully this gives you a little flavor of what's out there. And these are some of the most important ones that are currently being used. We'll take a look at linear regression, decision tree, and the support vector machine. Let's start with a closer look at linear regression. Linear regression is perhaps one of the most well-known and well-understood algorithms in statistics and machine learning. Linear regression is a linear model. For example, a model that assumes a linear relationship between the input variables x and the single output variable y. And you'll see this if you remember from your algebra classes, y equals mx plus c. Imagine we are predicting distance traveled y from speed x. Our linear regression model representation for this problem would be y equals m times x plus c, or distance equals m times speed plus c, where m is the coefficient and c is the y-intercept. And we're going to look at two different variations of this. First, we're going to start with time is constant. And you can see we have a bicyclist. He's got his safety gear on, thank goodness. Speed equals 10 meters per second. And so over a certain amount of time, his distance equals 36 kilometers. We have a second bicyclist who's going twice the speed, or 20 meters per second. And you can guess if he's going twice the speed and time is a constant, then he's going to go twice the distance. And that's easily to compute. 36 times 2, you get 72 kilometers. And so if you had the question of how fast would somebody who's going 3 times that speed, or 30 meters per second is, you can easily compute the distance. In our head, we can do that without needing a computer. But we want to do this for more complicated data, so it's kind of nice to compare the two, but let's just take a look at that and what that looks like in a graph. So in a linear regression model, we have our distance to the speed, and we have our m equals the VE slope of the line. And we'll notice that the line has a plus slope. And as the speed increases, distance also increases, hence the variables have a positive relationship. And so your speed of the person, which equals y equals mx plus c, distance traveled in a fixed interval of time. And we could very easily compute, either following the line or just knowing it's 3 times 10 meters per second, that this is roughly 102 kilometers distance that this third bicyclist has traveled. One of the key definitions on here is positive relationship. So the slope of the line is positive. As distance increase, so does speed increase. Let's take a look at our second example where we put distance is a constant. So we have speed equals 10 meters per second. They have a certain distance to go, and it takes them 100 seconds to travel that distance. And we have our second bicyclist who's still doing 20 meters per second. Since he's going twice the speed, we can guess that he'll cover the distance in about half the time, 50 seconds. And of course you could probably guess on the third one, 100 divided by 30, since he's going 3 times the speed, you could easily guess that this is 33.333 seconds time. When we put that into a linear regression model or a graph, if the distance is assumed to be constant, let's see the relationship between speed and time. And as time goes up, the amount of speed to go that same distance goes down. So now your m equals a minus VE slope of the line. As the speed increases, time decreases. Hence the variable has a negative relationship. Again, there's our definition. Positive relationship and negative relationship dependent on the slope of the line. And with a simple formula like this, and even a significant amount of data, let's see with the mathematical implementation of linear regression. And we'll take this data. So suppose we have this data set where we have x, y, x equals 1, 2, 3, 4, 5, standard series, and the y value is 3, 2, 2, 4, 3. When we take that and we go ahead and plot these points on a graph, you can see there's kind of a nice scattering, and you could probably eyeball a line through the middle of it. But we're going to calculate that exact line for linear regression. And the first thing we do is we come up here and we have the mean of xi. And remember, mean is basically the average. So we added 5 plus 4 plus 3 plus 2 plus 1 and divide by 5. And that simply comes out as 3. And then we'll do the same for y. We'll go ahead and add up all those numbers and divide by 5. And we end up with a mean value of y of I equals 2.8, where the xi references it's an average or means value, and the yi also equals a means value of y. And when we plot that, you'll see that we can put in the y equals 2.8 and the x equals 3 in there on our graph. We kind of gave it a little different color so you could sort it out with the dashed lines on it. And it's important to note that when we do the linear regression model should go through that dot. Now let's find our regression equation to find the best fit line. Remember, we go ahead and take our y equals mx plus c, so we're looking for m and c. So to find this equation for our data, we need to find our slope of m and our coefficient of c. And we have y equals mx plus c, where m equals the sum of x minus x average times y minus y average, or y means and x means, over the sum of x minus x means squared. That's how we get the slope of the value of the line. And we can easily do that by creating some columns here where we have x, y. Computers are really good about iterating through data, and so we can easily compute this and fill in a graph of data. And in our graph, you can easily see that if we have our x value of 1, and if you remember the xi, or the means value, is 3, 1 minus 3 equals a negative 2, and 2 minus 3 equals a negative 1, so on and so forth. And we can easily fill in the column of x minus xi, y minus yi, and then from those we can compute x minus xi squared and x minus xi times y minus yi. And you can guess it that the next step is to go ahead and sum the different columns for the answers we need. So we get a total of 10 for our x minus xi squared, and a total of 2 for x minus xi times y minus yi. And we plug those in, we get 2/10, which equals 0.2. So now we know the slope of our line equals 0.2. So we can calculate the value of c. That'd be the next step, is we need to know where it crosses the y-axis. And if you remember, I mentioned earlier that the linear regression line has to pass through the means value, the one that we showed earlier. We can just flip back up there to that graph, and you can see right here there's our means value, which is 3, x equals 3 and y equals 2.8. And since we know that value, we can simply plug that into our formula, y equals 0.2x plus c. So we plug that in, and we get 2.8 equals 0.2 times 3 plus c, and you can just solve for c. So now we know that our coefficient equals 2.2. And once we have all that, we can go ahead and plot our regression line. Y equals 0.2 times x plus 2.2. And then from this equation, we can compute new values. So let's predict the values of y using x equals 1, 2, 3, 4, 5 and plot the points. Remember, the 1, 2, 3, 4, 5 was our original x values. So now we're going to see what y thinks they are, not what they actually are. And when we plug those in, we get y of designated with y of p. You can see that x equals 1 equals 2.4, x equals 2 equals 2.6, and so on and so on. So we have our y predicted values of what we think it's going to be when we plug those numbers in. And when we plot the predicted values along with the actual values, we can see the difference. And this is one of the things that's very important with linear regression in any of these models, is to understand the error. And so we can calculate the error on all of our different values. And you can see over here we plotted x and y predict. And we draw in a little line so you can sort of see what the error looks like there between the different points. So our goal is to reduce this error. We want to minimize that error value on our linear regression model. Minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. We keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. So to recap with a very simple linear regression model, we first figure out the formula of our line through the middle, and then we slowly adjust the line to minimize the error. Keep in mind, this is a very simple formula. The math gets, even though the math is very much the same, it gets much more complex as we add in different dimensions. So this is only 2 dimensions, y equals mx plus c, but you can take that out to x, z, I, j, q, all the different features in there, and they can plot a linear regression model on all of those using the different formulas to minimize the error. Let's go ahead and take a look at decision trees, a very different way to solve problems in the linear regression model. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of a tree represents a possible decision, occurrence, or reaction. We have data which tells us if it is a good day to play golf. And if we were to open this data up in a general spreadsheet, you can see we have the outlook, whether it's rainy, overcast, sunny, temperature, hot, mild, cool, humidity, windy, and did I like to play golf that day, yes or no? So we're taking a census, and certainly I wouldn't want a computer telling me when I should go play golf or not. But you can imagine if you got up in the night before, you're trying to plan your day, and it comes up and says tomorrow would be a good day for golf for you in the morning, and not a good day in the afternoon, or something like that. This becomes very beneficial, and we see this in a lot of applications coming out now where it gives you suggestions and lets you know what would fit the match for you for the next day or the next purchase or the next whatever, next meal out. In this case, is tomorrow a good day for playing golf based on the weather coming in? And so we come up and let's determine if you should play golf when the day is sunny and windy. So we found out the forecast tomorrow is going to be sunny and windy. And suppose we draw our tree like this. We're going to have our humidity, and then we have our normal, which is if you have a normal humidity, you're going to go play golf. And if the humidity is really high, then we look at the outlook. And if the outlook is sunny, overcast, or rainy, it's going to change what you choose to do. So if you know that it's a very high humidity and it's sunny, you're probably not going to play golf because you're going to be out there miserable, fighting off the mosquitoes that are out joining you to play golf with you. Maybe if it's rainy, you probably don't want to play in the rain. But if it's slightly overcast and you get just the right shadow, that's a good day to play golf and be outside, out on the green. Now in this example, you can probably make your own tree pretty easily because it's a very simple set of data going in. But the question is, how do you know what to split? Where do you split your data? What if this is much more complicated data where it's not something that you would particularly understand? Like studying cancer, they take about 36 measurements of the cancerous cells, and then each one of those measurements represents how bulbous it is, how extended it is, how sharp the edges are. Something that as a human we would have no understanding of. So how do we decide how to split that data up? And is that the right decision tree? So that's a question that's going to come up. Is this the right decision tree? For that, we should calculate entropy and information gain. Two important vocabulary words there are the entropy and the information gain. Entropy. Entropy is a measure of randomness or impurity in the data set. Entropy should be low. So we want the chaos to be as low as possible. We don't want to look at it and be confused by the images or what's going on there with mixed data. And the information gain. It is a measure of decrease in entropy after the data set is split, also known as entropy reduction. Information gain should be high, so we want our information that we get out of the split to be as high as possible. Let's take a look at entropy from the mathematical side. In this case, we're going to denote entropy as I of P of and N, where P is the probability that you're going to play a game of golf, and N is the probability where you're not going to play the game of golf. Now, you don't really have to memorize these formulas. There's a few of them out there depending on what you're working with. But it's important to note that this is where this formula is coming from, so when you see it, you're not lost when you're running your programming, unless you're building your own decision tree code in the back. And we simply have a log squared of P over P plus N minus N over P plus N times the log squared of N of P plus N. But let's break that down and see what it actually looks like when we're computing that from the computer script side. Entropy of a target class of the data set is the whole entropy. So we have entropy play golf. And when we look at this, if we go back to the data, you can simply count how many yeses and no in our complete data set for playing golf days. In our complete set, we find we have 5 days we did play golf and 9 days we did not play golf. And so our I equals, if you add those together, 9 plus 5 is 14. And so our I equals 5 over 14 and 9 over 14. That's our P and N values that we plug into that formula. And you can go 5 over 14 equals 0.36, 9 over 14 equals 0.64. And when you do the whole equation, you get the minus 0.36 log root squared of 0.36 minus 0.64 log squared root of 0.64. And we get a set value. We get 0.94. So we now have a full entropy value for the whole set of data that we're working with. And we want to make that entropy go down. And just like we calculated the entropy out for the whole set, we can also calculate entropy for playing golf and the outlook. Is it going to be overcast or rainy or sunny? And so when we look at the entropy, we have P of sunny times E of 3 of 2. And that just comes out how many sunny days yes and how many sunny days no over the total, which is 5. Don't forget to put we'll divide that 5 out later on. Equals P overcast equals 4 comma 0 plus rainy equals 2 comma 3. And then when you do the whole setup, we have 5 over 14. Remember I said there was a total of 5? 5 over 14 times the I of 3 of 2 plus 4 over 14 times the 4 comma 0 and 514 over I of 2, 3. And so we can now compute the entropy of just the part that has to do with the forecast. And we get 0.693. Similarly, we can calculate the entropy of other predictors like temperature, humidity, and wind. And so we look at the gain outlook. How much are we going to gain from this? Entropy play golf minus entropy play golf outlook. And we can take the original 0.94 for the whole set minus the entropy of just the rainy day and temperature, and we end up with a gain of 0.247. So this is our information gain. Remember, we define entropy and we define information gain. The higher the information gain, the lower the entropy, the better. The information gain of the other three attributes can be calculated in the same way. So we have our gain for temperature equals 0.029. We have our gain for humidity equals 0.152, and our gain for a windy day equals 0.048. And if you do a quick comparison, you'll see the 0.247 is the greatest gain of information, so that's the split we want. Now let's build the decision tree. So we have the outlook. Is it going to be sunny, overcast, or rainy? That's our first split because that gives us the most information gain. And we can continue to go down the tree using the different information gains with the largest information. We can continue down the nodes of the tree where we choose the attribute with the largest information gain as the root node and then continue to split each subnode with the largest information gain that we can compute. And although it's a little bit of a tongue twister to say all that, you can see that it's a very easy to view visual model. We have our outlook, we split it 3 different directions. If the outlook is overcast, we're going to play. And then we can split those further down if we want. So if the outlook is sunny, but then it's also windy, if it's windy, we're not going to play. If it's not windy, we'll play. So we can easily build a nice decision tree to guess what we would like to do tomorrow and give us a nice recommendation for the day. So we want to know if it's a good day to play golf when it's sunny and windy. Remember the original question that came out? Tomorrow's weather report is sunny and windy. You can see by going down the tree, we go outlook sunny, outlook windy. We're not going to play golf tomorrow. So our little smartwatch pops up and says, I'm sorry, tomorrow's not a good day for golf. It's going to be sunny and windy. And if you're a huge golf fan, you might go, uh-oh, it's not a good day to play golf. We can go in and watch a golf game at home. So we'll sit in front of the TV instead of being out playing golf in the wind. Now that we looked at our decision tree, let's look at the third one of our algorithms we're investigating. Support vector machine. Support vector machine is a widely used classification algorithm. The idea of support vector machine is simple. The algorithm creates a separation line which divides the classes in the best possible manner. For example, dog or cat, disease or no disease. Suppose we have a labeled sample data which tells height and weight of males and females. A new data point arrives and we want to know whether it's going to be a male or a female. So we start by drawing a line. We draw decision lines, but if we consider decision line 1, then we will classify the individual as a male. And if we consider decision line 2, then it will be a female. So you can see this person kind of lies in the middle of the two groups, so it's a little confusing trying to figure out which line they should be under. We need to know which line divides the classes correctly, but how? The goal is to choose a hyperplane. And that is one of the key words they use when we talk about support vector machines. Choose a hyperplane with the greatest possible margin between the decision line and the nearest point within the training set. So you can see here we have our support vector, we have the 2 nearest points to it, and we draw a line between those 2 points. And the distance margin is the distance between the hyperplane and the nearest data point from either set. So we actually have a value, and it should be equally distant between the 2 points that we're comparing it to. When we draw the hyperplanes, we observe that line 1 has a maximum distance. So we observe that line 1 has a maximum distance margin, so we'll classify the new data point correctly. And our result on this one is going to be that the new data point is male. One of the reasons we call it a hyperplane versus a line is that a lot of times we're not looking at just weight and height. We might be looking at 36 different features or dimensions. And so when we cut it with a hyperplane, it's more of a three-dimensional cut in the data, or multi-dimensional. It cuts the data a certain way. And each plane continues to cut it down until we get the best fit or match. Let's understand this with the help of an example. Problem statement. I always start with a problem statement when you're going to put some code together. We're going to do some coding now. Classifying muffin and cupcake recipes using support vector machines. So the cupcake versus the muffin. Let's have a look at our data set. And we have the different recipes here. We have a muffin recipe that has so much flour. I'm not sure what measurement 55 is in, but it has 55, maybe it's ounces? But it has a certain amount of flour, a certain amount of milk, sugar, butter, egg, baking powder, vanilla, and salt. And so based on these measurements, we want to guess whether we're making a muffin or a cupcake. And you can see in this one, we don't have just two features. We don't just have height and weight as we did before between the male and female. In here, we have a number of features. In fact, in this, we're looking at 8 different features to guess whether it's a muffin or a cupcake. What's the difference between a muffin and a cupcake? Turns out muffins have more flour, while cupcakes have more butter and sugar. So basically the cupcake's a little bit more of a dessert, where the muffin's a little bit more of a fancy bread. But how do we do that in Python? How do we code that to go through recipes and figure out what the recipe is? And I really just want to say cupcakes versus muffins, like some big professional wrestling thing. Before we start in our cupcakes versus muffins, we are going to be working in Python. There's many versions of Python, many different editors. That is one of the strengths and weaknesses of Python, is it just has so much stuff attached to it, and it's one of the more popular data science programming packages you can use. In this case, we're going to go ahead and use Anaconda and Jupyter Notebook. The Anaconda Navigator has all kinds of fun tools. Once you're into the Anaconda Navigator, you can change environments. I actually have a number of environments on here. We'll be using Python 3.6 environment. So this is in Python version 3.6. Although it doesn't matter too much which version you use. I usually try to stay with the 3x because they're current, unless you have a project that's very specifically in version 2x. 2.7 I think is usually what most people use in the version 2. And then once we're in our Jupyter Notebook editor, I can go up and create a new file. And we'll just jump in here. In this case, we're doing SVM muffin versus cupcake. And then let's start with our packages for data analysis. And we almost always use there's a few very standard packages we use. We use import numpy. That's for number Python. And they usually denote it as NP. That's very common. And then we're going to import pandas as PD. And numpy deals with number arrays. There's a lot of cool things you can do with the numpy setup as far as multiplying all the values in an array, in a numpy array, data array. Pandas, I can't remember if we're using it actually in this data set. I think we do as an import. It makes a nice data frame. And the difference between a data frame and a numpy array is that a data frame is more like your Excel spreadsheet. You have columns, you have indexes, you have different ways of referencing it, easily viewing it, and there's additional features you can run on a data frame. And pandas kind of sits on numpy, so you need them both in there. And then finally, we're working with the support vector machine. So from sklearn, we're going to use the sklearn model, import SVM, support vector machine. And then as a data scientist, you should always try to visualize your data. Some data obviously is too complicated or doesn't make any sense to the human. But if it's possible, it's good to take a second look at it so that you can actually see what you're doing. Now for that, we're going to use two packages. We're going to import matplotlibary.pyplot as PLT, again very common. And we're going to import Seaborn as SNS. And we'll go ahead and set the font scale in the SNS right in our import line. That's what this semicolon followed by a line of data. We're going to set the SNS. And these are great because the Seaborn sits on top of matplotlibary, just like pandas sits on numpy. So it adds a lot more features and uses and control. We're obviously not going to get into matplotlibary and Seaborn. That'd be its own tutorial. We're really just focusing on the SVM, the support vector machine from sklearn. And since we're in Jupyter Notebook, we have to add a special line in here for our matplot library. And that's your percentage sign or ampersand matplot library in line. Now, if you're doing this in just a straight code project, a lot of times I use like Notepad++, and I'll run it from there. You don't have to have that line in there because it'll just pop up as its own window on your computer, depending on how your computer's set up. Because we're running this in the Jupyter Notebook as a browser setup, this tells it to display all of our graphics right below on the page. So that's what that line is for. I remember the first time I ran this, I didn't know that, and I had to go look that up years ago. It was quite a headache. So matplot library inline is just because we're running this on the web setup. And we can go ahead and run this, make sure all our modules are in. They're all imported, which is great. If you don't have them import, you'll need to go ahead and pip, use the PIP or however you do it. There's a lot of other install packages out there, although pip is the most common. And you have to make sure these are all installed on your Python setup. The next step, of course, is we got to look at the data. You can't run a model for predicting data if you don't have actual data. So to do that, let me go ahead and open this up and take a look. And we have our cupcakes versus muffins. And it's a CSV file, or .csv, meaning that it's comma-separated variable. And it's going to open it up in a nice spreadsheet for me. And you can see up here we have the type. We have muffin, 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 cupcake, cupcake, cupcake. And then it's broken up into flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. So what we can do is we can go ahead and look at this data also in our Python. Let us create a variable recipes equals, we're going to use our pandas module, .read CSV. Remember, it was a comma-separated variable. And the file name happened to be cupcakes versus muffins. Oops, I got double brackets there. Do it this way. There we go. Cupcakes versus muffins. Because the program I loaded, or the place I saved this particular Python program is in the same folder, we can get by with just the file name. But remember, if you're storing it in a different location, you have to also put down the full path on there. And then because we're in pandas, we're going to go ahead and you can actually, inline you can do this, but let me do the full print. You can just type in recipes.head in the Jupyter Notebook. But if you're running in code in a different script, you need to go ahead and type out the whole print recipes.head. And pandas knows that that's going to do the first 5 lines of data. And if we flip back on over to the spreadsheet where we opened up our CSV file, you can see where it starts on line 2. This one calls it 0, and then 2, 3, 4, 5, 6 is going to match. Go and close that out because we don't need that anymore. And it always starts at 0. And it automatically indexes it since we didn't tell it to use an index in here. So that's the index number for the left-hand side. And it automatically took the top row as labels. So pandas using it to read a CSV is just really slick and fast. One of the reasons we love our pandas. Not just because they're cute and cuddly teddy bears. And let's go ahead and plot our data. And I'm not going to plot all of it. I'm just going to plot the sugar and flour. Now, obviously, you can see where they get really complicated if we have tons of different features. And so you'll break them up and maybe look at just 2 of them at a time to see how they connect. And to plot them, we're going to go ahead and use Seaborn. So that's our SNS. And the command for that is sns.lmplot. And then the 2 different variables I'm going to plot is flour and sugar. Data equals recipes. The hue equals type. And this is a lot of fun because it knows that this is pandas coming in. So this is one of the powerful things about pandas mixed with Seaborn in doing graphing. And then we're going to use a palette set 1. There's a lot of different sets in there. You can go look them up for Seaborn. We'll do a fit regular equals false, so we're not really trying to fit anything. And it's a scatter, KWS. A lot of these settings you can look up in Seaborn. Half of these you could probably leave off when you run them. Somebody played with this and found out that these were the best settings for doing a Seaborn plot. And let's go ahead and run that. And because it does it inline, it just puts it right on the page. And you can see right here that just based on sugar and flour alone, there's a definite split. And we use these models because you can actually look at it and say, hey, if I drew a line right between the middle of the blue dots and the red dots, we'd be able to do an SVM and a hyperplane right there in the middle. Then the next step is to format or pre-process our data. And we're going to break that up into two parts. We need a type label, and remember, we're going to decide whether it's a muffin or a cupcake. Well, a computer doesn't know muffin or cupcake, it knows 0 and 1. So, what we're going to do is we're going to create a type label, and from this we'll create a numpy array np where, and this is where we can do some logic. We take our recipes from our panda, and wherever type equals muffin, it's going to be 0. And then if it doesn't equal muffin, which is cupcakes, it's going to be 1. So we create our type label. This is the answer. So when we're doing our training model, remember we have to have a training data. This is what we're going to train it with, is that it's 0 or 1. It's a muffin or it's not. And then we're going to create our recipe features. And if you remember correctly from right up here, the first column is type. So we really don't need the type column because that's our muffin or cupcake. And in pandas, we can easily sort that out. We take our value recipes dot columns. That's a pandas function built into pandas. Dot values, converting them to values. So it's just the column titles going across the top. And we don't want the first one. So what we do is, since it always starts at 0, we want 1 colon till the end. And then we want to go ahead and make this a list, and this converts it to a list of strings. And then we can go ahead and just take a look and see what we're looking at for the features, make sure it looks right. Let me go ahead and run that. And I forgot the S on recipes, so we'll go ahead and add the S in there and then run that. And we can see we have flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. And that matches what we have up here, right where we printed out everything but the type. So we have our features and we have our label. Now, the recipe features is just the titles of the columns, and we actually need the ingredients. And at this point, we have a couple options. One, we could run it over all the ingredients. And when you're doing this, usually you do, but for our example, we want to limit it so you can easily see what's going on. Because if we did all the ingredients, we have, that's what, 7, 8 different hyperplanes that would be built into it. We only want to look at one so you can see what the SVM is doing. And so we'll take our recipes and we'll do just flour and sugar. Again, you can replace that with your recipe features and do all of them, but we're going to do just flour and sugar, and we're going to convert that to values. We don't need to make a list out of it because it's not string values. These are actual values on there. And we can go ahead and just print ingredients, and you can see what that looks like. And so we have just the amount of flour and sugar, just the 2 sets of plots. And just for fun, let's go ahead and take this over here and take our recipe features. And so if we decided to use all the recipe features, you'll see that it makes a nice column of different data. So it just strips out all the labels and everything. We just have just the values. But because we want to be able to view this easily in a plot later on, we'll go ahead and take that and just do flour and sugar. And we'll run that and you'll see it's just the 2 columns. So the next step is to go ahead and fit our model. We'll go ahead and just call it model. And it's a SVM. We're using a package called SVC. And in this case, we're going to go ahead and set the kernel equals linear. So it's using a specific setup on there. And if we go to the reference on their website for the SVM, you'll see that there's 8 of them here. 3 of them are for regression, 3 are for classification, the SVC, support vector classification, is probably one of the most commonly used. And then there's also one for detecting outliers, and another one that has to do with something a little bit more specific on the model. But SVC and SVR are the two most commonly used, standing for support vector classifier and support vector regression. Remember, regression is an actual value, a float value or whatever you're trying to work on, and SVC is a classifier, so it's a yes, no, true, false. But for this, we want to know 0, 1, Muffin, Cupcake. We go ahead and create our model, and once we have our model created, we're going to do model.fit, and this is very common, especially in the sklearn. All their models are followed with the fit command. And what we put into the fit, what we're training with it, is we're putting in the ingredients, which in this case we limited to just flour and sugar, and the type label. Is it a muffin or a cupcake? Now, in more complicated data science series, you'd want to split into, we won't get into that today, we split it into training data and test data, and they even do something where they split it into thirds, where a third is used for where you switch between which one's training and test. There's all kinds of things that go into that, and it gets very complicated when you get to the higher end. Not overly complicated, just an extra step which we're not going to do today because this is a very simple set of data. And let's go ahead and run this, and now we have our model fit. And I got an error here, so let me fix that real quick. It's capital SVC, it turns out. I did it lowercase. Support vector classifier. There we go. Let's go ahead and run that. And you'll see it comes up with all this information that it prints out automatically. These are the defaults of the model. You notice that we changed the kernel to linear. And there's our kernel linear on the printout. And there's other different settings you can mess with. We're going to just leave that alone for right now. For this, we don't really need to mess with any of those. So next, we're going to dig a little bit into our newly trained model. And we're going to do this so we can show you on a graph. And let's go ahead and get the separating. And we're going to say, we're going to use a W for our variable on here. We're going to do model.coefficient _0. So what the heck is that? Again, we're digging into the model. So we've already got a prediction and a train. This is the math behind it that we're looking at right now. And so the W is going to represent two different coefficients. And if you remember, we had y equals mx plus c. So these coefficients are connected to that, but in two-dimensional. It's a plane. We don't want to spend too much time on this because you can get lost in the confusion of the math. So if you're a math whiz, this is great. You can go through here and you'll see that we have a equals minus w of 0 over w of 1. Remember, there's two different values there. And that's basically the slope that we're generating. And then we're going to build an XX. What is XX? We're going to set it up to a numpy array. There's our np dot line space. So we're creating a line of values between 30 and 60. So it just creates a set of numbers for x. And then if you remember correctly, we have our formula, y equals the slope times x plus the intercept. Well, to make this work, we can do this as yy equals the slope times each value in that array. That's the neat thing about numpy. So when I do a times xx, which is a whole numpy array of values, it multiplies a across all of them. And then it takes those same values and we subtract the model intercept. That's your, remember we had mx plus c, so that'd be the c from the formula, y equals mx plus c. And that's where all these numbers come from. A little bit confusing because it's digging out of these different arrays. And then what we want to do is we're going to take this and we're going to go ahead and plot it. So plot the parallels to separating hyperplane that pass through the support vectors. And so we're going to create B equals a model support vectors, pulling our support vectors out there. Here's our YY, which we now know is a set of data. And we have we're going to create YY down equals A times XX plus B1 minus A times B0. And then model support vector B is going to be set that to a new value, the -1 setup. And yy up equals a times xx plus b1 minus a times b0. And we can go ahead and just run this to load these variables up. If you want to understand a little bit more of what's going on, you can see if we print yy, we just run that, you can see it's an array. This is a line. It's going to have, in this case, between 30 and 60, so it's going to be 30 variables in here. And the same thing with yy up, yy down. And we'll plot those in just a minute on a graph so you can see what those look like. You just go ahead and delete that out of here and run that so it loads up the variables. Nice clean slate. I'm just going to copy this from before. Remember this, our SNS, our seaborn plot, LM plot, flour, sugar. And I'll just go ahead and run that real quick so you can see remember what that looks like. It's just a straight graph on there. And then one of the neat things is because seaborn sits on top of pyplot, we can do the pyplot for the line going through. And that is simply plt.plot. And that's our xx and yy, our two corresponding values, xy. And then somebody played with this to figure out that the line width equals 2 and the color black would look nice. So let's go ahead and run this whole thing with the pyplot on there. And you can see when we do this, it's just doing flour and sugar on here. Corresponding line between the sugar and the flour and the muffin versus cupcake. And then we generated the support vectors, the yy down and yy up. So let's take a look and see what that looks like. So we'll do our PL plot. And again, this is all against xx, our x value. But this time we have yy down. And let's do something a little fun with this. We can put in a k dash dash. That just tells it to make it a dotted line. And if we're going to do the down one, we also want to do the up one. So here's our yy up. And when we run that, it adds both sets of line. And so here's our support, and this is what you expect. You expect these two lines to go through the nearest data point. So the dashed lines go through the nearest muffin and the nearest cupcake when it's plotting it. And then your SVM goes right down the middle. So it gives it a nice split in our data, and you can see how easy it is to see, based just on sugar and flour, which one's a muffin or a cupcake. Let's go ahead and create a function to predict muffin or cupcake. I've got my recipes I pulled off the internet, and I want to see the difference between a muffin or a cupcake. And so we need a function to push that through. And we'll create a function with def. And let's call it muffin or cupcake. And remember, we're just doing flour and sugar today. We're not doing all the ingredients. And that actually is a pretty good split. You really don't need all the ingredients to know it's flour and sugar. And let's go ahead and do an if-else statement. So if model predict is of flour and sugar equals 0. So we take our model and we run a predict. It's very common in sklearn where you have a dot predict. You put the data in, and it's going to return a value. In this case, if it equals 0, then print you're looking at a muffin recipe. Else, if it's not 0, that means it's 1, then you're looking at a cupcake recipe. That's pretty straightforward for a function, or def for definition. DEF is how you do that in Python. And of course, if you're going to create a function, you should run something in it. And so let's run a cupcake, and we're going to send it values 50 and 20, a muffin or a cupcake. I don't know what it is. And let's run this and just see what it gives us. And it says, oh, it's a muffin. You're looking at a muffin recipe. So it very easily predicts whether we're looking at a muffin or a cupcake recipe. Let's plot this. There we go. Plot this on the graph so we can see what that actually looks like. And I'm just going to copy it and paste it from below where we're plotting all the points in there. So this is nothing different than what we did before. If I run it, you'll see it has all the points and the lines on there. And what we want to do is we want to add another point. And we'll do PLT plot. And if you remember correctly, we did, for our test, we did 50 and 20. And then somebody went in here and decided we'll do YO for yellow, or it's kind of an orangish yellow color is going to come out. Marker size 9. Those are settings you can play with. Somebody else played with them to come up with the right setup so it looks good. And you can see there it is graphed, clearly a muffin. In this case, in Cupcakes versus Muffins, the muffin has won. And if you'd like to do your own Muffin Cupcake Contender series, you certainly can send a note down below, and the team at Simplilearn will send you over the data they use for the Muffin and Cupcake. And that's true of any of the data. We didn't actually run a plot on it earlier. We had men versus women. You can also request that information to run it on your data setup so you can test that out. So to go back over our setup, we went ahead for our support vector machine code. We did a predict 40 parts flour, 20 parts sugar. I think it was different than the one we did, whether it's a muffin or a cupcake. Hence, we have built a classifier using SVM, which is able to classify if a recipe is of a cupcake or a muffin, which wraps up our cupcake versus muffin.
The term generative AI has emerged seemingly out of nowhere in recent months, with a notable surge in interest according to Google Trends even within the past year. The spike in curiosity can be attributed to the introduction of generative models such as DALL-E 2, BARD, and ChatGPT. However, what does generative AI entail? As a part of our introductory series on generative AI, this video will provide a comprehensive overview of a subject starting from the basics. The explanation will cater to all levels of familiarity, ensuring that viewers gain a better understanding of how this technology operates and its growing integration to our daily lives. Generative AI is, after all, a tool that is based on artificial intelligence. A professional who seeks to switch careers with AI by learning from the experts. What is generative AI? Generative AI is a form of artificial intelligence possesses the capability to generate a wide range of content, including text, visual, audio, and synthetic data. The recent excitement surrounding generative AI stems from the user-friendly interfaces that allow users to effortlessly create high-quality text, graphics, and video within a second. Now moving forward, let's see how does generative AI works. Generative AI begins a prompt which can take form of text, image, video, design, audio, musical notes, or any input that AI system can process. Various AI algorithms that generate new content in response to the given prompt. This content can range from essay and problem solution to realistic, created using images or audio of a person. In the early stages of generative AI, utilizing the technology involved submitting data through an API or a complex process. Developers need to acquaint themselves with a specialized tool and writing application using programming language like Python. Some of the recent and fully operational generative AIs are Google Bard, DALL-E, OpenAI ChatGPT, Microsoft Bing, and many more. So now let's discuss ChatGPT, DALL-E, and Bard, which are the most popular generative AI interfaces. So first is DALL-E 2, which was developed using OpenAI GPT implementation in 2021. Exemplify a multimodal AI application. It has been trained on a vast dataset of images and their corresponding textual description. DALL-E is capable of establishing connection between various media forms such as vision, text, audio. It specifically links the meaning of words to visual elements. OpenAI introduced an enhanced version called DALL-E 2 in 2022, which empowers users to generate imagery in multiple styles based on their prompts. And the next one is ChatGPT. In November 2022, ChatGPT, an AI-powered chatbot built on OpenAI GPT 3.5 implementation, gained immense popularity worldwide. OpenAI enabled users to interact with and fine-tune the chatbot's text response through a chat interface with interactive feedback, unlike earlier version of GPT that was solely accessible via an API. ChatGPT brought a more interactive experience. On March 14, 2023, OpenAI released GPT-4. ChatGPT integrates the conversational history with a user, making a genuine dialogue. Microsoft, impressed by the success of new ChatGPT interface, announced a substantial investment in OpenAI and integrated a version of GPT into its Bing search engine. And the next one is Bard, Google Bard. Google was also an earlier forerunner in advancing transformer AI techniques for language processing, protein analysis, and other content types. It made some of these models open source for researchers but were not made available through a public interface. In response to Microsoft integration of GPT into Bing, Google hurriedly launched a public-facing chatbot named Google Bard. Bard's debut was met by an error when the language model incorrectly claimed that the web telescope was the first to discover a planet in a foreign solar system. As a consequence, Google's stock price suffered a significant decline. Meanwhile, Microsoft implementation of ChatGPT and GPT-powered system also faced criticism for producing inaccurate results and displaying erratic behavior in their early iteration. So, moving forward, let's see what are the use cases of generative AI. Generative AI has broad applicability and can be employed across a wide range of use cases to generate diverse forms of content. Recent advancements like GPT have made this technology more accessible and customizable for various applications. Some notable use cases for generative AI are as follows. Chatbot implementation. Generative AI can be utilized to develop chatbots for customer service and technical support, enhancing interaction with users and providing efficient assistance. The second one is language dubbing enhancement. In the realm of movies and educational content, generative AI can contribute to improving dubbing in different languages, ensuring accurate and high quality translation. And the third one is content writing. Generative AI can assist in writing email responses, dating profiles, resumes, and term papers, offering valuable support and generating customized content tailored to specific requirements. And the fourth one is art generation. Leveraging generative AI, artists can create photorealistic artwork in various styles, enabling the exploration of new artistic expression and enhancing creativity. The fifth one is product demonstration videos. Generative AI can enhance product demonstration video, making them more engaging, visually appealing, and effective in showcasing product features and benefits. So generative AI versatility allows it to employed in many other applications, making it a valuable tool for content creation and enhancing user experience across diverse domains. So after seeing use cases of generative AI, let's see what are the benefits of generative AI. So generative AI offers extensive application across various business domains, simplifying the interpretation and comprehension of existing content while also enabling the automated creation of a new content. Developers are actively exploring ways to leverage generative AI in order to enhance the optimize existing workflows and even to reshape workflows entirely to harness the potential of technology fully. Implementing generative AI can bring numerous benefits, including automated content creation. Generative AI can automate the manual process of writing content, saving time and effort by generating text or other form of content. The next one is efficient email response. Responding to emails can be made more efficient with generative AI, reducing the effort required and improving response time. And the third one is enhanced technical support. Generative AI can improve responses to specific technical queries, providing accurate and helpful information to users or customers. And the fourth one is realistic person generation. By leveraging generative AI, it becomes possible to create realistic representation of people, enabling applications like virtual characters or avatars. And the fifth one is coherent information summarization. Generative AI can summarize complex information into a coherent narrative, distilling key points and making it easier to understand and communicate complex concepts. The implementation of generative AI offers a range of potential benefits, streamlining process and enhancing content creation in various areas of business operation. So after seeing advantages of generative AI, let's move forward and see what are the limitations of generative AI. Early implementation of generative AI serve as vivid examples highlighting the numerous limitations associated with this technology. Several challenges arise from the specific approaches employed to implement various use cases. For instance, while a summary of a complex topic may be more reader-friendly than explanation incorporating multiple supporting sources, the ease of readability comes at the expense of transparent identifying the information sources. So the first one is, when implementing or utilizing a generative AI application, it is important to consider the following limitation. I repeat, the first one is lack of source identification. Generative AI does not always provide clear identification of content source, making it difficult to trace and verify origin of the information. The second one is assessment of bias. Assessing the bias of original sources used generative AI can be challenging, as it may be difficult to determine the underlying perspective or agenda of the data utilized in the training process. The third one is difficulty in identifying inaccurate information. Generative AI can generate realistic content, making identifying inaccuracy or falsehoods within the generated output harder. And the fourth one is adaptability to a new circumstances. Understanding how to fine-tune generative AI for a new circumstances or specific context can be complex, requiring careful consideration and expertise to achieve desired result. And the fifth one is glossing over bias, prejudice, and hatred. Generative AI results may amplify or perpetuate biases, prejudices, or hateful content present in the training data, requiring vigilant scrutiny to prevent such issues. So, awareness of these limitations is crucial when implementing or utilizing generative AI, as it helps users and developers critically evaluate and mitigate potential risks and challenges associated with the technology. So, future of generative AI. Furthermore, advances in AI development platforms will contribute to the accelerated progress of research and development in the realm of generative AI. The development will encompass various domains such as text, images, videos, 3D content, drugs, supply chains, logistic and business processes. While the current standalone tools are impressive, the true transformative impact generative AI will realize while these capabilities are seemingly integrated into the existing tools with regular use.
As we know, in 2024, AI and ML are evolving at lightning speed. AI tools like ChatGPT, Google Gemini, and Apple cutting-edge AI are transforming our world. ChatGPT is changing customer service, language translation, and even creative content, whereas Google Gemini is pushing the boundaries of AI, enhancing search experience and making information access smarter and more intuitive. Apple's AI, with innovations like Siri and Apple's intelligence, is taking user experience to the next level with a smarter personal assistant, enhanced device performance, and top-notch privacy features. With these advancements, these technologies are driving a huge demand for AI engineers and ML engineers. Companies across the globe are eager to integrate these advanced solutions to boost efficiency, personalize customer experience, and innovate in the fields like healthcare, logistics, and in many others. So the opportunities in AI and ML field are endless and incredibly exciting. So imagine being a part of this revolutionary wave, shaping the future with your skills. So in this video, we will show you exactly how to get there. We will cover the essential skills you need to learn, the best learning path, exciting hands-on project, and the hottest career opportunities. Whether you are just starting out to looking to advance your career, this roadmap will guide you to successfully become AI and ML engineer. So before moving forward, let me give you a quick information. As the demand for machine learning professionals keep increasing, it's crucial for aspiring individuals to have a clear roadmap to navigate their learning journey. So without any further ado, let's get started. So how this machine learning roadmap will help you? This machine learning roadmap offers a clear and structured path to mastering machine learning. By following this roadmap, you will not only gain valuable knowledge, but also develop a mindset geared towards innovation and adaptability. So what is machine learning and AI? Imagine a computer that learns from data like a student. That's machine learning. And machine learning is a subset of artificial intelligence, AI, that enables computer to learn from the data and make predictions or decisions without being explicitly programmed. It uses algorithm and stat models to improve performance or specific tasks through experience or data input. So artificial intelligence, on the other hand, covers a broader scope and involves developing computer systems that perform tasks typically requiring human intelligence. So machine learning is a crucial component of AI, providing the capability to learn and adapt from the data. So now let's move forward and see the steps for AI ML roadmap. So step-by-step machine learning roadmap. So this step-by-step machine learning roadmap guides you through mastering ML, a vital branch of AI, typically over 7 months to a year. So depending on your background, so start with prerequisites like programming Python R, stat, and linear algebra. Progress through understanding data processing, learning algorithms, and model evaluation and optimization. So this structured approach combined with hands-on projects will solidify your ML expertise while preparing you for the advanced topics and machine learning applications in the dynamic field. So now let's get started. This step 1, mastering mathematics. So to excel in machine learning, a strong foundation in mathematics is essential. So focus on the following areas. The first one is linear algebra and calculus. So linear algebra is the backbone of many machine learning algorithms. It helps you understand how each algorithm works. Whereas calculus is crucial for optimizing algorithms used in machine learning. Key concepts include like vectors, matrix, linear equations, eigenvalues, differentiation, integration, and gradient descent. The second one is probability and statistics. So probability and stats are fundamentals for analyzing data and making prediction. So here are some important topics like probability distribution, descriptive stat, hypothesis testing, regression analysis, and Bayesian stat. So moving forward, step 2, developing programming skills. Proficiency in programming is essential. Focus on Python and R, the top language for machine learning. The first one, Python. Python is popular due to its simplicity and extensive library like NumPy, Pandas, Scikit-learn. So it's great for both beginners and experts. The second one is R programming. R is excellent for statistical analysis and data visualization. Platforms like Simplilearn offer specialized courses in the R programming. The third, important Python libraries. Learn libraries like NumPy for numerical operations, Pandas for data manipulation, Matplotlib and Seaborn for data visualization, and Scikit-learn for machine learning. The third one, exploring core machine learning ML algorithms. So once you have got a good handle on math and programming, it's time to learn core machine learning algorithms. So understanding these will help you solve real-world problems. So here are some key algorithms to explore. The first one is unsupervised learning algorithm. Explore clustering, that is K-means clustering, and dimensional reduction, that is PCA, for understanding patterns in unlabeled data. The second one is supervised learning algorithms. Learn regression for continuous outcomes and classification for discrete labels, covering methods like linear regression, logistic regression, k-nearest neighbor, and support vector machine, SVMs. And the third one is model evaluation and validation. Understand evaluation metrics like accuracy, precision, recall, and F1 score. Learn cross-validation and performance metrics to assess model performance. And you can also learn other important machine learning algorithms like reinforcement learning, gradient descent, and algorithm for slope understanding. Step 4. Learn advanced topic in machine learning. So as you advance in machine learning, the journey, it's important to delve into more advanced topics. So these areas will deepen your understanding and help you tackle complex problems. So here are some key topics to focus on. The first one is deep learning and neural networks. The second is ensemble learning technique. Third one is generative models and adversarial learning. The fourth one is recommendation system and collaborative filtering. The last one is time series analysis and forecasting. So for step 5, there is learn deployment. So you have to learn how to deploy models using Flask, Django, cloud services like AWS, Azure, GCP, then Docker and Kubernetes. So deployment skills are crucial for making your model accessible and usable in real-world applications. So moving forward, let's see some machine learning projects. So work on real-world projects to apply your knowledge. Focus on data collection, preparation, and capstone project in image recognition NLP. And there is one more, predictive modeling and anomaly detection. So practical experience is the key to solidifying your skills. Step 7, continuous learning and exploration. So stay updated with the latest development by the following industry leaders, engaging in online communities, and working on your personal projects. So pursue advanced learning through courses and certification to keep your skills sharp. So now moving forward, let's see machine learning career opportunities with salary. So the job market for machine learning professional is booming. The average annual salary for machine learning engineers can vary based on location, experience, and company. So here are some roles like machine learning engineer, data scientist, NLP engineer, computer vision engineer, and AI ML researcher. So let's see how much they earn. So the first one, machine learning engineer. In US, they earn around $153,000, and in India, they earn around 11 lakhs per annum. The second is data scientist. They earn in US around $157,000, and in India, they earn around 12 lakhs per annum. The third one is NLP engineer. In US, they earn around $107,000, and in India, they earn around 7 lakh per annum. The fourth one, computer vision engineer. They earn around $126,000 in the US, and in India, they earn around 6.5 lakh per annum. The last one, AI and ML researcher. They earn around $130,000 in the US and 9 lakh per annum in India. So note that these figures can vary on the website to website and changes frequently. The machine learning roadmap provides a structured guide to help you navigate this dynamic field. By following this step-by-step guide and continuously honing your skills, you can embark on a successful career in machine learning. Embrace the challenge, stay curious, and equip yourself with the necessary knowledge and expertise to thrive in this ever-evolving domain. So what is deep learning? Deep learning is a subset of machine learning, which itself is a branch of artificial intelligence. Unlike traditional machine learning models, which require manual feature extraction, Deep learning models automatically discovers representation from raw data. So this is made possible through neural networks, particularly deep neural networks, which consist of multiple layers of interconnected nodes. So these neural networks are inspired by the structure and the function of human brain. Each layer in the network transforms the input data into more abstract and composite representation. For instance, in image recognition, the initial layer might detect simple features like edges and textures, while the deeper layer recognizes more complex structure like shapes and objects. So one of the key advantages of deep learning is its ability to handle large amount of unstructured data, such as images, audios, and text, making it extremely powerful for various applications. So stay tuned as we delve deeper into how these neural networks are trained, the types of deep learning models, and some exciting applications that are shaping our future. Types of deep learning. Deep learning AI can be applied supervised, unsupervised, and reinforcement machine learning using various methods for each. The first one, supervised machine learning. In supervised learning, the neural network learns to make prediction or classify that data using labeled datasets. Both input features and target variables are provided, and the network learns by minimizing the error between its prediction and the actual targets. A process called backpropagation. CNN and RNN are the common deep learning algorithms used for tasks like image classification, sentiment analysis, and language translation. The second one, unsupervised machine learning. In unsupervised machine learning, the neural network discovers patterns or clusters in unlabeled datasets without target variables. It identifies hidden pattern or relationship within the data. Algorithms like autoencoders and generative models are used for tasks such as clustering, dimensionality reduction, and anomaly detection. The third one, reinforcement machine learning. In this, an agent learns to make decisions in an environment to maximize a reward signal. The agent takes action, observes the records, and learns policies to maximize cumulative rewards over time. Deep reinforcement learning algorithms like deep Q networks and deep deterministic polygradient are used for tasks such as robotics and gameplay. Moving forward, let's see what are the artificial neural networks. Artificial neural networks, ANNs, inspired by the structure and the function of human neurons, consist of interconnected layers of artificial neurals or units. The input layer receives data from the external resources and it passes to one or more hidden layers. Each neuron in these layers computes a weighted sum of inputs and transfers the result to the next layer. During training, the weight of these connections are adjusted to optimize the network's performance. A fully connected artificial neural network includes an input layer or more hidden layers and an output layer. Each neuron in a hidden layer receives input from the previous layer and sends its output to the next layer. So this process continues until the final output layer produces a network response. So moving forward, let's see types of neural networks. So deep learning models can automatically learn features from data, making them ideal to tasks like image recognition, speech recognition, and natural language processing. So the most common architecture in deep learnings are the first one, feed-forward neural network, FNNs. So these are the simplest type of neural network where information flows linearly from the input to the output. They are widely used for tasks such as image classification, speech recognition, and natural language processing, NLP. The second one, convolutional neural network, designed specifically for image and video recognition. CNNs automatically learn features from images, making them ideal for image classification, object detection, and image segmentation. The third one, recurrent neural networks, RNNs, are specialized for processing sequential data time series and natural language. They maintain an internal state to capture information from previous input, making them suitable for tasks such as speech recognition, NLP, and language translation. So now let's move forward and see some deep learning application. The first one is autonomous vehicle. Deep learning is changing the development of self-driving car. Algorithms like CNNs process data from sensors and cameras to detect objects, recognize traffic signs, and make driving decisions in real time, enhancing safety and efficiency on the road. The second one is healthcare diagnostic. Deep learning models are being used to analyze medical images such as X-rays, MRIs, and CT scans with high accuracy. They help in early detection and diagnosis of diseases like cancer, improving treatment outcomes and saving lives. The third one is NLP. Recent advancement in NLP powered by deep learning models like Transformer, ChatGPT have led to more sophisticated and human-like text generation, translation, and sentiment analysis. So applications include virtual assistant, chatbots, and automated customer service. The fourth one, deepfake technology. So deep learning techniques are used to create highly realistic synthetic media known as deepfakes. While this technology has entertainment and creative application, it also raises ethical concern regarding misinformation and digital manipulation. The fifth one, predictive maintenance. In industries like manufacturing and aviation, deep learning models predict equipment failures before they occur by analyzing sensor data. Their proactive approach reduces downtime, lowers maintenance costs, and improves operational efficiency. So now let's move forward and see some advantages and disadvantages of deep learning. So first one is high computational requirements. So deep learning requires significant data and computational resources for training, whereas advantage is high accuracy, achieves state-of-the-art performance in tasks like image recognition and natural language processing. Whereas deep learning needs large labeled datasets, often require extensive labeled dataset for training, which can be costly and time consuming together. So second advantage of deep learning is automated feature engineering. Automatically discovers and learn relevant features from data without manual intervention. The third disadvantage is overfitting. So deep learning can overfit to training data, leading to poor performance on new unseen data. Whereas the third deep learning advantage is scalability. So deep learning can handle large complex dataset and learn from massive amount of data. So in conclusion, deep learning is a transformative leap in AI, mimicking human neural networks. It has changed healthcare, finance, autonomous vehicles, and NLP.
So welcome to the demo part of best AI coding tools for 2025. So in this, I will show you top 5 coding AI tools, right? First, we will start with ChatGPT. So I'm not talking about the simple one because simple one is everyone know, but recently ChatGPT launched GPT-4o with Canvas. So we will open this. Here I will write, give me login page code using HTML, CSS and CSS. Okay. See the magic. See, like this. So right now it's in beta version. Okay. So I guess those who have paid version, so they can, use this. So now, see here. What if I want to change these background color, only particular background color? I don't want to change all the code, but I just want to change these color, H2 color, or you can say display, it will block or something else. Okay, I want to change the padding of this particular class, right? So here what I will do, I will select this, and when pop-up will come, ask ChatGPT. So now you can just, here you can write, please change background color to blue. I don't know which color is that, but again I want to change it to blue. See, it will change only the background color. See, rest will be the same, right? See here, edited. So this is the best upgrade I can see with ChatGPT with coding, for coding. Okay, so let's see one more. Okay, so here what I will do, let's change the padding. Okay, here I will write increase, what is this, border radius, border radius. Okay, see here is 8, it will increase. See, it did 16, and the rest all is same. So this is one tool. Okay, ChatGPT 4o with Canvas. The second is Gemini. Okay, I'm not going to use Gemini into Gemini prompt, but I will open one thing, Google Colab. Okay, so here is Google Colab, and I will open new notebook. So here you will get Gemini inbuilt. Here you can see Gemini inbuilt. But first you have to log in. See, start coding or generate with AI. If I'll click on generate with AI, so it will ask me like this. So I will write, okay, give me code to find odd and even in C++. Okay, you can write anything. So I will write enter. See, it's generating and code is here in minute of seconds. Okay, if I will write in Java, the code is here in minute of seconds. Okay, in seconds it will give you. So this is the second. You can use Gemini as well in the while giving prompt here, or you can open Gemini, right? You can open Gemini as well, but it's better if you are using Gemini for code, so use in Google Colab. Why? Because you can use or you can run code directly. Okay, let's try to run it. Let me run it. See, it's running. Wait. Okay, some error is there. Invalid syntax. Why? Okay, why it's giving error? Because I opened this, notebook only. Okay, this is the Python notebook, right? That's why it's giving error. Okay, let me run this in Python. Oh my god. See, it's running nicely in Python because it's Python notebook. Okay, so these are the odd numbers and these are the even numbers, and numbers are already given here, right? So this is the second one, and the third one is Claude. Okay, I have to log in it first. So here, so in Claude as well, we have many models. You can say Claude 3.5 Sonnet and Haiku is there, and some more things are there. Okay, and here I will write. Okay, please give me code to make snake game in Python. Okay, so see, now it's generating. So some tools are to generate code from the scratch, and some tools are the suggestions tools. Okay, we will see the next one, the suggestion tool, what I am talking about. Okay, so here all the details for this particular code, and yeah, so third model is Claude. So this is how you can use Claude. So there are many models of Claude, like I told you already, 3.5 Sonnet is there, Haiku is there, and there is one more. Okay, where I can't see. Okay, but again, it's it's paid thing. Okay, and the next is Codium. Okay, so I will show you Codium. This is the Codium, right? This Codium is this. So I have already installed this Codium into my VS Code. Okay, see, Codium generate control plus I. See, this is the command. Just write. This is again Python one. Okay, give me code to find the prime numbers in Python. Okay, just submit, and the code will be here. See, okay, code will be here. Or if you write here, find the prime numbers. See, it will give you suggestion. Okay, if I will write def, define prime, and then see, again suggestion. If I will write this, again suggestion, then yeah, the code is complete. Okay, so it will give you suggestions as well. Okay, this is a Codium. So just like Codium, so this is our fourth tool, Codium, and just like Codium, there is one amazing tool which is called AWS Q Developer, Amazon Q Developer. This is the amazing tool. Okay, so recently they jumped into this thing, AI thing, AI coding, and you can install it to Visual Code directly as well. Okay, you can go here, and from where the extensions are there. You can write Amazon Q here. Okay, this thing you can install. Okay, it's like this Codium only. Let me show you some videos. Where are the videos? Okay, so how Codium works. Okay, not here. I will show you in this. See, this is how Codium works. Again, same thing. See, if you write this, again the suggestions will come. Okay, lambda function to publish user, like Codium. Okay, so the fifth one is our Amazon Q. Okay, so there are many models like Copilot. This GitHub Copilot is there. Copilot is there. GitHub Copilot is there for this AI coding, AI developer tool. And if you are curious to make a website within a second, so there is one more app called, not app, this tool, you can say WebSim. Okay, see what you like to create today. I will write here Amazon, but okay, let me first, but they use Sonnet 3.5, means Claude. They are using Claude. So I will write here, I want to create Amazon.in. See, it will create website for you. No coding, nothing, all. Directly it will give you website. Okay, it's loading, I guess. So this is how you can use WebSim. Right? See, OnePlus Node, this came. Okay. I just gave Amazon.in and the website is here within a second. Okay. So these are some, important tools to learn or how to use them in 2025, for 2025. Using AI tools for coding is essential to be in the race. Okay. So these are some.
So now let's see steps to get an AI engineer job. So to thrive in this field, developing a comprehensive skill set is crucial, while encompasses may specialized areas. So here are some certain core skills that are essential across most roles. So here is you can build these skills. First one is technical skills. So AI roles heavily rely on technical expertise, particularly in programming, data handling, or working with AI specific tools, or you can say the cloud specific tools. So here are some key areas to focus on. The first one is the programming languages. So proficiency in general purpose programming language like Python and R is the fundamental. Python in particular is widely used in AI for simplicity and robust libraries such as TensorFlow and PyTorch, which are crucial for machine learning and deep learning tasks. The second one is database management. So understanding how to manage and manipulate large datasets is essential in AI. Familiarity with database management systems like Apache Cassandra, Couchbase, and DynamoDB will allow you to store, retrieve, and process data efficiently. The third one, data analysis and statistics. Strong skills in data analysis are must. Tools like MATLAB, Excel, and Pandas are invaluable for statistical analysis, data manipulation, and visualization of trends in data, which are critical for developing AI models. The fourth one, cloud AI platform. Knowing of cloud-based AI platforms such as Microsoft Azure AI, Google Cloud AI, and IBM Watson is increasingly important. So these platforms provide pre-built models, tools, and infrastructure that can accelerate AI development and deployment. The second one is industry knowledge. While technical skills form the backbone of your AI expertise, understanding the industry context is equally important. For example, knowing how AI integrates with digital marketing goals and strategies can be a significant advantage if you are working in or targeting industries like e-commerce or advertising. So industry-specific knowledge allows you to apply AI solutions more effectively and communicate their value to stakeholders. The third one, workplace or soft skills. In addition to technical, industry-specific skills, developing workplace skills, or you can say soft skills, is essential for success in AI roles or any roles. So these soft skills often honed through experience include, the first one is communication. Clearly articulating complex AI concept to non-technical stakeholders is crucial. Whether you are explaining how machine learning model works or presenting data-driven insight, effective communication ensure that your work is understood and valued. Second one is collaboration. AI projects often require teamwork across diverse fields, including data science, software development, and other things. The third one is analytical thinking. AI is fundamentally about problem solving. You will need strong analytical thinking skills to approach challenges logically, break them down into manageable parts, and develop innovative solutions. The fourth one, problem solving. AI projects frequently involve unexpected challenges, whether it's a technical bug or an unforeseen data issue. Strong problem solving will help you navigate these hurdles and keep projects on track. So building these skills can be achieved through various methods, including self-study, online courses, boot camps, or formal education. Additionally, working on real projects, contributing to open source AI initiatives, and seeking mentorship can provide practical experience and further enhance your expertise. So next thing is learn advanced topics. So as you advance in your machine learning journey, it is important to delve into more advanced topics. These areas will deepen your understanding and help you tackle complex problems. So some key topics to focus are, the first one is deep learning and neural network. The second thing is ensemble learning techniques. The third thing is generative models and adversarial learning. The fourth one is recommendation system and collaborative filtering. The fifth one is time series analysis and forecasting. So now let's move forward and see some machine learning projects. So working on real world projects to apply your knowledge, focus on data collection and preparation, capstone project in image recognition and NLP, predictive modeling and anomaly detection, practical experience, key to solidifying your skills. So now let's move forward and see what is the next skill. That is earn a certification. So if you are already hold an undergraduate degree in a field of related to AI, enrolling in a specialized course to enhance your technical skills can be highly beneficial. Even if you don't have a degree, earning certification can show potential employers that you are committed to your career goals and actively investing in your professional development. So you can unleash your career potential with our artificial intelligence and machine learning courses, tailored for diverse industries and roles at top global firms. Our program features key tools, enhance your AI knowledge and business acumen, join the job market, and become sought-after professional. The next thing is continuous learning and exploration. So stay updated with the latest development by following industry leaders, engaging in online communities, and working on personal projects. Pursue advanced learning through courses and certification to keep your skills sharp. So now let's move forward and see some AI career opportunities with salary. So the job market for machine learning professional is booming. The average annual salary for AI engineers can be vary based on location, experience, and company. So here are some roles like machine learning engineer, data scientist, NLP engineer, computer vision, and AI ML researcher. So now let's see how much they earn. So the first one is ML engineer. So machine learning engineers earn $153,000 in US and 11 lakh in India per annum. The second one is data scientist. The data scientists earn $150,000 in US and 12 lakh per annum in India. The third one is NLP engineer. They earn $107,000 in US and 7 lakh in India per annum. Fourth one is computer vision engineer, CV engineer. They earn around $126,000 in US and 6,50,000 in India. The last one is AI ML researcher. They earn $130,000 in US and in India they earn around 9 lakh per annum. So note that these figures can vary on website to website and changes frequently. So now last step is start applying for entry-level jobs. When you feel confident in your training, begin researching and applying for jobs. Many entry-level AI positions like software engineer or developer roles are often labeled as entry-level or junior in the job description. Jobs that require less than 3 years of experience are usually suitable for those just starting out. If you need additional support in your job research, consider applying for internship, taking on freelance project, or participating in hackathons to further hone your skills. So these opportunities not only provide valuable feedback on your work, but also help you build connection that could benefit your career in the future.
What's in it for you? We're going to cover clustering. What is clustering? K-means clustering, which is one of the most common used clustering tools out there, including a flowchart to understand K-means clustering and how it functions. And then we'll do an actual Python live demo on clustering of cars based on brands. Then we're going to cover logistic regression. What is logistic regression? Logistic regression curve and sigmoid function. And then we'll do another Python code demo to classify a tumor as malignant or benign based on features. And let's start with clustering. Suppose we have a pile of books of different genres. Now we divide them into different groups like fiction, horror, education, and as we can see from this young lady, she definitely is into heavy horror. You can just tell by those eyes and the maple Canadian leaf on her shirt. But we have fiction, horror, and education, and we want to go ahead and divide our books up. Well, organizing objects into groups based on similarity is clustering. And in this case, as we're looking at the books, we're talking about clustering things with known categories. But you can also use it to explore data. So you might not know the categories, you just know that you need to divide it up in some way to conquer the data and to organize it better. But in this case, we're going to be looking at clustering in specific categories. And let's just take a deeper look at that. We're going to use K-means clustering. K-means clustering is probably the most commonly used clustering tool in the machine learning library. K-means clustering is an example of unsupervised learning. If you remember from our previous thing, it is used when you have unlabeled data. So we don't know the answer yet. We have a bunch of data that we want to cluster into different groups. Define clusters in the data based on feature similarity. So we've introduced a couple terms here. We've already talked about unsupervised learning and unlabeled data. So we don't know the answer yet. We're just going to group stuff together and see if we can find an answer of how things connect. We've also introduced feature similarity, features being different features of the data. Now with books, we can easily see fiction and horror and history books, but a lot of times with data, some of that information isn't so easy to see right when we first look at it. And so K-means is one of those tools where we can start finding things that connect, that match with each other. Suppose we have these data points and want to assign them into a cluster. Now when I look at these data points, I would probably group them into two clusters just by looking at them. I'd say two of these group of data kind of come together. But in K-means, we pick K clusters and assign random centroids to clusters, where the K clusters represents two different clusters. We pick K clusters and assign random centroids to the clusters, then we compute distance from objects to the centroids. Now we form new clusters based on minimum distances and calculate the centroids. So we figure out what the best distance is for the centroid, then we move the centroid and recalculate those distances. Repeat previous two steps iteratively till the cluster centroids stop changing their positions and become static. Repeat previous two steps iteratively till the cluster centroids stop changing and the positions become static. Once the clusters become static, then K-means clustering algorithm is said to be converged. And there's another term we see throughout machine learning is converged. That means whatever math we're using to figure out the answer has come to a solution, or it's converged on an answer. Shall we see the flow chart to understand? Make a little bit more sense by putting it into a nice, easy step-by-step. So we start, we choose K. We'll look at the elbow method in just a moment. We assign random centroids to clusters, and sometimes you pick the centroids because you might look at the data in a graph and say, oh, these are probably the central points. Then we compute the distance from the objects to the centroids. We take that and we form new clusters based on minimum distance and calculate their centroids. Then we compute the distance from objects to the new centroids. And then we go back and repeat those last two steps. We calculate the distances. So as we're doing it, it brings into the new centroid, and then we move the centroid around and we figure out which objects are closest to each centroid. So the objects can switch from one centroid to the other as the centroids are moved around. And we continue that until it is converged. Let's see an example of this. Suppose we have this data set of 7 individuals and their score on 2 topics, A and B. So here's our subject, in this case referring to the person taking the test. And then we have subject A where we see what they've scored on their first subject, and we have subject B and we can see what they score on the second subject. Now let's take 2 farthest apart points as initial cluster centroids. Now remember, we talked about selecting them randomly, or we can also just put them in different points and pick the furthest one apart so they move together. Either one works okay, depending on what kind of data you're working on and what you know about it. So we took the 2 furthest points, 1 and 1, and 5 and 7. And now let's take the 2 farthest apart points as initial cluster centroids. Each point is then assigned to the closest cluster with respect to the distance from the centroids. So we take each one of these points in there, we measure that distance, and you can see that if we measured each of those distances And you use the Pythagorean theorem for a triangle in this case, because you know the x and the y, and you can figure out the diagonal line from that. Or you can just take a ruler and put it on your monitor. That'd be kind of silly, but it would work if you're just eyeballing it. You can see how they naturally come together in certain areas. Now we again calculate the centroids of each cluster. So cluster 1 and then cluster 2, and we look at each individual dot. There's 1, 2, 3, we're in one cluster. The centroid then moves over. It becomes 1.8, 2.3. So remember it was at 1 and 1? Well, the very center of the data we're looking at would put it at the roughly 2, 2, but 1.8 and 2.3. And the second one, if we wanted to make the overall mean vector, the average vector of all the different distances to that centroid, we come up with 4, 1 and 5, 4. So we've now moved the centroids. We compare each individual's distance to its own cluster, mean, and to that of the opposite cluster, and we find, we can build a nice chart on here, that as we move that centroid around, we now have a new different kind of clustering of groups, and using Euclidean distance between the points and the mean, we get the same formula. You see new formulas coming up. So we have our individual dots, distance to the mean centroid of the cluster, and distance to the mean centroid of the cluster. Only individual 3 is nearer to the mean of the opposite cluster, cluster 2, than its own cluster 1. And you can see here in the diagram where we've kind of circled that one in the middle. So when we've moved the centroids of the clusters over, one of the points shifted to the other cluster because it's closer to that group of individuals. Thus, individual 3 is relocated to cluster 2, resulting in a new partition. And we regenerate all those numbers of how close they are to the different clusters. For the new clusters, we will find the actual cluster centroids. So now we move the centroids over, and you can see that we've now formed two very distinct clusters on here. On comparing the distance of each individual's distance to its own cluster mean and to that of the opposite cluster, we find that the data points are stable, hence we have our final clusters. Now, if you remember, I brought up a concept earlier, k-mean on the k-means algorithm. Choosing the right value of k will help in less number of iterations. And to find the appropriate number of clusters in a data set, we use the elbow method. And within sum of squares, WSS, is defined as the sum of the squared distance between each member of the cluster and its centroid. And so you see what we've done here is we have the number of clusters. And as you do the same k-means algorithm over the different clusters, and you calculate what that centroid looks like, and you find the optimal, you can actually find the optimal number of clusters using the elbow of the graph, is called as the elbow method. And on this, we guessed at 2 just by looking at the data. But as you can see, the slope, you actually just look for right there where the elbow is in the slope, and you have a clear answer that we want 2 different, to start with k-means equals 2. A lot of times people end up computing k-means equals 2, 3, 4, 5 until they find the value which fits on the elbow joint. Sometimes you can just look at the data, and if you're really good with that specific domain, remember domain, I mentioned that last time, you'll know that where to pick those numbers or where to start guessing at what that k value is. So let's take this, and we're going to use a use case using k-means clustering to cluster cars into brands using parameters such as horsepower, cubic inches, make, year, etc. So we're going to use the dataset cars data, having information about 3 brands of cars, Toyota, Honda, and Nissan. We'll go back to my favorite tool, the Anaconda Navigator with the Jupyter Notebook. And let's go ahead and flip over to our Jupyter Notebook. And in our Jupyter Notebook, I'm going to go ahead and just paste the basic code that we usually start a lot of these off with. We're not going to go too much into this code because we've already discussed NumPy, we've already discussed Matplotlib, and pandas. NumPy being the number array, pandas being the pandas data frame, and Matplot for the graphing. And don't forget, since if you're using the Jupyter Notebook, you do need the Matplotlib inline so that it plots everything on the screen. If you're using a different Python editor, then you probably don't need that because it'll have a pop-up window on your computer. And we'll go ahead and run this just to load our libraries and our setup into here. The next step is, of course, to look at our data, which I've already opened up in a spreadsheet. And you can see here we have the miles per gallon, cylinders, cubic inches, horsepower, weight pounds, how heavy it is, time it takes to get to 60. My card is probably on this one at about 80 or 90. What year it is. So this is, you can actually see this is kind of older cars, and then the brand, Toyota, Honda, Nissan. So the different cars are coming from all the way from 1971 if we scroll down to the 80s. We have between the 70s and 80s a number of cars that they've put out. And let's when we come back here, we're going to do importing the data. So we'll go ahead and do dataset equals. And we'll use pandas to read this in, and it's from a CSV file. Remember, you can always post this in the comments and request the data files for these, either in the comments here on the YouTube video or go to simplilearn.com and request that. The cars CSV, I put it in the same folder as the code that I've stored. So my Python code is stored in the same folder, so I don't have to put the full path. If you store them in different folders, you do have to change this and double check your name variables. And we'll go ahead and run this, and we've chosen dataset arbitrarily because it's a dataset we're importing, and we've now imported our cars CSV into the dataset. As you know, you have to prep the data, so we're going to create the X data. This is the one that we're going to try to figure out what's going on with. And then there's a number of ways to do this, but we'll do it in a simple loop so you can actually see what's going on. So we'll do for I in X dot columns. So we're going to go through each of the columns, and a lot of times it's important. I'll make lists of the columns and do this because I might remove certain columns, or there might be columns that I want to be processed differently. But for this, we can go ahead and take X of I, and we want to go fill NA, and that's a pandas command. But the question is, what are we going to fill the missing data with? We definitely don't want to just put in a number that doesn't actually mean something. And so one of the tricks you can do with this is we can take X of I, and then in addition to that, we want to go ahead and turn this into an integer, because a lot of these are integers. So we'll go ahead and keep it integers. And we add the bracket here. And a lot of editors will do this. They'll think that you're closing one bracket. Make sure you get that second bracket in there if it's a double bracket. That's always something that happens regularly. So once we have our integer of X of I, this is going to fill in any missing data with the average. And I was so busy closing one set of brackets, I forgot that the mean also has brackets in there for the pandas. So we can see here we're going to fill in all the data with the average value for that column. So if there's missing data, it's in the average of the data it does have. And then once we've done that, we'll go ahead and loop through it again and just check and see to make sure everything is filled in correctly. And we'll print, and then we take X is null, and this returns a set of the null value, or the how many lines are null, and we'll just sum that up to see what that looks like. And so when I run this, and so with the X, what we want to do is we want to remove the last column because that had the models. That's what we're trying to see, if we can cluster these things and figure out the models. There is so many different ways to sort the X out. For one, we could take the X and we could go dataset, our variable we're using, and use the iLocation, one of the features that's in pandas. And we could take that and then take all the rows and all but the last column of the data set. And at this time we could do values. We just convert it to values. So that's one way to do this. And if let me just put this down here and print X, it's a capital X we chose, and I run this, you can see it's just the values. We could also take out the values and it's not going to return anything because there's no values connected to it. What I like to do with this is, instead of doing the iLocation, which does integers, more common is to come in here and we have our data set, and we're going to do dataset dot columns. And remember, that lists all the columns. So if I come in here, let me just mark that as red, and I print dataset dot columns. You can see that I have my index here. I have my MPG, cylinders, everything, including the brand, which we don't want. So the way to get rid of the brand would be to do data columns of everything but the last one, -1. So now if I print this, you'll see the brand disappears. And so I can actually just take dataset columns -1, and I'll put it right in here for the columns we're going to look at. And let's unmark this and unmark this. And now if I do an x.head, I now have a new data frame, and you can see right here we have all the different columns except for the brand at the end of the year. And it turns out when you start playing with the data set, you're going to get an error later on, and it'll say cannot convert string to float value. And that's because for some reason these things, the way they recorded them, must have been recorded as strings. So we have a neat feature in here on pandas to convert. And it is simply convert objects. And for this, we're going to do convert underscore numeric equals true. And yes, I did have to go look that up. I don't have it memorized, the convert numeric in there. If I'm working with a lot of these things, I remember them, but depending on where I'm at, what I'm doing, I usually have to look it up. And we run that. Oops, I must have missed something in here. Let me double check my spelling. And when I double check my spelling, you'll see I missed the first underscore in the convert objects. And when I run this, it now has everything converted into a numeric value, because that's what we're going to be working with, is numeric values down here. And the next part is that we need to go through the data and eliminate null values. Most people, when they're doing small amounts, working with small data pools, discover afterwards that they have a null value and they have to go back and do this. So, be aware, whenever we're formatting this data, things are going to pop up, and sometimes you go backwards to fix it. And that's fine. That's just part of exploring the data and understanding what you have. And I should have done this earlier, but let me go ahead and increase the size of my window one notch. There we go. Easier to see. So we'll do for I in working with x dot columns. We'll page through all the columns. And we want to take x of I, and we're going to change that, and we're going to alter it. And so with this, we want to go ahead and fill in x of I. Pandas has the fill in a, and that just fills in any non-existent missing data. And we'll put my brackets up, and there's a lot of different ways to fill this data. If you have a really large data set, some people just void out that data and then look at it later in a separate exploration of data. One of the tricks we can do is we can take our column and we can find the means. And the means is in our quotation marks. So when we take the columns, we're going to fill in the non-existing one with the means. The problem is that returns a decimal float. So some of these aren't decimals. Certainly, we need to be a little careful of doing this, but for this example, we're just going to fill it in with the integer version of this. It keeps it on par with the other data that isn't a decimal point. And then what we also want to do is we want to double check. A lot of times you do this first part first to double check, then you do the fill, and then you do it again just to make sure you did it right. So we're going to go through and test for missing data. And one of the ways you can do that is simply go in here and take our x of I column. So it's going to go through the x of I column. It says is null. So it's going to return any place there's a null value. It actually goes through all the rows of each column is null. And then we want to go ahead and sum that. So we take that and we add the sum value. And these are all pandas. So is null is a panda command, and so is sum. And if we go through that and we go ahead and run it, and we go ahead and take and run that, you'll see that all the columns have 0 null values. So we've now tested and double checked, and our data is nice and clean. We have no null values. Everything is now a number value. We turned it into numeric. And we've removed the last column in our data. And at this point, we're actually going to start using the elbow method to find the optimal number of clusters. So we're now actually getting into the sklearn part, the k-means clustering on here. I guess we'll go ahead and zoom it up one more notch so you can see what I'm typing in here. And then from sklearn, we're going to our sklearn cluster, we're going to import k-means. I always forget to capitalize the k and the m when I do this. So it's capital K, capital M, k-means. And we'll go ahead and create a array, WCSS equals, we'll make it an empty array. If you remember from the elbow method from our slide, within the sum of squares, WSS is defined as the sum of square distance between each member of the cluster and its centroid. So we're looking at that change in differences as far as a square distance. And we're going to run this over a number of k-mean values. In fact, let's go for I in range, we'll do 11 of them. Range 0 of 11. And the first thing we're going to do is we're going to create the actual, we'll do it all lowercase. And so we're going to create this object from the k-means that we just imported. And the variable that we want to put into this is in clusters. And we're going to set that equals to I. That's the most important one because we're looking at how increasing the number of clusters changes our answer. There are a lot of settings to the k-means. Our guys in the back did a great job just kind of playing with some of them. The most common ones that you see in a lot of stuff is how you init your k-means. So we have k-means plus plus. This is just a tool to let the model itself be smart how it picks its centroids to start with, its initial centroids. We only want to iterate no more than 300 times. We have a max iteration we put in there. We have the nth init, the random state equals 0. You really don't need to worry too much about these when you're first learning this. As you start digging in deeper, you start finding that these are shortcuts that will speed up the process as far as the setup. But the big one that we're working with is the in clusters equals I. So we're going to literally train our k-means 11 times. We're going to do this process 11 times. And if you're working with big data, you know the first thing you do is you run a small sample of the data so you can test all your stuff on it. And you can already see the problem that if I'm going to iterate through a terabyte of data 11 times, and then the k-means itself is iterating through the data multiple times, that's a heck of a process. So you got to be a little careful with this. A lot of times, though, you can find your elbow, using the elbow method, find your optimal number on a sample of data, especially if you're working with larger data sources. So we want to go ahead and take our k-means, and we're just going to fit it. If you're looking at any of the sklearn, very common, you fit your model. And if you remember correctly, our variable we're using is the capital X. And once we fit this value, we go back to the array we made, and we want to go ahead and just append that value on the end. And it's not the actual fit we're pinning in there, it's when it generates the value you're looking for is inertia. So k-means.inertia will pull that specific value out that we need. And let's get a visual on this. We'll do our PLT plot, and what we're plotting here is first the x-axis, which is range 0, 11, so that will generate a nice little plot there, and the WCSS for our y-axis. It's always nice to give our plot a title, and let's see, we'll just give it the elbow method for the title, and let's get some labels. So let's go ahead and do PLT X label, and what we'll do number of clusters for that, and PLT Y label, and for that we can do, there we go, WCSS, since that's what we're doing on the plot on there. And finally we want to go ahead and display our graph, which is simply PLT dot show. There we go. And because we have it set to inline, it'll appear inline. Hopefully I didn't make a type error on there. And you can see we get a very nice graph. You can see a very nice elbow joint there at 2, and again right around 3 and 4, and then after that there's not very much. Now, as a data scientist, if I was looking at this, I would do either 3 or 4, and I'd actually try both of them to see what the output looked like. And they've already tried this in the back, so we're just going to use 3 as a setup on here. And let's go ahead and see what that looks like when we actually use this to show the different kinds of cars. And so let's go ahead and apply the k-means to the cars data set. And basically we're going to copy the code that we looped through up above, where k-means equals k-means number of clusters, and we're just going to set the number of clusters to 3, since that's what we're going to look for. And you could do 3 and 4 on this and graph them just to see how they come up differently. It'd be kind of curious to look at that. But for this we're just going to set it to 3. Go ahead and create our own variable, y k-means, for our answers. And we're going to set that equal to, whoops, a double equal there, to k-means, but we're not going to do a fit. We're going to do a fit predict is the setup you want to use. And when you're using untrained models, you'll see a slightly different, because usually you see fit and then you see just the predict. But we want to both fit and predict the k-means on this. And that's fit underscore predict, and then our capital X is the data we're working with. And before we plot this data, we're going to do a little pandas trick. We're going to take our x value and we're going to set x as matrix. So we're converting this into a nice rows and columns kind of setup, but we're going to have columns equals none, so it's just going to be a matrix of data in here. And let's go ahead and run that. Like a little warning. You'll see these warnings pop up because things are always being updated. So there's like minor changes in the versions and future versions. Instead of matrix, now it's more common to set it dot values instead of doing as matrix. But as matrix works just fine for right now, and you'll want to update that later on. But let's go ahead and dive in and plot this and see what that looks like. And before we dive into plotting this data, I always like to take a look and see what I am plotting. So let's take a look at why k-means. I'm just going to print that out down here. And we see we have an array of answers. We have 2, 1, 0, 2, 1, 2. So it's clustering these different rows of data based on the 3 different spaces it thinks it's going to be. And then let's go ahead and print x and see what we have for x. And we'll see that x is an array, it's a matrix, so we have our different values in the array. And what we're going to do, it's very hard to plot all the different values in the array. So we're only going to be looking at the first 2, or positions 0 and 1. And if you were doing a full presentation in front of the board meeting, you might actually do a little different and dig a little deeper into the different aspects, because this is all the different columns we looked at. But we'll only look at columns 1 and 2 for this to make it easy. So let's go ahead and clear this data out of here, and let's bring up our plot. And we're going to do a scatter plot here. So PLT scatter, and this looks a little complicated, so let's explain what's going on with this. We're going to take the x values, and we're only interested in y of k-means equals 0, the first cluster. Okay? And then we're going to take value 0 for the x-axis, and then we're going to do the same thing here. We're only interested in k-means equals 0, but we're going to take the second column. So we're only looking at the first 2 columns in our answer, or in the data. And then the guys in the back played with this a little bit to make it pretty. And they discovered that it looks good if it has a size equals 100. That's the size of the dots. We're going to use red for this one. And when they were looking at the data and what came out, it was definitely the Toyota on this. We're just going to go ahead and label it Toyota. Again, that's something you really have to explore in here as far as playing with those numbers and see what looks good. We'll go ahead and hit enter in there. And I'm just going to paste in the next 2 lines, which is the next 2 cars. And this is our Nissan and Honda. And you'll see with our scatter plot, we're now looking at where y underscore k means equals 1. And we want the 0 column, and y k means equals 2. Again, we're looking at just the first 2 columns, 0 and 1. And each of these rows then corresponds to Nissan and Honda. And I'll go ahead and hit enter on there. And finally, let's take a look and put the centroids on there. Again, we're going to do a scatter plot. And on the centroids, you can just pull that from our k-means, the model we created, dot cluster centers, and we're going to just do all of them in the first number and all of them in the second number, which is 0, 1, because you always start with 0 and 1. And then they were playing with the size and everything to make it look good. We'll do a size of 300. We're going to make the color yellow, and we'll label them. It's always good to have some good labels, centroids. And then we do want to do a title, PLT title, and pop up there. PLT title, because you always want to make your graphs look pretty, and we'll call it clusters of car make. And one of the features of the plot library is you can add a legend. It'll automatically bring in it since we've already labeled the different aspects of the legend with Toyota, Nissan, and Honda. And finally, we want to go ahead and show so we can actually see it. And remember, it's inline. So if you're using a different editor that's not the Jupyter Notebook, you'll get a pop-up of this. And you should have a nice set of clusters here. So we can look at this, and we have clusters of Honda in green, Toyota in red, Nissan in purple. And you can see where they put the centroids to separate them. Now, when we're looking at this, we can also plot a lot of other different data on here because we only looked at the first 2 columns. This is just column 1 and 2, or 0, 1 as you label them in computer scripting. But you can see here we have nice clusters of car make, and we were able to pull out the data And you can see how just these two columns form very distinct clusters of data. So if you were exploring new data, you might take a look and say, well, what makes these different? Almost going in reverse, you start looking at the data and pulling apart the columns to find out why is the first group set up the way it is. Maybe you're doing loans and you want to go, well, why is this group not defaulting on their loans? And why is the last group defaulting on their loans? And why is the middle group 50% defaulting on their bank loans? And you start finding ways to manipulate the data and pull out the answers you want. So now that you've seen how to use k-mean for clustering, let's move on to the next topic. Now let's look into logistic regression. The logistic regression algorithm is the simplest classification algorithm used for binary or multi-classification problems. And we can see we have our little girl from Canada who's into horror books is back. That's actually really scary when you think about that with those big eyes. In the previous tutorial, we learned about linear regression, dependent and independent variables. So, to brush up, y equals mx plus c. A very basic algebraic function of y and x. The dependent variable is the target class variable we are going to predict. The independent variables, x1 all the way up to xn, are the features or attributes we're going to use to predict the target class. We know what a linear regression looks like, but using the graph we cannot divide the outcome into categories. It's really hard to categorize 1.5, 3.6, 9.8. For example, a linear regression graph can tell us that with increase in number of hours studied, the marks of a student will increase, but it will not tell us whether the student will pass or not. In such cases where we need the output as categorical value, we will use logistic regression. And for that we're going to use the sigmoid function. So you can see here we have our marks, 0 to 100, number of hours studied. That's going to be what they're comparing it to in this example. And we usually form a line that says y equals mx plus c. And when we use the sigmoid function, we have p equals 1 over 1 plus e to the minus y. It generates a sigmoid curve. And so you can see right here when you take the ln, which is the natural logarithm. I always thought it should be nl, not ln. That's just the inverse of e, or e to the minus y. And so when we do this, we get ln of p over 1 minus p equals m times x plus c. That's the sigmoid curve function we're looking for. And we can zoom in on the function, and you'll see that the function, as it derives, goes to 1 or to 0, depending on what your x value is. And the probability, if it's greater than 0.5, the value is automatically rounded off to 1, indicating that the student will pass. So if they're doing a certain amount of studying, they will probably pass. Then you have a threshold value at the 0.5. It automatically puts that right in the middle usually. And your probability, if it's less than 0.5, the value rounded off to 0, indicating the student will fail. So if they're not studying very hard, they're probably going to fail. This, of course, is ignoring the outliers of that one student who's just a natural genius and doesn't need any studying to memorize everything. That's not me, unfortunately. I have to study hard to learn new stuff. Problem statement. To classify whether a tumor is malignant or benign. And this is actually one of my favorite data sets to play with because it has so many features, and when you look at them, you really are hard to understand. You can't just look at them and know the answer. So it gives you a chance to kind of dive into what data looks like when you aren't able to understand the specific domain of the data. But I also want you to remind you that in the domain of medicine, if I told you that my probability was really good at classified things at, say, 90% or 95%, and I'm classifying whether you're going to have a malignant or a benign tumor, I'm guessing that you're going to go get it tested anyways. So you got to remember the domain we're working with. So why would you want to do that if you know you're just going to go get a biopsy because, you know, it's that serious? This is like an all or nothing. Just referencing the domain, it's important. It might help the doctor know where to look just by understanding what kind of tumor it is. So it might help them or aid them in something they missed from before. So let's go ahead and dive into the code, and I'll come back to the domain part of it in just a minute. So use case, and we're going to do our normal imports here, where we're importing NumPy, Pandas, Seaborn, the Matplot library, and we're going to do Matplot library inline since I'm going to switch over to Anaconda. So let's go ahead and flip over there and get this started. So I've opened up a new window in my Anaconda Jupyter Notebook. And by the way, Jupyter Notebook, you don't have to use Anaconda for the Jupyter Notebook. I just love the interface and all the tools that Anaconda brings. So we got our import numpy as in P for our numpy number array. We have our pandas PD. We're going to bring in Seaborn to help us with our graphs as SNS. So many really nice tools in both Seaborn and Matplotlib. Then we'll do our matplotlib.pyplot as PLT, and then of course we want to let it know to do it in line. And let's go ahead and just run that so it's all set up. And we're just going to call our data, not creative today, equals PD, and this happens to be in a CSV file. So we'll use the pd.read_CSV, and I happen to name the file, I renamed it, data for p2.csv. You can, of course, write in the comments below the YouTube and request for the data set itself, or go to the Simplilearn website, and we'll be happy to supply that for you. And let's just open up the data before we go any further, and let's just see what it looks like in a spreadsheet. So when I pop it open in a local spreadsheet, and this is just a CSV file, comma separated variables, we have an ID, so I guess they categorize this for reference or what ID, which test was done. The diagnosis, M for malignant, B for B9, so there's two different options on there. And that's what we're going to try to predict is the M and B and test it. And then we have like the radius mean or average, the texture average, perimeter mean, area mean, smoothness. I don't know about you, but unless you're a doctor in the field, most of the stuff, I mean, you can guess what concave means just by the term concave, but I really wouldn't know what that means in the measurements they're taking. So they have all kinds of stuff like how smooth it is, the symmetry, and these are all float values. We can just page through them real quick, and you'll see there's, I believe, 36 if I remember correctly in this one. So there's a lot of different values they take and all these measurements they take when they go in there and they take a look at the different growth, the tumorous growth. So back in our data, and I put this in the same folder as the code. So I saved this code in that folder. Obviously, if you have it in a different location, you want to put the full path in there. And we'll just do pandas first 5 lines of data with the data.head. When we run that, we can see that we have pretty much what we just looked at. We have an ID, we have a diagnosis. If we go all the way across, you'll see all the different columns coming across displayed nicely for our data. And while we're exploring the data, our Seaborn, which we referenced as SNS, makes it very easy to go in here and do a joint plot. You'll notice very similar to, because it is sitting on top of the plot library, so the joint plot does a lot of work for us. And we're just going to look at the first 2 columns that we're interested in, the radius mean and the texture mean. We'll just look at those 2 columns. And data equals data. So that tells it which 2 columns we're plotting and that we're going to use the data that we pulled in. And let's just run that. And it generates a really nice graph on here. And there's all kinds of cool things on this graph to look at. I mean, we have the texture mean and the radius mean, obviously the axes. You can also see, and one of the cool things on here is you can also see the histogram. They show that for the radius mean. Where is the most common radius mean come up and where the most common texture is. So we're looking at on each growth its average texture and on each radius its average radius on there. It gets a little confusing because we're talking about the individual objects average, and then we can also look over here and see the histogram showing us the median or how common each measurement is. And that's only 2 columns, so let's dig a little deeper into Seaborn. They also have a heat map. And if you're not familiar with heat maps, a heat map just means it's in color. That's all that means. Heat map, I guess the original ones were plotting heat density on something, and so ever since then it's just called a heat map. And we're going to take our data and get our corresponding numbers to put that into the heat map. And that's simply data.corr for that. That's a pandas expression. So remember, we're working in a pandas data frame, so that's one of the cool tools in pandas for our data. And let's just pull that information into a heat map and see what that looks like. And you'll see that we're now looking at all the different features. We have our ID, we have our texture, we have our area, our compactness, concave points. And if you look down the middle of this chart, diagonal, going from the upper left to bottom right, it's all white. That's because when you compare texture to texture, they're identical. So they're 100%, or in this case, a perfect 1 in their correspondence. And you'll see that when you look at, say, area, or right below it, it has almost a black on there when you compare it to texture. So these have almost no corresponding data. They don't really form a linear graph or something that you can look at and say how connected they are. They're very scattered data. This is really just a really nice graph to get a quick look at your data. It doesn't so much change what you do, but it changes verifying. So when you get an answer or something like that, or you start looking at some of these individual pieces, you might go, hey, that doesn't match. According to showing our heat map, this should not correlate with each other. And if it is, you're going to have to start asking, well, why? What's going on? What else is coming in there? But it does show some really cool information on here. I mean, we can see from the ID, there's no real one feature that just says, if you go across the top line, that lights up. There's no one feature that says, hey, if the area is a certain size, then it's going to be benign or malignant. It says there's some that sort of add up. And that's a big hint in the data that we're trying to ID this, whether it's malignant or benign. That's a big hint to us as data scientists to go, okay, we can't solve this with any one feature. It's going to be something that includes all the features, or many of the different features, to come up with a solution for it. And while we're exploring the data, let's explore one more area, and let's look at data.isNull. We want to check for null values in our data. If you remember from earlier in this tutorial, we did it a little differently where we added stuff up and summed them up. You can actually, with pandas, do it really quickly, data.isNull, and sum it, and it's going to go across all the columns. So when I run this, you're going to see all the columns come up with no null data. So we've just to rehash these last few steps, we've done a lot of exploration. We have looked at the first two columns and seen how they plot with the seaborn, with a joint plot, which shows both the histogram and the data plotted on the XY coordinates. And obviously, you can do that more in detail with different columns and see how they plot together. And then we took and did the seaborn heat map, the SNS heat map of the data. And you can see right here where it did a nice job showing us some bright spots where stuff correlates with each other and forms a very nice combination or points of scattering points. And you can also see areas that don't. And then finally we went ahead and checked the data. Is the data null value? Do we have any missing data in there? Very important step because it'll crash later on. If you forget to do this step, it will remind you when you get that nice error code that says null values. Okay, so not a big deal if you miss it, but it's no fun having to go back when you're in a huge process and you've missed this step, and now you're 10 steps later and you got to go remember where you were pulling the data in. So we need to go ahead and pull out our x and our y. So we just put that down here, and we'll set the x equal to, and there's a lot of different options here. Certainly we could do x equals all the columns except for the first two, because if you remember, the first two is the ID and the diagnosis. So that certainly would be an option. But what we're going to do is we're actually going to focus on the worst radius, the worst texture, parameter, area, smoothness, compactness, and so on. One of the reasons to start dividing your data up when you're looking at this information is sometimes the data will be the same data coming in. So if I have two measurements coming into my model, it might overweigh them. It might overpower the other measurements because it's basically taking that information in twice. That's a little bit past the scope of this tutorial. What I want you to take away from this, though, is that we are dividing the data up into pieces, and our team in the back went ahead and said, hey, let's just look at the worst. So I'm going to create an array, and you'll see this array, radius worst, texture worst, perimeter worst. We've just taken the worst of the worst, and I'm just going to put that in my x. So this x is still a pandas data frame, but it's just those columns. And our y, if you remember correctly, is going to be, oops, hold on one second. It's not x, it's data. There we go. So x equals data, and then it's a list of the different columns, the worst of the worst. And if we're going to take that, then we have to have our answer for our y, for the stuff we know. And if you remember correctly, we're just going to be looking at the diagnosis. That's all we care about is what is it diagnosed? Is it benign or malignant? And since it's a single column, we can just do diagnosis. Oh, I forgot to put the brackets. There we go. Okay. So it's just diagnosis on there. And we can also real quickly do like x.head if you want to see what that looks like. and y dot head and run this. And you'll see it only does the last one. I forgot about that if you don't do print. You can see that the y dot head is just MMM because the first ones are all malignant. And if I run this, the x dot head is just the first 5 values of radius worst, texture worst, parameter worst, area worst, and so on. I'll go ahead and take that out. So moving down to the next step, we've built our 2 data sets, our answer and then the features we want to look at. In data science, it's very important to test your model. So we do that by splitting the data. And from sklearn model selection, we're going to import train test split. So we're going to split it into 2 groups. There are so many ways to do this. I noticed in one of the more modern ways, they actually split it into 3 groups, and then you model each group and test it against the other groups. So you have all kinds of, and there's reasons for that, which is past the scope of this, and for this particular example isn't necessary. For this, we're just going to split it into 2 groups, one to train our data and one to test our data. And the sklearn model selection, we have train test split. You could write your own quick code to do this where you just randomly divide the data up into 2 groups, but they do it for us nicely. And we can actually do it in one statement with this, where we're going to generate 4 variables, capital X train, capital X test. So we have our training data we're going to use to fit the model, and then we need something to test it. And then we have our Y train, so we're going to train the answer, and then we have our test. So this is the stuff we want to see how good it did on our model. And we'll go ahead and take our train test split that we just imported, and we're going to do X and our Y, our 2 different data that's going in for our split. And then the guys in the back came up and wanted us to go ahead and use a test size equals 0.3. That's test underscore size. Random state. It's always nice to kind of switch your random state around, but not that important. What this means is that the test size is we're going to take 30% of the data and we're going to put that into our test variables, our Y test and our X test. And we're going to do 70% into the X train and the Y train. So we're going to use 70% of the data to train our model and 30% to test it. Let's go ahead and run that and load those up. So now we have all our stuff split up and all our data ready to go. And now we get to the actual logistics part. We're actually going to create our model. So let's go ahead and bring that in from sklearn. We're going to bring in our linear model, and we're going to import Logistic Regression. That's the actual model we're using. And this, we'll call it log model. Oops, there we go, model. And let's just set this equal to our logistic regression that we just imported. So now we have a variable log model set to that class for us to use. And with most of the models in the sklearn, we just need to go ahead and do a fit on there. And we use our X train that we separated out with our Y train. Now let's go ahead and run this. So once we've run this, we'll have a model that fits this data, that 70% of our training data. And of course it prints this out that tells us all the different variables that you can set on there. There's a lot of different choices you can make. But for what we're just going to let all the defaults sit. We don't really need to mess with those on this particular example. And there's nothing in here that really stands out as super important until you start fine-tuning it. But for what we're doing, the basics will work just fine. And then we need to go ahead and test out our model. Is it working? So let's create a variable yPredict. And this is going to be equal to our log model. And we want to do a predict. Again, very standard format for the sklearn library is taking your model and doing a predict on it. And we're going to test yPredict against the Y test. So we want to know what the model thinks it's going to be. That's what our yPredict is. And with that, we want the capital X test. So we have our train set and our test set, and now we're going to do our yPredict. And let's go ahead and run that. And if we print yPredict, let me go ahead and run that. You'll see it comes up and it prints a nice array of B and M for benign and malignant for all the different test data we put in there. So it does pretty good. We're not sure exactly how good it does, but we can see that it actually works and is functional. It was very easy to create. You'll always discover with our data science that as you explore this, You spend a significant amount of time prepping your data and making sure your data coming in is good. There's a saying, good data in, good answers out. Bad data in, bad answers out. That's only half the thing. That's only half of it. Selecting your models becomes the next part as far as how good your models are. And then, of course, fine-tuning it depending on what model you're using. So we come in here, we want to know how good this came out. So we have our yPredict here, logModel.predictXtest. So for deciding how good our model is, we're going to go from the sklearn.metrics, we're going to import classification report. And that just reports how good our model is doing, and then we're going to feed it the model data. And let's just print this out. And we'll take our classification report, and we're going to put into there our test, our actual data. So this is what we actually know is true. And our prediction, what our model predicted for that data on the test side. And let's run that and see what that does. So we pull that up, you'll see that we have a precision for benign and malignant B and M. And we have a precision of 93 and 91, a total of 92. So it's kind of the average between these two of 92. There's all kinds of different information on here. Your F1 score, your recall, your support coming through on this. And for this, I'll go ahead and just flip back to our slides that they put together for describing it. And so here we're going to look at the precision using the classification report. And you see this is the same printout I had up above. Some of the numbers might be different because it does randomly pick out which data we're using. So this model is able to predict the type of tumor with 91% accuracy. So we look back here, you'll see where we have benign and malignant. It actually is 92 coming up here. But we're looking at about a 91% precision. And remember, I reminded you about domain. So when we're talking about the domain of a medical domain with a very catastrophic outcome, at 91 or 92% precision, you're still going to go in there and have somebody do a biopsy on it. Very different than if you're investing money and there's a 92% chance you're going to earn 10%. And 8% chance you're going to lose 8%, you're probably going to bet the money because at that odds it's pretty good that you'll make some money. And in the long run, you do that enough, you definitely will make money. And also with this domain, I've actually seen them use this to identify different forms of cancer. That's one of the things that they're starting to use these models for, because then it helps the doctor know what to investigate. So that wraps up this section. We're going to go in there and let's discuss the answer to the quiz asked in Machine Learning Tutorial Part 1. Can you tell what's happening in the following cases? Grouping documents into different categories based on the topic and content of each document. This is an example of clustering where k-means clustering can be used to group the documents by topics using bag of words approach. So if you've gotten in there that you're looking for clustering, and hopefully you had at least one or two examples like k-means that are used for clustering different things, then give yourself a 2 thumbs up. B. Identifying handwritten digits in images correctly. This is an example of classification. The traditional approach to solving this would be to extract digit-dependent features like curvature of different digits, etc., and then use a classifier like SVM to distinguish between images. Again, if you got the fact that it's a classification example, give yourself a thumb up, and if you're able to go, hey, let's use SVM or another model for this, give yourself those 2 thumbs up on it. C. Behavior of a website indicating that the site is not working as designed. This is an example of anomaly detection. In this case, the algorithm learns what is normal and what is not normal, usually by observing the logs of the website. Give yourself a thumbs up if you got that one. And just for a bonus, can you think of another example of anomaly detection? One of the ones I use it for in my own business is detecting anomalies in stock markets. Stock markets are very fickle and they behave very erratic. So finding those erratic areas and then finding ways to track down why they're erratic. Was something released in social media? Was something released? You can see where knowing where that anomaly is can help you to figure out what the answer is to it in another area. D. Predicting salary of an individual based on his or her years of experience. This is an example of regression. This problem can be mathematically defined as a function between independent, years of experience, and dependent variables, salary of an individual. And if you guessed that this was a regression model, give yourself a thumbs up. And if you're able to remember that it is between independent and dependent variables and that terms, give yourself 2 thumbs up. Summary. So to wrap it up, we went over what is k-means. And we went through also the chart of choosing your elbow method and assigning a random centroid to the clusters, computing the distance, and then going in there and figuring out what the minimum centroids is and computing the distance and going through that loop until it gets the perfect centroid. And we looked into the elbow method to choose k based on running our clusters across a number of variables and finding the best location for that. We did a nice example of clustering cars with k-means, even though we only looked at the first 2 columns to make it simple and easy to graph. You can easily extrapolate that and look at all the different columns and see how they all fit together. And we looked at what is logistic regression. We discussed the sigmoid function, what is logistic regression, and then we went into an example of classifying tumors with logistics. I hope you enjoyed part 2 of machine learning. Thank you for joining us today. For more information, visit www.simplilearn.com. Again, my name is Richard Kirschner, a member of the Simplilearn team. Get certified, get ahead. If you have any questions or comments, feel free to write those down below the YouTube video or visit us at simplilearn.com. We'll be happy to supply you with the data sets or other information as requested.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.
Today we're going to cover the k-nearest neighbors, a lot referred to as KNN. And KNN is really a fundamental place to start in the machine learning. It's a basis of a lot of other things, and just the logic behind it is easy to understand and incorporated in other forms of machine learning. So today, what's in it for you? Why do we need KNN? What is KNN? How do we choose the factor k? When do we use KNN? How does KNN algorithm work? And then we'll dive into my favorite part, the use case. Predict whether a person will have diabetes or not. That is a very common and popular used data set as far as testing out models and learning how to use the different models in machine learning. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those 2 characteristics. Now tell me if it is a cat or a dog. An odd question, usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or is not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of K is a process called parameter tuning and is important for better accuracy. So at K equals 3, we can classify, we have a question mark in the middle, as either as a square or not. Is it a square or is it, in this case, a triangle? And so if we set K equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put K equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the K changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of K? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right K? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of K, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your K is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing K, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your K value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the K value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise-free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where, I mean, you might get into a gig of data if it's really clean, it doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having 2 variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have 2 variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the 2 edges of a triangle. We're computing the 3rd edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13, and distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the 3 closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57,170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what, 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, you know, if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. You know, at 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import NumPy as NP. Pandas is the pandas data frame, and NumPy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our NumPy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember, in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6, that will skew results. So we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the k-neighbors classifier we're going to use. And finally, the last three are 3 tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our 2 general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this, so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put it in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, you know, the dataset 1 head, dataset 2 head, it only prints out the last one. So I usually always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those, you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do a direct. There's also one that you look for your NAN. A lot of different options in here. But the NAN, numpy NAN is what that stands for, is none, it doesn't exist. So the first thing we're doing here is we're replacing the 0 with a numpy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column .mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NAN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything where, except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, One of the tricks is you replace it with the average. What is the most common data for that? This way you can still use the rest of those values to do your computation, and it kind of just brings that particular value or those missing values out of the equation. Let's go ahead and take this and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you want to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle, because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set, we want to look at the I location, and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember, column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far, we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there, but the actual running of our KNN, we need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our X train equals sc_x dot fit transform. So we're creating the scaler on the X train variable, and then our X test, we're also going to transform it. So we've trained and transformed the X train, and then the X test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replace that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data. So now we have our test data and our training data. And then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using K-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be xtrain. Before we do this, let's go ahead and do import math and do math square root length of y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. And that's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the k neighbors classifier. N neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of ways to measure this, but the Euclidean's the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score, and finally accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, y test, y predict. So those are the two values we're going to put in there, and let me go ahead and run that and print it out. And the way you interpret this is you have the y predicted, which would be your title up here. We could do, let's just do PRED, predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model.
The principal component analysis, we're going to cover dimensionality reduction, principal component analysis, what is it, important PCA terminologies, and you'll see it abbreviated normally as PCA, principal component analysis, PCA properties, PCA example, and then we'll pull up some Python code in our Jupyter Notebook and have some hands-on demo on the PCA and how it's used. Dimensionality reduction. Dimensionality reduction refers to the technique that reduces the number of input variables in a data set. And so you can see on the table on the right shows the orders made at an automobile parts retailer. The retailer sells different automobile parts from different companies. And you can see we have company BPAX, Isomax, and they have the item, the tire, the axle, an order ID, a price number, and a quantity. In order to predict the future sales, we find out that using correlation analysis that we just need 3 attributes. Therefore, we have reduced the number of attributes from 5 to 3. And clearly we don't really care about the part number. I don't think the part number would have an effect on how many tires are bought. And even the store, who's buying them, probably does not have an effect on that. In this case, that's what they've actually done, is remove those. And we just have the item, the tire, the price, and the quantity. One of the things you should be taking away from this is, in the scheme of things, we are in the descriptive phase. We're describing the data, and we're pre-processing the data. What can we do to clean it up? Why dimensionality reduction? Well, number one, less dimensions for a given data set means less computation or training time. That can be really important if you're trying a number of different models and you're rerunning them over and over again. And even if you have 7 gigabytes of data, that can start taking days to go through all those different models. So this is huge. This is probably the hugest part as far as reducing our data set. Redundancy is removed after removing similar entries from the data set. Again, pre-processing, some of our models, like a neural network, if you put in 2 of the same data, it might give them a higher weight than they would if it was just 1. So we want to get rid of that redundancy. It also increases the processing time if you have multiple data coming in. Space required to store the data is reduced. So if we're committing this into a big data pool, we might not send the company that bought it. Why would we want to store 2 whole extra columns when we add it into that pool of data? Makes the data easy for plotting in 2D and 3D plots. This is my favorite part. Very important. You're in your shareholder meeting. You want to be able to give them a really good, clear, and simplified version. You want to reduce it down to something people can take in. It helps to find out the most significant features and skip the rest, which also comes in post-scribing. Leads to better human interpretation. That kind of goes with number 4, where it makes data easy for plotting. You have a better interpretation when we're looking at it. Principal component analysis. So what is it? Principal component analysis is a technique for reducing the dimensionality of data sets, increasing interpretability, but at the same time minimizing information loss. So we take some very complex data set with lots of variables, we run it through the PCA, we reduce the variables. We end up with a reduced variable setup. This is very confusing to look at, because if you look at the end result, we have the different colors all lined up. So what we're going to take a look at is, let's say we have a picture here. Let's say you are asked to take a picture of some toddlers and you are deciding which angle would be the best to take the picture from. So if we come up here, we look at this, we say, okay, this is, one angle. We get the back of a lot of heads, not many faces. So we'll do it from here. We might get the one person up front smiling. A lot of the people in the class are missing, so we have a huge amount off to the right of blank space. Maybe from up here, again, we have the back of someone's head. And it turns out that the best angle to click the picture from might be this bottom left angle. You look at it and you say, hey, that makes sense. It's a good configuration of all the people in the picture. Now, when we're talking about data, it's not, you really can't do it by what you think is going to be the best. We need to have some kind of mathematical formula so it's consistent and so it makes sense in the back end. One of the projects I worked on many years ago had something similar to the iris. And if you've ever done the iris data set, it's probably one of the most common ones out there, where they have the flower and they're measuring the stamen in the petals, and they have width and they have length of the petal. Instead of putting through the width and the length of the petal, we could just as easily do the width to length ratio. We can divide the width by the length and you get a single number where you had 2. That's the kind of idea that's going on into this, in pre-processing and looking at what we can do to bring the data down. A very simplified example on my iris petal example. When we look at the similarity in PCA, we find the best picture or projection of the data points. And so when we look down at from one angle, we've drawn a line down there, we can see these data points based on, in this case, just 2 variables. Now keep in mind, we're usually talking about 36, 40 variables. Almost all of your business models usually have about 26 to 27 different variables they're looking at. Same thing with like a bank loan model. We're talking 26 to 36 different variables they're looking at that are going in. So what we want to do is we want to find the best view. In this case, we're just looking at the XY. We look down at it, and we have our second idea, PC2. And again, we're looking at the XY, this time from a different direction. Here, for our ease, we can consider that we get two principal components, namely PC1 and PC2. Comparing both the principal components, we find the data points are sufficiently spaced in PC1. So if you look at what we got here, we have PC1. You can see along the line how the data points are spaced versus the spacing in PC2. And that's what they're coming up with. What is going to give us the best look for these data points when we combine them? And we're looking at them from just a single angle. Whereas in PC2, they are less spaced, which makes the observation and further calculations much more difficult. Therefore, we accept the PC1 and not the PC2 as the data points are more spaced. Now, obviously, the back-end calculations are a little bit more complicated when we get into the math of how they decide what is more valuable. This gives you an idea, though, that when we're talking about this, we're talking about the perspective, which would help in understanding how PCA analysis works. What we want to go ahead and do is dive into the important terminologies under PCA. And important terminologies are views, the perspective through which data points are observed. And so you'll hear that if someone's talking about a PCA presentation and they're not taking the time to reduce it to something that the average person, shareholders, can understand, you might hear them refer to it as the different views. What view are we taking? Dimension, number of columns in a data set are called the dimensions of that data set. And we talked about, you'll hear features, dimensions. I was talking about features. There's usually, when you're running a business, you're talking 25, 26, 27 different features, minimal. And then you have the principal component, new variables that are constructed as linear combinations or mixtures of the initial variables. Principal component is very important. It's a combination. If you remember my flower example, it would be the width over the length of the petal as opposed to putting both width and length in. You just put in the ratio instead, which is a single number versus two separate numbers. Projections, the perpendicular distance between the principal component and the data points. And that goes to that line we had earlier. It's that right angle line of where how all those points fall onto the line. Important properties. Important properties. Number of principal components is always less than or equal to the number of attributes. That just makes common sense. You're not going to do 10 principal properties with only 3 features. You're trying to reduce them, so it's just kind of goofy, but it is important to remember that. People will throw weird code out there and just randomly do stuff instead of really thinking it through. Principal components are orthogonal. And this is what we're talking about, that right angle from the line. When we do PC1, we're looking at how those points fall on to that line. Same thing with PC2. And we want to make sure that PC1 does not equal PC2. We don't want to have the same 2 principal points when we do 2 points. The priority of principal components decreases as their numbers increase. This is important to understand. If you're going to create one principal component, everything is summarized into that one component. As we go to 2 components, the priority, how much it holds value, decreases as we go down. So if you have 5 different points, each one of those points is going to have less value than just the one point, which has everything summarized in it. How PCA works. I said there was more in the back end when we talk about the math. This is what we're talking about, is how does it actually work. So now we have understanding that you're looking at a perspective. Now we want to see how that math side works. PCA performs the following operations in order to evaluate the principal components for a given data set. First, we start with the standardization. Then we have a covariance matrix computation. And we use that to generate our igene vectors and igene values, which is the feature vector. And if you remember, the igene vector is like a translation for moving the data from x equals 1 to x equals 2 or whatever, altering it. and the eigenvalue value is the final value that we generate. When we talk about standardization, the main aim of this step is to standardize the range of the attributes so that each one of them lie within similar boundaries. This process involves removal of the mean from the variable values and scaling the data with respect to the standard deviation. And you can see here we have z equals the variable values minus the mean over the standard deviation. The covariance matrix computation. Covariance matrix is used to express the correlation between any two or more attributes in multi-dimensional data set. The covariance matrix has the entries as the variance and the covariance of the attribute values. The variance is denoted by var and the covariance is denoted by cov. On the right, we can see the covariance matrix for two attributes and their values. When we do a hands-on look at the code, we'll do a display of this so you can see what we're talking about and what that looks like. For now, you can just notice that this is a matrix that we're generating with the variance and then the covariance of x to y. On the right side, we can see the covariance table for more than two attributes in a multi-dimensional data set. This is what I was talking about. We usually are looking at not just one feature or two features. We're usually looking at 25, 30 features going on. And so if we do a setup like this, we should see all those different features as the different variables. Covariance matrix tells us how the two or more variables are related. Positive covariance indicate that the value of one variable is directly proportional to the other variable. Negative covariance indicate that the value of one variable is inversely proportional to the other variable. That is always important to note whenever we're doing any of these matrices, that we're going to be looking at that positive and negative, whether it's inverted or not. And then we have the eigenvalues and the eigenvectors. Eigenvalues and eigenvectors are the mathematical value that are extracted from the covariance table. They are responsible for the generation of a new set of variables from the old set of variables, which further lead to the construction of the principal components. Eigenvectors do not change directions after linear transformation. Eigenvalues are the scalars or the magnitude of the eigenvectors. And again, this is just transforming that data. So we're going to change the vector b to the b prime as denoted on the chart. And so when we have like multiple variables, how do we calculate that new variable? And then we have feature vectors. Feature vectors is simply a matrix that has eigenvectors of the components that we decide to keep as the columns. Here we decide whether we must keep or discard the less significant principal components that we have generated in the above steps. This becomes really important as we start looking at the back end of this, and we'll do this in the demo, but one of the more important steps to understand. And so we have the PCA example. Consider matrix X with n rows or observations and k columns or variables. Now for this matrix, we would construct a variable space with as many dimensions as the variable. But for our simplicity, let's consider this 3 dimensions for now. Now each observation, row of the matrix X, is placed in the k-dimensional variable space, such that the rows in the data table form a swarm of points in this space. Now we find the mean of all the observations and then place it along the data points on the plot. The first principal component is a line that best accounts for the shape of the point swarm. It represents the maximal variance direction in the data. Each observation may be projected onto this line in order to get a coordinate value along the PC1. This value is known as a score. Usually only one principal component is insufficient to model the systematic variation for a data set. Thus, a second principal axis is created. The second principal component is oriented such that it reflects the second largest source of variation in the data. While being orthogonal to PC1, PC2 also passes through the average point. Let's go ahead and pull this up and just see what that means inside our Python scripting. I'm going to use the Anaconda Navigator, and I will be in Python 3.6 for this example. I believe there's even like a 3.9 out. I tend to stay in 3.6 because a lot of the models I use, especially with the neural networks, are stable in 3.6. And then we open up our Jupyter. I'm in Chrome, and we go ahead and create a new Python 3. And for ease of use, our team in the back was nice enough to put this together for me. And we'll go ahead and start with the libraries. The first thing I like to do whenever I'm looking at any new setup, well, you know what, let's do the libraries first. We're going to do our basic libraries, which is Matplot library, the PLT from the Matplot library. Pandas, our data frame, PD, NumPy, our numbers array, NP, Seaborn for graphing, SNS, that goes with the plot that actually sits on Matplot library, so the Seaborn sits on there. And then we have our ampersand, because we're in Jupyter Notebook, Matplot library inline. The newer version actually doesn't require that, but I put it in there anyway, just because I'm so used to it. And then we want to go ahead and take a look at the data. And in this case, we're going to pull in, certainly you can have lots of fun with different data, but we're going to use the cancer data set. And one of the reasons the cancer data set is it has like 36, 35 different features. So it's kind of fun to use that as our base for this. And we'll go ahead and run this and look at our keys. And the first thing we notice in our keys for the cancer data set is we have our data, we have our target, our frame, target names, description, feature names, and file name. So what we're looking for in all this is, well, let's take a look at the description. Let's go in here and pull up the description on here. I'm not going to spend a huge amount of time on the description because we don't want to get into a medical domain. We want to focus on our PCA setup. What's important is you start looking at what the different attributes are, what they mean. If you were in the medical field, you'd want to note all these different things, what they're measuring, where it's coming from. You can actually see the actual different measurements they're taking. No missing attributes. We page all the way to the bottom. And you're going to have your data, in this case our target. And if you dig deep enough to the target, let's actually do this. Let's go ahead and print target names. Real quick here, I always like to just take a look and see what's on the other end of this. Target names. Run that. And so the target name is it malignant or is it benign? So in other words, is this dangerous growth or is it something we don't have to worry about? That's the bottom line with the cancer in this case. And then we can go ahead and load our data. And you know what, let me go up just a notch here for easy of reading. It's hard to get that just right. I guess I'll have to do. So let's go ahead and look at our data. We're going to use our pandas, and we're going to go ahead and do our data frame. It's going to equal cancer data. Columns equals cancer, feature equals feature names. So remember up here, we already loaded the names up of the features in there. What is going to come out of this? Let me just see if we can get to that. It's at the top of target names. That's just this list of names here in the setup. And we can go ahead and run this code, and it'll print the head. And you can see here we have the mean radius, the mean texture, mean perimeter. I don't know about you, this is a wonderful data set if you're playing with it, because like most of the data that comes in, half the time we don't even know what we're looking at. We're just handed a bunch of stuff as a data scientist going, what the heck is this? And so this is a good place to start because this has a number of different features in there and we have no idea what these features mean or where they come from. We want to just look at the data and figure that out. And now we actually are getting into the PCA side of it. As we've noticed before, it is difficult to visualize high-dimensional data. We can use PCA to find the first two principal components and visualize the data, this new two-dimensional space, with a single scatter plot. Before we do this, we need to go ahead and scale our data. Now, I haven't run this to see if you really have to scale the data on this, but as just a general run time, I almost do that as the first step of any modeling. even if it's pre-modeling as we're doing here. In neural networks, that is so important. With PCA visualization, it's already going to scale it when we do the means and deviation inside the PCA. But just in case, it's always good to scale it. And then we're going to take our PCA with the scikit-learn uses very similar process to other pre-processing functions that come with scikit-learn. We instantiate a PCA object, find the principal components using the fit method, then apply the rotation and dimensionality reduction by calling transform. We can also specify how many components we want to keep when creating the PCA object. And so the code for this, oops, getting a little bit ahead. Let me go ahead and run this code. So the code for this is from sklearn decomposition import PCA. PCA equals PCA and components equals 2. And that's really important to note that because we're only going to want to look at 2 components. I would never go over 4 components, especially if you're going to demo this with somebody else. If you're showing this to the shareholders, the whole idea is to reduce it to something people can see. And then the PCA fit, we're going to is going to take the scaled data that we generated up here, and then you can see we've created our PCA model with in components equals 2. Now, whenever I use a new tool, I like to go in there and actually see what I'm using. So let's go to the scikit webpage for the PCA. And you can see in here, here's our call statement. It describes what all the different setups you have on there. Probably the biggest one to look at would be, well, the biggest one is your components. How many components do you want? Which you have to put in there pretty much. And then you also might look at the SVD solver. It's on auto right now, but you can override that and do different things with it. It does a pretty good job as it is. And if we go down, all the way down to, here we go, to our methods, if you notice we have fit, and we have fit transform. Nowhere in here is predict, because this is not used for prediction. It's used to look at the data. Again, we're in the describe setup. We're fitting the data. We're taking a look at it. We've already looked at our minimum maximum. We've already looked at what's in each quarter. We've done a full description of the data. This is part of describing the data. That's the biggest thing I take away when I come zooming in here. And of course, they have examples of it down here if you forget. And the biggest one, of course, is the number of components. And then, I mean, the rest you can play with. The actual solver, whether you're doing a full or randomized, there's different things. It does pretty good on the auto. And now we can transform this data to its first 2 principal components. And so we have our XPCA. We're going to set that equal to PCA transform scaled data. So there we go. There's our first transformation. And let's just go ahead and print the scaled data shape and the XPCA data shape. And the reason we want to do this is just to show us what's going on here. We've taken 30 features. I think I said 36 or something like that, but it's 30. And we've compressed it down to 2 features. And we decided we wanted 2 features, and that's where this comes from. We still have 569 data sets. I mean data rows, not data sets. We still have 569 rows of data, but instead of computing 30 features, we're now only doing our model on 2 features. So let's go ahead and plot these and take a look and see what's going on. And we're just going to use our PLT figure. We're going to set the figure size on here. Here's our scatter plot, XPCA, X underscore PCA of 1. These are our 2 different perceptions we're using. And then you'll see right here, C for color, cancer equals target. And so remember we have 0, we have 1. And if I remember correctly, 0 was malignant, 1 was benign. So everything in the 0 column is going to be one color, and the other color is going to be 1. And then we're going to use the plasma map, just kind of telling you what color it is. Add some labels, first principal component, second principal component. And we'll go ahead and run this. And you can see here, instead of having a chart, one of those heat maps with 30 different columns in it, we can look at this and say, hey, this one actually did a pretty good job of separating the data. And a couple things when I'm looking at this that I notice is, first, we have a very clear area where it's clumped together, where it's going to be benign. And we have a huge area, it's still clumped together, more spread out, where it's going to be malignant. Or I think I had that backwards. And then in the middle, because we're dealing with something, in this particular case, cancer, we would try to separate, I would be exploring how to separate this middle group out. In other words, there's an area where everything overlaps, and we're not going to have a clear result on it. Just because those are the people you want to go in there and have extra tests, or treat it differently, versus going in and saying just cutting into the cancer so that the body absorbs it and it dissipates, versus actively going in there, removing it, testing it, going through chemo and all the different things. That's a big difference, you know, as far as what's going to happen here. And that middle line where they overlap is going to be huge. That's domain specific. Going back to the data, we can see here, clearly by using these two components, we can easily separate these two classes. So the next step is, what does that mean? Interpreting the components. Unfortunately, with this great power of dimensionality reduction comes the cost of not being able to easily understand what these components represent. I don't know what principal component 1 represents, or second principal. The components correspond to combinations of original features. The components themselves are stored as an attribute of the filtered PCA object. And so when we look at that, we can go ahead and look at the PCA components. This is in our model we built. We've trained it. We can run that, and you can see here's the actual components. It's the two components each have their own array. And within the array, you can see what the scores they're using. And these actually give weight to what features are doing what. So in this NumPy matrix array, each row represents a principal component, and each column relates back to the original features. What's really neat about this is we can now go in reverse and drop this onto a heat map and start seeing what this means. And so let me go ahead and just put this down. Oops, I already got it down here. We'll go ahead and put this in here. We're going to use our dfcomp data frame, and we do our PCA components. And I want you to notice how easy this is. We're going to set our columns equal to cancer feature names. That just makes it really easy. And we're dumping it into a data frame. What's neat about a data frame is when we get to Seaborn, it will pull that data frame apart and set it up for us the way we want. And so we're just going to do the Seaborn heat map of our data frame composition, and we'll use the plasma coloring. And it creates a nice little color graph here. You can see we have the mean radius and all the different features along the bottom. On the right, we have a scale, so we can see we have the dark colors all the way to the really light colors, which are what's really shining there. This is like the primary stuff we want to look at. So this heat map and the color bar basically represent the correlation between the various features and the principal component itself. So, very powerful map to look at, and then you can go in here, and we might notice that the mean radius, look how on the bottom of the map it is on some of this. So you have some interesting correlations here that change the variations on that and what means what. This is more when you get to PostScribe, you can also use this to try to guess as what these things mean and what you want to change to get a better result. Regularization in machine learning. So our agenda on this one is fitting the data, understanding linear regression, bias and variance, what is overfitting, what is underfitting, and those are like the biggest things right now in data science is overfitting and underfitting. What does that mean? And what is regularization? And then we'll do a quick hands-on demo to take a look at this. So, fitting the data. Let's start with fitting the data. And we talk about what is data fitting. It's a process of plotting a series of data points and drawing the best fit line to understand the relationship between the variables. And this is what we called data fitting. And you can see here we have a couple of lines we've drawn on this graph. We're going to go in a little deeper on there. So we might have, in this case, just 2 dimensions. We have an efficiency of the car, and we have the distance traveled in 1,000 kilometers. And so what is data fitting? Well, it's a linear relationship. And a linear relationship, very specifically, linear means line. The line used to represent the relationship is a straight line that passes through the data points, and the variables have a linear relationship. Linear regression. So let's start with how linear regression works. A linear regression finds the line that best fits the data point and gives a relationship between the 2 variables. And so you can see here we have the efficiency of the car versus the distance traveled, and you can see this nice straight line drawn through there. And when you talk about multiple variables, all you're doing is putting this instead of a line, it now becomes a plane. It gets a little more complicated with multiple variables, but they all come down to this linear kind of drawing a line through your data and finding what fits the data the best. And so we can consider an example. Let's say that we want to find the relationship between the temperature outside versus the sales of ice cream. And so we start looking at that. We're looking at how many ice cream cones we're selling or how much money we sold in ice cream. And we're looking at how warm it is outside, which would hopefully draw a lot of people into the ice cream store. And suppose we have 2 lines. We're going to draw L1 and L2. And we're going to kind of guess which one we think is the best fit, and which claim to describe the relationship between the variables. And so first, we find the square of the distance between the line L1 and each data point and add them all and find the mean distance. And I want you to think about that when we square something. If it's a negative or positive number, it no longer matters, because a minus 2 squared is 4, 2 squared is 4. So we're removing what side of the line it's on, and we're just looking for the error. In this case, the mean distance of each of the little dotted lines you see here. This way of calculating the square of the distance, adding them, and then taking the mean is called mean square error, or loss function. And we talk about loss, how far off are we? That's what we're really talking about. What did we miss? And we have a positive distance and a negative distance, and of course when we square it, it just becomes a positive error. And so we take the mean square error, and a lot of times you'll see it referred to as MSE. If I look in a code and I'm going through my Python code and I see MSE, I know that's the mean squared error. And we take all the dotted lines and we calculate this error and we add them all together and then we average it or find the means. And in this case, they ran a demo on this and it was 1127.27 for our L1 line. Now we find the loss function for line L2 in a similar fashion, and we get the mean square error to be 6,397. And it's computed the same way. So maybe you put this line just way outside the data range, and this is the error you get. By analyzing our results, we find that the loss function, or the mean square error, is less for L1 than L2. Hence, L1 is the best fit line. This process describes a lot of machine learning processes. So we're going to keep guessing and get as close as we can to find the right answer. We have to have some way to calculate this and figure out which one's the best, and the mean square error is one of the better fits for doing this and most commonly used. We really want to talk about bias and variance. Very important terms to know in machine learning and with linear regression. So bias. Bias occurs when an algorithm has limited flexibility to learn from data. Variance defines the algorithm's sensitivity to specific sets of data. Let's start with bias and variance. You can see here we have the 2 different setups. Bias you can think is very generalized, where variance is very specific. And so when we talk about bias, such models pay very little attention to the training data and oversimplify the model. Therefore, the validation error or prediction error and training error follow similar trends. And with bias, if you oversimplify it so much, you're going to miss your local, if you have like a really good fit, you're going to miss it. You're going to just kind of guess what the average is, and that's what your answer is going to be. With variance, a model with a high variance pays a lot of attention to training data and does not generalize. Therefore, the validation error or prediction error are far apart from each other. Such models always lead to a high error on training and test data, as a bias does. Where a variance, such models usually perform very well on training data but have high error rates on test data. And I want you to think about this. When we're talking about a bias, the error is going to be high both when you're training it and you're testing it. Why? Because we're just kind of getting an average. We're not really fitting it close. With variance, we're fitting it so close that the test data does really good. It's going to nail it every time. If you're doing categorical testing, that's a car, that's a truck, that's a bicycle. But with variance, suddenly a truck has to have certain features, and it might have to be red because you had so many red pictures. So if it's an 18-wheeler, it has to be red. If it's blue, then it has to be a bicycle. That's the kind of variance we're talking about, where it picks up on something and it cannot get the right answer unless it gets a very specific data. And we see that so that as you're testing it in your models and you programmed it, you got to look for how I trained it, what is coming out, and if it's not looking good on either bias or if it's not looking good on the training or on the test data, then you're biasing your data. If it really looks good on the training data, then that's going to be your variance. You've overfitted the data. And those are very important things to know when you are building your models in regression of any kind or any kind of setup for predicting. So in dart games, if all the data fall on a particular pointer, this can be considered as a biased throw, and the player aims for the particular score. For variance, if all the darts fall on different pointers and no two darts fall on the same pointer, then this can be considered as a varied throw, and the player aims for various scores. Again, the bias sums everything up in one point, kind of averages it together, where the variance really looks for the individual predictions coming out. So let's go ahead and talk about overfitting. When we talk about overfitting, it's a scenario where the machine learning model tries to learn from the details along with the noise, and the data tries to fit each data point on the curve. You can see that if you plug in your coordinates, you're just going to get the whatever is fitted every point on the data stream. There's no average. There's no 2 points that might have y might have two different answers, because if the wind blows a certain way and your efficiency of your car, maybe you have a headwind, so your car might alter how efficient it is as it goes, and so there's going to be this variance on here, and this says no, you can't have any variance. It's going to be exactly this. So it can't be you can't be the same speed or the same car and have a slightly different efficiency. So as the model has very less flexibility, it fails to predict new data points, and thus the model rejects every new data point during the prediction. So you'll get like a really high error on here. And so reasons for overfitting. Data used for training is not cleaned and contains noise, garbage values in it. You can spend so much time cleaning your data, and it's so important. It's so important that if you have some kind of something wrong with the data coming in, it needs to be addressed. Whether it's the source of the data, maybe they use in medical different measuring tools, so you now have to adjust for data that came in from hospital A versus hospital B, or even off of machine A and machine B that's testing something, and those numbers are coming in wrong. The model has a high variance. Again, wind is a good example. I was talking about that with the car. You may have 100 tests, but because the wind's blowing, it's all over the place. Size of training data used is not enough. So a small amount of data is going to also cause this problem. You only have a few points and you try to plot everything. The model is too complex. This comes up a lot. We put too many pieces together and how they interact can't even be tracked. And so you have to go back, break it up, and find out actually what correlates and what doesn't. So, what is underfitting? A scenario where machine learning models can neither learn the relationship between the data points nor predict or classify a new data point. And you can see here we have our efficiency of our car and our line drawn, and it's just going to be way off for both the training and the predicting data. As the model doesn't fully learn the patterns, it accepts every new data point during the prediction. So instead of looking for a general pattern, we just kind of accept everything. Data used for training is not cleaned and contains noise, garbage, and values. Again, underfitting and overfitting, same issue. You got to clean your data. The model has a high bias. We've seen this in all kinds of things, from the most common is the driving cars to facial identification or whatever it is. The model itself, when they build it, might have a bias towards one thing. And this would be an underfitted model, would have that bias because it's averaged it out. So if you have 5 people from India and 10 people from Africa and 20 people from the US, you created a bias because it's looking at the 20 people, and you only have a small amount of data to work with. Size of training data used is not enough. That goes with the size I was just talking about. So we have a model with a high bias, we have size of training data used is not enough. The model is too simple. Again, this is one straight line through all the data when it has a slight shift to it for other reasons. So what is a good fit? A linear curve that best fits the data is neither overfitting or underfitting models, but is just right. And of course we have the nice examples here where we have overfitting, lines going up and down, every point's trying to be included. Underfitting, the line really is off from where the data is, and then a good fit is got to get rid of that, minimize that error coming through. Regularization is taking the guesswork out. You're looking at this graph and you're going, oh, which one is that really overfit or is that underfit? That's pretty hard to tell. So we talk about regularization. Regularization techniques are used to calibrate the linear regression models and to minimize the adjusted loss function and prevent overfitting or underfitting. So what that means, in this case, we're going to go ahead and take a look at a couple different things. We're going to look at regularization, which will start with a linear model. We'll look at the ridge regularization and the lasso regularization. And these models are just like we did the MLP, the multi-layered positron in the sklearn module. You could bring in the ridge module and you can bring in the lasso module. So when we talk about ridge regression, it modifies the overfitted or underfitted models by adding the penalty equivalent to the sum of the squares of the magnitude of the coefficients. And so we have a cost function equals loss equals lambda times the sum of w squared, or the absolute value of w, depending on how you're doing it. Now remember, we talked about error, whether we either square it or we absolute value it, because that removes the plus or minus sign on there. And there's reasons to do it either way, but it is more common to square the value. And then we have our, in this case, the lambda is going to be the penalty for the errors. We've thrown in a Greek character for you just to confuse everybody. And w is the slope of the curve of the line. So we're going to look at this, and we're going to draw a line. This is going to be like a linear regression model. So if you had in sklearn, you could import just a standard linear regression model. It would plot this line across whatever data we're working on. And we look at this, and of course we're just extrapolating this. I know they use some specific data, but you don't want to get into the actual domain. And so for a linear regression line, let's consider 2 points that are on the line. And we'll go ahead and have a loss equals 0, considering the 2 points on the line. We'll go ahead and do lambda equals 1. We'll set our w is going to be 1.4. Then the cost function equals 0 plus 1 times 1.4 squared, which equals 1.96. So really don't get caught up too much in the math on this, other than understanding that this is something that's very easy for a computer to calculate. And if you ever see the loss plus the lambda times w, the sum is w squared. And then let's say we have a ridge regression line, and it does this. We go ahead and plot it, and we do the calculations on the data. And for the ridge regression, let's assume a loss equals 0.3 squared plus 0.2 squared equals 0.13. So when they put all the calculations through of the 2 points, we end up with the 0.62. So we've now had a linear regression model. We now had a ridge regression model. And the ridge regression model plots a little differently than the standard linear regression model. And comparing the two models with all the data points, we can see that the ridge regression line fits the model more accurately than the linear regression line. And I find this true on a lot of data I work with. I'll end up using either the ridge regression model or the Lasso Mars regression model for fitting, especially dealing with a lot of like stock markets daily setup. They come out slightly better. You get a slightly better fit. And so we have our lasso. We just talked about lasso coming in here. And the cost function equals, instead of doing a squared, we're just going to do the absolute value. And so if you remember, this is where ridge regression changes. Where's my ridge regression model? We're squaring the value here. And if you look at this, we're not squaring the value. We're just finding the absolute value on here. And so the loss of the squared individuals, and here is our lambda symbol again, penalty for errors, and w equals the slope of the curve. And comparing the two models with all the data points, we can see that the lasso regression line fits the model more accurately than the linear regression line. And this is, like I said, I use these two models a lot. The ridge, and this is important, this is kind of the meat of the matter. How do you know which one to use? Some of it is you just do it a bunch of times and then you figure it out. Ridge regularization is useful when we have many variables with relatively smaller data samples. The model does not encourage convergence towards zero, but is likely to make them closer to zero and prevent overfitting. The Lasser regularization model is preferred when we are fitting a linear model with fewer variables. So in the iris thing, we had 4 or 5 variables as we measured the different leaf pieces. You might be doing the measurements on the cancer project, which has 36 different variables. So as we get down to the iris with 4 variables, Lasso LAR will probably work pretty good, where you might use the ridge regularization with more model, if you have something significantly larger. And it encourages the coefficients of the variables to go towards zero because of the shape of the constraint, which is an absolute value. And with any of this, we want to go ahead and do a demo in Lasso and ridge regression. So let's take a look and see what that looks like in our code and bring up our Jupyter notebook. We'll start with our imports. Pandas is PD, import NumPy as NP, import Matplotlib as PLT. sklearn, we're going to import our data sets. It's kind of more generic. We usually just import one data set instead of all of them, but you know, quick and dirty when you're putting some of these together. We have our sklearn model selection. We're going to import our train test split for splitting our data up, and then we'll bring in our linear regression model. And we'll go ahead and run these just to load them up, and then load our data set. We were just talking about that. You could just have imported the load Boston and Boston data set in there instead of loading all the data sets. And then once we've loaded our data set, we want to go ahead and take a look at that data and see what we got here. Let me just go ahead and pop that down there and go ahead and run it. And so we've gone ahead and taken our Boston data. We're going to we put it into our pandas data frame. The Boston data set, and then the Boston columns. So we want to see what's going on with them. We have our target, we have the house price, etc. And so our X equals Boston I location. Now remember, in pandas, the new updates to pandas, they want iLocation if you're going to pull data. We used to be able to leave this off, but it does something different. It creates a slice versus a direct setup, so make sure you're using that iLocation. And the output. So this is all just bringing our data together. And we can see here if we do, we print the Boston panda's head, we can see here all of our different aspects we're looking for. And if you're following the X and the Y, the X is everything except for the last column, where Y is that's what this means, all the rows except for the last column, and then Y is all the rows but just the last column. So Y is our house price, and the X is the Crim, Zian, Industry, Chas, Knox, and all these other different statistics they've collected for house sales in Boston. There we go. Whoops, control. So we'll go ahead and split our data. X train and our X test, Y train, Y test equals the train test split, which we imported. And we have our Boston. You could have easily used the X and Y on here as opposed to Boston iLocation. And we'll create our test size. We're going to take 25% of the data and put it in as a test. And then we'll go ahead and run this. Need an extra drink there. So we have our train and test, and then of course the print the train data shape. I love doing this kind of thing whenever I'm working with this data. Print out the shape, make sure everything looks correct, so that we have 127 by 13 and 127 by 1, 379 by 13. They should match. And if the data sets are not quite matching, then you know something's wrong and you're going to get all those errors. I don't know how many times I've gone through here and it's dropped a row on one of them and not on the other, or something weird has happened when I'm cleaning the data. This is pretty straightforward and simple because the data comes in a nice pre-package and is all clean for you. So let's go ahead and apply the multiple linear regression model. And we'll call this LREG, linear regression. And we're going to go ahead and fit that linear regression model to X train and Y train. Then we'll generate the prediction on the test set. So here's our LREG Y predict with our X test going into the prediction. And let's calculate that mean square error, MSE. I told you you'll see MSE used a lot. People use it in variables and things like that. It's pretty common. And we get our mean squared error equals, this is just the basic formula we've already been talking about. What's the difference squared? Then we look for the average of that. And we'll go ahead and just run this. And you can see when we get through the end of this, we have our mean square error on test. We have our total, and then we have each column coming down. And at this point, unless you really know the data you're working with, it's not going to mean a whole lot. So if it's in your domain, you might know what you're looking at when you see these kinds of numbers coming up. But if it's not, it's just a bunch of numbers, and that's okay. At least that's okay for this demo. And then we're going to go ahead and plot these so we can see what's going on. And this is always kind of fun. It's always nice to have a nice visual of what you're looking at. And you can see here, when we plot the coefficient scores on here, and the guys in the back did a great job putting some pretty colors together, making it look nice, and setting up the columns. You can see here, your Knox has like just a huge coefficient. When I look at a table like this, I look for what has very little different coefficients. They're not using a huge change, and what has huge changes. And that flags you for all kinds of things as you're working with the data, but it depends so much on the domain you're working with. These are great things, though, as just a quick look to see what's going on with your data and what you're looking for. And of course, once we look at this, now our motive is to reduce the coefficient score. So now we want to take these and bring them down as much as we can. And for that, we're going to work with the ridge regression on here. So let's start by going ahead and we're going to import our ridge model, the ridge regression from the sklearn library or the scikit. And we're going to go ahead and train the model. So here's our ridge, R equals alpha equals 1. And I mentioned that earlier. When I work with the ridge model, you'll see alpha equals 1. If you set alpha equal to 0, that's a standard linear regression model. So you have alpha equals 1, 2, 3, 4, and you usually use 1, 2, or 3, 4 and a standard integer on there. And we'll go ahead and fit the ridge model on there with our X-train and our Y-train data, generate a prediction for that, for our X-test, and we'll calculate the mean square error, just like we did before. This should all look familiar. And we'll go ahead and print that out, and we'll look at the ridge coefficients for our data and see what that looks like. Now, if I jump up and down between these two, you'll get a headache. You'll still see the Knox value. Let's just look at the Knox, because that was the biggest value, is a -9 here. And if we go back up here, the Knox value is a -18. So right off the bat, I'm seeing a huge change in the biggest coefficient there. So if we're going to do that nice setup, we want to go ahead and just print it and see what that looks like. Here we go. And we've set up our plots, subplots, and again, the team put together some nice colors, so it makes it look good. And we're doing an X bar based on the columns. And our L regress coefficients, color equals color, X spine bottom, and so forth. So just puts together a nice little graph. And you're starting to see, this, when you compare this, if you put it on the same graph as this one up here, this is up here at -18. This is at -9. And so this graph is half the size of the graph above. The same thing with these values here. They might look the same, but they're actually all almost half the value on here. And then finally, you can do the same thing for the lasso regression. This will all look very similar as far as what we worked on before. And I'm just going to go ahead and print that on here and run it. And again, let's go up to Knox. Look where Knox is. It's all the way down to 0. And if we look at our next biggest coefficient, it's -0.8. And really, here's our 22.73. We go up here, 16.7. And we go up here and we look at the same number, 16.69. And so we look at this, if I was running this and working on a project with this, I would look at these numbers. I start with the 16.69, come down here and compare it to 16.78. 6.9 is better than 7.8. So from the very beginning, we might start looking at this first model for overall predicting. But there's other factors involved. We might know that the Knox value is central and the other ones aren't quite as good. And so we might start looking at just certain setups, like what is this particular coefficient, because it might have a certain meaning to us, and so forth. And so you got to look at all those different items in there. Again, but the bottom dollar is our first model did better than our other two models. Our mean square error on the test set continues to come down on this.
We're going to cover reinforcement learning today. And what's in it for you? We'll start with why reinforcement learning. We'll look at what is reinforcement learning. We'll see what the different kinds of learning strategies are that are being used today in computer models under supervised versus unsupervised versus reinforcement. We'll cover important terms specific to reinforcement learning. We'll talk about Markov's decision process, and we'll take a look at a reinforcement learning example. Well, we'll teach a tic-tac-toe how to play. Why reinforcement learning? Training a machine learning model requires a lot of data, which might not always be available to us. Further, the data provided might not be reliable. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. You can see here we have the robot learning to walk. Very complicated setup when you're learning how to walk, and you'll start asking questions like, if I'm taking one step forward and left, well, what happens if I pick up a 50-pound object? How does that change how a robot would walk? These things are very difficult to program because there's no actual information on it until it's actually tried out. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. And we'll see here it learned how to walk. This is going to slow the growth that technology is capable of. Machines need to learn to perform actions by themselves and not just learn off humans. And you see the objective climb a mountain. A real interesting point here is that as human beings we can go into a very unknown environment and we can adjust for it and kind of explore and play with it. Most of the models, the non-reinforcement models in computer machine learning, aren't able to do that very well. There's a couple of them that can be used or integrated. To see how it goes is what we're talking about with reinforcement learning. So what is reinforcement learning? Reinforcement learning is a sub-branch of machine learning that trains a model to return an optimum solution for a problem by taking a sequence of decisions by itself. Consider a robot learning to go from one place to another. The robot is given a scenario and must arrive at a solution by itself. The robot can take different paths to reach the destination. It will know the best path by the time taken on each path. It might even come up with a unique solution all by itself. And that's really important as we're looking for unique solutions. We want the best solution, but you can't find it unless you try it. So when we're looking at our different systems, our different model, we have supervised versus unsupervised versus reinforcement learning. And with the supervised learning, that is probably the most controlled environment. We have a lot of different supervised learning models, whether it's linear regression, neural networks, there's all kinds of things in between, decision trees. The data provided is labeled data with output values specified. And this is important because when we talk about supervised learning, you already know the answer for all this information. You already know the picture has a motorcycle in it, so you're supervised learning. You already know that the outcome for tomorrow, for going back a week, you're looking at stock, you can already have like the graph of what the next day looks like, so you have an answer for it. And you have labeled data which is used, you have an external supervision, and solves problems by mapping labeled input to known output. So very controlled. Unsupervised learning, and unsupervised learning is really interesting because it's now taking part in many other models. They start with you can actually insert an unsupervised learning model in almost either supervised or reinforcement learning as part of the system, which is really cool. Data provided is unlabeled data. The outputs are not specified. Machine makes its own predictions. Used to solve association with clustering problems. Unlabeled data is used. No supervision. Solves problems by understanding patterns and discovering output. So you can look at this and you can think some of these things go with each other. They belong together. So it's looking for what connects in different ways. And there's a lot of different algorithms that look at this. When you start getting into those, there's some really cool images that come up of what unsupervised learning is. How it can pick out, say, the area of a donut. One model will see the area of the donut, and the other one will divide it into 3 sections based on its location versus what's next to it. So there's a lot of stuff that goes in with unsupervised learning. And then we're looking at reinforcement learning. Probably the biggest industry in today's market in machine learning, or growing market. It's very infant stage as far as how it works and what it's going to be capable of. The machine learns from its environment using rewards and errors. Used to solve reward-based problems. No predefined data is used. No supervision. Follows trial and error problem solving approach. So again, we have a random, at first you start with a random, I try this, it works and this is my reward, doesn't work very well maybe, or maybe doesn't even get you where you're trying to get it to do, and you get your reward back, and then it looks at that and says, well, let's try something else, and it starts to play with these different things, finding the best route. So let's take a look at important terms in today's reinforcement model. And this has become pretty standardized over the last few years, so these are really good to know. We have the agent. Agent is the model that is being trained via reinforcement learning. So this is your actual entity that has, however you're doing it, whether you're using a neural network or a Q table or whatever, combination thereof. This is the actual agent that you're using. This is the model. And you have your environment. The training situation that the model must optimize to is called its environment. And you can see here, I guess we have a robot who's trying to get a chest full of gems or whatever, and that's the output. And then you have your action. This is all possible steps that can be taken by the model, and it picks one action. And you can see here that it's picked 3 different routes to get to the chest of diamonds and gems. We have a state, the current position condition returned by the model. And you could look at this if you're playing like a video game. This is the screen you're looking at. So when you go back here, the environment is a whole game board. So if you're playing one of those Mobius games, you might have the whole game board going on, but then you have your current position. Where are you on that game board? What's around that? What's around you? If you were talking about a robot, the environment might be moving around the yard, where it is in the yard and what it can see, what input it has in that location. That would be the current position condition returned by the model. And then the reward. To help the model move in the right direction, it is rewarded. Points are given to it to appraise some kind of action. So, yeah, you did good, or if didn't do as good, trying to maximize the reward and have the best reward possible. And then policy. Policy determines how an agent will behave at any time. It acts as a mapping between action and present state. This is part of the model. What is your action that you're going to take? What's the policy you're using to have an output from your agent? One of the reasons they separate policy as its own entity is that you usually have a prediction of different options, and then the policy, well, how am I going to pick the best? Based on those predictions, I'm going to guess at different options, and we'll actually weigh those options in and find the best option we think will work. So it's a little tricky, but the policy thing is actually pretty cool how it works. Let's go ahead and take a look at a reinforcement learning example. And just in looking at this, we're going to take a look, consider what a dog that we want to train. So the dog would be like the agent. So you have your puppy or whatever. And then your environment is going to be the whole house or whatever it is where you're training them. And then you have an action. We want to teach the dog to fetch. So action equals fetching. And then we have a little biscuit, so we can get the dog to perform various actions by offering incentives such as a dog biscuit as a reward. The dog will follow a policy to maximize this reward, and hence will follow every command and might even learn new actions like begging by itself. So you have, so we start off with fetching. It goes, oh, I get a biscuit for that. It tries something else, and you get a handshake or begging or something like that, and it goes, oh, this is also reward based, and so it kind of explores things to find out what will bring it as biscuit. And that's very much like how a reinforced model goes. Is it looks for different rewards. How do I find? Can I try different things and find a reward that works? The dog also will want to run around and play and explore its environment. This quality of model is called exploration. So there's a little randomness going on in exploration. And it explores new parts of the house. Climbing on the sofa doesn't get a reward. In fact, it usually gets kicked off the sofa. So let's talk a little bit about Markov's decision process. Markov's decision process is a reinforcement learning policy used to map a current state to an action where the agent continuously interacts with the environment to produce new solutions and receive rewards. And you'll see here's all of our different vocabulary we just went over. We have a reward, our state, our agent, our environment, and our action. And so even though the environment kind of contains everything, that you really, when you're actually writing the program, your environment's going to put out a reward and state that goes into the agent. The agent then looks at this state, or it looks at the reward usually first, and it says, okay, I got rewarded for whatever I just did, or I didn't get rewarded. And then it looks at the state, and then it comes back, and if you remember from policy, the policy comes in, and then we have a reward. The policy is that part that's connected at the bottom. And so it looks at that policy and it says, hey, what's a good action that will probably be similar to what I did, or sometimes they're completely random, but what's a good action that's going to bring me a different reward? So taking the time to just understand these different pieces as they go is pretty important in most of the models today. And so a lot of them actually have templates based on this that you can pull in and start using. Pretty straightforward as far as once you start seeing how it works, you can see your environment says, hey, this is the agent did this. If you're a character in a game, this happened, and it shoots out a reward in a state. The agent looks at the reward, looks at the new state, and then takes a little guess and says, I'm going to try this action. And then that action goes back into the environment. It affects the environment. The environment then changes depending on what the action was. And then it has a new state and a new reward that goes back to the agent. So in the diagram shown, we need to find the shortest path between node A and D. Each path has a reward associated with it, and the path with a maximum reward is what we want to choose. The nodes A, B, C, D denote the nodes to travel from node A to B is an action. Reward is the cost of each path, and policy is each path taken. And you can see here A can go to B, or A can go to C right off the bat, or it can go right to D. And if you explored all three of these, you would find that A going to D was a 0 reward, A going to C and D would generate a different reward, or you could go A, C, B, D. There's a lot of options here. And so when we start looking at this diagram, you start to realize that even though today's reinforced learning models do really good at finding an answer, they end up trying almost all the different directions you see. And so they take up a lot of work or a lot of processing time for reinforcement learning. They're right now in their infant stage, and they're really good at solving simple problems. And we'll take a look at one of those in just a minute in a tic-tac-toe game. But you can see here, once it's gone through these and it's explored, it's going to find the A, C, D is the best reward. It gets a full 30 points for it. So let's go ahead and take a look at a reinforcement learning demo. In this demo, we're going to use reinforcement learning to make a tic-tac-toe game. You will be playing this game against the machine learning model. And we'll go ahead, and we're doing it in Python. So let's go ahead and go through not always, I actually have a lot of Python tools. Let's go through Anaconda, which will open up a Jupyter notebook. Seems like a lot of steps, but it's worth it to keep all my stuff separate, and it also has a nice display when you're in the Jupyter notebook for doing Python. So here's our Anaconda navigator. I open up the notebook, which is going to take me to a web page, and I've gone in here and created a new Python folder. In this case, I've already done it and enabled it to change the name to Tic-Tac-Toe. And then for this example, we're going to go ahead and import a couple things. We're going to import numpy as np. We'll go ahead and import pickle. Numpy, of course, is our number array, and then pickle is just a nice way sometimes for storing different information, different states that we're going to go through on here. And so we're going to create a class called state. We're going to start with that. And there's a lot of lines of code to this class that we're going to put in here. Don't let that scare you too much. There's not as much here. It looks like there's going to be a lot here, but there really is just a lot of setup going on in our class state. And so we have up here, we're going to initialize it. We have our board. It's a tic-tac-toe board, so we're only dealing with 9 spots on the board. We have player 1, player 2 is end. We're going to create a board hash. We'll look at that in just a minute. We're just going to store some information in there. Symbol of player equals 1. So there's a few things going on as far as the initialization. Then something simple, we're just going to get the hash of the board. We're going to get the information from the board on there, which is columns and rows. We want to know when a winner occurs. So if you get 3 in a row, that's what this whole section here is for. Let me go ahead and scroll up a little bit. And you can get a copy of this code if you send a note over to Simplilearn. We'll send you over this particular file, and you can play with it yourself and see how it's put together. I don't want to spend a huge amount of time on this because this is just some real general Python coding. But you can see here we're just going through all the rows, and you add them together, and if it equals 3 in a row. Same thing with columns. Diagonal, so you got to check the diagonal. That's what all this stuff does here, is it just goes through the different areas. Actually, let me go ahead and put, there we go. And then it comes down here and we do our sum, and it says true, -3 just says did somebody win or is it a tie. So you got to add up all the numbers on there anyway, just in case they're all filled up. And next we also need to know available positions. These are ones that no one's ever used before. This way when you try something or the computer tries something, it's not going to give it an illegal move. That's what the available positions is doing. Then we want to update our state. And so you have your position going in. We're just sending in the position that you just chose. And you'll see there's a little user interface we put in there. You can pick the row and column in there. And again, I mean, this is a lot of code. So really it's kind of a thing you'd want to go through and play with a little bit and just read through it, get a copy of it. A great way to understand how this works. And here is a given reward. So we're going to give a reward, result equals self winner. This is one of the hearts of what's going on here, is we have a result self.winner. So if there's a winner, then we have a result. If the result equals 1, here's our feedback. If it doesn't equal 1, then it gets a 0. So it only gets a reward in this particular case if it wins. And that's important to know because different systems of reinforced learning do rewarding a lot differently depending on what you're trying to do. This is a very simple example with a 3x3 board. Imagine if you're playing a video game, certainly you only have so many actions, but your environment is huge. You have a lot going on in the environment. And suddenly a reward system like this is going to be just, it's going to have to change a little bit. It's going to have different rewards and different setup. And there's all kinds of advanced ways to do that as far as weighing, you add weights to it. And so they can add the weights up depending on where the reward comes in. So it might be that you actually get a reward. In this case, you get the reward at the end of the game. And I'm spending just a little bit of time on this because this is an important thing to note. But there's different ways to add up those rewards. It might have, like if you take a certain path, the first reward is going to be weighed a little bit less than the last reward because the last reward is actually winning the game or scoring or whatever it is. So this reward system gets really complicated in some of the more advanced setups. In this case, though, you can see right here that they give a 0.1 and a 0.5 reward just for picking the right value and something that's actually valid instead of picking an invalid value. So rewards, again, that's like key. It's huge. How do you feed the rewards back in? Then we have a board reset. That's pretty straightforward. It just goes back and resets the board to the beginning because it's going to try out all these different things while it's learning. It's going to do it by trial and error, so you have to keep resetting it. And then, of course, there's the play. We want to go ahead and play rounds equals 100. Depends on what you want to do on here. You can set this different. You can obviously set that to higher level. But this is just going to go through, and you'll see in here that we have player 1 and player 2. This is the computer playing itself. One of the more powerful ways to learn to play a game or even learn something that isn't a game is to have two of these models that are basically trying to beat each other. And so they keep explore new things. This one works for this one, so this one tries new things. It beats this. We've seen this in chess, I think was a big one, where they had the two players in chess with reinforcement learning. It was one of the ways they trained one of the top computer chess playing algorithms. So this is just what this is. It's going to choose an action, it's going to try something, and the more it tries stuff, the more we're going to record the hash. We actually have a board hash where they get the hash set up on here where it stores all the information. And then once you get to a win, one of them wins, it gets the reward. Then we go back and reset and try again. And then kind of the fun part we actually get down here is we're going to play with a human. So we'll get a chance to come in here and see what that looks like when you put your own information in. And then it just comes in here and does the same thing it did above. It gives it a reward for its things, or sees if it wins or ties, looks at available positions, all that kind of fun stuff. And then finally we want to show the board. So it's going to print the board out each time. Really, as an integration, is not that exciting. What's exciting in here is one, looking at this reward system. Whoops, play one more up. The reward system is really the heart of this. How do you reward the different setup? And the other one is when it's playing, it's got to take an action. And so what it chooses for an action is also the heart of reinforcement learning. How do we choose that action? And those are really key to right now where reinforcement learning is in today's technology, is figuring this out. How do we reward it, and how do we guess the next best action? So we have our environment, and you can see the environment is or the state, which is kind of like what's going on. We're going to return the state depending on what happens. And we want to go ahead and create our agent, in this case our player. So each one is, let me go and grab that. And so we look at a class player. This is where a lot of the magic is really going on, is how is this player figuring out how to maneuver around the board, and then the board of course returns a state that it can look at and a reward. So we want to take a look at this. We have name, self-state. This is class player. And when we say class player, we're not talking about a human player. We're talking about just the computer players. And this is kind of interesting. So remember I told you, depending on what you're doing, there's going to be a decay gamma, explore rate. These are what I'm talking about, is how do we train it? As you try different moves, it gets to the end. The first move is important, but it's not as important as the last one. And so you could say that the last one has the heaviest weight, and then as you get there, the first one, let's see, the first move gives you a 5 reward, the second gives you a 2 reward, and the third one gives you a 10 reward, because that's the final ending. You got it. The 10's going to count more than the first step. And here's our, we're going to get the board information coming in, and then choose an action. This was the second part that I was talking about that was so important. So once you have your training going on, we have to do a little randomness, and you can see right here is our NP random uniform. So it's picking out a random number. Take a random action. This is going to just pick which row and which column it is. And so choosing the action, this one you can see we're just doing random states, choice, length of positions, action position, and then it skips in there and takes a look at the board for P in positions. And it's actually storing the different boards each time you go through, so it has a record of what it did, so it can properly weigh the values. And this simply just appends a hash state. What's the last state? Append it to the to our states on here. Here's our feedback reward. So the reward comes in, and it's going to take a look at this and say, is it none? What is the reward? And here is that formula. Remember I was telling you about up here that was important because it has decay gamma times the reward. This is where, as it goes through each step, and this is really important. This is kind of the heart of this, of what I was talking about earlier. You have step 1, and this might have a reward of 2. You have step 2. I probably should have done ABC. This has a step 3, step 4, and so on until you get to step N. And this might have a reward of 10. So reward of 10. We're going to add that, but we're not adding, let's say this one right here, let's say this reward here right before 10 was, let's say it's also 10. That just makes the math easy. So we had 10 and 10. We had 10, this is 10 and 10n, whatever it is, but it's 0.9. So instead of putting a full 10 here, we only do 9. That's 0.9 times 10. And so this formula, as far as the decay times the reward minus the cell state value, it basically adds in, it says here's 1, or here's 2, I'm sorry, I should have done this ABC, it would have been easier. So the first move goes in here and it puts 2 in here. Then we have our self set up on here. You can see how this gets pretty complicated in the math, but this is really the key, is how do we train our states? And we want the final state, the win, to get the most points. If you win, you get most points. And the first step gets the least amount of points. So you're really training this almost in reverse. You're training it from the last place where you have, like it says, okay, this is now where I need to sum up my rewards, and I want to sum them up going in reverse, and I want to find the answer in reverse. Kind of an interesting play on the mind when you're trying to figure this stuff out. And of course we want to go ahead and reset the board down here and save the policy, load policy. These are the different things that are going in between the agent and the state to figure out what's going on. Let's go ahead and load that up. And then finally we want to go ahead and create a human player. And the human player is going to be a little different in that you choose an action, row and column. Here's your action. If action in positions, meaning positions that are available, you return the action. If not, it just keeps asking you until you get the action that actually works. And then we're going to go ahead and append to the hash state, which we don't need to worry about because it returns the action up here, and feed forward. Again, this is because it's a human. At the end of the game, backpropagate and update state values. This part isn't being done because it's not programming the model. The model is getting its own rewards. So we've gone ahead and loaded this in here. So here's all our pieces, and the first thing we want to do is set up P1 player 1, P2 player 2, and then we're going to send our players to our state. So now it has P1, P2, and it's going to play, 50,000 rounds. Now we can probably do a lot less than this, and it's not going to get the full results. In fact, you know what? Let's go ahead and just do 5, just to play with it, because I want to show you something here. Oops, somewhere in there I forgot to load something. There we go. I must have forgot to run this. Run. Oops, forgot a reference there for the board, rows and columns, 3 by 3. There is actually in the state, it references that. We can just tack it on the end. It was supposed to be at the beginning. So now I've only set this up with, let's see, where are we going here? I've only set this up to train 5 times. And the reason I did that is we're going to come in and actually play it, and then I'm going to change that, and we can see how it differs on there. There we go. And it didn't even make it through a run, and we're going to go ahead and save the policy. So now we have our player 1 and our player 2 policy. The way we set it up, it has 2 separate policies loaded up in there. And then we're going to come in here, and we're going to do player 1 is going to be the computer, experience rate 0, load policy 1, human player human, and we're going to go ahead and play this. Now remember, I only went through it just 1 round of training, in fact minimal training, and so it puts an X there, and I'm going to go ahead and do row 0, column 1. And you can see this is very basic on here, and so I put in my 0, and then I'm going to go 0, block it, 0, 0, and you can see right here it let me win. Just like that, I was able to win. 0, 2, and woo, human wins. So I only trained it 5 times. We're going to run this again, and this time, instead of 5, let's do 5,000 or 50,000. I think that's what the guys in the back had. And this takes a while to train it. This is where reinforcement learning really falls apart. Look how simple this game is. We're talking about a 3 by 3 set of columns. And so for me to train it on this, I could do a Q table which would go much quicker. You could build a quick Q table with almost all the different options on there, and you would probably get the same result much quicker. We're just using this as an example. So when we look at reinforcement learning, you need to be very careful what you apply it to. It sounds like a good deal until you do like a large neural network where you're doing, you set the neural network to a learning increment of 1, so every time it goes through it learns, and then you do your action, so you pick from the learning setup, And you actually try actions on the learning setup until you get what you think is going to be the best action. So you actually feed what you think is right back through the neural network. There's a whole layer there, which is really fun to play with. And then it has an output. Well, think of all those processes. I mean, that is just a huge amount of work it's going to do. Let's go ahead and skip ahead here. Give it a moment. It's going to take a minute or two to go ahead and run. Now, to train it, we went ahead and let it run, and it took a while. This took, I got a pretty powerful processor, and it took about 5 minutes plus to run it. And we'll go ahead and run our player setup on here. Oops, it brought in the last, whoops, it brought in the last round. So give me just a moment to redo the policy save. There we go. I forgot to save the policy back in there. And then go ahead and run our player again. So we've saved the policy, and then we want to go ahead and load the policy for P1 as a computer. And we can see the computer's gone in the bottom right corner. I'm going to go ahead and go 1, 1, which is the center. And it's gone right up the top, and if you have ever played Tic-Tac-Toe, you know the computer has me. But we'll go ahead and play it out. Row 0, column 2. There it is, and then it's gone here, and so I'm going to go ahead and go row 0, 1, 2, no, 0, 1, there we go, and column 0. That's where I wanted. Oh, and it says, okay, your action, there we go, boom. So you can see here, we've got didn't catch the win on this, it said tie. Kind of funny that it didn't catch the win on there. But if we play this a bunch of times, you'll find that it's going to win more and more. The more we train it, the more the reinforcement happens. This lengthy training process is really the stopper on reinforcement learning. As this changes, reinforcement learning will be one of the more powerful packages evolving over the next decade or two. In fact, I would even go as far as to say it is the most important machine learning tool and artificial intelligence tool out there, as it learns not only a simple tic-tac-toe board, but we start learning environments. And the environment would be like in language. If you're translating a language or something from one language to the other, so much of it is lost if you don't know the context it's in, what's the environments it's in. And so being able to attach environment and context and all those things together is going to require reinforcement learning to do. So again, if you want to get a copy of the tic-tac-toe board, it's kind of fun to play with. Run it, you can test it out, you can do test it for different values. You can switch from P1 computer where we loaded the policy 1 to load the policy 2 and just see how it varies. There's all kinds of things you can do on there.
Imagine you are a robot in a maze, and every step you take brings you closer to the treasure or into the trap. But here's the catch. You don't have a map. So how will you figure out the best path without any guidance? This is where Q-learning steps in, one of the most exciting branches of reinforcement learning. It is like teaching an agent or a robot to play a game of trial and error, learning to maximize rewards and avoid penalties, all without knowing the rules in advance. In this tutorial, we will dive into the core concepts behind Q-learning, from understanding how an agent explores its environment to making smart decisions that leads to victory. Now, before we move on and learn more about Q-learning, I request you guys that do not forget to hit the subscribe button and click the bell icon for further updates. So let's start by understanding first, what is Q-learning? So Q-learning is a type of reinforcement learning which is basically used in machine learning algorithms to find optimal action selection policy for any given problem for reinforcement learning. Now you'll be wondering what this type of technical jargon means. So let me tell you in easy words what reinforcement learning exactly means and how Q-learning is a part of it. So let us consider a scenario. Imagine there is a robot whose task is basically to clean the room, a kind of vacuum cleaner robot. In that room, there would be obstacles like furniture, and there are dirt scattered around. The goal of this robot is to learn how to clean the room efficiently. Now, there are certain points. So, this is called learning by rewards. So, we have +1 for positive reward if the given vacuum cleaner cleans up the dirt. We have -1 or negative reward for bumping into the walls or any furnitures. And we have the higher plus 10 reward for this robot when it completes the cleaning of a room in a shorter period of time. Now, if we talk about this kind of learning, how this robot is learning, so suppose this robot starts up to cleaning the room. Now, after it has started to clean the room, it found some obstacle and it got collided with this. So it learned that it is getting -1 for the same. So next time when it encountered any obstacles, it just ignores it, or it just changes its direction. And this is called learning by rewards. So in this scenario, we have the agent as robot. The environment which we have is room full of dirt, furnitures and wall. Now if I talk about actions, then we can say the robot can move left, right, backward or forward. So this is a scenario that we have set up for our robot. So by trial and error, the robot learns a strategy or a policy that maximizes its reward by avoiding obstacles, prioritizing areas with more dirt, and move efficiently to cover the entire room. Eventually, after enough learning episodes, the robot vacuum develops an optimal cleaning strategy, navigating the room without getting stuck and cleaning it in the shortest time possible. But this is the scenario for the reinforcement learning. And under this comes the Q learning. So, in the simpler words, if I have to say, then Q learning is basically a machine learning approach that enables a model to iteratively learn and improve over time by taking the correct action, which means the optimal action selection policy. So as we have seen in the example, how this robot has maximized its total reward by avoiding obstacles, prioritizing areas with more dirt, and moving efficiently to cover the entire room. So this is one of the examples of reinforcement learning. So this is basically a Q learning approach. Okay, so this is a part of machine learning. Now let's move ahead and try to understand the components of Q learning. Now if I talk about Q learning, guys, so now discover the key components of Q learning. The first one that we have all over here is state, action and rewards. So basically Q learning revolves around it. Now let us dive deep into it and understand more of the key components. So if we talk in depth about the key components, so we have the Q values or the action values we have. So if I talk about Q values, guys, Q values are basically defined for states and action. So it is written as QS of A, which is an estimation of how good is it to take an action at a given state S. And this estimation of Q of S of A will be iteratively computed using the TD update rule, or we can say temporal difference update rule, which we are going to see in our given example. So if I talk about rewards and episodes, so we can see all over here that an agent, like throughout its lifetime, starts from a start state and makes several transitions from its current state to the next state based on its choice of action and also the environment the agent is interacting in. So at every step of transition, the agent from state takes an action, observes the reward from the environment, and also then do the transition to the another state. So for example, if at any point of time, the agent ends up in one of the terminating states, okay, that means like there are no further transitions possible. So this is meaning that it is completed one episode. So this is rewards and episodes for the same. The next that we have all over here is temporal difference. So the temporal difference update rule. Now if we talk about temporal difference, it could be written something like this. So you can see an equation all over here. So this shows the temporal difference equation, where we have Q of S of A, and this is being redirected all over here. So Q of S of A plus an alpha R plus gamma Q of new values of SNA and minus Q of SNA. So what is this basically? So if we talk all over here, this is basically an update rule. Okay, I'll write all over here. Now, this update rule basically what it does, guys, that it is applied at every time at the step of agent's interaction with the environment. Now, you would be wondering what S and A are. So S, if I talk about S is, so if I talk about S means the current state of the agent. And if I talk about A, It is according to the current action picked according to the policy. Now, if I talk about the change S dash, so it is means the next state where the agent ends up. And if I talk about A dash all over here, so it means that next best action, okay, to be picked using the current Q value. So these are the certain definitions all over here. And if I talk about certain other variables all over here, so we have also seen in this equation, we have R, alpha and gamma. Let us discuss about R, alpha and gamma. Okay. Now, if I talk about R, guys, so R here is, the current reward, which is basically observed from the environment in response of the current action. Okay. So if we talk about R, guys, R means current reward observed. Then if I talk about gamma, okay, so gamma here means there are two conditions. Either it should be greater than or equal to 0, okay, or it can be less than equal to 1. Now, this is basically a discounting factor. This means that gamma is a discounting factor in our given determination of the Q values. And this is basically for future rewards. So future rewards are less valuable than the current rewards, so they must be discounted. Okay, so this is a logic for it. And since Q value is an estimation of expected rewards, okay, so here from a given state, the discounting rule also applies all over here. So for the same purpose, we'll be using gamma. And if I talk about alpha all over here, so alpha is a step length basically. Okay, let's remember it. Alpha is a step length which is here taken to estimate the update estimation of Q of S of A. Okay, so this is basically a step length, how much steps it takes to update, how much this given state of the robot is, updated. Basically, the step length taken to update the estimation of this factor or this Q of S of A. This is the alpha. Now, we have understood the temporal difference, how we have calculated using this formulation, okay, and what are the mathematical variables involved in this step. Now, finally, we have exploration and exploitation. So basically, exploration and exploitation comes under selecting the course of action with a greedy policy, which is basically a simple method for selecting an action to take based on the current estimates of the Q value. So here the greedy policy applies. Now, if I talk about exploitation all over here, it means the superior Q value action. So we have the probability all over here that there will be certain probability, and the factor epsilon all over here, it should be less than that. Now, exploitation means all over here that to use its current knowledge, and explore means try new things. So here the E-greedy policy helps the agent to decide what to do, whether to exploit means to use its current knowledge or to explore, try new things. So let me tell you the mathematical formulation for the same. So if I talk about exploitation, so here most of the time there is a probability of 1 minus E, okay, so it is basically epsilon, and here the agent will pick the action that has currently the highest quick value. So if I talk about exploitation, guys, it means that it is using the current knowledge, and most of the time with a probability of 1 minus E or 1 minus epsilon. So here the agent will pick the action that currently has the highest Q value, and this is called exploitation because the agent is using its current knowledge to choose what it thinks is the best for the action. If I talk about exploration all over here, it means trying new things. So here we have the small probability E, okay, the same E that we are using all over here. Now, the agent will take up a random action instead of the best known action, and this is called as exploration, because the agent is trying to discover if there are better options available or not. So by balancing the exploitation and exploration, the agent can learn better over time. If it only exploits, it might miss discovering the better strategies that are available. And also, if it explores too much, it might waste the time on bad actions. So the E-greedy policy, okay, which helps us to decide what agent should do, basically combine both exploitation and exploration. So this is a method which helps the agent to find the right balance between doing what it knows is best and trying new things to improve its knowledge. Now, if I talk about determining Q value, then here we have the two techniques. But what is Q value exactly? Q value is the matrix that is used to evaluate actions at a specific state. So, as we have discussed in the given example of the robot, so there can be a various state for a robot. So we have to calculate the matrix which will be helping us to evaluate what action should be taken at this specific states. So there are two ways to calculate the Q values. The first one is the temporal difference that we have discussed. The second one is Bellman's Ford equation. Q of S of A, R of S of A, gamma max, Q of S of dash and A. Since we have discussed all about it, okay. Now, if I talk about temporal difference, it is calculated by comparing the current state and action values with the previous one. And Bellman's Ford equation is a recursive equation, okay, which is basically a formula invented by the scientist Bellman Ford. And it is used to calculate the value of a given state and determine its optimal position. It provides also a recursive formula for calculating the value of a given state. So in a Markov's decision process, so it's a mathematical term that we use for the stochastic processes, and in particularly it is very, very influential, or you can say very much important in the context of Q learning and optimal decision making. So this equation that I have shown you earlier is also very, very important in determining the Q value. Now, similarly, we create the Q table. So Q table is a repository of rewards, basically, which is associated with the optimal actions for each state in a given environment. It basically serves as a guide for the agent, which helps it to determine which actions are likely to yield the best outcomes. So agent will always be interacting with the Q table and dynamically update the reflected agents in the evolving understanding and also enabling more informed decision making. Now, let us try to implement the Q learning environment. So there are certain steps that we have to follow. The step one will be defining the environment. So let us type step one, that we have defining the environment. So here we have to set up our environment parameters, including like number of states, action, and initialize the Q table. So let us mention all over here that we have like number of states, okay, we have actions and initializing the Q table. Now, in the next step, all we have to set up the hyperparameters. Now, if I talk about setting up the hyperparameters, so with respect to the Q learning algorithm, we have to include the learning rate, okay. We have to also include the discount factor. We have to include the exploration probability. We have to also train the number of training epochs. So this is the parameters that we have involved in the second step. Now in the step 3, we have to implement the Q learning algorithm. So we will be performing Q learning algorithm over multiple of epochs. So each epoch will be involving selecting the action based on epsilon greedy strategy and also updating the Q values based on rewards received, and also that will help us in transitioning to the next state. Now, so you'll be wondering what epochs means, okay? So in a machine learning algorithm, an epoch is basically a complete pass of a training data which is set through an algorithm. So it means that it is a single pass of the entire training data set. So the model updates its internal calculation after each epoch, means the entire training data set that we have taken, to study basically for our given model. So that is an epoch, the single pass. So when all the training data is used at once and it is defined as a total number of iterations of all the training data in one cycle for a given training, then for that machine learning model, it is called an epoch. Okay. So I hope so you would have got an idea regarding epochs. Now let us try to code this in Python. So you can see all over here. So this is a given code for our Q-learning algorithm. So here I'm importing NumPy as NP. Okay, that is our library that we'll be using. Then here we are defining the environment. Okay, the first one is number of states. Okay, say n equals to 16. Then number of actions, so number of possible actions that we have discussed for a given robot. So up, down, left and right. And what is the goal state? Okay, so this is our environments that we have set up. So we have states, action, okay, and goal state. Now we'll be initializing our Q table with 0. So for the same purpose, we'll be using NumPy. So np.zeros, and here we have n states and action. So we have initialized our Q table. Now we are defining the parameters all over here. So we have the learning rate at 0.8, discount factor, we have given certain value, exploration probability, and epochs. So I have told you about epochs, guys. So epochs here means that when all the training data is used at once, and it is defined as a total number of iterations for all the training data in one cycle for a training. So that is epoch, and that we have set to 1000. Now for the Q learning, so we have taken this epoch. Okay, so for epoch, in the range of epochs, this is iteration. So we are setting the current state. Okay, so we are using np.random, and it is taking a random integer. It is starting from any random state all over here. This line means that same. So now we are using the conditional. So while the current state is not equal to the goal state, okay, this is our goal state that we have to achieve. Okay, that is 50. So choose an action with the epsilon greedy strategy. So here we have applied the logic for the same. So if np.random.rand is less than exploration probability, then our current action is set to np.random.randend, and here 0n action. So if I talk about n action, means number of possible actions that can go up, which can be up, down, left and right. So it is choosing the best action with the epsilon greedy strategy, or else we are putting the action as np argmax, and now we are updating the Q table with respect to the current state. This is the exploitation. So based on your Q table, choose the next state. So this is like selecting, what should an agent do? It should explore or exploit. So for exploitation, it is using the Q table that we have initialized earlier, and for exploration, it is using the np random.randend, and it is choosing the action up, down, left and right. So based on the probability of epsilon, the exploration action is also going to happen. Now we have to simulate the environment or move to the next state. So here the next state is set to current state plus 1 modulo n states. Now you can see we have initialized the n states as 16. So number of states available total. Okay, consider it as a grid. So based on that, now here what we have done, defining a simple reward function. Okay, so here if the goal state is reached, so you will be given 1 point, otherwise the probability will be 0. So reward is 1 if the next state goal equals to goal state, otherwise put it up as 0. Now we have to update the Q value. So all over here we have updated the Q value. So Q current state and action plus learning rate multiplied by reward plus discount factor multiplied np max, and in parentheses we have Q table and the next state minus Q table current state and action. So this is basically the formulation which I have told you how the updating Q value happens with the help of Bellman-Ford's equation. Okay, now I'll write all over here. Now finally you are moving the current state to the next state, and after training you are printing the learned Q values. Now let us try to run this. Make sure that your server is connected. So you can see we have got the learned Q table. So we have all the possible values all over here, okay? And in this way, the agent is going to select from this Q table, okay, which action should take. So based on the given data that we have given, we have successfully, created our Q table with the help of NumPy. So this was a very simple example to showcase you how the robots in our present scenario, like which are learned robots, which can, tackle the obstacles and also learn, which step to take next. So this is one type of the reinforcement learning, and I hope so you would have got a brief idea regarding this algorithm.
Learning objectives. Welcome to Math Refresher, Linear Algebra. In this lesson, we are going to explain the concepts of linear algebra, solve a linear system of equations, describe matrix, forms of matrix and matrix operations, and define vectors and list down its properties. Introduction to linear algebra. Linear algebra. Linear algebra refers to study of linear combinations. For linear transformations to be carried out, a study of vector spaces, lines, and planes, as well as some mappings is necessary. It contains linear functions, vectors, and matrices. It is an examination of characteristic of linear set transformations. Linear equations. Linear algebra's major goal is to establish systematic techniques for solving systems of linear equations. A linear equation with n variables can be represented as a1x1 plus a2x2 plus a3x3 and so on till an xn equals to b, where x1, x2, x3 and so on till xn are the unknown quantities that are to be found, while a1, a2, a3 and so on until an are the coefficients. B here is a constant term. A linear equation with two variables, x and y, is a linear connection between x and y. The value of one variable, often y, is determined by the value of the other, that is x. The independent variable in this situation is x, while the term dependent variable refers to y. Since it depends on x, let's consider some examples for linear equations. Linear equations in one variable can be written as 3x plus 5 equals 0, or 3 by 2 of x plus 7 equals to 0, or 98x equals to 49. Linear equations in two variables. Examples can include y plus 7x equals to 3, or 3a plus 2b equals to 5, 6x plus 9, y minus 12 equals to 0. Linear equations can also be written with three variables as x plus y plus z equals to 0, a minus 3b equals to c, 3x plus 12 y equals to half of z. Identifying linear and nonlinear equations. Linear equations present themselves as a straight line on a graph. However, nonlinear equations represent themselves as a non-straight line on the graph. Here, equations like y equals to 8x minus 9 or y plus 3x minus 1 equals to 0 are examples of linear equations. However, y equals to x squared minus 7 is a nonlinear equation because x is raised to the power 2. Hence, denoting a nonlinear relationship or a non-straight line relationship between x and y. Similarly, square root of y plus x equals to 6 or y raised to the power 2 minus x equals to 9 are examples of nonlinear equations, as y is raised to the power half and 2 respectively. Forms of linear equation. Linear equations can be represented in three forms: a standard form, a slope-intercept form, or a point-slope form. Linear equation in standard form. A linear equation in standard form for a single variable can be represented as a x plus b equals to 0. where a and b are real integers and x is the variable. While a linear equation in standard form for two variable can be represented as ax plus by equals 2c, where a, b, and c are real integers, while x and y are the variables. To summarize, a linear equation for variables can be written as ax plus by equals to c, where x and y are the variables. C is the constant and a and b are the coefficients of x and y respectively. Linear equation in the slope-intercept form. A linear equation slope can be calculated to see how one variable varies in response to a unit change in another variable. It is represented as y equals to mx plus b, where m is the slope, b is the intercept on the y-axis and x, and y are the line's distance from the x and the y-axis respectively. Consider this example. The line's point x, y represents the distance from the x and the y-axis respectively, while the line intercept on the y-axis is at point 0, b. Linear equation slope. The slope indicates how steep a line is with respect to y-axis. When seen from left to right, it indicates whether the line goes up or down. The slope describes how independent variable has been changed, while the dependent variable is changing. Types of slope. There are 4 types of slopes based on the relationship between the two variables x and y. The first is the positive slope here as x increases. Y is also increasing in a negative slope as x increases. Y decreases. If a line is parallel to x-axis, it is a 0 slope. On the other hand, if the line is parallel to y-axis, then the slope is undefined. Linear equation in point-slope form. A straight line is represented in point-slope form by its slope, and a point on the line. It is represented as y minus y1 equals to m of x minus x1, where x1 and y1 are the coordinates of the point. Linear equation forms, some examples. Consider solving the linear equation given as 2x minus 10 divided by 2 equals to 3x minus 1. First, we will clear the fraction. In this example, we can see only left-hand side we have 2x minus 10 divided by 2. If from the numerator we take 2 as common, we will be left with 2 times x minus 5 divided by 2, hence x minus 5 on the left-hand side. On the right-hand side, we still have 3 times x minus 1. Now, as a part of next step, we simplify both sides of the equation that is open up the brackets. When we do that on the right side, we end up getting 3x minus 3 by multiplying 3 to x minus 1. Solving further, we can write as x equals to 3x plus 2. Finally, we try to clear the fraction to solve for x. We can rearrange the equation as x minus 3x equals to 2. Solving it further, we get minus 2x equals to 2. And then we solve for x as minus 1. System of linear equation. A system of linear equations is a finite collection of linear equations, usually involving the same variables. It can be represented as a11x1 plus a12x2, and so on equals to b1, a21x1 plus a22x2, so on equals to b2, and so on. Here this example is for n variables. A system of m equations. A linear system can have unlimited number of solutions. One solution or no solution at all. In case of a single linear equation, a consistent linear system has a solution, while an inconsistent linear system has no solution. Solving a linear equation. Solving linear system of equations. Various methods can be used to solve linear system of equations, which include graphic method, substitution method, linear combination or elimination method, or a matrix method. Graphing method. Let's try and solve these two linear equations using the graphic method. The first equation is defined as y equals 0.5x plus 2, and the second equation is y equals to minus 2x minus 3. The two equations, as we can see, are in the slope-intercept form. The first line has a slope of 0.5 and a y-intercept of positive 2, while the second line has a slope of negative 2 and a y-intercept of negative 3. Let's have a look at these lines through a plot. Here, the blue line is the first line represented by y equals 2.5x plus 2. And the red line is represented by y equals to negative 2x negative 3. These two lines intersect at a point at negative 2, 1. Hence we can say that x equals to negative 2 and y equals to 1. Solving systems of linear equation using substitution. For substitution, we start by putting one of the equations in the form of variable equals to. We then substitute that variable in the other equation in its place. Take the other equation to solve. If there are more than two variables involved, we repeat the process from steps 1 through 3. Let's consider an example. Let's consider the equation 3x plus 2 y equals to 19 and x plus y equals to 8. We could begin with any equation and variable. In this case, let's look at the second equation with variable y. We start with subtracting x from both sides of x plus y equals to 8. And we end up getting y equals to 8 minus x. The first equation still retains its form. Now we take the value of y, that is 8 minus x, and substitute in the first equation in place of y. We end up getting the equation 3x plus 2 times 8 minus x equals to 19. We further simplify and solve this equation using algebra method to get 3x plus 16 minus 2x equals 290. We solve this equation further, and we end up getting x plus 16 equals to 19, and finally x equals to 3. Now we take the value of x and substitute in the new reformed second equation as y equals to 8 minus x. That gives us y equals to 8 minus 3, hence y equals to 5. The final answer remains x equals to 3 and y equals to 5. Solving systems of linear equation using elimination. In this case, we start by multiplying an equation by a constant anything other than 0. We then add or subtract an equation onto the other equation. Let's consider the same example of 3x plus 2, y equals to 19 and x plus y equals 8. We first start by multiplying the second equation by 2, and we get 2x plus 2, y equals 216. Now we subtract the second equation from the first equation. That is 3x minus 2x, 2y minus 2y, and 19 minus 60. On solving this, we end up getting x equals to 3. Now using these steps of substitution, we put the value of x in the original second equation, that is x plus y equals to 8, and achieve a value of y equals to 5. Hence the answer remains x equals to 3 and y equals to 5. We can verify the solution by using the graph. Here again, the blue line represents the point at which 3x plus 2, y equals to 19 is true. while the red line represents the point where x plus y equals to 8 is true. The solution is found at the point where x equals to 3 and y equals to 5. This is the point where both lines intersect. Introduction to matrices. Matrix. A matrix is a rectangular array or table with rows and columns of numbers, symbols, expressions used to represent a mathematical object or an attribute. For example, here A is a matrix of 2 rows and 3 columns, as 2, 1, 3, minus 1, 2, and 4. Well, B is a squared matrix with 2 rows and 2 columns given as 2, 1, 3, 4. Matrix size. The matrix size is expressed as M cross N, where M is the number of rows, and N is the number of columns. A matrix with 2 rows and 3 columns can be referred to as 2 by 3 matrix or a 2 cross 3 matrix, or a matrix of dimension 2 cross 3. Notation of a matrix. A matrix with M rows and N columns can be presented as this. Here each element will be identified by its row number and column number. For example, the element over here is in the 3rd row and the 1st column. Hence, it is identified as a 3-1. Forms of matrix. The matrix is termed as a squared matrix. If n equals to m, that is, the number of rows and number of columns are equal. An element's entry in the matrix of from A, I is located on the diagonal. Hay is called a diagonal matrix if Hay ij equals to 0, when I is not equals to j, that is in a square matrix. Apart from diagonal at all places, we have 0 as a value. Matrix operations. Addition. Addition of 2 matrices is adding their corresponding elements, as in A11 plus B11, A12 plus B12, A21 plus B21, A22 plus B22, and so on. Consider the example over here. We have a matrix A as 22, 32, 11, 16, and matrix B as 13, 8, 13, and 16. Matrix A is of the order 2 cross 2, and matrix B is also of the same order, 2 cross 2. Hence, the corresponding elements can be quickly added as 22 plus 13, 32 plus 8, 11 plus 13, and 16 plus 16, giving us the result in matrix of 35, 40, 24, and 32. Addition rules. Only matrices with the same size can be added. That is, the 2 matrices should have same number of rows and same number of columns. Matrix addition follows commutative property. That means A plus B is equals to B plus A. Subtraction. Matrix subtraction is same as matrix addition. It is subtracting the corresponding values. Let's consider the same example of matrix A and B. The result of A minus B can be given as 22 minus 13. That is A11 minus B11. 32 minus 8. That is A12 minus B12. 11 minus 13. A21 minus B21. And 16 minus 16. That is A22 minus B22. Giving us result as 9, 24, -2, and 0. Subtraction rules. Only matrices with the same number of rows and columns can be subtracted. Matrix subtraction does not follow commutative property. That means A minus B is not equals to B minus A. Multiplication. Matrix multiplication results in what is called as a product matrix. In matrix multiplication, Each row of the first matrix is multiplied to each column of the second matrix. To compute each of these elements in the matrix, the values are then added. For example, consider the matrix A and B. To get the first element, we will multiply the first row of matrix A to the first column of matrix B, and then add the individual elements, that is 22, multiplied to 13, and 32 multiplied to 13, and then add them up to get this particular element. For the second element, we multiply the first row of A to the second column of B, hence getting 22 multiplied to 8 plus 32 multiplied to 16. Similarly, we compute all the remaining elements, that is the second row multiplied to the first column, and added 11 multiplied to 13 plus 16 multiplied to 13, and the second row now multiplied to the second column, that is 11 multiplied to 8 plus 16 multiplied to 16. This gives us the resulting matrix as 702, 688, 351, and 344 multiplication rules. Let us say C equals to AB. Here, C is our product matrix, which can be computed as summation over A at ij dot bjk. For a matrix of size ij, matrix B of size jk, to calculate the value of each member in the I cross K matrix of C. The matrix product AB is defined only when the number of columns in A equals to the number of rows in B. The matrix product of BA is defined only when the number of columns in B is equals to the number of rows in A dot B is not always equals to B dot A. Transpose. A transpose is a matrix form by turning all the rows of a given matrix into the columns and vice versa. The transpose of a matrix A is denoted as AT. For example, if the matrix A is 22, 32, 11, and 16, the transpose of A would be 22, 11, 32, and 16. Here we can see the row has been converted to column. Inverse. If it is a non-singular square matrix, there exists n cross n matrix, a minus one known as A's inverse, that satisfies A dot A inverse equals to A inverse dot A equals to I, where I is the identity matrix. And identity matrix is characterized as a diagonals 1 and all other elements are 0. Also, AB equals to B dot A equals to IN, where IN denotes the n cross n identity matrix. Special matrix types. Symmetric matrix. A matrix A is set to be symmetric. If A is equals to transpose of A, diagonal matrix, A matrix D is diagonal only if Dij equals to 0. For all I not equals to J. Identity matrix. Identity matrix is denoted as IN, where AIN equals to IN dot A equals to A. Tensors. Tensors are arrays with more than 2 axes. A tensor can have n dimensions. Aijk is the value in the tensor A at coordinates ij and k. The principal component analysis PCA, which is a statistical technique used to reduce the number of dimensions in a given data set while we preserve its variability. So there are different use cases of PCA in real-time scenarios. One of the major use cases is in the healthcare domain, so technically known as the spike-triggered covariance analysis. It uses the principle of PCA in neuroscience, to identify the specific properties of a stimulus that increase a neuron's probability of generating an action potential. So it is using reduction techniques, which is going to be really helpful in detecting the coordinated activities of large neuronal ensembles. So it is basically used for identifying a neuron from the shape of its action potential. Then in terms of quantitative finance. So PCA help us in reducing the dimensionality of a complex problem. Let's say a fund manager has 200 stocks in his portfolio. Now to analyze these stocks quantitatively, a stock manager will require a correlational metric of a size 200 by 200, which makes the problem very complex. However, if he has to extract 10 principal components, which best represents the variance in the stock price, this will reduce the complexity of the problem while still explaining the movement of all 200 stocks. So we use it for analyzing the shape of the yield curve in terms of forecasting the portfolio returns, developing the asset allocation algorithms, and so on. And it is also widely used in image compression. So PCA is also used for image compression. So if we go ahead and use any of the PyCharm IDE, so here we can work with Matplotlib, ImagePyPlot, and the NumPy as NP. And here we can also import from sklearn. And we can import the PCA. So basically we are trying to print the shape of the image by reading the image. This is a sample logo.png, which has been placed in the same directory. We are trying to print the image. So if we run this particular code, then we will be able to see the shape of the image. Return to us first the current shape based on the image which has been deducted, which is 156, 94, and 3. So what does this mean? This means image is in the form of 156 rows, and each row containing 194 pixels, and then having 3 channels, which is red, green, and blue. So we had to resize the image so that it is in a format required for PCA input, which is 196 by 3, which is going to be 582. So here we can see we have performed a simple operation as image_r, where we are using the NumPy library for reshaping the image. And then we are printing the shape of the image again. So here we can see 156 and 582 has been returned as a response. Now running the PCA with 32 principal components, we can use this fit for the image that has been reshaped, and then we are trying to train the transform image. So with these 32 components, we are able to express 98.7% of the variance. So inverse transforming the PC output and reshaping the visualization can also be done forward. And that's how PCA is widely used as a part of the medical and the other sciences. For example, is used for object detection model for the healthcare domain for the transportation, aviation, and location-based services. Introduction to vectors. Objects with both magnitude and direction are called as vectors. The magnitude of the vector determines its size. It is represented as a line with an arrow, where the length of the line indicates the vector's magnitude, and the arrow points in the desired direction. Other names for it include Euclidean vector, geometric vector, spatial vector, or simply vector. Its length is indicated by the symbol double bar v double bar, and it begins at the original 0, 0. Notation of a vector. A vector can be represented in a standard form as A equals to AI cap plus BJ cap plus CK cap, where A, B, and C are numeric values. The unit vectors along the x, y, z axis are I, j, and k cap respectively.
Did you know that within just a few lines of code, you can transform an AI model into something far more powerful? Something that responds to questions, connects to live data, pulls insights from databases, and even interacts with other apps in real time. That's what Langchain allows you to do. And it's quickly becoming the go-to framework for AI developers. Think about this. You're about to create something amazing, an AI that can think, learn, and grow in ways we once only dreamed of. And here's the best part. You don't need to be an AI expert to make that happen. Langchain is like a toolkit that connects the most advanced large language models like OpenAI's GPT to real-time data, allowing you to build AI applications that are smart, flexible, and highly interactive. Langchain is more than just a way to make AI development easier. It's a framework that allows different language models to work together seamlessly. So whether you want to understand user questions with one LLM, create human-like responses with another, or pull in data from an API or a database, Langchain makes all possible. The framework takes care of heavy lifting, connecting models, managing data flows, and even customizing how your AI interacts with external sources. Now the question is, why is Langchain so popular? It has become one of the most fastest growing open source projects because it's solving a huge problem for developers. The challenge of integrating generative AI and LLMs with external data and complex workflows. As AI becomes more central to our lives in 2024, Langchain is helping developers create smarter, more powerful applications. So whether it's just for chatbots, content creation, or advanced data analysis. In this tutorial, I'll show you exactly how to get started with Langchain, from setting up your environment to building the first AI-powered app. I'll walk you through it. So Langchain makes it possible to train models on our own custom data, opening up more possibilities for building specialized intelligent applications. By the end of this video, you will be ready to start building with Langchain, and trust me, once you see how easy it is, you'll wonder why you didn't start using it sooner. Let's start with a simple question: why should we use Langchain? Imagine you're working with large language models like GPT-4 or Hugging Face models, and you want to take their capabilities further, like integrating them with your own data sources or allowing them to take action based on information they retrieve. This is where Langchain comes in. Langchain is like an open source framework that allows you to build intelligent applications by connecting large language models with external data sources. It can turn static AI interactions into dynamic, data-aware workflows. One of the best parts is you don't have to manually code everything from scratch. Langchain abstracts away much more complexity of working with LLMs, allowing developers to focus on building functional applications instead of wrangling API calls and managing data pipelines. So Langchain is set to play even bigger role in AI development because it enables you to harness true power of generative AI by connecting it with real-time data and external tools. So now we have understood what Langchain is. Let us now understand how to install Langchain. So let's start with the installation of Langchain. We'll just simply go to the website docs part, and we'll just read through this documentation. So here it has explained what Langchain is and what are the framework consisting of. So we also have these tutorials on how do we install Langchain. Okay, so for installing, you can just simply click on this quick start and see here it has written how do we set up on Jupyter Notebook. So this is the command if you want to install Langchain. We will use the pip command. So just simply you can copy this command pip install Langchain, and you have to open your command prompt or the terminal in your computer, and here you have to simply copy paste the command. So as you can see, it will load all the packages which is required for installing Langchain. So you can see your requirement already satisfied. This is because I had already installed my Langchain before. So we have understood how to install this Langchain by using this command, and you can also install the LLM chain. We'll understand it later. Now let me just show you what else you need to install. First, we have understood this Langchain. Then we have the Pinecone client. So we'll just simply search here Pinecone client, and it will redirect us to this page. So Pinecone client is actually a vector store for storing and retrieving embeddings, which we will use in the later steps. So Pinecone is also used to actually, create secret API keys. So here you can also create the API keys. You can also read the documentation part. So we'll understand how to create API keys using OpenAI. But first, let us install Pinecone client in our system. So we'll again go to command prompt this terminal and we'll just copy paste pip install Pinecone client. So you can see here it will download and install all the packages required. So it has been installed. Now the third thing we're talking about is OpenAI client. So we'll use OpenAI models for a large language task. So we'll just simply search here OpenAI. Okay. And so it has redirected us to this page, OpenAI platform. And okay, before starting this, so this is the platform here where you can create, export an API key in OpenAI. Okay, so you can see here overview, quick start, concept, everything is there. And to create an API key, we'll just simply click here and here you have to select this option, create a new secret key. Suppose I give my secret key name, anything you can give. Suppose I give test 1, 2, 3. Okay, and permissions is all, and we create the secret key. Now you need to actually save your key. We'll just copy this key because it will be required later while debugging the code. So we will just copy paste this secret key. We will require it later, and then done. So these are the keys I have created. So actually ChatGPT and other LLM models like OpenAI and Hugging Face uses Langchain to integrate with other APIs to create your own custom LLM models or chatbots. So suppose here we have logged in our ChatGPT here, and if I search here who won the WTC World Cup in 2023. So here it has shown the answer, but for example, if I search who won the cricket match World Cup so here, as you can see, the ChatGPT has given answer as my last knowledge update, the 24 Men's World Cup has not taken place yet. This is happening because this ChatGPT older version has not been trained on the latest upcoming news or whatever the new technology is. So by using Langchain, you can integrate with other APIs and you can create your own customized LLM models or chatbots, which help you to train your own custom data using various tools and APIs. So before we move on, I've already showed you how to create the secret API key and how you have to store the API key address. So first we have already understood how do we install Langchain here. So by using the pip command, we do it. And so you also need to install Python 3.8 or later installed in your system. So I already have Python installed. And to check that, you can just simply, I already have it installed in my system. So to check that, I'll simply just type here Python -- version and click enter. So as you can see, it has shown me the Python version which is installed in my computer. So the second step is already we have discussed, which is OpenAI API key here. So second step, we have already discussed how do we create our OpenAI API key. So we have to sign up in our OpenAI, then go to the API keys section and then create a new secret key. And these are the keys I have created, and you can just keep it later. Later you'll use that. So now we'll come to the third step, which is create a project directory and setup. So what we do is we have Jupyter installed in our system. So we'll just go to command prompt here and type JUPY, Jupyter Notebook. So it will redirect us to the Jupyter Notebook installed in our system. So if not, we can just simply go from here. So it is loading right now, we have to wait. Now you just need to click on this new and Python 3 IPy kernel, because Python is being installed in my system. So we will use Python as our kernel here. And here you can just give the prompts, the command. Before that, you have to create a Python file, which we can also create this Python file in the Visual Studio Code. Just simply go to Visual Studio Code here and just simply click on File, New File, and I'll just type here python.py. And you have to first store the API key. For this, we use the command OpenAI underscore API underscore key equal to, and just give your secret key. Okay, you can just simply copy paste your secret key and just store this. So this ensures that your API key is stored securely and it can be used whenever needed. Now the step 4 is to initialize a project and install the required libraries. So you need to add some additional libraries like Streamlit to make a user interface. So let's add that too in our project folder. You can either create a text file named requirements.txt and then install all these. We have already installed the OpenAI Langchain. We just need to install Streamlit. So here you can just give the command pip install Streamlit. So as you can see, this I have already installed Streamlit before. Same wise, you can also install OpenAI if it is not installed in your system using the command terminal, the Windows PowerShell. So we have understood this, what all packages and what all we need to install. Now the next step is to build your first Langchain app. To create a simple app which uses a input query, and the app will generate a response using OpenAI's GPT model. So you have to create a Python file named main.py here. So as you can see, I've already imported this main.py, and this is my code here. Import Streamlit as st from Langchain and the constants I have created, and then I have initialized the OpenAI with our API key. So you have to just type this prompt here. I'm using VS Code here. You can also do it in your Jupyter notebook. And then to create the Streamlit app, you have to give a title, Langchain Demo with OpenAI. So this is the title I have provided. And then the text input for prompt. The prompt is st.text input and enter a prompt. You can just type enter a prompt or whatever you wish to. And then display the response. So if prompt response is LLM.predict prompt, so you can use the predict method for LLM. So here what the app will, so after creating and debugging this in the terminal, so your app will initialize OpenAI using your API key, and the user inputs a prompt through the Streamlit interface. Langchain processes the input and sends it to the OpenAI's GPT model, and the AI generates a response which is then displayed in the app. So now you can use all these prompts to run on your app. So to do this, you can just, to see your app in action, you can just go to the terminal and run the following command, which is streamlit run main.py. So you can just simply go to the terminal here and just simply type the command, which is streamlit run main.py. So by giving this prompt, a new tab in your browser will open displaying the app, and you can also type any question into the input box. So now we have understood all these steps. So this was a quite basic tutorial on how to install Langchain and then, integrate it with the app. You can also customize and expand. So Langchain's flexibility allows you to integrate other APIs also, external data sources, or even add memory to your AI application. So whether you're building a simple chatbot or more complex AI system, the possibilities are endless. So by following all these steps, you will have a fully functioning app running in your system in no time.
Today, I will tell you a story of a guy named Leo. Leo, a young software engineer with big dreams. He loved building things, mobile apps, web platforms, and even small kits. But coding was tricky, even for someone as skilled as Leo. No matter how much experience he had, he kept running into bugs and inefficiencies that made his applications crash or run slowly. He would spend hours staring at his computer screen, debugging line after line of codes, trying to figure out where things went wrong. One day, Leo heard about Cursor AI, a powerful code editor that could help him code faster and smarter. Unlike regular code editors, Cursor AI didn't just highlight errors, it understood the code deeply. It could analyze problems, suggest better solutions, and even write sections of code for him. Feeling curious, Leo decided to give it a try. He opened Cursor AI and loaded his project, which had been stuck for days due to a tricky bug.
Almost instantly, Cursor AI flagged the error in the code and suggested an efficient fix. Not only that, it also recommended a cleaner way to structure his code, making it easier to read and less prone to future bugs. Leo followed the suggestions and his app started running flawlessly. In fact, Cursor AI helped him optimize the entire project, making the application faster and smoother than before. Tasks that would usually take hours like debugging, refactoring, and testing were now completed in minutes. Before I tell you that you too can code in minutes like Leo, just for your information, in this video, I will let you know what Cursor AI is and your ultimate guide to use it as a beginner. So let's jump into the video. Let us understand what is Cursor AI. Cursor AI is a smart coding assistant that speeds up your workflow by suggesting code completions, fixing bugs, and optimizing code in real time. It supports multiple languages, helps with code reviews, and even generate documentation, making coding faster, easier, and more efficient for developers of all levels. Well, after we have a basic understanding of Cursor AI, let us explore more. I will first take you to the browser, and in that, you need to search for Cursor AI. And the first official website that will appear is www.cursor.com. You need to click on it and obviously download it. It is free and you need to sign in as you are using their model. So it is very important to log in before exploring their model. After you download and install it, I will show you what screen you are gonna get. Yeah. This is the visual representation of Cursor AI, the code editor, and it somewhat looks like VS Code. If you have seen VS Code before, it almost looks like this. This is basically your project section. And yeah, obviously file, edit, selection, view, go, run, and everything. So initially, it is very important to start with the basics. So obviously, you're using a new application for the first time. It is very important to learn the cursor settings. So to see the cursor settings, for that press Command Shift plus P. Command Shift plus P. Yeah, see? It will direct you to a menu bar on the top of the application and search there as cursor settings. See, it is already available. So cursor settings. So basically cursor setting has 4 types of settings: general, models, features, and beta. So initially start with this general. Account, basically the account shows like through what Gmail account you have logged in. And currently I'm using this pro trial and it is basically of 2 weeks, I guess, for free. And after that, if you want to use it, then you can use it like upgrading to pro. And after that, there is VS Code import. This is basically for like if you have VS Code in this particular laptop or system you're using, then you can obviously import the type of extensions or key bindings you have there. You can generally import it. And after that comes rules for AI. This is basically the section where you can like tell or instruct the Cursor AI what are the things you want or even what are the things you don't want. Like for example, you're working on a particular project and you only want to like use a particular language, then you can just type there, like I will show you. Use only React.js. So basically you can write there and it will automatically get saved, but obviously I won't be using that. And after that comes a very important part. There is a privacy mode. It is already written. If on, none of your code will be stored by us. If off, we may save prompts or collect telemetry data to improve cursor. So obviously I don't want my data to get to them. So obviously I have enabled it. If you have no problem in showing your data to the cursor, so you can obviously disable it. Then I will show you about the models. This is basically the section where you can see what are the type of models, API models you're using or it is getting used, and even you can even add your own model and see like OpenAI API key, Anthropic API key, Google API. Oh wow, this is nice. Azure API key, they're almost there. Let's come to beta. This is basically a section where if any of the new features like get upgraded in Cursor AI, then you can obviously see it over here. And it is like a default setting is disabled, so let it be. Like, don't have to do anything. So after you have seen the Cursor settings, I will take you to see the actual presentation where you can actually code more faster than any of the editors. So I will take you to see a magic. So let's start. So I will cross it. I will now show you why Cursor AI is the next code editor. For that, press Ctrl+Shift+I and you can see the composer. It is named as composer. You can write here any instructions or commands that you want Cursor AI to execute. So basically you can give prompts like create a particular website for me using this. So I will let you understand with an example. Create a simple retro game using HTML, CSS and JavaScript. I hope it does. And enter. See, it has even started to build this game. Pong style, retro style Pong game using HTML, CSS and JavaScript. Okay, it has already made index.html and it has been building with JavaScript. Okay, it has only used HTML and JavaScript. Okay, I wanted to use CSS too for better appearance. Obviously, CSS is the thing you need to. Okay, it has already started linking. Okay, here's the code for the game. Okay, maybe some confusion has occurred. Okay, it has used CSS as a. Okay, it has not made a different file. So I wanted to make a CSS as a different file. I want a separate file for CSS. Okay, now see, it has actually executed what I said. Okay. Now, after you have got it, you can just accept all and see if it is actually working or not. So let's start. Accept all. After that, you can close this composer window and you will find that files already in your project section. See, it is there. If you want to like run the game and see if it is actually getting the code is running or not and the game is playable or not, you need to download one extension. Yeah, here like live server. Yeah, I have already installed it. You need to just install it and you are ready to go. Let's come back and right click on the index.html and open with live server. Okay, see, it's nice. Oh, wow. Move your mouse up and down to control the left paddle first to 10 points. First to 10 points win. Okay. This is nice. So I want basically my game is glowing. Yeah. So I want to use one theme. So see if it can. Let's see. After the game is basically made, you can just use your imagination or your creativeness on how you can design your game. So Ctrl+Shift+I. Yeah. Wow, the game is nice. I don't know why I'm appreciating, but yes, you need to appreciate because it did so much work for you. Oh, wow, the game is nice. I want you to use Harry Potter theme. I think everyone knows Harry Potter, and I wanted basically to use Harry Potter theme in the game and submit. So it has started formulating it. I think it is nice. Okay, accept all. And now you can cross it. And let's see. Open with live server. Wow, see. Oh, it is nice. See, it is almost green and yellow, the type of that is used in Harry Potter and everything. See, it is nice. And it is also written golden snitch. Wow, it is nice. So basically, you can do anything. You can even use a particular type of like font. You can do anything. Let's see how we can improve it. Control Shift I. Yeah, this is nice. Can you just use the font style used in Harry Potter movie? I hope it does. Enter. I understand. Yeah, it is trying. Because of the copyright, maybe it fully can't, but yeah, it is trying. Let's see. Accept all. Cross it. And right click and open with live server. Okay. Maybe there's a difference there. There is a difference. I can see. Fine. It is nice. So in this way, you can just command it and do anything. You can even like attach files, I guess. You can over here, you can just use @ and you can like upload files, folders, code, web, like you can attach, you can @ web, and you can even tell it to take a picture from the website and replicate it, use that for reference and anything. So it basically depends upon your designing and your creativeness, how you want to make it, and it will just code for you. This is the power of AI. So you can do anything over here, I believe. It will help you to code much faster.
Hello everyone, I am Mank and welcome to today's video where we will be talking about LLM benchmarks, tools used to test and measure how well large language models like GPT and Google Gemini performs. If you have ever wondered how AI models are evaluated, this video will explain it in simple terms. LLM benchmarks are used to check how good these models are at tasks like coding, answering questions, and translating languages or summarizing text. These tests use sample data and specific measurement to see how well the model performs. For example, the model might be tested with a few examples, like few short learning, or none at all, like zero short learning, to see how it handles new tasks. So now the question arises, why are these benchmarks important? They help developers understand where a model is strong and where it needs improvement. They also make it easier to compare different models, helping people choose the best one for their needs. However, LLM benchmarks do have some limits. They don't always predict how well a model will work in real-world situations, and sometimes model can overfit, meaning they perform well on test data but struggle in practical use. We will also cover how LLM leaderboards rank different models based on their benchmark scores, giving us a clear picture of which models are performing the best. So stay tuned as we dive into how LLM benchmarks work and why they are so important for advancing AI. So without any further ado, let's get started. So what are LLM benchmarks? LLM benchmarks are standardized tools used to evaluate the performance of large language models. They provide a structured way to test LLMs on a specific task or question, using sample data and predefined metrics to measure their capabilities. These benchmarks assess various skills such as coding, common sense reasoning, and NLP tasks like machine translation, question answering, and text summarization. The importance of LLM benchmark lies in their role in advancing model development. They track the progress of an LLM, offering quantitative insights into where the model performs well and where improvement is needed. This feedback is crucial for guiding the fine-tuning process, allowing researchers and developers to enhance model performance. Additionally, benchmarks offers an objective comparison between different LLMs, helping developers and organizations choose the best model for their needs. So how LLM benchmarks work? LLM benchmark follow a clear and systematic process. They present a task for LLM to complete, evaluate its performance using specific metrics, and assign a score based on how well the model performs. So here is a breakdown of how this process works. The first one is setup. LLM benchmark come with pre-prepared sample data including coding challenges, long documents, math problems, and real-world conversation. The task span various areas like common sense reasoning, problem solving, question answering, summary generation, and translation, all present to the model at the start of testing. The second step is testing. The model is tested on one of the three ways. Few shot, the LLM is provided with a few examples before being prompted to complete a task, demonstrating its ability to learn from limited data. The second one is zero shot. The model is asked to perform a task without any prior examples, testing its ability to understand new concepts and adapt to unfamiliar scenarios. The third one is fine-tune. The model is trained on a dataset similar to the one used in the benchmark, aiming to enhance its performance on the specific task involved. The third step is scoring. So after completing the task, the benchmark compares the model's output with the expected answer and generates a score, typically ranging from 0 to 100, reflecting how accurately the LLM performed. So now moving forward, let's see key metrics for benchmarking LLMs. So LLM's benchmark uses various metrics to assess the performance of large language model. So here are some commonly used metrics. The first one is accuracy or precision. Measure the percentage of correct prediction made by the model. The second one is recall, also known as sensitivity. Measure the number of true positive reflecting the correct prediction made by the model. The third one is F1 score. Combines both accuracy and recall into a single metric, weighing them equally to address any false positive or negatives. F1 score ranging from 0 to 1, where 1 indicates perfect precision and recall. The fourth one is exact match. Tracks the percentage of predictions that exactly match the correct answer, which is especially used for the tasks like translation and question answering. The fifth one is perplexity gauges. Here it will tell you how well a model predicts the next word or token. A lower perplexity score indicates better task comprehension by the model. The sixth one is BLUE, bilingual evaluation understudy. Is used for evaluating machine translation by comparing n-grams, sequence of adjacent text element, between the model's output and the human-produced translation. So these quantitative metrics are often combined for more through evaluation. So in addition, human evaluation introduces qualitatively factors like coherence, relevance, and semantic meaning, provide a nuanced assessment. However, human evaluation can be time-consuming and subjective, making a balance between quantitative and qualitative measures important for comprehensive evaluation. So now let's moving forward see some limitation of LLM benchmarking. While LLM benchmarking are valuable for assessing model performance, they have several limitations that prevents them from the fully predicting real-world effectiveness. So here are some few. The first one is bounded scoring. Once a model achieves the highest possible scores on the benchmark, that benchmark loses its utility and must be updated with more challenging tasks to remain a meaningful assessment tool. The second one is broad dataset. LLM benchmark often rely on sample data from diverse subjects and tasks. So this wide scope may not effectively evaluate a model's performance in edge cases, specialized fields, or specific use cases where more tailored data would be needed. The third one is finite assessment. Benchmark only tests a model's current skills, and as LLMs evolve and new capabilities emerge, new benchmarks must be created to measure these advancements. The fourth one is overfitting. So if an LLM is trained on the same data used for benchmarking, it can be lead to overfitting, where the model performs well on the test data but struggles with the real task. So this result is scores that don't truly represent the model's broader capabilities. So now what are LLM leaderboards? So LLM leaderboards publish a ranking of LLMs based on the variety of benchmarks. Leaderboards provide a way to keep track to the myriad LLMs and compare their performance. LLM leaderboards are especially beneficial in making decisions on which models to use. So here are some. So in this you can see here OpenAI is leading and GPT-4o second and the Llama third with 405 parameter B and 3.5 sonnet is there. So this is best in multitask reasoning. What about the best in coding? So here OpenAI O1 is leading. I guess this is the Orion one, and the second one is 3.5 sonnet, and after that in the third position there is GPT-4o. So this is in best in coding. So next comes fastest and most affordable models. So fastest models are Llama 8B parameter, and the second one is LLAMA Llama 70B, The third one is 1.5 flash. This is Gemini 1. And lowest latency. And here it is leading Llama again. In cheapest models, again Llama 8B is leading. And in the second number, we have Gemini Flash 1.5. And in third, we have GPT-4o Mini. Moving forward, let's see standard benchmarks between Claude 3 Opus and GPT-4. So in general, they are equal. In reasoning, Claude 3 Opus is leading, and in coding, GPT-4 is leading. In math, again GPT-4o is leading. In tool use, Claude 3 Opus is leading, and in multilingual, Claude 3 Opus is leading.
And this is one of the things that's very important with linear regression in any of these models, is to understand the error. And so we can calculate the error on all of our different values. And you can see over here we plotted x and y predict. And we draw in a little line so you can sort of see what the error looks like there between the different points. So our goal is to reduce this error. We want to minimize that error value on our linear regression model. Minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. We keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. So to recap with a very simple linear regression model, we first figure out the formula of our line through the middle, and then we slowly adjust the line to minimize the error. Keep in mind this is a very simple formula. The math gets, even though the math is very much the same, it gets much more complex as we add in different dimensions. So this is only 2 dimensions, y equals mx plus c, but you can take that out to x, z, ijk, all the different features in there, and they can plot a linear regression model on all of those using the different formulas to minimize the error. Let's go ahead and take a look at decision trees, a very different way to solve problems in the linear regression model. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of a tree represents a possible decision, occurrence, or reaction. We have data which tells us if it is a good day to play golf. And if we were to open this data up in a general spreadsheet, you can see we have the outlook, whether it's rainy, overcast, sunny, temperature, hot, mild, cool, humidity, windy, and did I like to play golf that day, yes or no? So we're taking a census. And certainly I wouldn't want a computer telling me when I should go play golf or not. But you can imagine if you got up in the night before, you're trying to plan your day, and it comes up and says tomorrow would be a good day for golf for you in the morning, and not a good day in the afternoon, or something like that. This becomes very beneficial, and we see this in a lot of applications coming out now where it gives you suggestions and lets you know what would fit the match for you for the next day or the next purchase or the next whatever, next meal out. In this case, is tomorrow a good day for playing golf based on the weather coming in? And so we come up and let's determine if you should play golf when the day is sunny and windy. So we found out the forecast tomorrow is going to be sunny and windy. And suppose we draw our tree like this. We're going to have our humidity, and then we have our normal, which is if you have a normal humidity, you're going to go play golf. And if the humidity is really high, then we look at the outlook. And if the outlook is sunny, overcast, or rainy, it's going to change what you choose to do. So if you know that it's a very high humidity and it's sunny, you're probably not going to play golf because you're going to be out there miserable, fighting off the mosquitoes that are out joining you to play golf with you. Maybe if it's rainy, you probably don't want to play in the rain. But if it's slightly overcast and you get just the right shadow, that's a good day to play golf and be outside, out on the green. Now in this example, you can probably make your own tree pretty easily because it's a very simple set of data going in. But the question is, how do you know what to split? Where do you split your data? What if this is much more complicated data where it's not something that you would particularly understand? Like studying cancer, they take about 36 measurements of the cancerous cells, and then each one of those measurements represents how bulbous it is, how extended it is, how sharp the edges are. Something that as a human we would have no understanding of. So how do we decide how to split that data up? And is that the right decision tree? So that's a question that's going to come up. Is this the right decision tree? For that, we should calculate entropy and information gain. 2 important vocabulary words there are the entropy and the information gain. Entropy. Entropy is a measure of randomness or impurity in the data set. Entropy should be low. So we want the chaos to be as low as possible. We don't want to look at it and be confused by the images or what's going on there with mixed data. And the information gain. It is the measure of decrease in entropy after the data set is split, also known as entropy reduction. Information gain should be high, so we want our information that we get out of the split to be as high as possible. Let's take a look at entropy from the mathematical side. In this case, we're going to denote entropy as I of P of and N, where P is the probability that you're going to play a game of golf, and N is the probability where you're not going to play the game of golf. Now, you don't really have to memorize these formulas. There's a few of them out there depending on what you're working with. But it's important to note that this is where this formula is coming from, so when you see it, you're not lost when you're running your programming, unless you're building your own decision tree code in the back. And we simply have a log squared of P over P plus N minus N over P plus N times the log squared of N of P plus N. But let's break that down and see what it actually looks like when we're computing that from the computer script side. Entropy of a target class of the data set is the whole entropy. So we have entropy play golf. And when we look at this, if we go back to the data, you can simply count how many yeses and no in our complete data set for playing golf days. In our complete set, we find we have 5 days we did play golf and 9 days we did not play golf. And so our I equals, if you add those together, 9 plus 5 is 14. And so our I equals 5 over 14 and 9 over 14. That's our P and N values that we plug into that formula. And you can go 5 over 14 equals 0.36, 9 over 14 equals 0.64. And when you do the whole equation, you get the minus 0.36 log root squared of 0.36 minus 0.64 log squared root of 0.64. And we get a set value. We get 0.94. So we now have a full entropy value for the whole set of data that we're working with. And we want to make that entropy go down. And just like we calculated the entropy out for the whole set, we can also calculate entropy for playing golf and the outlook. Is it going to be overcast or rainy or sunny? And so when we look at the entropy, we have P of sunny times E of 3 of 2. And that just comes out how many sunny days yes and how many sunny days no over the total, which is 5. Don't forget to put we'll divide that 5 out later on. Equals P overcast equals 4, 0 plus rainy equals 2, 3. And then when you do the whole setup, we have 5 over 14. Remember I said there was a total of 5? 5 over 14 times the I of 3 of 2 plus 4 over 14 times the 4, 0 and 514 over I of 2, 3. And so we can now compute the entropy of just the part that has to do with the forecast, and we get 0.693. Similarly, we can calculate the entropy of other predictors like temperature, humidity, and wind. And so we look at the gain outlook. How much are we going to gain from this? Entropy play golf minus entropy play golf outlook. And we can take the original 0.94 for the whole set minus the entropy of just the rainy day and temperature, and we end up with a gain of 0.247. So this is our information gain. Remember, we define entropy and we define information gain. The higher the information gain, the lower the entropy, the better. The information gain of the other 3 attributes can be calculated in the same way. So we have our gain for temperature equals 0.029. We have our gain for humidity equals 0.152, and our gain for a windy day equals 0.048. And if you do a quick comparison, you'll see the 0.247 is the greatest gain of information, so that's the split we want. Now let's build the decision tree. So we have the outlook. Is it going to be sunny, overcast, or rainy? That's our first split because that gives us the most information gain. And we can continue to go down the tree using the different information gains with the largest information. We can continue down the nodes of the tree where we choose the attribute with the largest information gain as the root node, and then continue to split each subnode with the largest information gain that we can compute. And although it's a little bit of a tongue twister to say all that, you can see that it's a very easy to view visual model. We have our outlook, we split it 3 different directions. If the outlook is overcast, we're going to play. And then we can split those further down if we want. So if the outlook is sunny, but then it's also windy, if it's windy, we're not going to play. If it's not windy, we'll play. So we can easily build a nice decision tree to guess what we would like to do tomorrow and give us a nice recommendation for the day. So we want to know if it's a good day to play golf when it's sunny and windy. Remember the original question that came out? Tomorrow's weather report is sunny and windy. You can see by going down the tree, we go outlook sunny, outlook windy, we're not going to play golf tomorrow. So our little smartwatch pops up and says, I'm sorry, tomorrow's not a good day for golf. It's going to be sunny and windy. And if you're a huge golf fan, you might go, uh-oh, it's not a good day to play golf. We can go in and watch a golf game at home. So we'll sit in front of the TV instead of being out playing golf in the wind. Now that we looked at our decision tree, let's look at the third one of our algorithms we're investigating. Support vector machine. Support vector machine is a widely used classification algorithm. The idea of support vector machine is simple. The algorithm creates a separation line which divides the classes in the best possible manner. For example, dog or cat, disease or no disease. Suppose we have a labeled sample data which tells height and weight of males and females. A new data point arrives and we want to know whether it's going to be a male or a female. So we start by drawing a line. We draw decision lines, but if we consider decision line 1, then we will classify the individual as a male. And if we consider decision line 2, then it will be a female. So you can see this person kind of lies in the middle of the two groups, so it's a little confusing trying to figure out which line they should be under. We need to know which line divides the classes correctly, but how? The goal is to choose a hyperplane, and that is one of the key words they use when we talk about support vector machines. Choose a hyperplane with the greatest possible margin between the decision line and the nearest point within the training set. So you can see here we have our support vector, we have the two nearest points to it, and we draw a line between those 2 points. And the distance margin is the distance between the hyperplane and the nearest data point from either set. So we actually have a value, and it should be equally distant between the two points that we're comparing it to. When we draw the hyperplanes, we observe that line 1 has a maximum distance. So we observe that line 1 has a maximum distance margin, so we'll classify the new data point correctly. And our result on this one is going to be that the new data point is male. One of the reasons we call it a hyperplane versus a line is that a lot of times we're not looking at just weight and height. We might be looking at 36 different features or dimensions. And so when we cut it with a hyperplane, it's more of a three-dimensional cut in the data, or multi-dimensional. It cuts the data a certain way. And each plane continues to cut it down until we get the best fit or match. Let's understand this with the help of an example. Problem statement. I always start with a problem statement when you're going to put some code together. We're going to do some coding now. Classifying muffin and cupcake recipes using support vector machines. So the cupcake versus the muffin. Let's have a look at our data set. And we have the different recipes here. We have a muffin recipe that has so much flour. I'm not sure what measurement 55 is in, but it has 55, maybe it's ounces? But it has a certain amount of flour, a certain amount of milk, sugar, butter, egg, baking powder, vanilla, and salt. And so based on these measurements, we want to guess whether we're making a muffin or a cupcake. And you can see in this one, we don't have just two features. We don't just have height and weight as we did before between the male and female. In here, we have a number of features. In fact, in this, we're looking at 8 different features to guess whether it's a muffin or a cupcake. What's the difference between a muffin and a cupcake? Turns out muffins have more flour, while cupcakes have more butter and sugar. So basically the cupcake's a little bit more of a dessert, where the muffin's a little bit more of a fancy bread. But how do we do that in Python? How do we code that to go through recipes and figure out what the recipe is? And I really just want to say cupcakes versus muffins, like some big professional wrestling thing. Before we start in our cupcakes versus muffins, we are going to be working in Python. There's many versions of Python, many different editors. That is one of the strengths and weaknesses of Python, is it just has so much stuff attached to it, and it's one of the more popular data science programming packages you can use. In this case, we're going to go ahead and use Anaconda and Jupyter Notebook. The Anaconda Navigator has all kinds of fun tools. Once you're into the Anaconda Navigator, you can change environments. I actually have a number of environments on here. We'll be using Python 3.6 environment. So this is in Python version 3.6. Although it doesn't matter too much which version you use. I usually try to stay with the 3x because they're current, unless you have a project that's very specifically in version 2x. 2.7 I think is usually what most people use in the version 2. And then once we're in our Jupyter Notebook editor, I can go up and create a new file. And we'll just jump in here. In this case, we're doing SVM muffin versus cupcake. And then let's start with our packages for data analysis. And we almost always use there's a few very standard packages we use. We use import numpy, that's for number Python. And they usually denote it as NP, that's very common. And then we're going to import pandas as PD. And numpy deals with number arrays. There's a lot of cool things you can do with the numpy setup as far as multiplying all the values in an array, in a numpy array, data array. Pandas, I can't remember if we're using it actually in this data set. I think we do as an import. It makes a nice data frame. And the difference between a data frame and a numpy array is that a data frame is more like your Excel spreadsheet. You have columns, you have indexes, so you have different ways of referencing it, easily viewing it, and there's additional features you can run on a data frame. And Pandas kind of sits on numpy, so you need them both in there. And then finally, we're working with the support vector machine. So from sklearn, we're going to use the sklearn model, import svm, support vector machine. And then as a data scientist, you should always try to visualize your data. Some data obviously is too complicated or doesn't make any sense to the human. But if it's possible, it's good to take a second look at it so that you can actually see what you're doing. Now for that, we're going to use two packages. We're going to import matplotlibary.pyplot as PLT, again very common. And we're going to import Seaborn as SNS. And we'll go ahead and set the font scale in the SNS right in our import line. That's what this semicolon followed by a line of data. We're going to set the SNS. And these are great because the Seaborn sits on top of matplotlibary, just like Pandas sits on numpy. So it adds a lot more features and uses and control. We're obviously not going to get into matplotlibary and Seaborn. That'd be its own tutorial. We're really just focusing on the SVM, the support vector machine from sklearn. And since we're in Jupyter Notebook, we have to add a special line in here for our matplotlibary. And that's your percentage sign or ampersand matplotlibary in line. Now, if you're doing this in just a straight code project, a lot of times I use like Notepad++, and I'll run it from there. You don't have to have that line in there because it'll just pop up as its own window on your computer, depending on how your computer's set up. Because we're running this in the Jupyter Notebook as a browser setup, this tells it to display all of our graphics right below on the page. So that's what that line is for. I remember the first time I ran this, I didn't know that, and I had to go look that up years ago. It was quite a headache. So matplotlibary inline is just because we're running this on the web setup. And we can go ahead and run this, make sure all our modules are in. They're all imported, which is great. If you don't have them import, you'll need to go ahead and pip, use the PIP or however you do it. There's a lot of other install packages out there, although pip is the most common. And you have to make sure these are all installed on your Python setup. The next step, of course, is we got to look at the data. You can't run a model for predicting data if you don't have actual data. So to do that, let me go ahead and open this up and take a look. And we have our cupcakes versus muffins. And it's a CSV file, or .csv, meaning that it's comma-separated variable. And it's going to open it up in a nice spreadsheet for me. And you can see up here we have the type. We have muffin, 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 cupcake, cupcake, cupcake. And then it's broken up into flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. So what we can do is we can go ahead and look at this data also in our Python. Let us create a variable recipes equals, we're going to use our pandas module, .read CSV. Remember, it's a comma-separated variable. And the file name happened to be cupcakes versus muffins. Oops, I got double brackets there. Do it this way. There we go. Cupcakes versus muffins. Because the program I loaded, or the place I saved this particular Python program is in the same folder, we can get by with just the file name. But remember, if you're storing it in a different location, you have to also put down the full path on there. And then because we're in pandas, we're going to go ahead and you can actually, inline you can do this, but let me do the full print. You can just type in recipes.head in the Jupyter Notebook. But if you're running in code in a different script, you need to go ahead and type out the whole print recipes.head. And Pandas knows that that's going to do the first 5 lines of data. And if we flip back on over to the spreadsheet where we opened up our CSV file, you can see where it starts on line 2. This one calls it 0, and then 2, 3, 4, 5, 6 is going to match. Go and close that out because we don't need that anymore. And it always starts at 0. And it automatically indexes it since we didn't tell it to use an index in here. So that's the index number for the left-hand side. And it automatically took the top row as labels. So Pandas using it to read a CSV is just really slick and fast. One of the reasons we love our pandas. Not just because they're cute and cuddly teddy bears. And let's go ahead and plot our data. And I'm not going to plot all of it. I'm just going to plot the sugar and flour. Now obviously you can see where they get really complicated if we have tons of different features. And so you'll break them up and maybe look at just 2 of them at a time to see how they connect. And to plot them, we're going to go ahead and use Seaborn. So that's our SNS. And the command for that is sns.lmplot. And then the 2 different variables I'm going to plot is flour and sugar. Data equals recipes. The hue equals type. And this is a lot of fun because it knows that this is pandas coming in. So this is one of the powerful things about pandas mixed with Seaborn and doing graphing. And then we're going to use a palette set 1. There's a lot of different sets in there. You can go look them up for Seaborn. We'll do a fit regular equals false, so we're not really trying to fit anything. And it's a scatter, KWS. A lot of these settings you can look up in Seaborn. Half of these you could probably leave off when you run them. Somebody played with this and found out that these were the best settings for doing a Seaborn plot. And let's go ahead and run that. And because it does it in line, it just puts it right on the page. And you can see right here that just based on sugar and flour alone, there's a definite split. And we use these models because you can actually look at it and say, hey, if I drew a line right between the middle of the blue dots and the red dots, we'd be able to do an SVM and a hyperplane right there in the middle. Then the next step is to format or pre-process our data. And we're going to break that up into 2 parts. We need a type label, and remember, we're going to decide whether it's a muffin or a cupcake. Well, a computer doesn't know muffin or cupcake, it knows 0 and 1. So, what we're going to do is we're going to create a type label, and from this we'll create a numpy array, np, where, and this is where we can do some logic. We take our recipes from our panda, and wherever type equals muffin, it's going to be 0. And then if it doesn't equal muffin, which is cupcakes, it's going to be 1. So we create our type label. This is the answer. So when we're doing our training model, remember we have to have a training data. This is what we're going to train it with, is that it's 0 or 1. It's a muffin or it's not. And then we're going to create our recipe features. And if you remember correctly from right up here, the first column is type. So we really don't need the type column because that's our muffin or cupcake. And in pandas, we can easily sort that out. We take our value recipes dot columns. That's a pandas function built into pandas. Dot values, converting them to values. So it's just the column titles going across the top. And we don't want the first one. So what we do is, since it always starts at 0, we want 1 colon till the end. And then we want to go ahead and make this a list, and this converts it to a list of strings. And then we can go ahead and just take a look and see what we're looking at for the features, make sure it looks right. Let me go ahead and run that. And I forgot the S on recipes, so we'll go ahead and add the S in there and then run that. And we can see we have flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. And that matches what we have up here, right where we printed out everything but the type. So we have our features and we have our label. Now, the recipe features is just the titles of the columns, and we actually need the ingredients. And at this point, we have a couple options. One, we could run it over all the ingredients. And when you're doing this, usually you do. But for our example, we want to limit it so you can easily see what's going on. Because if we did all the ingredients, we have, that's what, 7, 8 different hyperplanes that would be built into it. We only want to look at one so you can see what the SVM is doing. And so we'll take our recipes and we'll do just flour and sugar. Again, you can replace that with your recipe features and do all of them, but we're going to do just flour and sugar, and we're going to convert that to values. We don't need to make a list out of it because it's not string values. These are actual values on there. And we can go ahead and just print ingredients, and you can see what that looks like. And so we have just the amount of flour and sugar, just the 2 sets of plots. And just for fun, let's go ahead and take this over here and take our recipe features. And so if we decided to use all the recipe features, you'll see that it makes a nice column of different data. So it just strips out all the labels and everything. We just have just the values. But because we want to be able to view this easily in a plot later on, we'll go ahead and take that and just do flour and sugar. And we'll run that and you'll see it's just the 2 columns. So the next step is to go ahead and fit our model. We'll go ahead and just call it model. And it's a SVM. We're using a package called SVC. In this case, we're going to go ahead and set the kernel equals linear. So it's using a specific setup on there. And if we go to the reference on their website for the SVM, you'll see that there's 8 of them here. 3 of them are for regression. 3 are for classification. The SVC, support vector classification, is probably one of the most commonly used. And then there's also one for detecting outliers, and another one that has to do with something a little bit more specific on the model. But SVC and SVR are the 2 most commonly used, standing for support vector classifier and support vector regression. Remember, regression is an actual value, a float value or whatever you're trying to work on. And SVC is a classifier, so it's a yes, no, true, false. But for this, we want to know 0, 1, Muffin, Cupcake. We go ahead and create our model. And once we have our model created, we're going to do model.fit. And this is very common, especially in the sklearn. All their models are followed with the fit command. And what we put into the fit, what we're training with it, is we're putting in the ingredients, which in this case we limited to just flour and sugar. And the type label, is it a muffin or a cupcake? Now, in more complicated data science series, you'd want to split into, we won't get into that today, we split it into training data and test data. And they even do something where they split it into thirds, where a third is used for, where you switch between which one's training and test. There's all kinds of things that go into that, and it gets very complicated when you get to the higher end. Not overly complicated, just an extra step, which we're not going to do today because this is a very simple set of data. And let's go ahead and run this, and now we have our model fit. And I got an error here, so let me fix that real quick. It's capital SVC, it turns out. I did it lowercase. Support vector classifier. There we go. Let's go ahead and run that. And you'll see it comes up with all this information that it prints out automatically. These are the defaults of the model. You notice that we changed the kernel to linear. And there's our kernel linear on the printout. And there's other different settings you can mess with. We're going to just leave that alone for right now. For this, we don't really need to mess with any of those. So next, we're going to dig a little bit into our newly trained model. And we're going to do this so we can show you on a graph. And let's go ahead and get the separating. And we're going to say, we're going to use a W for our variable on here. And we're going to do model.coefficient_0. So what the heck is that? Again, we're digging into the model. So we've already got a prediction and a train. This is the math behind it that we're looking at right now. And so the W is going to represent 2 different coefficients. And if you remember, we had y equals mx plus c. So these coefficients are connected to that, but in 2-dimensional. It's a plane. We don't want to spend too much time on this because you can get lost in the confusion of the math. So if you're a math whiz, this is great. You can go through here and you'll see that we have A equals minus W of 0 over W of 1. Remember, there's two different values there. And that's basically the slope that we're generating. And then we're going to build an XX. What is XX? We're going to set it up to a numpy array. There's our NP dot line space. So we're creating a line plus the intercept. Well, to make this work, we can do this as YY equals the slope times each value in that array. That's the neat thing about numpy. So when I do A times XX, which is a whole numpy array of values, it multiplies A across all of them. And then it takes those same values and we subtract the model intercept. That's your, remember we had mx plus c, so that'd be the c from the formula, y equals mx plus c. And that's where all these numbers come from. A little bit confusing because it's digging out of these different arrays. And then what we want to do is we're going to take this and we're going to go ahead and plot it. So plot the parallels to separating hyperplane that pass through the support vectors. And so we're going to create B equals a model support vectors. Pulling our support vectors out there. Here's our YY, which we now know is a set of data. And we have we're going to create YY down equals A times XX plus B1 minus A times B0. And then model support vector B is going to be set that to a new value, the minus 1 setup. And YY up equals A times XX plus B1 minus A times B0. And we can go ahead and just run this to load these variables up. If you want to understand a little bit more of what's going on, you can see if we print YY, we just run that, you can see it's an array. This is a line. It's going to have, in this case, between 30 and 60, so it's going to be 30 variables in here. And the same thing with YY up, YY down. And we'll plot those in just a minute on a graph so you can see what those look like. You just go ahead and delete that out of here and run that so it loads up the variables. Nice clean slate. I'm just going to copy this from before. Remember this, our SNS, our seaborn plot, LM plot, flour, sugar. And I'll just go ahead and run that real quick so you can see remember what that looks like. It's just a straight graph on there. And then one of the neat things is because seaborn sits on top of pyplot, we can do the pyplot for the line going through. And that is simply plt.plot. And that's our XX and YY, our two corresponding values, XY. And then somebody played with this to figure out that the line width equals 2 and the color black would look nice. So let's go ahead and run this whole thing with the pyplot on there. And you can see when we do this, it's just doing flour and sugar on here. Corresponding line between the sugar and the flour and the muffin versus cupcake. And then we generated the support vectors, the YY down and YY up. So let's take a look and see what that looks like. So we'll do our PL plot. And again, this is all against XX, our X value. But this time we have YY down. And let's do something a little fun with this. We can put in a K dash dash. That just tells it to make it a dotted line. And if we're going to do the down one, we also want to do the up one. So here's our YY up. And when we run that, it adds both sets of line. And so here's our support, and this is what you expect. You expect these two lines to go through the nearest data point. So the dashed lines go through the nearest muffin and the nearest cupcake when it's plotting it. And then your SVM goes right down the middle. So it gives it a nice split in our data, and you can see how easy it is to see, based just on sugar and flour, which one's a muffin or a cupcake. Let's go ahead and create a function to predict muffin or cupcake. I've got my recipes I pulled off the internet, and I want to see the difference between a muffin or a cupcake. And so we need a function to push that through. And we'll create a function with def. And let's call it muffin or cupcake. And remember, we're just doing flour and sugar today. We're not doing all the ingredients. And that actually is a pretty good split. You really don't need all the ingredients to know it's flour and sugar. And let's go ahead and do an if-else statement. So if model predict is of flour and sugar equals 0. So we take our model and we run a predict. It's very common in sklearn where you have a dot predict. You put the data in and it's going to return a value. In this case, if it equals 0, then print you're looking at a muffin recipe. Else, if it's not 0, that means it's 1, then you're looking at a cupcake recipe. That's pretty straightforward for a function, or def for definition. DEF is how you do that in Python. And of course, if you're going to create a function, you should run something in it. And so let's run a cupcake, and we're going to send it values 50 and 20, a muffin or a cupcake. I don't know what it is. And let's run this and just see what it gives us. And it says, oh, it's a muffin. You're looking at a muffin recipe. So it very easily predicts whether we're looking at a muffin or a cupcake recipe. Let's plot this. Oops, there we go. Plot this on the graph so we can see what that actually looks like. And I'm just going to copy it and paste it from below where we're plotting all the points in there. So this is nothing different than what we did before. If I run it, you'll see it has all the points and the lines on there. And what we want to do is we want to add another point. And we'll do PLT plot. And if you remember correctly, we did, for our test, we did 50 and 20. And then somebody went in here and decided we'll do YO for yellow, or it's kind of an orangish yellow color is going to come out. Marker size 9. Those are settings you can play with. Somebody else played with them to come up with the right setup so it looks good. And you can see there it is graphed, clearly a muffin. In this case, in cupcakes versus muffins, the muffin has won. And if you'd like to do your own muffin cupcake contender series, you certainly can send a note down below, and the team at Simplilearn will send you over the data they use for the muffin and cupcake. And that's true of any of the data. We didn't actually run a plot on it earlier. We had men versus women. You can also request that information to run it on your data setup so you can test that out. So to go back over our setup, we went ahead for our support vector machine code. We did a predict 40 parts flour, 20 parts sugar. I think it was different than the one we did, whether it's a muffin or a cupcake. Hence, we have built a classifier using SVM, which is able to classify if a recipe is of a cupcake or a muffin, which wraps up our cupcake versus muffin. Today, in our second tutorial, we're going to cover k-means and linear regression, along with going over the quiz questions we had during our first tutorial. What's in it for you? We're going to cover clustering. What is clustering? K-means clustering, which is one of the most common used clustering tools out there, including a flowchart to understand k-means clustering and how it functions. And then we'll do an actual Python live demo on clustering of cars based on brands. Then we're going to cover logistic regression. What is logistic regression? Logistic regression curve and sigmoid function. And then we'll do another Python code demo to classify a tumor as malignant or benign based on features. And let's start with clustering. Suppose we have a pile of books of different genres. Now we divide them into different groups like fiction, horror, education, and as we can see from this young lady, she definitely is into heavy horror. You can just tell by those eyes and the maple Canadian leaf on her shirt. But we have fiction, horror, and education, and we want to go ahead and divide our books up. Well, organizing objects into groups based on similarity is clustering. And in this case, as we're looking at the books, we're talking about clustering things with known categories. But you can also use it to explore data. So you might not know the categories, you just know that you need to divide it up in some way to conquer the data and to organize it better. But in this case, we're going to be looking at clustering in specific categories. And let's just take a deeper look at that. We're going to use k-means clustering. K-means clustering is probably the most commonly used clustering tool in the machine learning library. K-means clustering is an example of unsupervised learning. If you remember from our previous thing, it is used when you have unlabeled data. So we don't know the answer yet. We have a bunch of data that we want to cluster into different groups. Define clusters in the data based on feature similarity. So we've introduced a couple terms here. We've already talked about unsupervised learning and unlabeled data. So we don't know the answer yet. We're just going to group stuff together and see if we can find an answer of how things connect. We've also introduced feature similarity, features being different features of the data. Now with books, we can easily see fiction and horror and history books, but a lot of times with data, some of that information isn't so easy to see right when we first look at it. And so K-means is one of those tools where we can start finding things that connect, that match with each other. Suppose we have these data points and want to assign them into a cluster. Now when I look at these data points, I would probably group them into two clusters just by looking at them. I'd say two of these group of data kind of come together. But in K-means, we pick K clusters and assign random centroids to clusters, where the K clusters represents two different clusters. We pick K clusters and assign random centroids to the clusters, then we compute distance from objects to the centroids. Now we form new clusters based on minimum distances and calculate the centroids. So we figure out what the best distance is for the centroid, then we move the centroid and recalculate those distances. Repeat previous two steps iteratively till the cluster centroids stop changing their positions and become static. Repeat previous two steps iteratively till the cluster centroids stop changing and the positions become static. Once the clusters become static, then K-means clustering algorithm is said to be converged. And there's another term we see throughout machine learning is converged. That means whatever math we're using to figure out the answer has come to a solution, or it's converged on an answer. Shall we see the flow chart to understand? Make a little bit more sense by putting it into a nice, easy step-by-step. So we start, we choose K, we'll look at the elbow method in just a moment. We assign random centroids to clusters, and sometimes you pick the centroids, because you might look at the data in a graph and say, oh, these are probably the central points. Then we compute the distance from the objects to the centroids. We take that and we form new clusters based on minimum distance and calculate their centroids. Then we compute the distance from objects to the new centroids. And then we go back and repeat those last two steps. We calculate the distances. So as we're doing it, it brings into the new centroid, and then we move the centroid around and we figure out which objects are closest to each centroid. So the objects can switch from one centroid to the other as the centroids are moved around. And we continue that until it is converged. Let's see an example of this. Suppose we have this data set of 7 individuals and their score on two topics, A and B. So here's our subject, in this case referring to the person taking the test. And then we have subject A where we see what they've scored on their first subject, and we have subject B and we can see what they score on the second subject. Now let's take two farthest apart points as initial cluster centroids. Now remember, we talked about selecting them randomly, or we can also just put them in different points and pick the furthest one apart so they move together. Either one works okay, depending on what kind of data you're working on and what you know about it. So we took the two furthest points, 1 and 1, and 5 and 7. And now let's take the two farthest apart points as initial cluster centroids. Each point is then assigned to the closest cluster with respect to the distance from the centroids. So we take each one of these points in there, we measure that distance, and you can see that if we measured each of those distances, and you use the Pythagorean theorem for a triangle in this case, because you know the x and the y, and you can figure out the diagonal line from that. Or you can just take a ruler and put it on your monitor. That'd be kind of silly, but it would work if you're just eyeballing it. You can see how they naturally come together in certain areas. Now we again calculate the centroids of each cluster. So cluster 1 and then cluster 2, and we look at each individual dot. There's 1, 2, 3, we're in one cluster. The centroid then moves over. It becomes 1.8, 2.3. So remember, it was at 1 and 1? Well, the very center of the data we're looking at would put it at the roughly 2.2, but 1.8 and 2.3. And the second one, if we wanted to make the overall mean vector, the average vector of all the different distances to that centroid, we come up with 4, 1 and 5, 4. So we've now moved the centroids. We compare each individual's distance to its own cluster, mean, and to that of the opposite cluster, and we find, we can build a nice chart on here, that as we move that centroid around, we now have a new different kind of clustering of groups, and using Euclidean distance between the points and the mean, we get the same formula. You see new formulas coming up. So we have our individual dots, distance to the mean, centroid of the cluster, and distance to the mean, centroid of the cluster. Only individual 3 is nearer to the mean of the opposite cluster, cluster 2, than its own cluster 1. And you can see here in the diagram where we've kind of circled that 1 in the middle. So when we've moved the centroids of the clusters over, one of the points shifted to the other cluster because it's closer to that group of individuals. Thus, individual 3 is relocated to cluster 2, resulting in a new partition. And we regenerate all those numbers of how close they are to the different clusters. For the new clusters, we will find the actual cluster centroids. So now we move the centroids over, and you can see that we've now formed two very distinct clusters on here. On comparing the distance of each individual's distance to its own cluster mean and to that of the opposite cluster, we find that the data points are stable, hence we have our final clusters. Now, if you remember, I brought up a concept earlier, K-mean on the K-means algorithm. Choosing the right value of K will help in less number of iterations. And to find the appropriate number of clusters in a data set, we use the elbow method. And within sum of squares, WSS, is defined as the sum of the squared distance between each member of the cluster and its centroid. And so you see what we've done here is we have the number of clusters. And as you do the same K-means algorithm over the different clusters, and you calculate what that centroid looks like, and you find the optimal, you can actually find the optimal number of clusters using the elbow of the graph, is called as the elbow method. And on this, we guessed at 2 just by looking at the data. But as you can see, the slope, you actually just look for right there where the elbow is in the slope, and you have a clear answer that we want 2 different, to start with K-means equals 2. A lot of times people end up computing K-means equals 2, 3, 4, 5 until they find the value which fits on the elbow joint. Sometimes you can just look at the data, and if you're really good with that specific domain, remember domain, I mentioned that last time, you'll know that where to pick those numbers or where to start guessing at what that K value is. So let's take this, and we're going to use a use case using K-means clustering to cluster cars into brands using parameters such as horsepower, cubic inches, make, year, etc. So we're going to use the dataset cars data, having information about 3 brands of cars, Toyota, Honda, and Nissan. We'll go back to my favorite tool, the Anaconda Navigator with the Jupyter Notebook. And let's go ahead and flip over to our Jupyter Notebook. And in our Jupyter Notebook, I'm going to go ahead and just paste the basic code that we usually start a lot of these off with. We're not going to go too much into this code because we've already discussed NumPy, we've already discussed Matplotlib, and pandas. NumPy being the number array, pandas being the pandas data frame, and Matplot for the graphing. And don't forget, since if you're using the Jupyter Notebook, you do need the Matplotlib inline so that it plots everything on the screen. If you're using a different Python editor, then you probably don't need that because it'll have a pop-up window on your computer. And we'll go ahead and run this just to load our libraries and our setup into here. The next step is, of course, to look at our data, which I've already opened up in a spreadsheet. And you can see here we have the miles per gallon, cylinders, cubic inches, horsepower, weight pounds, how heavy it is, time it takes to get to 60. My card is probably on this one at about 80 or 90. What year it is. So this is, you can actually see this is kind of older cars, and then the brand, Toyota, Honda, Nissan. So the different cars are coming from all the way from 1971, if we scroll down, to the 80s. We have between the 70s and 80s a number of cars that they've put out. And let's, when we come back here, we're going to do importing the data. So we'll go ahead and do dataset equals, and we'll use pandas to read this in, and it's from a CSV file. Remember, you can always post this in the comments and request the data files for these, either in the comments here on the YouTube video or go to Simplilearn.com and request that. The cars CSV, I put it in the same folder as the code that I've stored. So my Python code is stored in the same folder, so I don't have to put the full path. If you store them in different folders, you do have to change this and double check your name variables. And we'll go ahead and run this, and we've chosen dataset arbitrarily because it's a dataset we're importing, and we've now imported our cars CSV into the dataset. As you know, you have to prep the data, so we're going to create the X data. This is the one that we're going to try to figure out what's going on with. And then there's a number of ways to do this, but we'll do it in a simple loop so you can actually see what's going on. So we'll do for I in x.columns. So we're going to go through each of the columns, and a lot of times it's important. I'll make lists of the columns and do this because I might remove certain columns, or there might be columns that I want to be processed differently. But for this, we can go ahead and take x of I, and we want to go fill NA, and that's a pandas command. But the question is, what are we going to fill the missing data with? We definitely don't want to just put in a number that doesn't actually mean something. And so one of the tricks you can do with this is we can take x of I, And then in addition to that, we want to go ahead and turn this into an integer, because a lot of these are integers. So we'll go ahead and keep it integers. And we add the bracket here. And a lot of editors will do this. They'll think that you're closing one bracket. Make sure you get that second bracket in there if it's a double bracket. That's always something that happens regularly. So once we have our integer of x of y, this is going to fill in any missing data with the average. And I was so busy closing one set of brackets, I forgot that the mean also has brackets in there for the pandas. So we can see here we're going to fill in all the data with the average value for that column. So if there's missing data, it's in the average of the data it does have. And then once we've done that, we'll go ahead and loop through it again and just check and see to make sure everything is filled in correctly. And we'll print, and then we take x is null, and this returns a set of the null value, or the how many lines are null, and we'll just sum that up to see what that looks like. And so when I run this, and so with the x, what we want to do is we want to remove the last column because that had the models. That's what we're trying to see, if we can cluster these things and figure out the models. There is so many different ways to sort the x out. For one, we could take the x and we could go data set, our variable we're using, and use the iLocation, one of the features that's in pandas. And we could take that and then take all the rows and all but the last column of the data set. And at this time we could do values. We just convert it to values. So that's one way to do this. And if let me just put this down here and print x, it's a capital X we chose, and I run this, you can see it's just the values. We could also take out the values and it's not going to return anything because there's no values connected to it. What I like to do with this is, instead of doing the iLocation, which does integers, more common is to come in here and we have our data set, and we're going to do dataset dot columns. And remember, that lists all the columns. So if I come in here, let me just mark that as red, and I print dataset dot columns. You can see that I have my index here. I have my MPG, cylinders, everything, including the brand, which we don't want. So the way to get rid of the brand would be to do data columns of everything but the last one, -1. So now if I print this, you'll see the brand disappears. And so I can actually just take dataset columns -1, and I'll put it right in here for the columns we're going to look at. And let's unmark this and unmark this. And now if I do an x.head, I now have a new data frame, and you can see right here we have all the different columns except for the brand at the end of the year. And it turns out when you start playing with the data set, you're going to get an error later on, and it'll say cannot convert string to float value. And that's because for some reason these things, the way they recorded them, must have been recorded as strings. So we have a neat feature in here on pandas to convert. And it is simply convert objects. And for this we're going to do convert underscore numeric equals true. And yes, I did have to go look that up. I don't have it memorized, the convert numeric in there. If I'm working with a lot of these things, I remember them, but depending on where I'm at, what I'm doing, I usually have to look it up. And we run that. Oops, I must have missed something in here. Let me double check my spelling. And when I double check my spelling, you'll see I missed the first underscore in the convert objects. And when I run this, it now has everything converted into a numeric value, because that's what we're going to be working with, is numeric values down here. And the next part is that we need to go through the data and eliminate null values. Most people, when they're doing small amounts, working with small data pools, discover afterwards that they have a null value and they have to go back and do this. So, be aware, whenever we're formatting this data, things are going to pop up, and sometimes you go backwards to fix it. And that's fine. That's just part of exploring the data and understanding what you have. And I should have done this earlier, but let me go ahead and increase the size of my window one notch. There we go. Easier to see. So we'll do for I in working with x dot columns. We'll page through all the columns. And we want to take x of I, and we're going to change that. We're going to alter it. And so with this, we want to go ahead and fill in x of I. Pandas has the fill in A. and that just fills in any non-existent missing data. And we'll put my brackets up, and there's a lot of different ways to fill this data. If you have a really large data set, some people just void out that data and then look at it later in a separate exploration of data. One of the tricks we can do is we can take our column and we can find the means. And the means is in our quotation marks. So we take the columns, we're going to fill in the non-existing one with the means. The problem is that returns a decimal float. So some of these aren't decimals. Certainly, we need to be a little careful of doing this, but for this example, we're just going to fill it in with the integer version of this. It keeps it on par with the other data that isn't a decimal point. And then what we also want to do is we want to double check. Ways you can do that is simply go in here and take our x of I column. So it's going to go through the x of I column. It says is null. So it's going to return any place there's a null value. It actually goes through all the rows of each column is null, and then we want to go ahead and sum that. So we take that and we add the sum value, and these are all pandas. So is null is a panda command, and so is sum. And if we go through that and we go ahead and run it, and we go ahead and take and run that, you'll see that all the columns have 0 null values. So we've now tested and double checked, and our data is nice and clean. We have no null values. Everything is now a number value. We turned it into numeric. And we've removed the last column in our data. And at this point, we're actually going to start using the elbow method to find the optimal number of clusters. So we're now actually getting into the sklearn part, the k-means clustering on here. I guess we'll go ahead and zoom it up one more notch so you can see what I'm typing in here. And then from sklearn, we're going to our sklearn cluster, we're going to import k-means. I always forget to capitalize the k and the m when I do this. So it's capital K, capital M, k-means. And we'll go ahead and create a array, WCSS equals, we'll make it an empty array. If you remember from the elbow method from our slide, within the sum of squares, WSS is defined as the sum of square distance between each member of the cluster and its centroid. So we're looking at that change in differences as far as a square distance. And we're going to run this over a number of k-mean values. In fact, let's go for I in range, we'll do 11 of them. Range 0 of 11. And the first thing we're going to do is we're going to create the actual, we'll do it all lowercase. And so we're going to create this object from the k-means that we just imported. And the variable that we want to put into this is in clusters. And we're going to set that equals to I. That's the most important one because we're looking at how increasing the number of clusters changes our answer. There are a lot of settings to the k-means. Our guys in the back did a great job just kind of playing with some of them. The most common ones that you see in a lot of stuff is how you init your k-means. So we have k-means plus plus. This is just a tool to let the model itself be smart how it picks its centroids to start with, its initial centroids. We only want to iterate no more than 300 times. We have a max iteration we put in there. We have the nth init, the random state equals 0. You really don't need to worry too much about these when you're first learning this. As you start digging in deeper, you start finding that these are shortcuts that will speed up the process as far as the setup. But the big one that we're working with is the in clusters equals I. So we're going to literally train our k-means 11 times. We're going to do this process 11 times. And if you're working with big data, you know the first thing you do is you run a small sample of the data so you can test all your stuff on it. And you can already see the problem that if I'm going to iterate through a terabyte of data 11 times, and then the k-means itself is iterating through the data multiple times, that's a heck of a process. So you got to be a little careful with this. A lot of times, though, you can find your elbow, using the elbow method, find your optimal number on a sample of data, especially if you're working with larger data sources. So we want to go ahead and take our k-means and we're just going to fit it. If you're looking at any of the sklearn very common you fit your model. And if you remember correctly, our variable we're using is the capital X. And once we fit this value, we go back to the array we made, and we want to go ahead and just append that value on the end. And it's not the actual fit we're pinning in there, it's when it generates the value you're looking for is inertia. So k-means.inertia will pull that specific value out that we need. And let's get a visual on this. We'll do our PLT plot, and what we're plotting here is first the x-axis, which is range 0, 11, so that will generate a nice little plot there, and the WCSS for our y-axis. It's always nice to give our plot a title, and let's see, we'll just give it the elbow method for the title, and let's get some labels. So let's go ahead and do PLT X label, and what we'll do number of clusters for that, and PLT Y label, and for that we can do, there we go, WCSS, since that's what we're doing on the plot on there. And finally we want to go ahead and display our graph, which is simply PLT dot show. There we go. And because we have it set to inline, it'll appear inline. Hopefully I didn't make a type error on there. And you can see we get a very nice graph. You can see a very nice elbow joint there at 2, and again right around 3 and 4, and then after that there's not very much. Now, as a data scientist, if I was looking at this, I would do either 3 or 4, and I'd actually try both of them to see what the output looked like. And they've already tried this in the back, so we're just going to use 3 as a setup on here. And let's go ahead and see what that looks like when we actually use this to show the different kinds of cars. And so let's go ahead and apply the k-means to the cars data set. And basically we're going to copy the code that we looped through up above, where k-means equals k-means number of clusters, and we're just going to set the number of clusters to 3, since that's what we're going to look for. And you could do 3 and 4 on this and graph them just to see how they come up differently. It'd be kind of curious to look at that. But for this we're just going to set it to 3. Go ahead and create our own variable y k-means for our answers. And we're going to set that equal to, whoops, a double equal there, to k-means, but we're not going to do a fit. We're going to do a fit predict is the setup you want to use. And when you're using untrained models, you'll see a slightly different, because usually you see fit and then you see just the predict. But we want to both fit and predict the k-means on this. And that's fit underscore predict, and then our capital X is the data we're working with. And before we plot this data, we're going to do a little pandas trick. We're going to take our x value and we're going to set x as matrix. So we're converting this into a nice rows and columns kind of setup, but we're going to have columns equals none, so it's just going to be a matrix of data in here. And let's go ahead and run that. Like a little warning. You'll see these warnings pop up because things are always being updated. So there's like minor changes in the versions and future versions. Instead of matrix, now it's more common to set it dot values instead of doing as matrix. But as matrix works just fine for right now, and you'll want to update that later on. But let's go ahead and dive in and plot this and see what that looks like. And before we dive into plotting this data, I always like to take a look and see what I am plotting. So let's take a look at y k-means, and I'm just going to print that out down here. And we see we have an array of answers. We have 2, 1, 0, 2, 1, 2. So it's clustering these different rows of data based on the 3 different spaces it thinks it's going to be. And then let's go ahead and print x and see what we have for x. And we'll see that x is an array, it's a matrix, so we have our different values in the array. And what we're going to do, it's very hard to plot all the different values in the array. So we're only going to be looking at the first 2, or positions 0 and 1. And if you were doing a full presentation in front of the board meeting, you might actually do a little different and dig a little deeper into the different aspects, because this is all the different columns we looked at. But we'll only look at columns 1 and 2 for this to make it easy. So let's go ahead and clear this data out of here, and let's bring up our plot. And we're going to do a scatter plot here. So PLT scatter, and this looks a little complicated, so let's explain what's going on with this. we're going to take the x values, and we're only interested in y of k means equals 0, the first cluster. Okay? And then we're going to take value 0 for the x-axis, and then we're going to do the same thing here. We're only interested in k means equals 0, but we're going to take the second column. So we're only looking at the first two columns in our answer, or in the data. And then the guys in the back played with this a little bit to make it pretty. And they discovered that it looks good if it has a size equals 100. That's the size of the dots. We're going to use red for this one. And when they were looking at the data and what came out, it was definitely the Toyota on this. We're just going to go ahead and label it Toyota. Again, that's something you really have to explore in here as far as playing with those numbers and see what looks good. We'll go ahead and hit enter in there. And I'm just going to paste in the next two lines, which is the next two cars. And this is our Nissan and Honda. And you'll see with our scatter plot, we're now looking at where y underscore k means equals 1. And we want the 0 column, and yk means equals 2. Again, we're looking at just the first two columns, 0 and 1. And each of these rows then corresponds to Nissan and Honda. And I'll go ahead and hit enter on there. And finally, let's take a look and put the centroids on there. Again, we're going to do a scatter plot. And on the centroids, you can just pull that from our k-means, the model we created, dot cluster centers, and we're going to just do all of them in the first number and all of them in the second number, which is 0, 1, because you always start with 0 and 1. And then they were playing with the size and everything to make it look good. We'll do a size of 300. We're going to make the color yellow, and we'll label them. It's always good to have some good labels, centroids. And then we do want to do a title, PLT title, and pop up there. PLT title, because you always want to make your graphs look pretty, and we'll call it clusters of car make. And one of the features of the plot library is you can add a legend. It'll automatically bring in it since we've already labeled the different aspects of the legend with Toyota, Nissan, and Honda. And finally, we want to go ahead and show, so we can actually see it. And remember, it's inline, so if you're using a different editor that's not the Jupyter Notebook, you'll get a pop-up of this. And you should have a nice set of clusters here. So we can look at this, and we have clusters of Honda in green, Toyota in red, Nissan in purple. And you can see where they put the centroids to separate them. Now, when we're looking at this, we can also plot a lot of other different data on here because we only looked at the first two columns. This is just column 1 and 2. Or 0, 1 as you label them in computer scripting. But you can see here we have nice clusters of car make, and we were able to pull out the data, and you can see how just these two columns form very distinct clusters of data. So if you were exploring new data, you might take a look and say, well, what makes these different? Almost going in reverse, you start looking at the data and pulling apart the columns to find out why is the first group set up the way it is. Maybe you're doing loans and you want to go, well, why is this group not defaulting on their loans? And why is the last group defaulting on their loans? And why is the middle group 50% defaulting on their bank loans? And you start finding ways to manipulate the data and pull out the answers you want. So now that you've seen how to use k-mean for clustering, let's move on to the next topic. Now let's look into logistic regression. The logistic regression algorithm is the simplest classification algorithm used for binary or multi-classification problems. And we can see we have our little girl from Canada who's into horror books is back. That's actually really scary when you think about that with those big eyes. In the previous tutorial, we learned about linear regression, dependent and independent variables. So, to brush up, y equals mx plus c. Very basic algebraic function of y and x. The dependent variable is the target class variable we are going to predict. The independent variables, x1 all the way up to xn, are the features or attributes we're going to use to predict the target class. We know what a linear regression looks like, but using the graph we cannot divide the outcome into categories. It's really hard to categorize 1.5, 3.6, 9.8. For example, a linear regression graph can tell us that with increase in number of hours studied, the marks of a student will increase, but it will not tell us whether the student will pass or not. In such cases where we need the output as categorical value, we will use logistic regression. And for that, we're going to use the sigmoid function. So you can see here we have our marks, 0 to 100, number of hours studied. That's going to be what they're comparing it to in this example. And we usually form a line that says y equals mx plus c. And when we use the sigmoid function, we have p equals 1 over 1 plus e to the minus y. It generates a sigmoid curve. And so you can see right here, when you take the ln, which is the natural logarithm, I always thought it should be nl, not ln. That's just the inverse of e, or e to the minus y. And so when we do this, we get ln of p over 1 minus p equals m times x plus c. That's the sigmoid curve function we're looking for. And we can zoom in on the function, and you'll see that the function, as it derives, goes to 1 or to 0, depending on what your x value is. And the probability, if it's greater than 0.5, the value is automatically rounded off to 1, indicating that the student will pass. So if they're doing a certain amount of studying, they will probably pass. Then you have a threshold value at the 0.5. It automatically puts that right in the middle usually. And your probability, if it's less than 0.5, the value rounded off to 0, indicating the student will fail. So if they're not studying very hard, they're probably going to fail. This, of course, is ignoring the outliers of that one student who's just a natural genius and doesn't need any studying to memorize everything. That's not me, unfortunately. I have to study hard to learn new stuff. Problem statement. To classify whether a tumor is malignant or benign. And this is actually one of my favorite data sets to play with because it has so many features, and when you look at them, you really are hard to understand. You can't just look at them and know the answer. So it gives you a chance to kind of dive into what data looks like when you aren't able to understand the specific domain of the data. But I also want you to remind you that in the domain of medicine, if I told you that my probability was really good at classified things at, say, 90% or 95%, and I'm classifying whether you're going to have a malignant or a benign tumor, I'm guessing that you're going to go get it tested anyways. So you got to remember the domain we're working with. So why would you want to do that if you know you're just going to go get a biopsy because, you know, it's that serious? This is like an all or nothing. Just referencing the domain, it's important. It might help the doctor know where to look just by understanding what kind of tumor it is. So it might help them or aid them in something they missed from before. So let's go ahead and dive into the code, and I'll come back to the domain part of it in just a minute. So use case, and we're going to do our normal imports here, where we're importing NumPy, Pandas, Seaborn, the Matplot library, and we're going to do Matplot library inline since I'm going to switch over to Anaconda. So let's go ahead and flip over there and get this started. So I've opened up a new window in my Anaconda Jupyter Notebook. And by the way, Jupyter Notebook, you don't have to use Anaconda for the Jupyter Notebook. I just love the interface and all the tools that Anaconda brings. So we got our import NumPy as in P for our NumPy number array. We have our Pandas PD. We're going to bring in Seaborn to help us with our graphs as SNS. So many really nice tools in both Seaborn and Matplot library. Then we'll do our Matplot library.pyplot as PLT. And then, of course, we want to let it know to do it in line. And let's go ahead and just run that so it's all set up. And we're just going to call our data, not creative today, equals PD. And this happens to be in a CSV file. So we'll use the pd.read_CSV. And I happen to name the file, I renamed it, data for p2.csv. You can, of course, write in the comments below the YouTube and request for the data set itself, or go to the Simplilearn website, and we'll be happy to supply that for you. And let's just open up the data before we go any further, and let's just see what it looks like in a spreadsheet. So when I pop it open in a local spreadsheet, and this is just a CSV file, comma-separated variables, we have an ID, so I guess they categorize this for reference or what ID, which test was done. The diagnosis, M for malignant, B for benign, so there's two different options on there. And that's what we're going to try to predict is the M and B and test it. And then we have like the radius mean or average, the texture average, perimeter mean, area mean, smoothness. I don't know about you, but unless you're a doctor in the field, most of the stuff, I mean, you can guess what concave means just by the term concave, but I really wouldn't know what that means in the measurements they're taking. So they have all kinds of stuff like how smooth it is, the symmetry, and these are all float values. We can just page through them real quick. And you'll see there's, I believe, 36, if I remember correctly, in this one. So there's a lot of different values they take and all these measurements they take when they go in there and they take a look at the different growth, the tumorous growth. So back in our data, and I put this in the same folder as the code. So I saved this code in that folder. Obviously, if you have it in a different location, you want to put the full path in there. And we'll just do pandas first 5 lines of data with the data.head. When we run that, we can see that we have pretty much what we just looked at. We have an ID, we have a diagnosis. If we go all the way across, you'll see all the different columns coming across displayed nicely for our data. And while we're exploring the data, our Seaborn, which we referenced as SNS, makes it very easy to go in here and do a joint plot. You'll notice very similar to, because it is sitting on top of the plot library. So the joint plot does a lot of work for us. And we're just going to look at the first 2 columns that we're interested in, the radius mean and the texture mean. We'll just look at those 2 columns. And data equals data. So that tells it which 2 columns we're plotting and that we're going to use the data that we pulled in. And let's just run that. And it generates a really nice graph on here. And there's all kinds of cool things on this graph to look at. I mean, we have the texture mean and the radius mean, obviously the axes. You can also see, one of the cool things on here is you can also see the histogram. They show that for the radius mean. Where is the most commonest radius mean come up and where the most common texture is. So we're looking at on each growth its average texture and on each radius its average radius on there. It gets a little confusing because we're talking about the individual object's average, and then we can also look over here and see the histogram showing us the median or how common each measurement is. And that's only 2 columns, so let's dig a little deeper into Seaborn. They also have a heat map. And if you're not familiar with heat maps, a heat map just means it's in color. That's all that means. Heat map, I guess the original ones were plotting heat density on something, and so ever since then it's just called a heat map. And we're going to take our data and get our corresponding numbers to put that into the heat map. And that's simply data.corr for that. That's a pandas expression. So remember, we're working in a pandas data frame, so that's one of the cool tools in pandas for our data. And let's just pull that information into a heat map and see what that looks like. And you'll see that we're now looking at all the different features. We have our ID, we have our texture, we have our area, our compactness, concave points. And if you look down the middle of this chart, diagonal, going from the upper left to bottom right, it's all white. That's because when you compare texture to texture, they're identical. So they're 100%, or in this case, a perfect 1 in their correspondence. And you'll see that when you look at, say, area, or right below it, it has almost a black on there when you compare it to texture. So these have almost no corresponding data. They don't really form a linear graph or something that you can look at and say how connected they are. They're very scattered data. This is really just a really nice graph to get a quick look at your data. It doesn't so much change what you do, but it changes verifying. So when you get an answer or something like that, or you start looking at some of these individual pieces, you might go, hey, that doesn't match. According to showing our heat map, this should not correlate with each other. And if it is, you're going to have to start asking, well, why? What's going on? What else is coming in there? But it does show some really cool information on here. I mean, we can see from the ID, there's no real one feature that just says, if you go across the top line, that lights up. There's no one feature that says, hey, if the area is a certain size, then it's going to be benign or malignant. It says there's some that sort of add up. And that's a big hint in the data that we're trying to ID this, whether it's malignant or benign. That's a big hint to us as data scientists to go, okay, we can't solve this with any one feature. It's going to be something that includes all the features or many of the different features to come up with a solution for it. And while we're exploring the data, let's explore one more area and let's look at data.isNull. We want to check for null values in our data. If you remember from earlier in this tutorial, we did it a little differently where we added stuff up and summed them up. You can actually, with pandas, do it really quickly, data.isNull and sum it, and it's going to go across all the columns. So when I run this, you're going to see all the columns come up with no null data. So we've just to rehash these last few steps, we've done a lot of exploration. We have looked at the first two columns and seen how they plot with the seaborn, with a joint plot which shows both the histogram and the data plotted on the XY coordinates. And obviously you can do that more in detail with different columns and see how they plot together. And then we took and did the seaborn heat map, the SNS heat map of the data. And you can see right here where it did a nice job showing us some bright spots where stuff correlates with each other and forms a very nice combination or points of scattering points. And you can also see areas that don't. And then finally we went ahead and checked the data. Is the data null value? Do we have any missing data in there? Very important step because it'll crash later on. If you forget to do this step, it will remind you when you get that nice error code that says null values. Okay, so not a big deal if you miss it, but it's no fun having to go back when you're in a huge process and you've missed this step and now you're 10 steps later and you got to go remember where you were pulling the data in. So we need to go ahead and pull out our X and our Y. So we just put that down here and we'll set the X equal to, and there's a lot of different options here. Certainly we could do X equals all the columns except for the first two, because if you remember the first two is the ID and the diagnosis. So that certainly would be an option. But what we're going to do is we're actually going to focus on the worst radius, the worst texture, parameter, area, smoothness, compactness, and so on. One of the reasons to start dividing your data up when you're looking at this information is sometimes the data will be the same data coming in. So if I have two measurements coming into my model, it might overweigh them. It might overpower the other measurements because it's basically taking that information in twice. That's a little bit past the scope of this tutorial. What I want you to take away from this, though, is that we are dividing the data up into pieces, and our team in the back went ahead and said, hey, let's just look at the worst. So I'm going to create an array, and you'll see this array, radius worst, texture worst, perimeter worst. We've just taken the worst of the worst, and I'm just going to put that in my X. So this X is still a pandas data frame, but it's just those columns. And our Y, if you remember correctly, is going to be, oops, hold on one second. It's not X, it's data. There we go. So X equals data, and then it's a list of the different columns, the worst of the worst. And if we're going to take that, then we have to have our answer for our Y, for the stuff we know. And if you remember correctly, we're just going to be looking at the diagnosis. That's all we care about is what is it diagnosed? Is it benign or malignant? And since it's a single column, we can just do diagnosis. Oh, I forgot to put the brackets. There we go. Okay. So it's just diagnosis on there. And we can also real quickly do like X dot head if you want to see what that looks like. And Y dot head. And run this. And you'll see it only does the last one. I forgot about that if you don't do print. You can see that the Y dot head is just MMM because the first ones are all malignant. And if I run this, the X dot head is just the first 5 values of radius worst, texture worst, parameter worst, area worst, and so on. I'll go ahead and take that out. So moving down to the next step, we've built our two data sets, our answer and then the features we want to look at. In data science, it's very important to test your model. So we do that by splitting the data. And from sklearn model selection, we're going to import train test split. So we're going to split it into 2 groups. There are so many ways to do this. I noticed in one of the more modern ways, they actually split it into 3 groups, and then you model each group and test it against the other groups. So you have all kinds of, and there's reasons for that, which is past the scope of this, and for this particular example isn't necessary. For this, we're just going to split it into 2 groups, one to train our data and one to test our data. And the sklearn model selection, we have train test split. You could write your own quick code to do this where you just randomly divide the data up into 2 groups, but they do it for us nicely. And we can actually do it in one statement with this, where we're going to generate 4 variables, capital X train, capital X test. So we have our training data we're going to use to fit the model, and then we need something to test it. And then we have our Y train, so we're going to train the answer, and then we have our test. So this is the stuff we want to see how good it did on our model. And we'll go ahead and take our train test split that we just imported, And we're going to do X and our Y, our two different data that's going in for our split. And then the guys in the back came up and wanted us to go ahead and use a test size equals 0.3. That's test underscore size. Random state, it's always nice to kind of switch your random state around, but not that important. What this means is that the test size is we're going to take 30% of the data and we're going to put that into our test variables, our Y test and our X test. And we're going to do 70% into the X train and the Y train. So we're going to use 70% of the data to train our model and 30% to test it. Let's go ahead and run that and load those up. So now we have all our stuff split up and all our data ready to go. And now we get to the actual logistics part. We're actually going to create our model. So let's go ahead and bring that in from sklearn. We're going to bring in our linear model and we're going to import Logistic Regression. That's the actual model we're using. And this, we'll call it log model. Oops, there we go, model. And let's just set this equal to our logistic regression that we just imported. So now we have a variable log model set to that class for us to use. And with most of the models in the sklearn, we just need to go ahead and do a fit on there. And we use our X train that we separated out with our Y train. Now let's go ahead and run this. So once we've run this, we'll have a model that fits this data, that 70% of our training data. And of course it prints this out that tells us all the different variables that you can set on there. There's a lot of different choices you can make. But for what we're doing, we're just going to let all the defaults sit. We don't really need to mess with those on this particular example. And there's nothing in here that really stands out as super important until you start fine-tuning it. But for what we're doing, the basics will work just fine. And then we need to go ahead and test out our model. Is it working? So let's create a variable yPredict, and this is going to be equal to our log model. And we want to do a predict. Again, very standard format for the sklearn library is taking your model and doing a predict on it. And we're going to test yPredict against the Y test. So we want to know what the model thinks it's going to be. That's what our yPredict is. And with that, we want the capital X test. So we have our train set and our test set, and now we're going to do our yPredict. And let's go ahead and run that. And if we print yPredict, let me go ahead and run that, you'll see it comes up and it prints a nice array of B and M for benign and malignant for all the different test data we put in there. So it does pretty good. We're not sure exactly how good it does, but we can see that it actually works and is functional. It was very easy to create. You'll always discover with our data science that as you explore this, you spend a significant amount of time prepping your data and making sure your data coming in is good. There's a saying, good data in, good answers out. Bad data in, bad answers out. That's only half the thing. That's only half of it. Selecting your models becomes the next part as far as how good your models are. And then, of course, fine-tuning it depending on what model you're using. So we come in here, we want to know how good this came out. So we have our yPredict here, logModel.predict X test. So for deciding how good our model is, we're going to go from the sklearn.metrics, we're going to import classification report. And that just reports how good our model is doing. And then we're going to feed it the model data. And let's just print this out. And we'll take our classification report and we're going to put into there our test, our actual data. So this is what we actually know is true. And our prediction, what our model predicted for that data on the test side. And let's run that and see what that does. So we pull that up, you'll see that we have a precision for benign and malignant, B and M. And we have a precision of 93 and 91, a total of 92. So it's kind of the average between these two of 92. There's all kinds of different information on here. Your F1 score, your recall, your support coming through on this. And for this, I'll go ahead and just flip back to our slides that they put together for describing it. And so here we're going to look at the precision using the classification report. And you see this is the same printout I had up above. Some of the numbers might be different because it does randomly pick out which data we're using. So this model is able to predict the type of tumor with 91% accuracy. So when we look back here, you'll see where we have benign and malignant. It actually is 92 coming up here. But we're looking at about a 91% precision. And remember, I reminded you about domains. So when we're talking about the domain of a medical domain with a very catastrophic outcome, at 91 or 92% precision, you're still going to go in there and have somebody do a biopsy on it. Very different than if you're investing money and there's a 92% chance you're going to earn 10% and 8% chance you're going to lose 8%, you're probably going to bet the money, because at that odds it's pretty good that you'll make some money, and in the long run, you do that enough, you definitely will make money. And also with this domain, I've actually seen them use this to identify different forms of cancer. That's one of the things that they're starting to use these models for, because then it helps the doctor know what to investigate. So that wraps up this section. We're going to go in there and let's discuss the answer to the quiz asked in Machine Learning Tutorial Part 1. Can you tell what's happening in the following cases? Grouping documents into different categories based on the topic and content of each document. This is an example of clustering, where k-means clustering can be used to group the documents by topics using bag of words approach. So if you've gotten in there that you're looking for clustering, and hopefully you had at least one or two examples like k-means that are used for clustering different things, then give yourself a 2 thumbs up. B. Identifying handwritten digits in images correctly. This is an example of classification. The traditional approach to solving this would be to extract digit-dependent features like curvature of different digits, etc., and then use a classifier like SVM to distinguish between images. Again, if you got the fact that it's a classification example, give yourself a thumb up, and if you're able to go, hey, let's use SVM or another model for this, give yourself those 2 thumbs up on it. C. Behavior of a website indicating that the site is not working as designed. This is an example of anomaly detection. In this case, the algorithm learns what is normal and what is not normal, usually by observing the logs of the website. Give yourself a thumbs up if you got that one. And just for a bonus, can you think of another example of anomaly detection? One of the ones I use it for in my own business is detecting anomalies in stock markets. Stock markets are very fickle and they behave very erratic. So finding those erratic areas and then finding ways to track down why they're erratic. Was something released in social media? Was something released? You can see where knowing where that anomaly is can help you to figure out what the answer is to it in another area. D. Predicting salary of an individual based on his or her years of experience. This is an example of regression. This problem can be mathematically defined as a function between independent, years of experience, and dependent variables, salary of an individual. And if you guessed that this was a regression model, give yourself a thumbs up. And if you're able to remember that it is between independent and dependent variables and that terms, give yourself 2 thumbs up.
We're going to cover mathematics for machine learning. So today's agenda is going to cover data and its types. Then we're going to dive into linear algebra and its concepts, calculus, statistics for machine learning, probability for machine learning, hands-on demos. And of course, thrown in there in the middle is going to be your matrices and a few other things to go along with all this. Data and its types. Data denotes the individual pieces of factual information collected from various sources. It is stored, processed, and later used for analysis. And so we see here just a huge grouping of information, a lot of text stuff, money, dollar signs, numbers, and then you have your performing analytics to drive insights. And hopefully you have a nice your shareholders gathered at the meeting and you're able to explain it in something they can understand. So we talk about types of data. We have, in our types of data, we have a qualitative, categorical. You think nominal or ordinal. And then you have your quantitative or numerical, which is discrete or continuous. And let's look a little closer at those data types. Vocabulary, always people's favorite is the vocabulary words. Okay, not mine. But let's dive into this, what we mean by nominal. Nominal, they are used to label label our variables without providing any measurable value. Country, gender, race, hair, color, etc. It's something that you either mark true or false. This is a label. It's on or off. Either they have a red hat on or they do not. So a lot of times when you're thinking nominal data labels, think of it as a true-false kind of setup. And we look at ordinal. This is categorical data with a set order or a scale to it. And you can think of salary range as a great one. Movie ratings, etc. You can see here the salary range. If you have 10,000 to 20,000, number of employees earning that rate is 150. 20,000 to 30,000, 100, and so forth. Some of the terms you'll hear is bucket. This is where you have 10 different buckets and you want to separate it into something that makes sense into those 10 buckets. And so when we start talking about ordinal, a lot of times when you get down to the brass bones, again, we're talking true false. So if you're a member of the 10 to 20K range, so forth. Those would each be either part of that group or you're not. But now we're talking about buckets and we want to count how many people are in that bucket. Quantitative numerical data falls into two classes, discrete or continuous. And so data with a final set of values which can be categorized. Class strength, questions answered correctly, and runs hit in cricket. A lot of times when you see this, you can think integer, and a very restricted integer, i.e. you can only have 100 questions on a test, so it's very discrete. I only have 100 different values that it can attain. So usually you're talking about integers, but within a very small range. They don't have an open end or anything like that. So discrete is very solid, simple to count, set number. Continuous, on the other hand, continuous data can take any numerical value within a range. So water pressure, weight of a person, etc. Usually we start thinking about float values where they can get phenomenally small in what they're worth. And there's a whole series of values that falls right between discrete and continuous. You can think of the stock market. You have dollar amounts. It's still discrete, but it starts to get complicated enough when you have jump in the stock market from $525.33 to $580.67. There's a lot of point values in there. It'd still be called discrete, but you start looking at it as almost continuous because it does have such a variance in it. Now, we talk about we went over nominal and ordinal, almost true-false charts, and we looked at quantitative and numerical data, which we're starting to get into numbers. Discrete, you can usually, a lot of times discrete could be put into true-false, but usually it's not. So we want to address this stuff, and the first thing we want to look at is the very basic, which is your algebra. So we're going to take a look at linear algebra. You can remember back when your Euclidean geometry. We have a line. Well, let's go through this. We have a linear algebra is the domain of mathematics concerning linear equations and their representations in vector spaces and through matrices. I told you we're going to talk about matrices. So a linear equation is simply 2x plus 4y minus 3z equals 10. Very linear. 10x plus 12.4y equals z. And now you can actually solve these two equations by combining them. And that's what we're talking about, a linear equation. In the vectors, we have a plus b equals c. Now we're starting to look at a direction. And these values usually think of an x, y, z plot. So each one is a direction. And the actual distance of like a triangle, AB, is c. And then your matrix can describe all kinds of things. I find matrices confuse a lot of people, not because they're particularly difficult, but because of the magnitude and the different things they're used for. And a matrix is a chart, or think of a spreadsheet, but you have your rows and your columns. And you'll see here we have A times B equals C. Very important to know your counts. So depending on how the math is being done, what you're using it for, making sure you have the same rows and number of columns or a single number. There's all kinds of things that play in that can make matrices confusing. But really it has a lot more to do with what domain you're working in. Are you adding in multiple polynomials where you have like ax squared plus by plus, you start to see that it can be very confusing versus a very straightforward matrix. And let's just go a little deeper into these, because these are such primary. This is what we're here to talk about, is these different mathematical computations that come up. So when we're looking at linear equations, let's dig deeper into that one. An equation having a maximum order of 1 is called a linear equation. So it's linear because when you look at this, we have ax plus b equals c, which is a 1 variable. We have two variable ax plus by equals c, ax plus by plus cz equals d, and so forth. But all of these are to the power of 1. You don't see x squared. You don't see x cubed. So when we're talking about linear equations, that's what we're talking about. In their addition, if you have already dived into, say, neural networks, you should recognize this ax plus by plus cz setup plus the intercept, which is basically your neural network, each node adding up all the different inputs. And we can drill down into that. Most common formula is your y equals mx plus c. So you have your y equals the m, which is your slope, your x value plus c, which is your y-intercept. I kind of labeled it wrong here. Threw me for a loop. But the c would be your y-intercept. So when you set x equal to 0, y equals c. And that's your y-intercept right there. And they just had a reversed value of y when x equals 0. It equals the y-intercept, which is c. And your slope gradient line, which is your m. So you get your y equals 2x plus 3. And there's lots of easy ways to compute this. This is why we always start with the most basic one when we're solving one of these problems. And then, of course, one of the most important takeaways is the slope gradient of the line. So the slope is very important, that m value. In this case, we went ahead and solved this. If you have y equals 2x plus 3, you can see how it has a nice line graph here on the right. So, matrices. A matrix refers to a rectangular representation of an array of numbers arranged in columns and rows. So we're talking m rows by n columns. Here, A11 denotes the element of the first row in the first column. Similarly, A12, and it's really pronounced A11 in this particular setup. So it's row 1, column 1. A12 is row 1, column 2. First row and second column, and so on. And there's a lot of ways to denote this. I've seen these as like a capital letter A, small case a for the top row. Or, I mean, you can see where they can go all kinds of different directions as far as the value. You just take a moment to realize there needs to be some designation as far as what row it's in and what column it's in. And we have our basic operations. We have addition. So when you think about addition, you have two matrices of 2 by 2, and you just add each individual number in that matrix. And then when you get to the bottom, you have, in this case, the solution is 12, 10 plus 2 is 12, 5 plus 3 is 8, and so on. And the same thing with subtraction. Now, again, you're counting matrices. You want to check your dimensions of the matrix. The shape. You'll see shape come up a lot in programming. So when we're talking about dimensions, we're talking about the shape. If the two shapes are equal, this is what happens when you add them together or subtract them. And we have multiplication. When you look at the multiplication, you end up with a very slightly different setup going. Now, if we look at our last one, we're like, why? This always gets to me when we get to matrices, because they don't really say why you multiply matrices. My first thought is 1 times 2, 4 times 3. But if you look at this, we get 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5. 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. If you're looking at these matrices, think of this more as an equation. And so we have, if you remember, when we back up here for our multiple line equations, let's just go back up a couple slides where we were looking at 2 variable. So this is a 2 variable equation, ax plus by equals c. And this is a way to make it very quick to solve these variables, and that's why you have the matrix, and that's why you do the multiplication the way they do. And this is the dot product of 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. And it gives us a nice little 14, 23, 21, and 33 over here, which then can be used and reduced down to a simple formula as far as solving the variables as you have enough inputs. And then in matrix operations, when you're dealing with a lot of matrices, now keep in mind, multiplying matrices is different than finding the product of 2 matrices. Okay? So when we're talking about multiplication, we're talking about solving for equations. When you're finding the product, you are just finding 1 times 2. Keep that in mind, because that does come up. I've had that come up a number of times where I am altering data and I get confused as to what I'm doing with it. Transpose, flipping the matrix over its diagonal. Comes up all the time, where you still have 12, but instead of it being 12, 8, it's now 12, 14, 8, 21. You're just flipping the columns and the rows. And then, of course, you can do an inverse, changing the signs of the values across this main diagonal. And you can see here we have the inverse a to the minus 1, and it ends up with, instead of 12, 8, 14, 12, it's now minus 22, minus 12. Vectors. Vector just means we have a value and a direction. And we have down 4 numbers here on our vector. In mathematics, a one-dimensional matrix is called a vector. So if you have your x-plot and you have a single value, that value is along the x-axis and it's a single dimension. If you have 2 dimensions, you can think about putting them on a graph. You might have x and you might have y, and each value denotes a direction. And then, of course, the actual distance is going to be the hypothesis of that triangle. And you can do that with 3 dimensionals, x, y, and z. And you can do it all the way to nth dimensions. So when they talk about the k-means for categorizing and how close data is together, they will compute that based on the Pythagorean theorem. So you would take the square of each value, add them all together, and find the square root, and that gives you a distance as far as where that point is, where that vector exists, or an actual point value. And then you can compare that point value to another one. And it makes a very easy comparison versus comparing 50 or 60 different numbers. And that brings us up to igene vectors and igene values. Igene vectors, the vectors that don't change their span while transformation, and igene values, the scalar values that are associated to the vectors. Conceptually, you can think of the vector as your picture. You have a picture, it's 2 dimensions, x and y. And so when you do those 2 dimensions and those 2 values, or whatever that value is, that is that point. But the values change when you skew it. And so if we take and we have a vector A, and that's a set value, B is you have A and B, which is your igene vector. 2 is the igene value. So we're altering all the values by 2. That means maybe we're stretching it out one direction, making it tall, if you're doing picture editing. That's one of the places this comes in. But you can see when you're transforming your different information, how you transform it is then your igene value. And you can see here vector after line transition. We have 3a. A is the igene vector. 3 is the igene value. So A doesn't change. That's whatever we started with. That's your original picture. And 3 is skewing it one direction, and maybe B is being skewed another direction. And so you have a nice tilted picture because you've altered it by the igene values. So let's go ahead and pull up a demo on linear algebra. And to do this, I'm going to go through my trusted Anaconda into my Jupyter notebook, and we'll create a new notebook called linear algebra. Since we are working in Python, we're going to use our NumPy. I always import that as NP, our NumPy array. Probably the most popular module for doing matrices and things in. Given that this is part of a series, I'm not going to go too much into NumPy. We are going to go ahead and create 2 different variables, A for a NumPy array 10, 15, and B 29. We'll go ahead and run this, and you can see there's our 2 arrays, 10, 15, 29. And I went ahead and added a space there in between, so it's easier to read. And since it's the last line, we don't have to put the print statement on it unless you want. We can simply do A plus B. So when I run this, we have 10, 15, 29, and we get 30, 24, which is what you expect. 10 plus 20, 15 plus 9. You could almost look at this addition as being just adding up the columns on here coming down. And if we wanted to do it a different way, we could also do A dot T plus B dot T. Remember that T flips them. And so if we do that, we now get them, we now have 30, 24 going the other way. We could also do something kind of fun. There's a lot of different ways to do this. As far as a plus b, I can also do a plus b dot t. And you're going to see that that will come out the same, the 30, 24, whether I transpose a and b or transpose them both at the end. And likewise, we can very easily subtract two vectors. I can go a minus b. And we run that, and we get minus 10, 6. Now remember, this is the last line in this particular section, so I don't have to put the print around it. And just like we did before, we can transpose either the individual or we can transpose the main setup, and then we get a minus 10, 6 going the other way. Now, we didn't mention this in our notes, but you can also do a scalar multiplication. Let me just put down scalar so you can remember that. What we're talking about here is I have this array here, u, and if I go a times u, we'll take the value 2, we'll multiply it by every value in here. So 2 times 30 is 60, 2 times 15. And just like we did before, this happens a lot because when you're doing matrices, you do need to flip them. You get 60, 30 coming this way. So in NumPy, we have what they call dot product. And with this is in a two-dimensional vectors. It is the equivalent to matrix multiplication. And remember, we were talking about matrix multiplication, where it is well, let's walk through it. We'll go ahead and start by defining two NumPy arrays. We'll have 10, 20, 25, 6, or our u and our v. And then we're going to go ahead and do, if we take the values, and if you remember correctly, an array like this would be 10 times 25 plus 20 times 6. We'll go ahead and print that. There we go. And then we'll go ahead and do the np dot of u comma v. And we'll find when we do this, we go ahead and run this, we're going to get 370, 370. So this is a strain multiplication where they use it to solve linear algebra when you have multiple numbers going across. And so this could be very complicated. We could have a whole string of different variables going in here. But for this, we get a nice value for our dot multiplication. And we did addition earlier, which was just your basic addition. And of course, the matrix, you can get very complicated on these, or in this case, we'll go ahead and do, let's create two complex matrices. This one is a matrix of 12, 10, 4, 6, 4, 31. We'll just print out A so you can see what that looks like. Here's print A. When we print A out, you can see that we have a 2 by 3 layer matrix for A. And we can also put together, always kind of fun when you're playing with print values, we could do something like this. We could go in here. There we go. We could print A, we have it end with equals A, run, and this kind of gives it a nice look. Here's your matrix. That's all this is. Comma n means it just tags it on the end. That's all that is doing on there. And then we can simply add in what is A plus B, and you should already guess, because this is the same as what we did before. There's no difference. When we do a simple vector addition, we have 12 plus 2 is 14, 10 plus 8 is 18, and so on. And just like we did the matrix addition, we can also do A minus B and do our matrix subtraction. And we look at this, we have what? 12 minus 2 is 10, 10 minus 8, where are we? Oh, there we go. 8 minus, confusing what I'm looking at. I should have reprinted out the original numbers. But we can see here 12 minus 2 is, of course, 10. 10 minus 8 is 2. 4 minus 46 is minus 42, and so forth. So same as a subtraction as before, we just call it matrix subtraction. It's identical. Now, if you remember up here, we had scalar addition, where we're adding just one number to a matrix. You can also do scalar multiplication. And so simply, if you have a single value A and you have B, which is your array, we can also do A times B. When we run that, you can see here we have 2 times 4 is 8, 5 times 4 is 20, and so forth. You're just multiplying the 4 across each one of these values. And this is an interesting one that comes up. A little bit of a brain teaser is matrix and vector multiplication. And so when we're looking at this, we are, just do a regular arrays. It doesn't necessarily have to be a NumPy array. We have A, which has our array of arrays, and B, which is a single array. And so we can, from here, do the dot AB, and this is going to return 2 values. And the first value is that, you could say it's like we're doing this array, B array, first with A and then with a second one. And so it splits it up. So you have a matrix of vector multiplication, and you can mix and match. When you get into really complicated back-end stuff, this becomes more common because you've got layers upon layers of data, and so you'll end up with a matrix and a set of vector matrices that you want to multiply. Now, keep in mind that if you're doing data science, a lot of times you're not looking at this. This is what's going on behind the scenes. So if you're in the scikit looking at sklearn, where you're doing linear regression models, this is some of the math that's hidden behind the scenes that's going on. Other times, you might find yourself having to do part of this and manipulate the data around so it fits right, and then you go back in and you run it through the scikit. And if we can do, up here where we did a matrix and vector multiplication, we can also do matrix to matrix multiplication. And if we run this, where we have the 2 matrices, you can see we have a very complicated array that, of course, comes out on there for our dot. And just to reiterate it, we have our transpose matrix, which is your dot T. And so if we create a matrix A and then we do transpose it, you can see how it flips it from 5, 10, 15, 20, 25, 30 to 5, 15, 25, 10, 20, 30, rows and columns. And certainly with the math, this comes up a lot. It also comes up a lot with XY plotting. When you put it into PyPlot, you have one format where they're looking at pairs of numbers, and then they want all of X's and all Y's. So, the transpose is an important tool both for your math and for plotting and all kinds of things. Another tool that we didn't discuss is your identity matrix. And this one is more definition. The identity matrix, we have here one where we just did 2. So it comes down as 1, 0, 0, 1, 1, 0, 0, 0, 1, 0. It creates a diagonal of 1. And what that is when you're doing your identities, you can be comparing all your different features to the different features and how they correlate. And of course, when you have feature 1 compared to feature 1 to itself, it is always 1, where usually it's between 0 and 1, depending on how well it correlates. So when we're talking about identity matrix, that's what we're talking about right here, is that you create this preset matrix, and then you might adjust these numbers depending on what you're working with and what the domain is. And then another thing we can do, to kind of wrap this up, we'll hit you with the most complicated piece of this puzzle here, is an inverse A matrix. And let's just go ahead and put the, it's a lengthy description. Let's go ahead and put the description. This is straight out of the website for NumPy. So given a square matrix A, here's our square matrix A, which is 2, 1, 0, 0, 1, 0, 1, 2, 1. Keep in mind, 3 by 3, it's square. It's got to be equal. It's going to return the matrix A inverse satisfying dot A inverse. So here's our matrix multiplication. And then, of course, it equals the dot, A inverse of A, with an identity shape of A dot shape 0. This is just reshaping the identity. That's a little complicated there. So we go ahead and have here's our array. We'll go ahead and run this, and you can see what we end up with is we end up with an array 0.5 minus 0.5 and so forth, with our 2, 1, 1 going down, 2, 1, 0, 0, 1, 0, 1, 2, 1. Getting into a little deep on the math, understanding when you need this is probably really is what's really important when you're doing data science versus handwriting this out and looking up the math and handwriting all the pieces out. You do need to know about the linear algorithm inverse of A. So if it comes up, you can easily pull it up, or at least remember where to look it up. You took a look at the algebra side of it. Let's go ahead and take a look at the calculus side of what's going on here with the machine learning. So calculus, oh my goodness, and differential equations, you got to throw that in there because that's all part of the bag of tricks, especially when you're doing large neural networks, but it also comes up in many other areas. The good news is most of it's already done for you in the back end. So when it comes up, you really do need to understand from the data science, not data analytics. Data analytics means you're digging deep into actually solving these math equations. And a neural network is just a giant differential equation. So when we talk about calculus, we're going to go ahead and understand it by talking about cars versus time and speed. So it helps to calculate the spontaneous rate of change. So suppose we plot a graph of the speed of a car with respect to time. So as you can see here, going down the highway, probably merged into the highway from an on-ramp. So I had to accelerate, so my speed went way up. Stuck in traffic, merged into the traffic. Traffic opens up, and I accelerate again up to the speed limit, and maybe it peters off up there. So you can look at this as the speed versus time. I'm getting faster and faster because I'm continually accelerating, and if I hit the brakes, it go the other way. So the rate of change of speed with respect of time is nothing but acceleration. How fast are we accelerating? The acceleration is the area between the start point of x and the end point of delta x. So we can calculate a simple, if you had x and delta x, we could put a line there, and that slope of the line is our acceleration. Now, that's pretty easy when you're doing linear algebra, but I don't want to know it just for that line and those 2 points. I want to know it across the whole of what I'm working with. That's where we get into calculus. So when we talk about the distance between x and delta x, it has to be the smallest possible near to 0 in order to approximate the acceleration. So the idea is that instead of, if you ever took a basic calculus class, they would draw bars down here, and you would divide this area up. Let's go back up a screen. You divide this area of this time period up into maybe 10 sections, and you'd use that, and you could calculate the acceleration between each one of those 10 sections kind of thing. And then we just keep making that space smaller and smaller until delta x is almost infinitesimally small. And so we get a function of a equals a limit as h goes to 0 of a function of a plus h minus a function of a over h. And that is you're computing the slope of the line. We're just computing that slope under smaller and smaller and smaller samples. And that's what calculus is. Calculus is the integral. You can see down here we have our nice integral sign. Looks like a giant S. And that's what that means, is that we've taken this down to as small as we can for that sampling. So we're talking about calculus. We're finding the area under the slope is the main process in the integration. Similar, small intervals are made of the smallest possible length of x plus delta x, where delta x approaches almost an infinitesimally small space. And then it helps to find the overall acceleration by summing up all the lengths together. So we're summing up all the accelerations from the beginning to the end. And so here's our integral. We sum of a of x times d of x equals a plus c. That is our basic calculus here. So when we talk about multivariate calculus deals with functions that have multiple variables. And you can see here we start getting into some very complicated equations. Change in w over change of time equals change of w over change of z. The differential of z to dx, the differential of x to dt. It gets pretty complicated. And it really translates into the multivariate integration using double integrals. And so you have the sum of f of x of y of d of a equals the sum from C to D and A to B of f of x of y dx dy equals the sum of A to B, sum of C to D of f x of y dy dx. Understanding the very specifics of everything going on in here and actually doing the math is usually calculus 1, calculus 2, and differential equations. So you're talking about 3 full-length courses to dig into and solve these math equations. What we want to take from here is when we're talking about calculus, we're talking about summing of all these different slopes. And so we're still solving a linear expression. We're still solving y equals mx plus b. But we're doing this for infinitesimally small x's, and then we want to sum them up. That's what this integral sign means. The sum of a of x d of x equals a plus c. And when you see these very complicated multivariate differentiation using the chain rule, when we come in here and we have the change of w to the change of t equals a change of w dz, and so forth. That's what's going on here. That's what these means. We're basically looking for the area under the curve, which really comes to how is the change changing? Speed's going up. How is that changing? And then you end up with a multiple layer. So if I have 3 layers of neural networks, how is the third layer changing based on the second layer changing, which is based on the first layer changing? And you get the picture here that now we have a very complicated multivariate integration with integrals. The good news is we can solve this mathematically, and that's what we do when you do neural networks and reverse propagation. So the nice thing is that you don't have to solve this on paper unless you're data analysis and you're working on the back end of integrating these formulas and building the script to actually build them. So we talk about applications of calculus. It provides us the tools to build an accurate predictive model. So it's really behind the scenes. We want to guess at what the change of the change of the change is. That's a little goofy. I know. I just threw that out there. It's kind of a meta term. But if you can guess how things are going to change, then you can guess what the new numbers are. Multivariate calculus explains the change in our target variable in relation to the rate of change in the input variables. So there's our multiple variables going in there. If one variable is changing, how does it affect the other variable? And then in gradient descent, calculus is used to find the local and global maxima. And this is really big. We're actually going to have a whole section here on gradient descent because it is really, I mean, I talked about neural networks and how you can see how the different layers go in there, but gradient descent is one of the most key things for trying to guess the best answer to something. So let's take a look at the code behind gradient descent. And before we open up the code, let's just do real quick gradient descent. Let's say we have a curve like this. And most common is that this is going to represent your error. Oops. Error. There we go. Error. Hard to read there. And I want to make the error as low as possible. And so when I'm looking at it is I want to find this line here, which is the minimum value. So we're looking for the minimum. And it does that by sampling there. And then based on this, it guesses it might be someplace here. And it goes, hey, this is still going down. It goes here, and then goes back over here, and then goes a little bit closer. And it's just playing a high-low until it gets to that spot, that bottom spot. And so we want to minimize the error. On the flip note, you could also want to be maximizing something. You want to get the best output of it. That's simply minus the value. So if you're looking for where the peak is, this is the same as a negative for where the valley is. I'm looking for that valley. That's all that is, and this is a way of finding it. So the cool thing is all the heavy lifting's done. I actually ended up putting together one of these a while back when I didn't know about Sidekick and I was just starting. Boy, it's a long while back. And is playing high-low. How do you play high-low, not get stuck in the valleys, figure out these curves and things like that? Well, you do that, and the back end is all the calculus and differential equations to calculate this out. The good news is you don't have to do those. So instead, we're going to put together the code. And let's go ahead and see what we can do with that. So, guys in the back put together a nice little piece of code here, which is kind of fun. Some things we're going to note, and this is really important stuff, because when you start doing your data science and digging into your machine learning models, you're going to find these things are stumbling blocks. The first one is current X. Where do we start at? Keep in mind, your model that you're working with is very generic. So whatever you use to minimize it, the first question is, where do we start? And we started at this because the algorithm starts at x equals 3. So we arbitrarily picked 5. Learning rate is how many bars to skip going one way or the other. In fact, I'm going to separate that a little bit because these two are really important. If we're dealing with something like this where we're talking about, well, here's the function we're going to use. Our gradient of our function, 2 times x plus 5, keep it simple. So that's the function we're going to work with. So if I'm dealing with increments of 1,000, 0.1 is going to be a very long time. And if I'm dealing with increments of 0.001, 0.1 is going to skip over my answer. So I won't get a very good answer. And then we look at precision. This tells us when to stop the algorithm. So again, very specific to what you're working on. If you're working with money and you don't convert it into a float value, you might be dealing with 0.01, which is a penny. That might be your precision you're working with. And then, of course, the previous step size, max iterations. We want something to cut out at a certain point. Usually that's built into a lot of minimization functions. And then here's our actual formula we're going to be working with. And then we come in and we go, while previous step size is greater than precision and iters is less than max iters. Say that 10 times fast. We're just saying if it's if we're still greater than our precision level, we still got to keep digging deeper. And then we also don't want to go past 1,000 or whatever this is, 1,000,000 or 10,000 running. That's actually pretty high. We almost never do max iterations more than like 100 or 200. Rare occasions you might go up to 400 or 500 if it's depending on the problem you're working with. So we have our previous equals our current. That way we can track time-wise. The current now equals the current minus the rate times the formula of our previous x. So now we've generated our new version. Previous step size equals the absolute current previous. So we're looking for the change in x. Iters equals iterations plus 1. That's so we know to stop if we get too far. And then we're just going to print the local minimum occurs at x on here. And if we go ahead and run this, you can see right here it gets down to this point and it says, hey, local minimum is minus 3.3222 for this particular series we created. And this is created off of our formula here, lambda x 2 times x plus 5. Now, when I'm running this stuff, you'll see this come up a lot in with the sklearn kit. And one of the nice reasons of breaking this down the way we did is I could go over those top pieces. Those top pieces are everything when you start looking at these minimization toolkits and built-in code. And so from, we'll just do, it's actually docs.scipy.org, and we're looking at the scikit. There we go. Optimize, minimize. You can only minimize one value. You have the function that's going in. This function can be very complicated. So we used a very simple function up here. It could be, there's all kinds of things that could be on there. And there's a number of methods to solve this as far as how they shrink down. And your x naught. There's your start value. So your function, your start value, there's all kinds of things that come in here that you can look at, which we're not going to. Optimization automatically creates, constraints, bounds. Some of this it does automatically, but the big thing I want to point out here is you need to have a starting point. You want to start with something that you already know is mostly the answer. If you don't, then it's going to have a heck of a time trying to calculate it out. Or you can write your own little script that does this and does a high-low guessing and tries to find the max value. That brings us to statistics. what this is kind of all about is figuring things out. A lot of vocabulary in statistics. So statistics, well, I guess it's all relative. It's definitely not an EDL class. So a bunch of stuff going on in statistics. Statistics concerns with the collection, organization, analysis, interpretation, and presentation of data. That is a mouthful. So we have from end to end, where does it come from? Is it valid? What does it mean? How do we organize it? How do we analyze it? And then you got to take those analyses and interpret it into something that people can use, kind of reduce it to understandable. And nowadays you have to be able to present it. If you can't present it, then no one else is going to understand what the heck you did. So when we look at the terminologies, there's a lot of terminologies depending on what domain you're working in. So clearly if you're working in a domain that deals with viruses and T cells and how does, where does that come from, and you're studying the different people, then you're going to have a population. If you are working with mechanical gear, a little bit different. If you're looking for the wobbling statistics to know when to replace a rotor on a machine or something like that, that can be a big deal. We have these huge fans that turn in our sewage processing systems. And so those fans, they start to wobble and hum and do different things that the sensors pick up. At one point, do you replace them instead of waiting for it to break, in which case it costs a lot of money. Instead of replacing a bushing, you're replacing the whole fan unit. An interesting project that came up for our city a while back. So population. All objects or measurements whose properties are being observed. So that's your population, all the objects. It's easy to see it with people because we have our population in large. But in the case of the sewer fans, we're talking about the fan units. That's the population of fans that we're working with. You have a parameter, a metric that is used to represent a population or characteristic. You have your sample, a subset of the population studied. You don't want to do them all because then you don't have if you come up with a conclusion for everyone, you don't have a way of testing it. So you take a sample. Sometimes you don't have a choice. You can only take a sample of what's going on. You can't study the whole population. And a variable, a metric of interest for each person or object in a population. Types of sampling. We have a probabilistic approach, selecting samples from a larger population using a method based on the theory of probability. And we'll go into a little bit more deeper on these. We have random, systematic, stratified. And then you have a non-probabilistic approach, selecting samples based on the subjective judgment of the researcher rather than random selection. It has to do with convenience, trying to reach a quota, or snowball. And they're very biased. That's one of the reasons you'll see this big stamp on it that says biased. So you gotta be very careful on that. So probabilistic sampling. When we talk about a random sampling, we select random size samples from each group or category. So it's as random as you can get. When we talk about systematic sampling, we're selecting random size samples from each group or category with a fixed periodic interval. So we kind of split it up. This would be like a time setup or our different categories. And you might ask your question, well, what is a category or a group? If you look at, I'm going to go back a window. Let's say we're studying economics of an area. We know pretty much that based on their culture and where they came from, they might need to be separated. And so, and when I say separated, I don't mean separated from their place where they live. I mean, as far as the analysis, we want to look at the different groups and make sure they're all represented. So if we had like an 80% of a group that is, say, Hispanic or Indian, and also in that same area, we have 20% who are, let's call our expatriates. They left America and they're nice, and your Caucasian group. We might want to sample a group that is representative of both. So we're talking about stratified sampling, and we're talking about groups. Those are the groups we're talking about. And that brings us to stratified sampling, selecting approximately equal size samples from each group or category. This way we can actually separate the categories and give us an insight into the different cultures and how that might affect them in that area. So you can see these are very, very different, kind of depends on what you're working with as far as your data and what you're studying. And so we can see here, just to go a little bit more, we'd have selecting 25 employees from a company of 250 employees randomly. Don't care anything about them, what groups are in, which office they're in, nothing. And we might be selecting one employee from every 50 unique employees in a company of 250 employees. And then we have selecting one employee from every branch in the company office. So we have all the different branches. There's our group, or our categories by the branch. And the category could depend on what you're studying. So it has a lot of variation on there. You see this kind of grouping and categorizing is also used to generate a lot of misinformation. So if you only study one group and you say this is what it is, then everybody knows everything. So be very careful. So types of statistics. When we talk about statistics, we're going to talk about descriptive and inferential statistics. There are many terms in statistics. We're talking about a particular setup. So we're talking about descriptive and inferential statistics. So the word describe is pretty solid. You're describing the data. What does it look like? With inferential statistics, we have a simulation to a large population. So if you're a company, you might get the data say these people were helped by this drug. They did 80% health or 80% better survival rate than the people who do not have the drug. So we can infer that that drug will work in the population health. So your are going to affect the greater population. So statistics, you describe the basic data. We have a measure of central tendencies. We have your mean, median, and mode. And then we have a measure of spread, like your range, your quartile, your variation. We'll call it in a second. But one of them you can think of is how the data differences, what's the max, min, range, all that stuff is spread. And anything similar to your central tendencies, measure of central tendencies. So we talk about the mean, it is the average of the set values this is on. And the median is the higher half and the lower half of data. So where's the center point of all your different data points? So your mean might have a couple really big numbers that skew it, so that the average is much higher. If you get those outliers out, the median might give you a much lower number. You might say that's much higher than the median. Well, it's because you have some outliers. Or why is it so much lower? And then the mode is the most frequent appearing value. This is really interesting if you're studying economics and how people are doing. Income, like in the U.S., was $1,24,000 a year, where the average was close to $80,000. And it's like, wow, what a difference. People use that way up. So the average person is not making that kind of money. And look at the average. So that's a very interesting way of looking at the data. Again, these are all central tendencies, single numbers you can look at for the whole spread of the data. Central tendencies, the mean is the average marks of a student in a classroom. So here we have the mean, sum of the marks of the students, total number of students. And as we talked about the median, we have 0 to 10, half the numbers on the other side of the line, we end up 5 in the middle. And then mode, what marks a student in a test. A simple case where most people scored like an 82%, that's easy to figure out. Not so easy when you have different areas where like you have like about economy, a little more difficult to calculate, scores that makes 1,000, and a slightly bigger group that makes 26,000. So what do you put down for the mode? So there's a way to calculate that, and there's different variations depending on what you do. So measure fed. Range, what's the difference between the highest and the lowest value? Maybe 100%, so we got 100%, or maybe 60 to 90%, so people could not get 100%. We have your rank ordered data set into 4 equal parts. Very common thing to do are all the basic packages, whether you're working in working in Scala, whether you're working in R. You'll see this come up where you have range, your min, your max, and then it'll have your interquartile range. How does it look like in each quarter of data? Variance measures how far each number in the set is from the mean, and therefore from every other number in the set. So you have like how much turbulence is going on in this data. And then the deviation is a version of set of values from the mean. And you'll usually see, if I'm doing a graph, I might have the value graphed. Then based on the standard in the error on the graph as a background, so you can see how far off it is. So standard deviation is used a lot. So measurement of spread, marks of a student out of 100. We have here from 50 to 63 or 50 to 90. So the range, maximum marks, minimum marks, we have 90 to 45, and the spread of that is 45, 90 minus 45. And then we have the interquartile range using the same marks over there. You can see here where the median is, and then there's the first quarter, the second quarter, the fourth quarter, the values. And then in the very standard deviation, we first find out the mean. So here are calculating the average there. We end up at approximately 66 for the average. And then we look at that, the variance, once we know the means, we can do equal marks minus the mean squared. Why is it squared? Because one, you want to make sure you don't have, like, if you're putting all this stuff together, you end up with error as far as one's negative, one's positive, one's a little higher, one's a little lower. So you always see the squared value and over the total observations. And so the standard deviation equals the square root of the variance, which is approximately 16. If you're looking at predictable model, you would be looking at the deviation based on area. That's, again, really important to know if you're predicting what's the chance of it being way off or it's a little bit off. Now we looked at the tools, or basic talk. Let's go ahead and pull up a little demo, see what that's like in Python. Let's see some little hands on here. For that, let's go back into our book. Almost all of this you can do in NumPy. That's what we're Let's go ahead and use pandas. And if you remember from pandas on here, this is basically a data frame. Print df.head. Run that. You can see we have the name Jane, Michael, William, Rosie, Hannah, and their salaries on here. And of course, instead of having to do all the calculations and everything, use the command mean in pandas. And so if I go ahead and do this, print df, pick our column, salary, because we want to find the means of that column. We want to find the means of that column. And we go ahead and print this out, and you can see that the average income here is 71,000. And let's just go ahead and do this. We'll go ahead and put in means. And if we're going to do that, we also might want to find the median. And median is very similar. Actually, this median. We're used to means and average. It's kind of interesting that they use the two different words. There can be, in some computations, slight differences, but for the most part, the means is the average. And the median, whoops, let's put a median here, df salary, that way it displays a little better. You can see the median is 54. Why? Because somebody makes 189,000. Darn you, Rosie, for throwing off our numbers. But that's something you want to notice. The difference between is huge, and so what does it mean behind when you're looking at the different data coming in. And of course, we also want to find out, hey, what's the most common income that people make? In this example, we'll go into the mode. You can see 50,000. So this is very telling that most people are making 50,000. The middle point is at 54,000, so half the people are making more than that. What that tells me is that if the most common income is below the median, then there's a lot of high salaries going up, but there's some really low salaries in there. And so this trend, which is very common in statistics, when you're analyzing the economy and different people's income, is pretty common. And the bigger difference between these is also very important when we're studying statistics. And when you hear someone just say, hey, the average income was, you might start asking questions at that point. Why aren't you talking about the median income? Why aren't you talking about the mode, the most common income? What are you hiding? And if you're doing these analyses, you should be looking at these saying, hey, why are these discrepancies? Why are these so different? And of course, with any analysis, it's important to find out the minimum and the maximum. So we'll go ahead. It's just simply dot min. We'll pull minimum and dot max. Straightforward on as far as translating, put your lowest value and what your highest value is here. You'll do that later on. And real quick on mode, note that it puts mode 0. Like I said, there's a couple different ways you can compute mode. The range, which is your max minus your min. So now we have a range of 140 values. There is a feature in pandas. And so pandas can actually do DF describe. If we do this, you can see we have there's 7 sets of mean. Our standard deviation, which we didn't compute, which is the LSTM. If it computes it, it looks for axes and things like that. We have our minimum value, our maximum value, and of course the name salary. So these are the basic statistics. You can pull them up and just describe. This is a dictionary, so I could actually do something like, in here I could actually go count and run, and now it just prints the count. So because this is a dictionary, you can pull any one of these values out of here. It's kind of a quick and dirty way to pull all the different information and then split it up depending on what you need. Now, if I just walked in and gave you this information in a meeting, at some point you would just kind of fall asleep. That's what I would do anyway. So we want to go ahead and see about graphing it here. And we'll go ahead and put it into a histogram and plot that graph on it of the salaries. And let's just go ahead and put that in here. So we do our matplot inline. Remember, that's a Jupyter's Notebook thing. A lot of the new version of the matplot library does it automatically, but just in case, I always put it in there. Import matplot library, pyplot is PLT, that's my plotting. And then we have our data frame. I guess I really don't need to respell the data frame. Maybe we could just remind ourselves what's in it. So we'll go ahead and just print df. That way we still have it. And then we have our salary, df salary, salary.plot history title, salary distribution, color gray, plot AXV line, salary, the mean value. So we're going to take the mean value, color violet, line style dash. This is just all making it pretty. What color, dash line, line width of 2, that kind of thing. And the median. And let's go ahead and run this just so you can see what we're talking about. And so up here we are getting a lot. So here's the data, our data, you see it with the salaries. And we're looking at the salary distribution. And just look at this. You have our, in this case, we did let's see, we had red for the median. We have violet for our average. Really, I mean, here's our outlier. Here's our person who makes a lot of money. Here's the average. Here's the median. Based on the average, it really doesn't tell you much about what people are really taking home. All it does is tell you how much money is in this, with the salaries. So, in addition to this, is that it's very easy to plot an AXV line. These are these unknown lines for markers. And as you display the data, you can add on to this. We can definitely do a histogram and stuff like that. The picture's worth 1,000 words. What you really can do is you can do a basic describe, which pulls all the information from the describe, because this is a dictionary. And so if we want to go ahead and look up the mean value, we can also describe means. We're doing a lot of being able to, it doesn't have the print on there, so it's only going to print out the mean. You can very easily reference any one of these. And then you can also, if you don't need just the basics, you can come through and pull any one of the individual references from the pandas on here. So now we've had a chance to describe our data. Let's get into inferential statistics. Inferential statistics allows you to make predictions or inferences from data. And you can see here we have a nice little picture of movie ratings, and people said, hey, how many people like the movie, dislike it, can't say. And then you ask a movie who hasn't been in the study, you can infer that 55% chance of saying liked, 35% chance of saying disliked, or 10 or 11% can't say. So that's real basics of what we're talking about, is you're going to infer that the next person doesn't follow these statistics. So let's look at point estimation. The approximate value for a population's parameter. Vaccines and flu bugs, all of that. It's a pretty big thing of how do you test these out and make sure they're going to run the population. Are generalized for the whole population. So here's here's our small group up here. We've selected them. We file them, and the results work for the population. Nice diagram with the arrows going back and forth and the very scary applications of inferential statistics. Very central is what they call hypotheses testing. And the confidence interval, which go with that. And then as we get into probability, we get into our binomial theorem, our normal distribution, and central limit theorem. Hypothesis testing. Hypothesis testing is used to measure the plausibility of a hypothesis, assumption, by using sample data. Now, when we talk about theorems, theory, hypothesis, keep in mind that if you are in a philosophy class, theory is the same as hypothesis, where theorem is a scientific statement that is something that has been proven, although it is always up for debate, because in science we always want to make sure things are up to debate. So a hypothesis is the same as a philosophical class calling a theory, where theory in science is not the same. Theory in science says this has been well proven. Gravity is a theory. So if you want to debate the theory of gravity, try jumping up and down. If you want to have a theory about why the economy is collapsing in your area, that is a philosophical debate. Very important. I've heard people mix those up, and it is a pet peeve of mine. When we talk about hypotheses testing, the steps involved in hypotheses testing is first we formulate a hypothesis. We figure out the right test to test our hypothesis, and we make a decision. And so when you're talking about hypothesis, you're usually trying to disprove it. If you can't disprove it and it works for all the facts, then you might call that a theorem at some point. So in a use case, let's consider an example. We have 4 students who were given a task to clean a room every day. Sounds like working with my kids. They decided to distribute the job of cleaning the room among themselves. They did so by making 4 chits, which has their names on it, and the name that gets picked up has to do the cleaning for that day. Rob took the opportunity to make chits and wrote everyone's name on it. So here's our 4 people: Nick, Rob, Imlia, and Summer. Now Rick, Imlia, and Summer are asking us to decide whether Rob has done some mischief in preparing the chits, i.e. whether Rob has written his name on one of the chit. For that, we will find out the probability of Rob getting the cleaning job on first day, second day, third day, and so on till 12 days. The probability of Rob getting the job decreases every day, i.e. his turn never comes up, then definitely he has done some mischief while making the chits. So the probability of not doing work on day 1 is 3 out of 4. There's a 0.75 chance that he didn't do it. 2 days, 3/4 times 3/4 equals 0.56. 3 days, you have 3/4, 3/4, 3/4, which equals 0.42. When you get to day 12, it's 0.032, which is less than 0.05. Remember this 0.05. That comes up a lot when we're talking about certain values, when we're looking at statistics. Rob is cheating as he wasn't chosen for 12 consecutive days. That's a very probably man. 12, he still hasn't gotten the room. Hypothesis. A general statement that there is no relationship between a phenomenon or no association among the groups. Alternative hypothesis. Contrary to the hypothesis, whenever something is happening, it refers to an old one. So hypotheses go hand in hand. So your null, this is always interesting in when we're talking about data science and the math behind it. It's about proving that the things have no correlation. Null hypothesis, you have zero together. Relative hypothesis, we have p-value. The p-value is the probability of finding the observed or extreme results when the null hypothesis study question is true. And the t is calculated in units of standard error. The greater the magnitude of t, the greater the evidence against the null hypothesis. And you look at the t value being specific to the test you're doing, where the p-value is by far called the 0.05, showing that it has a high correlation. So digging in deeper, let's assume the new drug is available. It's like a null value here that you don't have any drug. The null value here is more than the existing drug. Now, if we get that, that says our null hypothesis is correct. There is no correlation, and the new drug is strong. The alternative hypothesis, the new drug doesn't look better than the new drug there. Showing positive results, which will reject the null hypothesis. And again, looking for all the positive test results and finding means of different samples in order to test hypothesis. This is how they have. And this leads us to the confidence intervals. Confidence interval values, we sure are values of observations. How many cans of food do you buy for your per year? On an average, around 95% of the people bought around 200 cans. Hence, we can say that we have a confidence interval of 200-300, where 95% of our values lie in that. That helps a lot, so you can start seeing what you're looking at here, where you have the 95%. You have your nice bell curve equal on both sides. It's not asymmetrical. And 90% lie, there's no ring, and then you have your outliers, the 2.5% going each way. So we touched upon hypothesis, and we're going to move into probability. So you have your hypothesis. Once you've generated your hypothesis, we want to know the probability of something occurring. Probability likely to occur. Any event can be predicted with total certainty and can only be predicted as a likelihood of occurrence. So any event cannot be predicted with total certainty, can only be predicted as a likelihood of its occurrence. Score prediction, how good you're going to do in whatever sport you're in, weather predictions, physics, and chaos theory, even the location of the chair you're sitting on has been like the calculator does under 1 in trillions upon trillions. So it's the better the probability, the more likely it's going to happen. There are some things that have such a low probability that we don't see them. So we talk about a random variable. Random variable is a variable whose possible values are numerical outcomes of random phenomena. So we have the coin toss. How many heads will occur in the series of 20 coin flips? Probably, on average they're 10, but you really can't know because it's very random. How many times a red ball is picked from a bag of balls, if there's equal number of red balls and blue balls and green balls in there. How many times the sum of digits on 2 dice result are 5 each. So, there's how often are you going to roll 2 5s on your pair of dice. So in a use case, let's consider the example of rolling 2 dice. We have a random variable outcome equals y. You can take values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a random variable and a combination of dice. And instead of looking at how many times both dice will roll 5, let's go ahead and look at total sum of 5. And you have, as far as your random variables, you can have a 1, 4 equals 5, 4, 1, 2, 3, 3, 2. So 4 of those rolls can be 4. If you look at all the different options you have, 4 of those random rolls can be a 5. And if we look at the total number, which happens to be 36 different options, you can see that we have 4 out of 36 chance every time you roll the dice that you're going to roll a total of 5. You're going to have an outcome of 5. And we'll look a little deeper as to what that means. But you could think of that at what point, if someone never rolls a 5 or they always roll a 5, can you say, hey, that person's probably cheating? We'll look a little closer at the math behind that. But let's just consider this as one of the cases is rolling 2 dice and gambling. There's also binomial distribution. It is the probability of getting success or failure as an outcome in an experiment or trial that is repeated multiple times. And the key is bi, meaning 2, binomial. So passing or failing an exam, winning or losing a game, and getting either head or tails. So if you ever see binomial distribution, it's based on a true-false kind of setup. You win or lose. Let's consider a use case, and let's consider the game of football between two clubs, Barcelona and Dortmund. The teams will have to play a total of 4 matches, and we have to find out the chances of Barcelona winning the series.
Hello everyone, I am Mayank and welcome to this video where I will show you how to run Llama 3.1 on your systems, all while keeping your data private. If you are curious about AI and want to use it on your own PC without relying on online services, you are in the right place. Llama 3.1 is a powerful AI tool that can help with tasks like text generation, but instead of using it in the cloud, you can run it directly on your computer. So in this video, I will guide you through everything from setting up your system to installing and running Llama 3.1 step by step. It's a great way to experiment with AI while keeping your work private. So by the end of this video, you will have Llama 3.1 up and running on your own systems. And you won't need to worry about sharing your data with anyone else. Whether you are just learning about AI or planning to use it for bigger projects, this tutorial will make it easy for you to get started. So let's dive in, follow along, and by the end, you will have your own private AI setup. Don't forget to like, subscribe, and let's start running Llama 3.1. So without any further ado, let's get started. So yeah, welcome to this demo part of this Llama, how to install Llama 3.1 in your system. So I'm using Windows right now. It is available for Mac OS, Linux, and Windows. So first, what we will do, we will install this Llama. Just type llama.com, and I will provide this link in the description as well. Then here you have to press the download. Here you can choose your system, your OS, Mac OS, Linux, Windows. Just follow the steps later. So I will download for the Windows. So the application will get download. It is like 625 MB. So it is downloading. Till then there is no official documentation for this Llama. So here in GitHub there is one. So Llama, this is Windows for here, Windows, Mac OS, Linux, you can download, and these are some models. See, Llama 3.1, Llama 3.1, Llama 3.1, and 5, Gemma, and Mistral is there, Moondream is there, and so on. And see, these are some parameters. 8B is 4.7 GB, 70B is 40 GB, and for 05B is 231 GB. So here, note, you should have at least 8 GB of RAM available to run 7B models. 16 GB RAM to run 13B models, and 32 GB RAMs to run 32B models. So here we will install this 8B parameters. You can choose anyone as per your specification of your system, your OS. So still it's downloading. I have already installed in this, but again I will reinstall it. Fine. So now we have Llama setup. Just double click on this and install. See why it is showing this error. And why it is showing this error? Why? Because the following applications are using files that need to be updated by setup. It is recommended that you allow setups to automatically. It is automatically installed. See, it's a simple steps. There are 3-4 steps that you have to do. So yeah, the setup is done, and now what you can do, I am using PowerShell. You can use your command prompt as well. So here I will write Llama. So here you can see these are some available command I can do. So to run a model, you have to just write run and this. Now if you will see here, to install, to download Llama 3.1, 8B parameter 1, 4.7 GB will be the size. So this is the command. Just copy it and paste it here. And enter. So why it is coming like this? Because it is already installed on my system. Fine. So now Llama 3.1 is installed. Okay, so here you can write your questions. Okay, what is Llama 3.1? So see, it is start generating the output. So this is how you can, privately run or install Llama into your large language models applications into your system. See, it is like ChatGPT. If you are looking for more details, can you please provide context or more background about why you are interested in Llama 3.1? That would be me try to find more relevant information for you. Okay, so here what I will write what is ChatGPT. Okay, so it will give you the answer. See, ChatGPT is a conversational AI model developed by OpenAI, a leading artificial intelligence research laboratory. Okay, what you have to note, just you have to note what's the size of your RAM. Okay, I have 16 GB of RAM, that's why I installed this 8B one. Okay, and if you have 8 GB RAM, there is no model of 7B. 7B we have Lava, and we have Code Llama, and we have Mistral. So if you have 16 GB of RAM and this one Llama 3.1, the latest one, is enough. Okay, so let's check. Yeah, see, ChatGPT stands for Conversational Generative Pre-trained Transformer. It is an AI chatbot designed to understand and respond to human-like language input. And some key features are this. So this is how you can, be protected from your data as well. And you can ask anything to this. Okay, and there is one more thing. If you will go here, this API section. Okay, yeah, so there is one thing, I guess here is a thing. So yeah, if you type this localhost 11434, so this is an API for the Llama. See, here you can see Llama is running. Fine. So this is how you can do this, perform or install your Llama 3.1 in your local system. See, it is now asking me, how is that? Did I cover what you wanted to know about ChatGPT? Okay, and you can give your prompt, and again you can do something. So okay, I will write what is hello world. See, hello world is a simple phrase that has become iconic in the world of computer programming. Everyone know to print hello world, I guess so. So this is how you can install Llama 3.1 in your local system. Okay, just you have to install Llama first, then search this Llama run 3.1, or if you want to explore more thing, you can write version, so the version, server, create, and all that thing. Okay, so hello guys, welcome to this demo part of this video. So here what I will do, I will go to new, then Python 3 file, then here I will give it the name called Exploratory Data Analysis. Basically we have one dataset file of roller coaster basically, so we will be using that, and you can download that file from the description box below, from the below link, drive link. Okay, so we will be doing some small basic function using Python, and later on we will make some good charts. Okay, we will remove duplicates and all, we will do all that thing. We'll do data preparation, we'll do feature engineering. Okay, and we'll remove the duplicates, we'll check for the duplicates, we'll make charts like histogram, KD blocks, box plot, and like many more similar to that. like heat map will make, scatter plot, group by comparison. Okay, we all do that, right? So just stick with me and you can write side along with me this code. Okay, so let's start with importing pandas first. I guess everyone know what is pandas and numpy. Fine. As np, then I will import numpy as np. Why this is np and pd? Sorry, my bad, pd is here. Because I don't want to write again and again this pandas, this numpy. So basically I can write this is small version. Okay. Yeah. So if you guys don't know what is Panda, so Panda is very popular library for working with data. Okay, its goal is to be the most powerful and flexible open source tool. Okay, so it has that goal. So data frames are the center of Pandas. And what is data frame? A data frame is structured like a table or a spreadsheet. Okay, the rows and the columns. Okay, whereas NumPy is an open source Python library again that facilitates efficient numerical operation on large quantities of data. Okay, so there are many functions in NumPy as well. Those we can use in the pandas data frame. Got it? So we'll import one more .pyplot .pylab, okay, as plt. Okay, there is one more library, matplotlib, for plotting the graph, and there is one more, import seaborn as SNS. So what is Seaborn? Seaborn is again the Python data visualization library based on matplotlib. Okay, it provides a high-level interface for drawing attractive and informative statistical graphs. Okay, then I will write here plt dot style dot use, will write ggplot. Got it? ggplot. Fine. So yeah, let me run it. So what is ggplot? So ggplot is this is an open source data visualization package for statistical programming. Okay, so yeah, you can say, or a general scheme for data visualization which breaks up graph into semantic components such as scales and layers. Okay, matplotlib.py. Okay, it's pylab. P. Okay, yeah. So now we will import our data set. df means data frame. You can write any word of your choice. Then pd, again pandas dot read underscore csv, used for reading csv file. Okay, excel files. Got it? Then here I will write my this coaster dot csv. Okay, I'm not writing any path because my this data set is here itself. This is coaster.csv. Okay, if you have your data set in another location, as in like in C drive, D drive, or whatever, okay, you can give that path. Okay, let me run it. Yeah, so now we will do some data understanding. Okay, we'll see data frame shape, head and tail, data types, and describe like small function we will use. df dot shape. Right. So we have 1087 rows and 56 columns in our data set. Okay, then we will see df dot head 5. So df dot head means it will give me top 5 rows of my data set. Okay, you can see 1 2 3 4 5. Okay, 5 rows and 56 columns. Here 56 columns, but we have 1087 rows. Okay, so we have coaster name, length, speed, location, status, opening date, type, this. Okay, we will do we'll make some graphs using these columns. Okay, and there is one more df dot tail. Again, last 5 rows. So df.tail gives you the last 5 rows. See 1086, 1085. Okay. And if you want to see full data, it is here. Okay, 0 to 1086. Fine. Yeah. So we have one more df.columns to check all the columns. See, coaster name, length, speed, location, status, opening date, type, and these all are my columns names. Fine. So we have one more data types. Actually, we have like many data types, but let me show you some important ones, or you can say some of the basics ones. Okay, so df dot d types. D types means data types. Coaster name is object type, length object, and inversion is float. Okay, we'll check inversion. Where's inversion? Yeah, float type. Okay. Then everything is object, and year introduces int, numeric one, and latitude float. Okay. So basically we have 3 types: float, int, and object. Okay. Then what we will do? Let's just quickly check this. Describe. Okay. So what is the count of this inversion? 932. Okay. It won't include any, what is it? Empty cells. Okay. It won't count empty cells. Right. Mean of this particular table, then standard deviation, then mean, minimum value, 25%, 70%, 75%, and max. It will describe you all this. Okay. And there is one more df.info to get the info. See, coaster name 1087 value, non-null object. Then length 953, non-null. Okay, like this. Yeah. So now moving forward, what we will do? We will do data preparation. Okay. What comes in data preparation? Like dropping irrelevant columns and rows, which we don't want. Okay. Then second thing is identifying duplicates columns. Then third is renaming columns. Then we will do some feature creations. Right. So if you want to drop a column, okay, how you can drop? So you have to write just df.drop. First I will give here hashtag data preparation. Okay, yeah. So how you can drop a column? Okay, df.drop. Then here I will write opening date, comma, axis equals to 1. Okay. Opening, okay, axis spelling is wrong. Instead of this, okay, maybe what is the opening date? Okay, O is capital here. Instead of this, you can use double equals to. Okay, axis is not defined. My bad. So what you have to do, you have to give this here and you have to put it here. Yeah. Again, axis is not defined. Yeah, fine. Okay. So as you can see here, first I will show you this. Question name, length, speed, location, status, and opening date is here. Fine. So if you will go here, question name, length, speed, location, status, nothing, opening date is there. Right? So this is how you can drop a table. Fine. For a while I'm making it as a comment. Maybe in future upcoming, making graph, I'll need this. Okay. So yeah. So I will write here df equals to df coaster name, comma, location, then comma, status. Then here I will write manufacturer. Fine. Then again comma. Then I will give here year, introduced, then comma, latitude. Wait, I will tell you why I'm doing this. Then longitude, latitude, longitude. Then I will give you type main. Okay. Then opening, date, clean. Fine. Then speed into in meter per hour. It is right. Speed into meter per hour. Okay. Then comma. What else? Then height, foot, inversion, clean, comma, g-force, clean, dot, copy. Yeah. Fine. So here I will write, okay, let's type in. Okay, one more mistake is here. Fine. So now what I will do, I will write here opening, date, clean equals to pd2 dot date time df opening, date, clean. Fine. What happened? So what does this pd dot to date time do? Okay, so it converts argument to date time. Okay, so this function, you can say converts a scalar, array like, or series or data frame, dictionary like, to a pandas date time object. Okay, so now let's rename the columns. Okay, then to for better things, df equals to df dot rename columns equals to coaster name, then poster name, comma, year introduced, then year introduced. Okay, opening date clean to opening date. Okay, then I will write as speed in meter per hour, then I will write caps speed underscore meter per hour. Got it? Then height into foot, I will write it as capital. So why I'm writing this? Because this is a very good practice as a professional way, as a data analyst or as a business analyst, whatever you are working on machine learning projects or whatever the thing. So this is a good practice. Okay, so inversions, clean, then it should be like inversions, then g-force clean to g-force. Fine, let me run it. Okay, now let's check the column. Yeah, so now you can say our column name is changed. Fine. So I will write is NA dot sum. So what does this is NA dot sum do? So is NA function returns a boolean value of true if the value is NaN and the false otherwise, and the sum function returns the sum of the true values which equals to the number of NaN values in the column. So here we have 0 NaN, here same, this status 213, here 217, 5, height foot is 916. Okay, so now what we will do, we will write here df dot location df dot duplicate. I told you in starting will duplicate it. Okay, so question name, location, status, okay, it's duplicated now. Okay, so now what we will do, I will check duplicates for the question name. So you can write df dot go loc, then df dot duplicated and subset equals to poster name, then dot head. Okay, head of 5. Now everyone know, right, what this head does. Okay, yeah, so here you can see, so these are duplicate, okay, of the question name, right? Why? Because you can just check the type and wood and all. Fine. So now checking with an example duplicate, let's check df dot query question name is equals to crystal. Now you will get beach cyclone. Okay, I took this crystal beach cyclone. Fine, then run it. So now you can see 39 and 43 are the same. Okay, everything is same. So this one is duplicate. So now what I will do, I will write here, just let me give some space. Yeah, df dot columns, then I will write here df equals to df dot location, then df dot duplicated subset equals to question name, then location, then opening date. Okay, dot dset index, then drop that. Okay, so now what we will do, we will do some feature understanding. Okay, so now we will do some feature understanding. Okay, so in this we will plot some feature distribution like histogram, KD, box plot. Okay, for that I will write here df year introduced. Okay, then I will write value counts. So now what I will do, let's create bar chart. Okay, ax equals to df year introduced dot value counts. Okay, then dot head 10 max I need, then dot plot kind equals to I need bar, then title is top. I like what should we give? Top 10 years coasters introduced. Okay, then I will write here ax dot set x label. Then I will write here year introduced. Okay, then I will write here ax dot set y label. Then count. Okay, let me run it. Okay, unexpected character after line continuation. Okay, we can remove this as well. Unexpected intended. So now let me run it. Yeah, so this is our bar plot. Okay, so this is how you can create bar plot using your data. Okay, so a bar plot is one of the most common types of graphics in this data visualization or EDA. It shows the relationship between a numerical and the categorical variable. Okay, so each entity of this categoric variable is represented as a bar. Got it? So now let's do some more. So what let's make a histogram class. Okay, histogram. So for that I will write ax equals to df speed equal r, then plot kind equals to histogram, then comma, I will write bins here. Okay, bins equals to 20, then title equals to coaster speed, okay, in meter per hour, then ax dot set x label is speed meter per hour. Okay, forgot to give this. Okay, yeah. So a histogram displays numerical data by grouping data into bins of equal width. So here each bin is plotted as a bar whose height corresponds to how many data points are in that bin. So bins, you can say, are also sometimes called the intervals or classes or buckets. Basically, it's the same. So here for this much is the bin. For this much is the bin. So this is like that. Okay. So now let's create KD plot. So for that, it's very simple. Ax equals to df. Then I can write as speed in meter per hour. Then plot kind equals to KD, comma, then title. I can write anything, coaster speed, then ax dot set x label speed, okay, meter per hour. Yeah. So KD, what does KD means? A kernel density estimate. This plot is a method of visualizing the distribution of observation in a dataset, analogs to a histogram. So KD represents the data using a continuous probability density curve in one or more dimension. Okay, in one or more dimension, that curve. Fine. So now let's do some feature relationship. So in this we will make scatter plot, heat map correlation, and pair plot. Okay, or we can also do some group by comparison. Fine. So now let's first make scatter plot. Okay. So df dot plot kind equals to scatter, comma, x equals to speed meter per hour, comma, y equals to height in foot, Fine. Then comma, let's give the title equals to coaster speed versus height. Fine. Then plt dot show. Okay, some error is there. Speed meter per hour. Okay, S should be capital and H should be capital. Yeah. So this is scatter plot. Speed versus height. This is speed versus height. Okay. If the I can see here height is directly proportional to speed somewhat, because if you can see the 350's speed is then 120 km per hour. No, it's not like that. Okay, fine. So scatter plot identifies the possible relationship between change observed in two different sets of variables. Here the variables are height and the speed. Okay, it provides a visual and the statistical means to test the strength of relationship between two variables. Fine. Now let's make one more to give you better idea. Okay, with legend. Now I will show you with SNS dot scatter plot, then x equals to speed meter per hour, comma y equals to height into foot, feet, whatever you can say. Then hue will be there, then year introduced. Okay, then data equals to df, then ax equals to set title, then coaster speed versus height, then plt dot show. Yeah, so now you can see, so this color, the light color, let me zoom it. Okay, so this color we have some here which are introduced in 90s. Okay, and this color which are introduced in 1925, and these colors which are introduced in 2000. Okay, so you can see like this as well. So now let's make pair plot. Okay, it's look amazing. So let me write SNS dot pair plot, then df comma variables equals to, I need year introduce, then speed meter per hour, comma that should be capital, height foot. Just remember the spelling. Okay, it's case sensitive. Inversions, comma g-force. Okay, comma hue, I will put what. Okay, I will put type main. Fine, then plt dot show. Okay, let me run it. Okay, some error is there. Here introduced, y will be capital, and same here. So that's why I'm saying just remember the proper spelling. Again, some error, sorry, my bad. Inversions. Is inversions. Now let me run it. Okay, again some errors there. Okay, what inversions? Okay, let me check here while renaming. Inversions only. Okay, fine. Inversions. Let me paste it, but nothing changes. Let me check again. Okay, some error is there. Wait. So yeah, you can see it's running fine. So after this, what I will do? So what is the pair plot? So pair plot function allows the user to create, then an axis grid via which each numerical variable stored in the data is shared across the x and the y, okay, in the structured column. So this is how, see, type in wood, other and steel. This red one is wood, other are the blue one, and the purple are the steel one. Okay, the different format. Okay, now let's create the last graph, which is heat map. Okay, so let me write df correlation equals to df here introduced comma speed meter per hour comma height into foot. Again it will be the same, comma inversions comma g-force, then drop NA, then correlation, okay, df minus correlation. Okay, here introduced ice capital, yeah. So this is correlation values of all the things, right? So now let's write SNS dot heat map then tf underscore corr comma and not will be true. Okay, now let me run it. Yeah, so to create heat map in Python, so you can use this, okay, Bond library for this heat map. So this function takes a data frame, as an input and generates a heat map type of things as the output. Okay, so this is how you can perform EDA using any data set, or you can show your data or insights with a beautiful representation using graphs and all like this. Web scraping is a powerful technique that allows you to automatically extract data from website, turning the vast amount of information available online into something you can easily analyze and use. Whether you are gathering data for research, building a dataset for machine learning project, or just curious about how websites work behind the scenes, web scraping is an essential skill to have in your toolkit. On the other hand, Python is one of the most popular programming languages for web scraping, thanks to its simplicity and the wealth of libraries available. In this video, we will explore how to use Python to scrape data from websites, and we will dive into practical examples using Python libraries like request and beautiful soup to fetch and parse web content. But it's not just about the code. Web scraping comes with its own set of challenges and ethical consideration. We will talk about how to scrape responsibly, respecting the rules set by websites, and ensuring that your scraping activity don't negatively impact the sites you are collecting data from. So by the end of this video, you will have a solid understanding of how to start scraping data from the web using Python. Whether you are new to programming or looking to add web scraping to your skill set, this video will give you the knowledge and tools you need to get started. So let's jump in and see how Python can help you unlock the full potential of the web. So here I am using this Google Colab for the web scraping. Okay, you can use your own like Jupyter Notebook, Visual Code Studio, anything. Okay, so here I will write web scraping using Python. Okay, then here first you have to install some libraries like request, and you have to install beautiful soup, and you have to install that pandas, because we will create one data frame and we will save it, then we will check our data. Okay, and you can install some basic Python libraries like NumPy and all that. Okay, So here first I will import request. Okay, then I will write from BS4 import beautiful soap. Okay, soap. Then I will write import pandas as Peli. Fine. Then now what I will do? Okay, let's see what is this request and all this. So request is an HTTP client library for the Python programming language. So request is one of the most downloaded Python libraries. Okay, with like more like over 2000, not exactly 2000, sorry, 200 or 300 million monthly download. Okay, so what it does, it maps the HTTP protocol onto Python's object-oriented semantics. And here, beautiful soup. So beautiful soup is a Python package for parsing the HTML and XML documents, including those with malformed markup. It creates a parse tree for documents that can be used to extract data HTML from HTML, which is useful for web scraping. Let me run it. Here, our second step will be define the URL and the headers. Okay, URL and the headers. So URL, okay, from where you want to extract your data. So I will write here Simplilearn. Then this. Okay, let's open this PMP certification. Okay, let's cut it. Yeah. So here I will write this. And headers equals to. So these are the headers. Okay. So like in which device or you are working on, which browser you are working on. So these are for the headers. So now what I will do, I will send a GET request to the Simplilearn page. Okay, to this URL. For that, right, let me write this, sending GET request. Okay, here write response equals to requests dot get, then URL comma headers equals to headers. Okay, let me run it. Okay, working fine. So now let's check if the request is successful or not. For that, if response dot status code equals to 200, then soup equals to beautiful soup. Okay, then response dot content comma HTML dot parser. Okay, here, so here I will write codes titles. Why? Because here I'm initializing the list to store our titles or whatever the things are. Okay, basically the data. Okay, why I'm writing course here? Because this is again course page, that's why, nothing else. Okay, here I will give the empty list. So now we will find all course titles based on the actual HTML structure. What is HTML structure? You have to go to the page, right click, then inspect. Okay, according to this, HTML structure means what is the class name, what is the, this PMP certification is which heading, H1 heading, H2 heading, which heading it is. Okay, so let's see which heading it is. Okay, this PMP certification training H1 heading. Okay, just remember H1 heading. So here I will write for course
inso dot find or h1. Okay, then title equals to course text dot strip. Okay, then here I will write course titles dot append title. Okay, now what I will do, I will check if any data was extracted before it not. Okay, I will write if course titles. Here I will create a data frame. df equals to pd dot data frame. In this I will write course title. It will be our that column name. So for I will write it course data. Okay, then course titles. Okay, then here I will write df dot to csv, then just create Simplilearn.csv. Okay, so our data will be saved in this Simplilearn.csv. Okay, CSV. Fine. Here what I will do, I will write index equals to false. Print data, and data is saved in CSV, Simplilearn.csv. Fine. So here I will write else print web page. Okay, write field to retrieve the web page. Okay, that's it. Let me run it. Okay, if response storage to this group, response object has no attribute, status code. Okay, okay, title, it is text. Some minor spelling mistakes are there. Okay, dear dot field. Sorry, my bad. Again. Okay, sorry. D will be capital, F will be capital. Yeah, so now you can see data is saved in Simplilearn.csv. So what I will do, I will write data equals to, everyone know how to read CSV in Python. read underscore CSV. What was our file name? Simplilearn.csv. Okay, let me copy paste, run it, and then find data. Okay, PMP certification training data is fetched. Okay, here you can see H1 we gave, and that's why PMP certification training came. Let's take what's in H2. Okay, in H2 there is leading premier PMI partner, something is there. Okay, I will change here H1 to H2, then I will run it. Okay, fine. See, leading premier PMI. Okay, let me make it big. Yeah, so now you can see course data we mentioned. So if you will see, this H1 didn't come. Why? Because we have mentioned H2. That's why. So these all are the H2. Okay.
So what is this? I don't know. Okay. This is a time series graph. This is Google Colab thing. Okay. So this is how you can literally retrieve your data from any website. Okay. Just remember that some websites don't give you access to their, for their scraping, just like Amazon don't give. So you have to use at that time API. And this is not ethical also to use someone's data, okay, without asking or whatever you guys.
Learning objectives. Welcome to Math Refresher, Probability and Statistics. In this lesson, we are going to explain the concepts of statistics and probability. Describe conditional probability, define the chain rule of probability, discuss the measure of variance, identify the types of Gaussian distribution. Basic of statistics and probability. Probability and statistics. Data science relies heavily on estimates and predictions. A significant portion of data science is made up of evaluations and forecast. Statistical methods are used to make estimates for further analysis. Probability theory is helpful for making predictions. Statistical methods are highly dependent on probability theory, and all probability and statistics are dependent on data. Data is information acquired for reference or research via observations, facts, and measurements. Data is a set of facts structured in the form that computers can interpret, such as numbers, words, estimations, and views. Importance of data. Data aids in seeing more about the information by identifying possible connections between two features. Data assists in the detection of distortion by uncovering hidden patterns. Based on prior information patterns, data may be utilized to anticipate the future or predict the current state of affairs. Also, data aids in determining whether two pieces of information have any instance in common or not. Types of data. Data might be quantitative. That is data that can be measured or counted in numbers. Or it may be qualitative, which is data which is generally divided into groups or, in simpler words, which cannot be counted or measured in numbers. Let's consider an example. A customer information data of a bank may contain quantitative and qualitative data. Consider this snapshot where we have customer ID, surname, geography, gender, age, balance, has CR card, is active member. Amongst these variables, we can see surname is mostly qualitative as it cannot be counted and measured in numbers. Geography and gender are also qualitative as they cannot be counted in numbers and are mostly groups. Has CR card, that is, has credit card, and is active member, although are containing numerical in form. But these are categorical. That means these have been divided into groups of 1 and 0 that represent yes and no as an answer. Hence, these two variables are also qualitative. Customer ID is again, although a numerical data. However, the significance or intuition behind customer ID is categorical. Hence, it may be kept in the qualitative data also. However, age and balance. These are numerical information which have been measured or counted, and numerical operations can be performed on them. Hence, these are under quantitative data categories. Introduction to descriptive statistics. Descriptive statistics. A descriptive measurement is summary measure that quantitatively portrays the most important features of a set of data, allowing for a better comprehension of the information. Data can be measured as different levels. The levels of measurement describe the nature of information stored in the data assigned to the variables. Qualitative data can be measured as nominal or ordinal. Quantitative data can be measured in terms of interval and ratio type. Nominal data. The data is categorized using names, labels, or qualities. For example, brand name, zip code, and gender. Ordinal data can be arranged in order or ranked, and can be compared. Examples include grades, star reviews, position in race, and date. Interval data is the data that is ordered and has meaningful differences between the data points, example, temperature in Celsius and year of birth. Ratio data is similar to the interval level with the added property of inherent zero. Mathematical calculations can be performed on both interval as well as ratio data. For example, height, age, and weight. Population versus sample. Before analyzing the data, it's important to figure out if it's from a population or a sample. Population is a collection of all available items as well as each unit in our study. Sample is a subset of the population that contains only a few units of the population. Population data is used for study when the data pool is very small and can give all the required information. Samples are collected randomly and represent the entire population in the best possible way. Measures of central tendency. The central tendency is a single value that aids in the description of the data by determining its center position. Measures of central tendency are sometimes known as summary statistics or measures of central location. The most popular measurements of central tendency are mean, median, and mode. The normal distribution is a bell-shaped, symmetrical distribution in which mean, median, and mode all are equal. The curve over here shows the bell-shaped curve or the normal distribution of variable x. The point over here that is x1 is the point which represents the mean, median, and mode of this distribution. Mean. Mean is calculated by dividing the sum of all data values by the total number of data values. It gets affected when there are unusual or extreme values. It is sensitive to the outliers. Mean can be calculated as summation over all the values of x in a collection divided by the size of the collection. For example, we have a collection where we have values as 7, 3, 4, 1, 6, and 7. We find out the sum of these values, which is 28, and there are a total of 6 values. So 28 divided by 6 gives us a mean value of 4.66. Median. It is the middle value in the set of the data that has been sorted in ascending order. It is a better alternative to mean, since it is less impacted by outliers and skewness. It is closer to the actual central value. Median is calculated differently for different sizes of data. Differentiated as if the total number of values is odd, or if the total number of values is even, if the size of the data is odd. For example, in this case, we have 5 elements. After sorting, whatever middle value we get. That means n plus 1 by 2th term in this case. 5 plus 1 divided by 2. That is the 3rd term, which is 4 is the median value. In case when the total number of values is even like here, there are 6 values. The average or the mean of the 2 central values is considered as the median. In this case, the median is the mean of 6 and 4, which is 5. Mode. Mode represents the most common value in the dataset. It is not at all affected by extreme observations. It is the best measure of central tendency for highly skewed or non-normal distribution. Mode for categorical data is determined by estimating the frequencies for each categories, and then the category with the highest frequency is considered to be mode. Like in this case, 7 has the highest frequency, hence 7 becomes the mode value. However, in case of continuous data or quantitative data, the calculation of mode is slightly different. The first step in calculation of mode is dividing the data into classes which are equal with, then getting the frequency of data points lying within that range of classes, and finally selecting the class with the highest frequency. Using the range of that class and the frequencies, we can get the final mode value. Using the formula L plus fm minus f1 multiplied to h divided by fm minus f1 plus fm minus f2. Here L is the lower limit, or the lower observation of the mode class. H is the size of the mode class. Fm is the frequency of the mode class. F1 is the frequency of the class proceeding to mode. And F2 is the frequency of the class succeeding to mode. This gives us the final mode value. Mean versus expectation. Now let's talk about mean versus expectation. So in general, we use the expected value or expectation when we want to calculate the mean of a probability distribution that represents the average value we expect to occur before collecting any data. And mean, on the other hand, mean is basically used when we want to calculate the average value of a given sample. This represents the average value of raw data that we may have already collected. We can understand this by using a simple example. Now, to calculate the expected value of this probability distribution, we can use a specific formula from the previous discussion. This is going to be the expected value, where x is going to be the data value, and this px is the probability of value. For example, we could calculate the expected value for this probability distribution to be as shown. So here, it will be 1.45 goals. So this represents the expected number of goals that the team will score in any given game. And then if you talk about calculating mean, so we typically calculate the mean after we have actually collected raw data. For example, suppose we record the number of goals that a soccer team will score in 15 different games. Now to calculate the mean number of goals scored per game, we can use the following formula, where sum of x is basically the sum of all the goals divided by n and the number of records, or we can say the sample size. It is as shown on the screen. So this represents the mean number of goals scored per game by the team. Measures of asymmetry. The difference between the three distinct curves can be studied in this image. The central curve is the normal or no skewness curve. Here mean, median, and mode all lie on the same point. This normal curve is symmetrical about its mean, median, and mode. That means the left-hand side of the curve is a mirror image of the right-hand side of the curve. However, in case of negatively skewed data, the tail is elongated on the left-hand side, and the mean is smaller than the mode and the median values, or is on the left-hand side of the mode, hence indicating that the outliers are in the negative direction. On the other hand, in case of positively skewed, the data is concentrated on the left-hand side of the curve, while the tail is elongated or longer on the right-hand side of the curve. The mean is greater than the mode and median, or is on the right-hand side of the mode and median, indicating that the outliers are in the positive direction. Let's consider an example. The graph here shows the global income distribution for the year 2003, 2013, and a projection for 2035. If we see the global income distribution statistics for 2003, it is highly right-skewed. We can observe in the previous graph that in 2003, the mean of $3,451 was higher than the median of $1,090. The global income is definitely not evenly distributed. The majority of people make less than $2,000 each year, while only a small percentage of the population earns more than $14,000. Measures of variability. Measures of variability. Dispersion. The measure of central tendencies provide a single value that addresses the full worth. However, the central tendency cannot depict the viewpoint entirely. The metric of dispersion helps us focus on the inconsistency in the data spread. Measures of dispersion describe the spread of the data. The range, interquartile range, standard deviation, and variance are examples of dispersion measures. Range. The range of distribution is the difference between the largest and the smallest amount of data. The range, for example, does not include all of a series' positive aspects. It concentrates on the most shocking aspects and ignores that aren't considered critical. For example, for a set 13, 33, 45, 67, 70, the range is 57. That is, the maximum of this, which is 70 minus the minimum over here, which is 13. Variance. Variance is the average of all squared deviations. It is defined as the sum of squared distance between each point and the mean or the dispersion around the mean. The standard deviation is used as variance suffers from a unit difference. Variance can be computed as sigma square summation over x minus mu square, divided by n, where mu is the mean of the data, x is the individual data point, and n is the size of the data. This representation is for a population data. For a sample data variance can be computed as x minus x bar whole square summation over it divided by n minus 1. Here x bar is the mean of these sample data, and n is the sample size. The units of values and variance are not equal, so another variability measure is used. Standard deviation. Standard deviation is a statistical term used to measure the amount of variability or dispersion around a mean. The standard deviation is calculated as the square root of variance. It depicts the concentration of the data around the mean of the dataset. Standard deviation, as indicated previously, can be computed as square root of variance. For a population data, standard deviation sigma can be computed as square root of summation over xi minus mu whole square divided by n, where mu is the mean of the data, xi are the data points, and n is the size. Let's consider an example. Let's find out the mean, variance, and standard deviation for this data. The data values are 3, 5, 6, 9, and 10. To find out the mean, we first find the sum of all these data values. That is 33, and divide it by the count, which is 5. We get the mean of 6.6. To compute the variance, we start by computing the deviation. That is x minus the mean of x. Here 3 is one of the values of the data, and 6.6 is the mean. So 3 minus 6.6 square, and we do that to find out sum of all the deviations divided by the count, which is 5. We end up getting an overall variance of 6.64. Standard deviation, as we know, is measured at square root of variance. That is square root of 6.64, which amounts to 2.576. Measures of relationship. Measures of relationship. Covariance. Covariance is the measure of joint variability of two variables. It measures the direction of the relationship between the variables. It determines if one variable will cause the other to alter in the same way. Covariance between variable x and y can be computed as summation over the product of xi minus x bar and yi minus y bar the whole divided by n minus 1. Here x bar and y bar are the mean of x and y respectively. The value of covariance can range from -infinity to a +infinity. Correlation. Correlation is normalized covariance. It measures the strength of association between two variables. The most common measure for correlation is the Pearson correlation coefficient. Correlation between two variables, x and y, can be measured with respect to covariance as covariance between x and y divided by the standard deviation of x and standard deviation of y. The value of correlation ranges from a -1 to +1. Types of correlation. Correlation can be either a positive correlation, zero correlation, or a negative correlation. The first picture over here represents a perfect positive correlation, wherein a straight line with a positive slope is representing the relationship between the two variables. Zero correlation means that the line representing the relationship between the two variables is horizontal to the x-axis. Perfect negative correlation can be represented by a straight line with a negative slope. Correlation equals to 1 implies a positive relationship. That is when one variable increases, the other variable also increases. A correlation value of -1 implies a negative relationship. That is when one variable increases, the other decreases. The correlation coefficient of 0 shows that the variables are completely independent of each other. Let's consider an example. Here, we have two variables, height and weight. To compute the correlation between height and weight, we use the correlation formula as covariance of x and y divided by standard deviation of x and standard deviation of y. Here height is the x variable and weight is the y variable. First, to compute covariance, we compute the x minus x bar and y minus y bar values, and then the product of them. We then compute x minus x bar square and y minus y bar square values to compute the standard deviations of height and weight respectively. Correlation, as we know, has been defined as covariance of x and y and y divided by standard deviations of x and y. This can also be represented as summation over x minus x bar multiplied to y minus y bar divided by square root of summation over sum of squared deviations. That is x minus x bar square multiplied to square root of summation over y minus y bar whole square. That is sum of square deviations for y. Now, let's find out values to put into this formula. First, we find out the overall sum of height to get the mean of height, which is 5.14. Similarly, we get the sum of weight to get the mean of weight as 50. We now get the summation over x minus x bar multiplied to y minus y bar to get the numerator for the formula. Then we compute x minus x bar square summation and y minus y bar square. That is sum of squared deviation of x and y respectively. Now we put in the values in this final correlation formula to get a correlation value of 0.889. This indicates that height and weight have a positive relationship. It is evident that as height grows, weight also increases. In this module, we will be talking about expectation and variance. So the expected value, or we can say mean of a given variable, that we can denote by x is a discrete random variable where it is a weighted average of the possible values that x can take, and each value is going to be according to the probability of that specific event occurring. So usually the expected value of x is denoted by a simple formula where we can define the expectation based on the x parameter, which is going to be the sum of each possible outcome multiplied by the probability of the outcome occurring. So in more concrete terms, the expectation is what we would expect the outcome of an experiment to be on average. We can take an example for the coin. If a coin is being tossed 10 times, then one is most likely to get 5 heads and 5 tails. Same logic can be discussed if we talk about another example of rolling a die. So there are 6 possible outcomes when you roll a die. 1, 2, 3, 4, 5, 6. And each of these has a probability of 1 by 6 of occurring. So we can say that the expectation is going to be 1 multiplied by the probability of that happening, which is going to be 1 by 6, plus 2 by 6, plus 3 by 6, plus 4 by 6, plus 5 by 6, plus 6 by 6, and that is going to give us 3.5 as an output. The expected value is 3.5. So if you think about it, 3.5 is halfway between the possible values that I can take. And this is what we should have expected. Next, we talk about the concept of variance. So variance of a random variable allows us to know something about the spread of the possible values of the variable. So for a discrete random variable x, the variances of x is going to be denoted by using a simple formula that is going to be var x equals ex minus m, the whole square where m is basically the expected value of the expectation of x. So this is more like a standard deviation of x, which can also be represented by using this formula. So the variance does not behave in the same way as expectation when we multiply and add constants to random variables. So now there are 2 different types of variance that we can have a fair understanding on. First of all, we have low variance, and then we have high variance. So low variance simply means that there is a small variation in the production of the target function, with changes in the training data set, and at the same time, high variance, as we can see here. High variance shows a large variation in prediction of the target function, with changes in the training data set. So a model that shows high variance learns a lot and perform well with the training data set. And it does not generalize well with the unseen data set. And that's why, as a result, such a model gives good results with training data set, but shows high error rates on the test data set. And since the high variance a model learns too much from the data set, it leads to an overfitting of the model. So model with high variance will be having a couple of issues, like it may lead to overfitting, or it may also lead to increase in model complexities. Next, we have skewness. So skewness in simple terms is basically a measure of asymmetry of a distribution. So distribution is asymmetrical when it's left and right sides are not the mirror images. Right now, this is a mirrored image, and a distribution can have right positive, or we can say negative, or it can have 0 skewness. So right skewed in this scenario is basically the distribution is longer on the right side of its peak. And a left skew distribution is going to be, we can say, where it is longer on the left side. So we can see we have this one as a part of right side. it is more elongated towards the right side, and this one is more elongated towards the left side. So we can think of skewness in terms of tails. A tail is long tampering and the end of a distribution. So it simply indicates that they are observations at one end of the distribution, but that they are relatively infrequent. So a right skew distribution has a long tail on the right side, as you can see here, so the number supports observed. Let's say we have a data on a per year basis. So again, we can have a more skewness towards the right side, where data is being dropping as we continue to increase the number of years. For example, we may have a high sales towards the beginning of year, suppose in 2022. But again, as we proceed to 2023, second half we are seeing the dip in performance. So that is rightly skewed. And same way, let's suppose if we started with the sales figure, it was really less in suppose 2002. But again, as we proceeded to 2023 now, our sales have been gradually increasing. So it's more like skew towards the left section as a part of negative skew. Next, we have kurtosis. So kurtosis is basically a measure of the tailedness of a distribution. So tailedness is how often the outliers occur, and acts as kurtosis is the tailedness of the distribution related to a normal distribution. So a distribution with medium kurtosis is called as mesokurtic. A distribution with low kurtosis like this one. This is called as the platykurtic, and then distribution with high kurtosis like this one. This is called as the leptokurtic. So tails here, they are tapering ends on either side of a distribution like this. So they represent the probability or the frequency of values that are extremely high or extremely low to the mean. In other words, tails here represents how often the outliers occur. So there are three types of kurtosis. We have platykurtic, which is negative, leptokurtic, which is a positive towards the upper end, and then we have mesokurtic, which is a normal distribution. So mesokurtic is the medium tail. So normal distributions, they have a kurtosis of 3. So any distribution with a kurtosis of a prox value of 3 is going to be mesokurtic, and kurtosis is described in terms of excess kurtosis, which is kurtosis minus 3. And since normal distribution, they have a kurtosis of 3 axis kurtosis, makes comparing a distribution kurtosis to a normal distribution even easier. Introduction to probability. Probability theory. Probability is a measure of the likelihood that an event will occur. Let's consider an example of coin toss, where the chances of getting heads on a coin are 1 by 2 or 50%. The probability of each given event is between 0 and 1, both inclusive. Sum of an event's cumulative probability cannot be greater than 1. Hence, the probability of an event x lies between 0 and 1. This means that the integral of probability of distribution over x equals to 1. Conditional probability. Conditional probability of any event A is defined as the probability of occurrence of A, given that event B has previously occurred. Condition probability of event A given B can be estimated as probability of A intersection B, that is, probability of both A and B happening together, divided by the probability of B. It is also written as that probability of A intersection B equals to probability of A given B multiplied to probability of B. Let's consider an example. In a coin, we are doing a 2-coin flip. Coin 1 gets heads, and tails in subsequent flips, while coin 2 gets tails, heads, and tails in the subsequent flips. Now the probability that coin 1 will get a head is 2 out of 4, while the probability that coin 2 will get heads is again 2 out of 4. The probability that both coin 1 and coin 2 will have a heads is just 1 out of the 4 flips. Hence, the probability that coin 1 will get heads given that coin 2 is already heads can be computed as probability of coin 1 edge intersection coin 2 edge. That is 1 by 4 divided by probability of coin 2 edge. That's a given that is 2 by 4, which is going to be 0.5 or 50% based. Bayes theorem. Bayes' theorem calculates the conditional probability of an event based on its prior probabilities. Basically, Bayes' theorem incorporates the prior probability distribution to predict the posterior probabilities. Bayes' theorem for conditional probability can be expressed as probability of A given B equals probability of B given A divided by probability of B multiplied to probability of A. Bayes' theorem allows updating the probability values by using new information or evidence. Here, probability of A is known as prior probability. That is the probability of event that before any new data is collected. Probability of A given B is known as the posterior probability. It is the revised probability of an event occurring after taking into consideration the new information. Probability of B given A is known as the likelihood, and probability of B is probability of observing an evidence. Bayes model. An example. Consider an example for calculating the likelihood of having diabetes based on frequency of fast food consumption. Here is the observed data. Let's say the fast food audience is 20%. Diabetes prevalence is 10%, and 5% is fast food and diabetes. The chances of diabetes given fast food, that is the conditional probability of D given B, can be calculated as probability of diabetes and fast food together divided by probability of fast food. That means 5% divided by 20%. That equals 25%. Define an analysis can state eating fast food increases the chance of having diabetes by 25%. The multiplication rule of probability. If events A and B are statistically independent and probability of A intersection B can be given as probability of A given B multiplied to probability of B. However, probability of A intersection B is also given as probability of A multiplied to probability of B. Here, probability of A given B equals to probability of A when we assume that probability of B is non-zero. Similarly, probability of B equals probability of B given A, assuming probability of A is non-zero. Chain rule of probability. Joint probability distributions over many random variables can be reduced into conditional distributions over a single variable. It can be expressed as probability of x1, x2, so on until xn equals probability of x1 intersection probability of xi, given probability of x1 till xi minus 1. For example, the joint probability of A, B, and C can be given as probability of A given B, C multiplied to probability of B, given C multiplied to probability of C. Logistic sigmoid. The logistics function is a type of sigmoid function that aims to predict the class to which a particular sample belongs. Its outcome is discrete binary value, a probability between 0 and 1. The logistic sigmoid is a useful function that follows the yes curve. It saturates when the input is very large or very small. Logistic sigmoid is expressed as sigma of x equals 1 upon 1 plus e to the power minus x. The logistic sigmoid can be expressed as sigmoid function of x is given as 1 upon 1 plus e to the power minus x, where e is the Euler's number. Gaussian distribution. The Gaussian distribution is a type of distribution in which data tends to cluster around a central value with little or no bias to the left or right. It is often referred to as normal distribution. In absence of prior information, the normal distribution is frequently a fair assumption in machine learning. Equation. The formula for calculating Gaussian distribution is described as the normal distribution of x. That is the function of x given mean as mu and variance is sigma square can be calculated as 1 upon sigma square root of 2 pi e to the power minus half x minus mu divided by sigma whole square, where mu is the mean or peak value, which also is the expected value of x. Sigma is the standard deviation, sigma square is the variance. A standard normal distribution has a mean of 0 and a standard deviation of 1. Gaussian distribution can be univariate, which describes the distribution of a single variable x. It can also be multivariate, where it can just use to describe the distribution of several variables. It is represented in 3D of ND formats. Law of large numbers. Now let's talk about law of large numbers. The law of large numbers states that an observed sample average from a large sample will be close to the true population average, and that it will get closer in the larger sample. So the law of large number does not guarantee that a given sample, spatially a small sample, will reflect the true population characteristics, or that a sample does not reflect the true population will be balanced by a subsequent sample. This is for the law of large numbers to express the relationship between scale and growth rate. So there are multiple examples through which we can understand, and it is widely used in statistical analysis in working with the central limit theorem in terms of the business growth. So there are multiple real-time setup in which these are going to be used. So if you talk about tossing a coin, so tossing a coin in a number of times will give us 2 different type of outcomes. The result will spread evenly between head and tails, and the expected average value is going to be half. That means 50 times tails and 30 times heads. But again, if you toss a coin 1,000 times, then the result can be in different manners, because out of 1,000, let's say 850 times it has been head, and only 150 times it has been tails, and so on. So that's why the possibility of one event occurring is going to be changed in large sample sets as compared to a small sample sets, as in let's say 10 times. So the number of heads and tails unbalanced for lower number of trials, so we can see it is unbalanced. But again, as soon as we toss more number of coins, more leans towards the balance value, or we can see the observed averages. Next, we have p-value. So p-value is basically a number calculated from the statistical test that describes how likely we are to have found a particular set of observations if the null hypothesis were true. So p-values are used in hypothesis testing to help decide whether to reject the null hypothesis. And the smaller the p-value, the more likely we are to reject the null hypothesis. So we have a term called as null hypothesis. So all statistical tests, they have null hypothesis. So for most tests, the null hypothesis is that there is no relationship between our variables of in first, or that there is no difference among groups. For example, in a two-tailed t-test, the non-hypothesis is that the difference between two groups is going to be 0. So p-value is going to tell us how likely it is that our data could have occurred under the null hypothesis. It is done by calculating the likelihood of a test statistic, which is the number calculated by a statistical test using our data. So p-value tell us how often we would expect to see a test statistic as extreme or more extreme than one calculated by a statistical test. if the null hypothesis of the test was true. So there are multiple limitations as well. So first one is the results can be significant, but again, they may not be practical as we have compared. It can be based on multiple hypotheses for a game, for the healthcare test. If the test is going to be positive or not, it may show even values of the effect of a variable, but not the magnitude in real life. What exactly is going to be the application of a drug test being failed in pharma company? Therefore, it is recommended to use confidence and levels in addition to the p-values to quantify, or we can say to give a solid figure to the reserve, which we are going to get. The p-values they are interpreted as supporting, or we can say refuting, the alternative hypothesis. So p-value can only tell you whether or not the null hypothesis is supported. It cannot tell us whether our alternative hypothesis is true or why. So the risk of rejecting the null hypothesis is often higher than the p-value. So especially when we are looking at a single study or when using small sample sizes. So this is because the smaller frame of reference, the greater are the chance that as we stumble across a statistically significant pattern completely by accident. Key takeaways. Key takeaways. Probability and statistics structure the premise of the data. The data helps in anticipating the future or gauging in view of the past patterns of information. The central tendency is a single value that helps to describe the data by identifying these central positions. The mean, median, and mode are the measures of central tendencies. The distribution where the data tends to be around a central value with a lack of bias or minimal bias towards the left or right is called as Gaussian distribution.
Welcome to our video about transformers in AI. And no, we don't mean the robot toys from the movies. We are diving into something even cooler in the world of computers and AI. Have you ever wondered how your phone knows what word you might type next, or how Google Translate works so well? That's where transformers come in. They are like super smart computer brains that can understand and create human-like text. Here's a fun example. I asked a transformer to tell me a joke and it said, "Why did the computer go to the art school?" Because it wanted to improve its draw speed. Okay, that's a bit cheesy, but it shows how these computer programs can come up with new ideas on their own. Transformers are changing how we use technology every day. They help us with things like translating languages, summarizing long articles, writing emails and stories, and even playing games like chess. In this video, we will explore how transformers work, why they are so special, and what cool things they might do in the future. So let's talk about what exactly are transformers. Transformers are an artificial intelligence model used to process and generate natural languages. They can read and understand huge amount of text and then use that knowledge to answer questions, translate languages, summarize information, and even create stories or write code. The magic behind transformers is their ability to focus on different text paths with attention mechanisms. This means that they can understand context better than older models, making their outputs more accurate and natural sounding. The basic structure of a transformer includes two main parts, the encoder and the decoder. Think of the encoder as a translator that understands and processes the input, and the decoder as the one that takes the processed information and turns it into the output. For example, if we are translating a sentence from English to French, the encoder reads the English sentence and converts it into a form that AI can understand. The decoder then takes this form and generates the French sentence. A great example of a transformer in action is ChatGPT. ChatGPT uses transformers to understand and generate human-like text. When you ask a question, it processes your input with its encoder and generates a response with its decoder. This lets it have conversations, write essays, and even tell jokes. For instance, if you ask ChatGPT, "What's the weather like today?" it uses its transformer model to understand your question and respond it with "It's sunny, with a chance of rain in the afternoon." This ability to understand and generate text makes transformers incredibly powerful. So let's talk about how transformers work. Transformers are especially good at sequence-to-sequence learning tasks, like translating a sentence from one language to another. Here's how they work. First, there's the attention mechanism. This allows the transformer to focus on different parts of input data. For example, if it's translating the sentence, "the cat sat on the mat," it can pay attention to each word's context to understand the meaning better. So it knows cat is related to sat and mat, helping it produce an accurate translation in another language. Transformers also use something called positional encoding. Since they process all words at once, they need a way to understand the order of the words. Positional encoding adds information about the position of each word to the input, helping the transformers understand the sequence. Another key feature is like parallel processing. Unlike older models like recurrent neural network, which is RNNs, the process text words by word. Transformers can process the entire sentence at once. This makes them much faster and more efficient. Let's compare transformers with recurrent neural networks. But first, let's understand what are RNNs. So RNNs is a type of neural network designed to handle sequential data. They process data one step at a time, maintaining a memory of previous steps. This makes them good for tasks where order matters, like speech recognition or time series prediction. However, RNNs have a problem called the vanishing gradient, which means that they can forget information from earlier in the sequence. Imagine trying to understand the sentence, "Alice went to the park and then to the store." And RNN might struggle to remember Alice by the time it gets to the store, but a transformer can easily keep track of Alice throughout the sentence. So why are transformers better? Unlike RNNs, transformers process the entire sentence at once, keeping the context intact. This solves the vanishing gradient problem and makes transformers faster and more accurate to tasks like language translation and text generation. So let's talk about the applications of transformers. At first, we have language translation. They are used by services like Google Translate to convert text from one language to another. For example, translating "hello, how are you" to Spanish as "hola." Then we have document summarization. They can take long articles and summarize them into shorter, more concise versions. For instance, summarizing a 10-page report into a few key points, making it easier to understand the main ideas without reading the whole document. Then we have content generation. Transformers can write articles, stories, and even code. They can create new content based on what they have learned. For example, you could ask a transformer to write a short story about a space adventure, and then it would come up with a unique narrative. Then we have game playing. Transformers can learn and play complex games like chess, making strategic decisions just like a human player. They analyze the entire board and make moves considering all possible outcomes. Let's talk about image processing. They are used in tasks like image classification and object detection, helping computers understand visual data. For example, identifying objects in a photo, like recognizing a cat, tree, or a car. Now let's understand the training process. The training transformers involves two main steps. Semi-supervised learning. They can learn from both labeled data where the answer is known and unlabeled data where the answer is not provided. This makes them very versatile. For example, a transformer could be trained on a mix of articles with and without summaries to learn how to summarize text effectively. Pre-training and fine-tuning. Transformers are pre-trained on a large dataset to learn general patterns. Then they are fine-tuned with specific tasks, making them highly versatile. For instance, a transformer might be pre-trained on a large collection of books to understand language and then fine-tuned to generate marketing copy for a specific brand. The future potential of transformers is huge. Researchers are continuously improving them, making them even more powerful. We can expect more advanced applications in areas like healthcare, finance, and more sophisticated AI systems that interact with humans in more natural ways. Imagine having an AI that can provide personalized medical advice or one that can help you write a novel. In conclusion, we can say that transformers are a revolutionary architecture in AI. They offer speed, efficiency, and versatility, changing how we interact with the technology. The future looks bright for transformers, and we can't wait to see what they'll do next.
So what is Q-learning? Q-learning is reinforcement learning policy which will fill the next best action given a current state. It chooses this action at random and aims to maximize the reward. And so you can see here's our standard reinforcement learning graph. By now, if you're doing any reinforcement learning, you should be familiar with this, where you have your agent takes an action, the action affects the environment, and then the environment sends back the reward or the feedback and the state, it's the new state the agent's in. Where is it at on the chessboard? Where is it at in the video game? If your robot's out there picking trash up off the side of the road, where is it at on the road? Consider an ad recommendation system. Usually when you look up a product online, you get ads which will suggest the same product over and over again. Using Q-learning, we can make an ad recommendation system which will suggest related products to our previous purchase. The reward will be if user clicks on the suggested product. And again, you can see you might have a lot of products on your web advertisement or your pages, but it's still not a float number. It's still a set number, and that's something to be aware of when you're using Q-learning. And you can see here that if you have 100 people clicking on ads and you click on one of the ads, it might go in there and say, okay, this person clicked on this ad. What is the best set of ads based on clicking on this ad or these two ads afterwards based on where they are browsing? So let's go ahead and take a look at some important terms when we talk about Q-learning. We have state. The state S represents the current position of an agent in an environment. The action A is the step taken by the agent when it is particular state. Rewards. For every action, the agent will get a positive or negative reward. And again, when we talk about states, we're usually not, when you're using a Q table, you're not usually talking about float variables. You're talking about true, false. And we'll take a closer look at that in a second. And episodes, when an agent ends up in a terminating state and can't take a new action. This might be if you're playing a video game, your character stepped in and is now dead or whatever. Q values used to determine how good an action A taken at a particular state S is Q A of S. And temporal difference, a formula used to find the Q value by using the value of the current state and action and previous state and action. And there's Bellman's equation, which basically is the equation that kind of covers what we just looked at in all those different terms. The Bellman equation is used to determine the values of a particular state and deduce how good it is to be in take that state. The optimal state will give us the highest optimal value. Factor influencing Q values, the current state and action, that's your SA, so your current state and your action. Then you have your previous state and action, which is your S, I guess prime, I'm not sure how they reference that, S prime, A prime. So this is what happened before. Then you have a reward for action, so you have your R reward, and you have your maximum expected future reward. And you can see there's also a learning rate put in there and a discount rate. So when we're looking at these, just like any other model, we don't want to have an absolute final value on here. We don't want it to, if you do absolute values instead of taking smaller steps, you don't really have that approach to the solution. You just have a jump, and then pretty soon if you jump one solution out, that's what's going to be the new solution, whichever one jumps up really high first. Kind of ruining the whole idea of doing a random selection. I'll go into the random selection in just a second. Steps in Q-learning. Step 1. Create an initial Q table with all values initialized to 0. Again, we're looking at 0, 1. So are you, here's our action. We start, we're in idle, we took a wrong action, we took a correct action, and end. And then we have our actions, fetching, sitting, and running. And of course, we're just using the dog example. And choose an action and perform it. Update values in the table. And of course, when we're choosing an action, we're going to kind of do something random and just randomly pick one. So you start out and you sit, and you have then depending on that action you took, you can now update the value for sitting after you start, from start to sitting. Get the value of the reward and calculate the value Q value using the Bellman equation. And so now we attach a reward to sitting. And when we attach all those rewards, we continue the same until the table is filled with or an episode ends. And I mentioned I was going to come back to the random side of this. And there's a few different formulas I use for the random setup to pick it. I usually let whatever Q model I'm using do their standard one because someone's usually gone in and done the math for the optimal spread. But you can look at this. If I have running has a reward of 10, sitting has a reward of 7, fetching has a reward of 5, just kind of without doing like a means, using the bell curve for the means value, and like I said, there's some math you can put in there to pick so that you're more like, so that running has even a higher chance. But even if you were just going to do an average on this, you could do an average, a random number by adding them all together. So you get 10 plus 7 plus 5 is 22. You could do 0 to 22, or 0 to 21, but 1 to 22. 1 to 5 would be fetching, and so forth, the last 10. So you can just look at this as what percentage are you going to go for that particular option. And then that gets your random setup in there, and then as you slowly increment these up, you see that if you're idle, where's one? Here we go. Sitting at the end, if you're at the end of wherever you're at, sitting gets a reward of 1. Where's a good one on here? Oh, wrong action. Running for a wrong action gets almost no reward. So that becomes very, very less likely to happen, but it still might happen. It still might have a percentage of coming up. And that's where the random programming and Q-learning comes in. The below table gives us an idea of how many times an action has been taken and how positively correct action or negatively wrong action it is going to affect the next state. So let's go ahead and dive in and pull up a little piece of code and see what this looks like in Python. In this demo, we'll use Q-learning to find the shortest path between two given points.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
If you've seen my videos before, I like to do it in the Anaconda Jupyter Notebook setup, just because it's really easy to see and it's a nice demo. And so here's my Anaconda. This one I'm actually using Python 3.6 environment that I set up in here. And we'll go ahead and launch the Jupyter Notebook on this. And once we're in our Jupyter Notebook, which has the kernel loaded with Python 3, we'll go ahead and create a new Python 3 folder in here. And we'll call this Q Learning. And to start this demo, let's go ahead and import our NumPy array. We'll just run that so it's imported. And like a lot of these model programs, when you're building them, you spend a lot of time putting it all together, and then you end up with this really short answer at the end. And we'll take a look at that as we come into it. So we go ahead and start with our location to state. So we have L1, L2. These are our 9 locations, 1 to 9. And then, of course, the state is going to be 0, 1, 2, 3, 4. It's just a mapping of our location to a integer on there. And then we have our actions. Our actions are simply moving from one location to another. So I can go to location 0, I can go to location 1, 2, 3, 4, 5, 6, 7, 8. So these are my actions I can choose. These are the locations of our state. And if you remember earlier, I'd mentioned that the limitation is that you don't want to put in a continually growing table, because you can actually create a dynamic queue table where you continually add in new values as they arise. Because if you have float values, it just becomes infinite, and then your memory in your computer is gone, or it's not going to work. At the same time, you might think, well, that kind of really limits the queue learning setup. But there are ways to use it in conjunction with other systems. And so you might look at, I've been doing some work in stock. And one of the questions that comes out is to buy or sell the stock. And the state coming in might be, you might take it and create what we call buckets, where anything that you predict is going to return more than a certain amount of money. The error for that stock that you've had in the past, you put those in buckets, and suddenly you start creating these buckets, you realize you do have a limited amount of information coming in. You no longer have a float number. You now have bucket 1, 2, 3, and 4. And then you can take those buckets put them through a Q learning table and come up with the best action. Which stock should I buy? It's like gambling. Stock is pretty much gambling if you're doing day trading. You're not doing long-term investments. And so you can start looking at it like that. A lot of the current feeds say that the best algorithms used for day traders, where you're doing it on your own, is really to ask the question, do I want to trade the stock? Yes or no? And now you have it in a Q learning table, and now you can take it to that next level, and you can see where that can be a really powerful tool at the end of doing a basic linear regression model or something. What is the best investment? And you start getting the best reward on there. And so if we're going to have rewards, these rewards we just create. It says if you're this should match our Q table, because it's going to be you have your state and you have your action across the top, if you remember from the dog. And so we have whatever state we're in going down, and then the next action and what the reward is for it. And of course, if you were actually doing something more connected, your reward would be based on the actual environment it's in. And then we want to go ahead and create a state to location so we can map the indexes. So just like we defined our rewards, we're going to go ahead and do state to location. And you can see here it's a dictionary setup for location state and location to state with items. And we also need to define what we want for learning rates. You remember we had our two different rates as far as like learning from the past and learning from the current. So we'll go ahead and set those to 0.75 and the alpha set to 0.9. And we'll see that when we do the formula. And of course, any of this code, send a note to our Simplilearn team. They'll get you a copy of this code on here. And let's go ahead and pull. There we go. Well, the next two sections. Since we're going to keep it short and sweet. Here we go. So let's go ahead and create our agent. So our agent is going to have our initialization where we send it all the information. We'll define our self gamma equals gamma. We could have just set the gamma rate down here instead of submitting it. It's kind of nice to keep them separate because you can play with these numbers. Our self alpha. Then we have our location state. We'll set that in here. We have our choice of actions. We're going to go ahead and just embed the rewards right into the agent. So obviously this would be coming from somewhere else instead of from self-generated. And then a self state to location equals our state to location dictionary. And we go ahead and create a Q learning table. And I went ahead and just set the Q learning table up to 0 to 0. What the setup is, location to state. How many of them are there? And this just creates an array of 0 to 0 setup on there. And then the big part is the training. We have our rewards new equals a copy of self.rewards. Ending state equals the self location state in location. So this is whatever we end up at. Rewards new equals ending state plus ending state equals 999. Just kind of goes to a dead end. And we start going through iterations. And we'll go ahead, let's do this. So this, we're going to come back and we're going to call it on here. Let me just erase that. Switch it to an arrow. There we go. So what we're doing is we're going to send in here to train it. We're going to say, hey, I want to iterate through this 1,000 times and see what happens. Now this part would actually be, instead of iterating, you might have your external environment and they're going back and forth and you iterate through outside of here. But just for ease of use, our agent's going to come in here and iterate through this. Sometimes I'll put this iteration in here and I'll have it call the environment and say, hey, this is what I did, what's the next state? And the environment does its thing right in here as I iterate through it. And then we want to go ahead and pick a random state to start with. That's what's going on here. You have to start somewhere. And then you have your playable actions. We're going to start with just an empty thing for playable actions and we'll fill that up. So that's what choices I have. And so we're going to iterate through the rewards matrix to get the states, directly reachable from the randomly chosen current state. Assign those states to a list named playable actions. And so you can see here we have range 9. I usually use length of whatever I'm looking at, which is our locations or states as they are. We have a reward, so we want to look at the rewards. The new reward is in our chart here of rewards underscore new current state plus J. J being what is the next state we want to try. And so we go ahead and do our playable actions and we append J. And so what we're doing is we're randomly trying different things in here to see what's going to generate a better reward. And then of course we go ahead and choose our next state. So we have our random choice playable actions. And if you remember, I mentioned on this, let me just go ahead and, let's do a free form. When we were talking about the next state, this right here just does a random selection. Instead of a random selection, you might do something where whatever the best selection is, which might be option 3 here, and then so you can see that it might use a bell curve, and then option 2 over here might have a bell curve like this. Oops. And we start looking at these averages and these spreads, or we can just add them all together and pick the one that kind of goes in all of those. So those are some of the options we have in here. We just go with a random choice. That's usually where you start, play with it. And then we have our reward section down here. And so we want to go ahead and find, well in this case, the temporal difference. So you have your rewards new plus the self gamma, and this is the formula we were looking at. This is Bellman's equation here. So we have our current value, our learning rate, our discount rate involved in there, the reward system coming in for that, and we can add it all together. This is of course our maximum expected future setup in here. So this is all of our Bellman's equation that we're looking at here. And then we come up in here and we update our Q table. That's all this is on this one. And that's right here. We have self Q, current state, next state, and we add in our alpha because we don't want to train all of it at once in case there's slight differentials coming in there. We want to slowly approach the answer. And then we have our route equals the start location, and next location equals start location. So we're just incrementing. We took a step forward. And then finally, remember I was telling you how we're going to do all this and just have some simple thing at the end where it just generates a simple path. We're going to go ahead and get the optimal route. We want to find the best route in here. And so we've created a definition for the optimal route down here. Just scroll down for that. And we get the optimal route. We go ahead and put the information in, including the Q table, self, start location, end location, next location, route, Q. And it says while next location is not equal to end location, so while we can still go, our start location equals self location to state start location. So we already have our best value for the start location. The next state looks at the Q table and says, hey, what's the next one with the best value? And then the next location, we go ahead and pull that in and we just append it. That's what's going on down here. And then our start location equals the next location. And we just go through all the steps. And we'll go ahead and run this. And now that we have our Q table, our Q agent loaded, we're going to go ahead and take our Q agent, load them up with our alpha, gamma that we set up above, along with the location step, action, reward, state to location. And our goal is to plot a course between L9 and L1. And we're going to go through 1,000 iterations on here. And so when I run that, it runs pretty quick. Why is this so fast? If you've been running neural networks and you've been doing all these other models, you sit here and wait a long time. Well, we're a very small amount of data. These are all integers. These aren't float values. The math is not heavy on the processing end, and this is where Q tables are so powerful. If you have a small amount of information coming in, you very quickly get an answer off of this, even though we went through it 1,000 times to train it. And you'll see here we have L9, 8, 5, 2, and 1. and that's based on our reward table we had set up on there. And this is the shortest path going between these different setups in here. And if you remember on our reward table, you can see that if you start here, you can go to here. There's places you can't go. That's how this reward table was set up. So I can only go to certain places. So kind of a little maze set up in there. And you can play with it. This is really fun setup to play with. And you can see how you can take this whole code and you can, like I was saying earlier, you can embed it into another setup and model and predictions where you put things into buckets and you're trying to guess the best investment, the best course of action. Long as you can take that course of action and reduce it down to a yes, no. Or if you're using text, you can use a one-hot encoder, which word is next. There's all kinds of things you can do with a Q table, depending on just how much information you're putting in there. So that wraps up our demo. In this demo, we've found the shortest distance between two paths based on whatever rules or state rewards we have to get from point A to point B and what available actions there are.
Hello and welcome to this tutorial on deep learning. My name is Mohan, and in the next about 1.5 hours I will take you through what is deep learning and into TensorFlow environment to show you an example of deep learning. Now, there are several applications of deep learning, really very interesting and innovative applications, and one of them is identifying the geographic location based on a picture. And how does this work? The way it works is pretty much we train an artificial neural network with millions of images which are tagged, their geolocation is tagged, and then when we feed a new picture, it will be able to identify the geolocation of this new image. For example, you have all these images, especially with maybe some significant monuments or significant locations, and you train with millions of such images, and then when you feed another image, it need not be exactly one of those that you have trained. It can be completely different. That is the whole idea of training. It will be able to recognize, for example, that this is a picture from Paris because it is able to recognize the Eiffel Tower. So the way it works internally, if we have to look a little bit under the hood, is these images are nothing but this is digital information in the form of pixels. So each image could be a certain size. It can be 256 by 256 pixel kind of a resolution, and then each pixel is either having a certain grade of color, and all that is fed into the neural network, and it then gets trained in, and it's able to, based on these pixel information, it is able to get trained and able to recognize the features and extract the features, and thereby it is able to identify these images and the location of these images. And then when you feed a new image, it kind of, based on the training, it will be able to figure out where this image is from. So that's the way, a little bit under the hood, how it works. So what are we going to do in this tutorial? We will see what is deep learning and what do we need for deep learning. And one of the main components of deep learning is neural networks. So we will see what is neural network, what is a perceptron, and how to implement logic gates like AND, OR, NOR, and so on using perceptrons. The different types of neural networks, and then applications of deep learning, and we will also see how neural networks works. So how do we do the training of neural networks? And at the end we will end up with a small demo code which will take you through in TensorFlow. Now, in order to implement deep learning code, there are multiple libraries or development environments that are available, and TensorFlow is one of them. So the focus at the end of this would be on how to use TensorFlow to write a piece of code using Python as a programming language. And we will take up an example which is a very common one, which is like the hello world of deep learning, the handwriting number recognition, which is a MNIST, commonly known as MNIST database. So we will take a look at MNIST database and how we can train a neural network to recognize handwritten numbers. So that's what you will see in this particular video. So let's get started. What is deep learning? Deep learning is like a subset of what is known as a high-level concept called artificial intelligence. You must be already familiar, must have heard about this term artificial intelligence. So artificial intelligence is like the high-level concept, if you will. And in order to implement artificial intelligence applications, we use what is known as machine learning. And within machine learning, a subset of machine learning is deep learning. Machine learning is a little bit more generic concept, and deep learning is one type of machine learning, if you will. And we will see a little later in maybe the following slides a little bit more in detail how deep learning is different from traditional machine learning. But to start with, we can mention here that deep learning uses one of the differentiators between deep learning and traditional machine learning is that deep learning uses neural networks. And we will talk about what are neural networks and how we can implement neural networks and so on and so forth as a part of this tutorial. So a little deeper into deep learning. Deep learning primarily involves working with complicated unstructured data compared to traditional machine learning, where we normally use structured data. In deep learning, the data would be primarily images or voice or maybe text file. And it is a large amount of data as well. And deep learning can handle complex operations. It involves complex operations. And the other difference between traditional machine learning and deep learning is that the feature extraction happens pretty much automatically. In traditional machine learning, feature engineering is done manually. The data scientists, we data scientists have to do feature engineering, feature extraction. But in deep learning, that happens automatically. And of course, deep learning, for large amounts of data, complicated unstructured data, deep learning gives very good performance. Now, as I mentioned, one of the secret sources of deep learning is neural networks. Let's see what neural networks is. Neural networks is based on our biological neurons. The whole concept of deep learning and artificial intelligence is based on human brain, and human brain consists of billions of tiny stuff called neurons, and this is how a biological neuron looks, and this is how an artificial neuron looks. So neural networks is like a simulation of our human brain. Human brain has billions of biological neurons, and we are trying to simulate the human brain using artificial neurons. This is how a biological neuron looks. It has dendrites, and the corresponding component with an artificial neural network is, or an artificial neuron, are the inputs. They receive the inputs through dendrites. And then there is the cell nucleus, which is basically the processing unit in a way. So in artificial neuron also there is a piece which is an equivalent of this cell nucleus, and based on the weights and biases, we will see what exactly weights and biases are as we move. The input gets processed, and that results in an output. In a biological neuron, the output is sent through a synapse, and in an artificial neuron there is an equivalent of that in the form of an output. And biological neurons are also interconnected. So there are billions of neurons which are interconnected. In the same way, artificial neurons are also interconnected. So this output of this neuron will be fed as an input to another neuron, and so on. Now, in neural network, one of the very basic units is a perceptron. So what is a perceptron? A perceptron can be considered as one of the fundamental units of neural networks. It can consist at least of one neuron, but sometimes it can be more than one neuron. But you can create a perceptron with a single neuron, and it can be used to perform certain functions. It can be used as a basic binary classifier. It can be trained to do some basic binary classification, and this is how a basic perceptron looks like. And this is nothing but a neuron. You have inputs x1, x2, to xn, and there is a summation function, and then there is what is known as an activation function. And based on this input, what is known as the weighted sum, the activation function either gives an output like a 0 or a 1. So we say the neuron is either activated or not. So that's the way it works. So you get the inputs. These inputs are, each of the inputs are multiplied by a weight, and there is a bias that gets added, and that whole thing is fed to an activation function, and then that results in an output. And if the output is correct, it is accepted. If it is wrong, if there is an error, then that error is fed back, and the neuron then adjusts the weights and biases to give a new output, and so on and so forth. So that's what is known as the training process of a neuron or a neural network. There's a concept called perceptron learning. So perceptron learning is again one of the very basic learning processes. The way it works is somewhat like this. So you have all these inputs like x1 to xn, and each of these inputs is multiplied by a weight, and then that sum, this is the formula, the equation. So that sum, wi xi sigma of that, which is the sum of all these product of x and w, is added up, and then a bias is added to that. The bias is not dependent on the input or the input values, but the bias is common for one neuron. However, the bias value keeps changing during the training process. Once the training is completed, the values of these weights, W1, W2 and so on, and the value of the bias gets fixed. So that is basically the whole training process, and that is what is known as the perceptron training. So the weights and biases keep changing till you get the accurate output, and the summation is of course passed through the activation function. As you see here, this wixi summation plus b is passed through activation function, and then the neuron gets either fired or not, and based on that there will be an output. That output is compared with the actual or expected value, which is also known as labeled information. So this is the process of supervised learning. So the output is already known, and that is compared, and thereby we know if there is an error or not. And if there is an error, the error is fed back, and the weights and biases are updated accordingly till the error is reduced to the minimum. So this iterative process is known as perceptron learning or perceptron learning rule, and this error needs to be minimized. So till the error is minimized, this iteratively the weights and biases keep changing, and that is what is the training process. So the whole idea is to update the weights and the bias of the perceptron till the error is minimized. The error need not be zero. The error may not ever reach zero, but the idea is to keep changing these weights and bias so that the error is minimum, the minimum possible that it can have. So this whole process is an iterative process, and the iteration continues till either the error is zero, which is an unlikely situation, or it is the minimum possible within these given conditions. Now, in 1943, two scientists, Warren McCulloch and Walter Pitts, came up with an experiment where they were able to implement the logical functions like AND, OR, and NOR using neurons. And that was a significant breakthrough in a sense. So they were able to come up with the most common logical gates. They were able to implement some of the most common logical gates, which could take two inputs like A and B and then give a corresponding result. So for example, in case of an AND gate, A and B, and then the output is AB. In case of an OR gate, it is A plus B, and so on and so forth. And they were able to do this using a single layer perceptron. Now, most of these gates, it was possible to use single layer perceptron except for XOR, and we will see why that is in a little bit. So this is how an AND gate works. The inputs A and B, the output should be fired, or the neuron should be fired only when both the inputs are 1. So if you have 0, 0, the output should be 0. For 0, 1, it is again 0, 1, 0, again 0, and 1, 1, the output should be 1. So how do we implement this with a neuron? So it was found that by changing the values of weights, it is possible to achieve this logic. So for example, if we have equal weights like 0.7, 0.7, and then if we take the sum of the weighted product, so for example 0.7 into 0, and then 0.7 into 0 will give you 0, and so on and so forth. And in the last case, when both the inputs are 1, you get a value which is greater than 1, which is the threshold. So only in this case the neuron gets activated and the output is, there is an output. In all the other cases, there is no output because the threshold value is 1. So this is implementation of an AND gate using a single perceptron or a single neuron. Similarly, an OR gate. In order to implement an OR gate, in case of an OR gate, the output will be 1 if either of these inputs is 1. So for example, 0, 1 will result in 1, or rather, in all the cases it is 1 except for 0, 0. So how do we implement this using a perceptron? Once again, if you have a perceptron with weights, for example 1.2, now if you see here, if in the first case when both are 0, the output is 0. In the second case, when it is 0 and 1, 1.2 into 0 is 0, and then 1.2 into 1 is 1. And in the second case, similarly, the output is 1.2. In the last case, when both the inputs are 1, the output is 2.4. So during the training process, these weights will keep changing, and then at one point where the weights are equal to W1 is equal to 1.2 and W2 is equal to 1.2, the system learns that it gives the correct output. So that is implementation of OR gate using a single neuron or a single layer perceptron. Now XOR gate. This was one of the challenging ones. They tried to implement an XOR gate with a single level perceptron, but it was not possible. And therefore, in order to implement an XOR, so this was like a roadblock in the progress of neural network. However, subsequently they realized that this can be implemented, an XOR gate can be implemented using a multi-level perceptron or MLP. So in this case, there are 2 layers instead of a single layer, and this is how you can implement an XOR gate. So you will see that X1 and X2 are the inputs, and there is a hidden layer, and that's why it is denoted as H3 and H4, and then you take the output of that and feed it to the output at O5 and provide a threshold here. So we will see here that this is the numerical calculation. So the weights are, in this case for X1 it is 20 and minus 20, and once again 20 and minus 20. So these inputs are fed into H3 and H4. So you will see here for H3 the input is 0, 1, 1, 1, and for H4 it is 1, 0, 1, 1. And if you now look at the output, final output, where the threshold is taken as 1, if we use a sigmoid with the threshold 1, you will see that in these 2 cases it is 0, and in the last 2 cases it is 1. So this is the implementation of XOR. In case of XOR, only when one of the inputs is 1, you will get an output. So that is what we are seeing here. If we have either both the inputs are 1 or both the inputs are 0, then the output should be 0. So that is what is an exclusive OR gate. So it is exclusive because only one of the inputs should be 1, and then only you will get an output of 1, which is satisfied by this condition. So this is a special implementation. XOR gate is a special implementation of perceptron. Now that we got a good idea about perceptron, let's take a look at what is a neural network. So we have seen what is a perceptron, we have seen what is a neuron, so we will see what exactly is a neural network. So neural network is nothing but a network of these neurons, and they are different types of neural networks. There are about 5 of them. These are artificial neural network, convolutional neural network, then recursive neural network or recurrent neural network, deep neural network, and deep belief network. So, and each of these types of neural networks have a special, they can solve a special kind of problems. For example, convolutional neural networks are very good at performing image processing and image recognition and so on, whereas RNN are very good for speech recognition and also text analysis and so on. So each type has some special characteristics, and they're good at performing certain special kind of tasks. What are some of the applications of deep learning? Deep learning is today used extensively in gaming. You must have heard about AlphaGo, which is a game created by a startup called DeepMind, which got acquired by Google. And AlphaGo is an AI which defeated the human world champion Lee Sedol in this game of Go. So gaming is an area where deep learning is being extensively used, and a lot of research happens in the area of gaming as well. In addition to that, nowadays there are neural networks or special type called generative adversarial networks, which can be used for synthesizing either images or music or text and so on, and they can be used to compose music. So the neural network can be trained to compose a certain kind of music. And autonomous cars, you must be familiar with Google's self-driving car, and today a lot of automotive companies are investing in this space, and deep learning is a core component of this autonomous cars. The cars are trained to recognize, for example, the road, the lane markings on the road, signals, any objects that are in front, any obstruction, and so on and so forth. So all this involves deep learning. So that's another major application. And robots, we have seen several robots, including Sophia. You may be familiar with Sophia, who was given a citizenship by Saudi Arabia. And there are several such robots which are very human-like, and the underlying technology in many of these robots is deep learning. Medical diagnostics and healthcare is another major area where deep learning is being used. And within healthcare diagnostics, again, there are multiple areas where deep learning and image recognition, image processing can be used. For example, for cancer detection, as you may be aware, if cancer is detected early on, it can be cured. And one of the challenges is in the availability of specialists who can diagnose cancer using these diagnostic images and various scans and so on and so forth. So the idea is to train neural network to perform some of these activities so that the load on the cancer specialist doctors or oncologists comes down. And there is a lot of research happening here, and there are already quite a few applications that are claimed to be performing better than human beings in this space. It can be lung cancer, it can be breast cancer, and so on and so forth. So healthcare is a major area where deep learning is being applied. Let's take a look at the inner working of a neural network. So how does an artificial neural network, let's say, can we train a neural network to identify the shapes like squares and circles and triangles when these images are fed? So this is how it works. Any image is nothing but it is a digital information of the pixels. So in this particular case, let's say this is an image of 28 by 28 pixel, and this is an image of a square. There is a certain way in which the pixels are lit up, and so these pixels have a certain value, maybe from 0 to 256, and 0 indicates that it is black or it is dark, and 256 indicates it is white or lit up. So that is like an indication or a measure of how the pixels are lit up. And so this is an image is, let's say, consisting of information of 784 pixels. So all the information, what is inside this image, can be kind of compressed into these 784 pixels. The way each of these pixels is lit up provides information about what exactly is the image. So we can train neural networks to use that information and identify the images. So let's take a look how this works. So each neuron, the value, if it is close to 1, that means it is white, whereas if it is close to 0, that means it is black. Now this is an animation of how this whole thing works. So these pixels, one of the ways of doing it is we can flatten this image and take this complete 784 pixels and feed that as input to our neural network. The neural network can consist of probably several layers. There can be a few hidden layers, and then there is an input layer and an output layer. Now the input layer takes the 784 pixels as input, the values of each of these pixels, and then you get an output which can be of three types or three classes. One can be a square, a circle, or a triangle. Now, during the training process, there will be initially, obviously, you feed this image and it will probably say it's a circle or it will say it's a triangle. So as a part of the training process, we then send that error back, and the weights and the biases of these neurons are adjusted till it correctly identifies that this is a square. That is the whole training mechanism that happens out here. Now let's take a look at a circle. Same way. So you feed these 784 pixels. There is a certain pattern in which the pixels are lit up, and the neural network is trained to identify that pattern. And during the training process, once again, it would probably initially identify it incorrectly, saying this is a square or a triangle, and then that error is fed back and the weights and biases are adjusted finally till it finally gets the image correct. So that is the training process. So now we will take a look at same way a triangle. So now if you feed another image which is consisting of triangles. So this is the training process. Now we have trained our neural network to classify these images into a triangle or a circle and a square. So now this neural network can identify these three types of objects. Now if you feed another image, and it will be able to identify whether it's a square or a triangle or a circle. Now what is important to be observed is that when you feed a new image, it is not necessary that the image or the triangle is exactly in this position. Now the neural network actually identifies the patterns. So even if the triangle is, let's say, positioned here, not exactly in the middle but maybe at the corner or in the side, it would still identify that it is a triangle. And that is the whole idea behind pattern recognition. So how does this training process work? This is a quick view of how the training process works. So we have seen that a neuron consists of inputs. It receives inputs, and then there is a weighted sum, which is nothing but this xi, wi, summation of that plus the bias. And this is then fed to the activation function, and that in turn gives us a output. Now during the training process, initially obviously when you feed these images, when you send maybe a square, it will identify it as a triangle, and when you maybe feed a triangle, it will identify as a square, and so on. So that error information is fed back, and initially these weights can be random. Maybe all of them have 0 values, and then it will slowly keep changing. So as a part of the training process, the values of these weights, W1, W2 up to Wn, keep changing in such a way that towards the end of the training process, it should be able to identify these images correctly. So till then, the weights are adjusted, and that is known as the training process. So, and these weights are numeric values. It could be 0.5, 0.25, 0.35, and so on. It could be positive or it could be negative, and the value that is coming here is the pixel value. As we have seen, it can be anything between 0 to 1. You can scale it between 0 to 1 or 0 to 256, whichever way, 0 being black and 256 being white, and then all the other colors in between. So that is the input. So these are numerical values. This multiplication or the product WIXI is a numerical value, and the bias is also a numerical value. We need to keep in mind that the bias is fixed for a neuron. It doesn't change with the inputs, whereas the weights are 1 per input. So that is one important point to be noted. So, but the bias also keeps changing. Initially, it will again have a random value, but as a part of the training process, the weights, the values of the weights W1, W2, Wn, and the value of B will change. And ultimately, once the training process is complete, these values are fixed for this particular neuron. W1, W2 up to Wn, and plus the value of the B is also fixed for this particular neuron. And in this way, there will be multiple neurons, and there may be multiple levels of neurons here, and that's the way the training process works. So this is another example of multi-layer. So there are 2 hidden layers in between, and then you have the input layer, values coming from the input layer, then it goes through multiple layers, hidden layers, and then there is an output layer. And as you can see, there are weights and biases for each of these neurons in each layer, and all of them keeps changing during the training process. And at the end of the training process, all these weights have a certain value, and that is a trained model, and those values will be fixed once the training is completed. Alright, then there is something known as activation function. Neural networks consists of one of the components in neural networks is activation function, and every neuron has an activation function, and there are different types of activation functions that are used. It could be a ReLU, it could be sigmoid, and so on and so forth. And the activation function is what decides whether a neuron should be fired or not. So whether the output should be 0 or 1 is decided by the activation function. And the activation function in turn takes the input, which is the weighted sum. Remember, we talked about WIXI plus B. That weighted sum is fed as an input to the activation function, and then the output can be either a 0 or a 1. And there are different types of activation functions which are covered in an earlier video you might want to watch. Alright, so as a part of the training process, we feed the inputs, the labeled data or the training data, and then it gives an output, which is the predicted output by the network, which we indicate as Y hat. And then there is a labeled data, because for supervised learning, we already know what should be the output. So that is the actual output. And in the initial process, before the training is complete, obviously there will be error. So that is measured by what is known as a cost function. So the difference between the predicted output and the actual output is the error. And the cost function can be defined in different ways. There are different types of cost functions. So in this case, it is like the average of the squares of the error. So, and then all the errors are added, which can sometimes be called as sum of squares, sum of square errors, or SSE. And that is then fed as a feedback in what is known as backward propagation or backpropagation. And that helps in the network adjusting the weights and biases. And so the weights and biases get updated till this value, the error value or the cost function, is minimum. Now there is a optimization technique which is used here called gradient descent optimization, and this algorithm works in a way that the error, which is the cost function, needs to be minimized. So there's a lot of mathematics that goes behind this. For example, they find the local minima, the global minima using the differentiation and so on and so forth. But the idea is this. So as a training process, as the part of training, the whole idea is to bring down the error, which is like, let's say this is the function, the cost function. At certain levels it is very high, the cost value of the cost function, the output of the cost function is very high. So the weights have to be adjusted in such a way, and also the bias of course, that the cost function is minimized. So there is this optimization technique called gradient descent that is used, and this is known as the learning rate. Now gradient descent, you need to specify what should be the learning rate, and the learning rate should be optimal, because if you have a very high learning rate, then the optimization will not converge, because at some point it will cross over to the side. On the other hand, if you have very low learning rate, then it might take forever to convert. So you need to come up with the optimum value of the learning rate, and once that is done using the gradient descent optimization, the error function is reduced, and that's like the end of the training process. Alright, so this is another view of gradient descent. So this is how it looks. This is your cost function, the output of the cost function, and that has to be minimized using gradient descent algorithm. And these are like the parameters, and weight could be one of them. So initially we start with certain random values, so cost will be high, and then the weights keep changing, and in such a way that the cost function needs to come down, and at some point it may reach the minimum value, and then it may increase. So that is where the gradient descent algorithm decides that, okay, it has reached a minimum value and it will kind of try to stay here. This is known as the global minima. Now sometimes these curves may not be, just for explanation purpose this has been drawn in a nice way, but sometimes these curves can be pretty erratic. There can be some local minima here, and then there is a peak, and so on. So the whole idea of gradient descent optimization is to identify the global minima and to find the weights and the bias at that particular point. So that's what is gradient descent. And then this is another example. So you can have these multiple local minima. So as you can see, at this point when it is coming down, it may appear like this is a minimum value, but then it is not. This is actually the global minimum value, and the gradient descent algorithm will make an effort to reach this level and not get stuck at this point. So the algorithm is already there and it knows how to identify this global minimum, and that's what it does during the training process. Now, in order to implement deep learning, there are multiple platforms and languages that are available, but the most common platform nowadays is TensorFlow, and so that's the reason we have this tutorial. We have created this tutorial for TensorFlow. So we will take you through a quick demo of how to write a TensorFlow code using Python. And TensorFlow is an open source platform created by Google. So let's just take a look at the details of TensorFlow. And so this is a library, a Python library, so you can use Python or any other languages. It's also supported in other languages like Java and R and so on. But Python is the most common language that is used. So it is a library for developing deep learning applications, especially using neural networks. And it consists of primarily two parts, if you will. So one is the tensors, and then the other is the graphs or the flow. That's the way the name, that's the reason for this kind of a name called TensorFlow. So what are tensors? Tensors are like multi-dimensional arrays, if you will. That's one way of looking at it. So usually you have a one-dimensional array. So first of all, you can have what is known as a scalar, which means a number. And then you have a one-dimensional array, something like this, which means this is like a set of numbers. So that is a one-dimensional array. Then you can have a two-dimensional array, which is like a matrix. And beyond that, sometimes it gets difficult. So this is a three-dimensional array, but TensorFlow can handle many more dimensions. So it can have multi-dimensional arrays. That is the strength of TensorFlow, and which makes computation, deep learning computation, much faster. And that's the reason why TensorFlow is used for developing deep learning applications. So TensorFlow is a deep learning tool, and this is the way it works. So the data basically flows in the form of tensors, and the way the programming works as well is that you first create a graph of how to execute it, and then you actually execute that particular graph in the form of what is known as a session. We will see this in the TensorFlow code as we move forward. So all the data is managed or manipulated in tensors, and then the processing happens using these graphs. There are certain terms called, like for example, ranks of a tensor. The rank of a tensor is like a dimensionality in a way. So for example, if it is scalar, so there is just a number, just one number, the rank is supposed to be 0. And then it can be a one-dimensional vector, in which case the rank is supposed to be 1. And then you can have a two-dimensional vector, typically like a matrix. Then in that case, we say the rank is 2. And then if it is a three-dimensional array, then rank is 3, and so on. So it can have more than 3 as well. So it is possible that you can store multi-dimensional arrays in the form of tensors. So what are some of the properties of TensorFlow? I think today it is one of the most popular platform. TensorFlow is the most popular deep learning platform or library. It is open source. It's developed by Google, developed and maintained by Google, but it is open source. One of the most important things about TensorFlow is that it can run on CPUs as well as GPUs. GPU is a graphical processing unit, just like CPU is central processing unit. Now, in earlier days, GPU was used primarily for graphics, and that's how the name has come. And one of the reasons is that it cannot perform generic activities very efficiently like CPU, but it can perform iterative actions or computations extremely fast and much faster than a CPU. So they are really good for computational activities, and in deep learning there is a lot of iterative computation that happens, so in the form of matrix multiplication and so on. So GPUs are very well suited for this kind of computation, and TensorFlow supports both GPU as well as CPU. And there's a certain way of writing code in TensorFlow we will see as we go into the code. And of course, TensorFlow can be used for traditional machine learning as well, but then that would be an overkill. But just for understanding, it may be a good idea to start writing code for a normal machine learning use case so that you get a hang of how TensorFlow code works, and then you can move into neural networks. So that is just a suggestion, but if you're already familiar with how TensorFlow works, then probably you can go straight into the neural networks part. So in this tutorial, we will take the use case of recognizing handwritten digits. This is like a hello world of deep learning, and this is a nice little, MNIST database is a nice little database that has images of handwritten digits, nicely formatted, because very often in deep learning and neural networks, we end up spending a lot of time in preparing the data for training. And with MNIST database, we can avoid that. You already have the data in the right format, which can be directly used for training. And MNIST also offers a bunch of built-in utility functions that we can straight away use and call those functions without worrying about writing our own functions. And that's one of the reasons why MNIST database is very popular for training purposes. Initially, when people want to learn about deep learning and TensorFlow, this is the database that is used. And it has a collection of 70,000 handwritten digits, and a large part of them are for training. Then you have test, just like in any machine learning process, and then you have validation, and all of them are labeled. So you have the images and their label, and these images, they look somewhat like this. So they are handwritten images collected from a lot of individuals. People have, these are samples written by human beings. They have handwritten these numbers going from 0 to 9. So people have written these numbers, and then the images of those have been taken and formatted in such a way that it is very easy to handle. So that is MNIST database. And the way we are going to implement this in our TensorFlow is we will feed this data, especially the training data, along with the label information. And the data is basically, these images are stored in the form of the pixel information, as we have seen in one of the previous slides. All the images are nothing but, these are pixels. So an image is nothing but an arrangement of pixels, and the value of the pixel, either it is lit up or it is not, or in somewhere in between. That's how the images are stored, and that is how they are fed into the neural network and for training. Once the network is trained, when you provide a new image, it will be able to identify within a certain error, of course. And for this, we will use one of the simpler neural network configurations called softmax. And for simplicity, what we will do is we will flatten these pixels. So instead of taking them in a two-dimensional arrangement, we just flatten them out. So for example, it starts from here. It is a 28 by 28, so there are 784 pixels. So pixel number 1 starts here, it goes all the way up to 28, then 29 starts here and goes up to 56 and so on. And the pixel number 784 is here. So we take all these pixels, flatten them out, and feed them like one single line into our neural network. And this is what is known as a softmax layer. What it does is, once it is trained, it will be able to identify what digit this is. So there are, in this output layer, there are 10 neurons, each signifying a digit. And at any given point of time, when you feed an image, only one of these 10 neurons gets activated. So for example, if this is trained properly, and if you feed a number 9 like this, then this particular neuron gets activated. So you get an output from this neuron. Let me just use a pen or a laser to show you here. Okay, so you're feeding a number 9. Let's say this has been trained, and now if you're feeding a number 9, this will get activated. Now let's say you feed 1 to the trained network, then this neuron will get activated. If you feed 2, this neuron will get activated, and so on. I hope you get the idea. So this is one type of a neural network or an activation function known as softmax layer. So that's what we will be using here. This is one of the simpler ones for quick and easy understanding. So this is how the code would look. We will go into our lab environment in the cloud, and we will show you there directly. But very quickly, this is how the code looks. And let me run you through briefly here, and then we will go into the Jupyter notebook where the actual code is, and we will run that as well. So as a first step, first of all, we are using Python here, and that's why the syntax of the language is Python. And the first step is to import the TensorFlow library. So, and we do this by using this line of code saying import TensorFlow as TF. TF is just for convenience, so you can give any name. And once you do this, TensorFlow is available as an object in the name of TF, and then you can run its methods and accesses its attributes and so on and so forth. And MNIST database is actually an integral part of TensorFlow, and that's again another reason why we, as a first step, we always use this example, MNIST database example. So you just simply import MNIST database as well using this line of code, and you slightly modify this so that the labels are in this format, what is known as one hot true, which means that the label information is stored like an array. And let me just use a pen to show what exactly it is. So when you do this one hot true, what happens is each label is stored in the form of an array of 10 digits, and let's say the number is 8. Okay, so in this case, all the remaining values, there will be a bunch of zeros. So this is like array at position 0, this is at position 1, position 2, and so on and so forth. Let's say this is position 7, then this is position 8. That will be 1 because our input is 8. And again, position 9 will be 0. Okay, so one hot encoding, this one hot encoding true will kind of load the data in such a way that the labels are in such a way that only one of the digits has a value of 1, and that indicates. So based on which digit is 1, we know what is the label. So in this case, the 8th position is 1, therefore we know this sample data, the value is 8. Similarly, if you have a 2 here, let's say, then the labeled information will be somewhat like this. So you have your labels. So you have this as 0, the 0th position. The first position is also 0. The second position is 1 because this indicates number 2. And then you have third as 0 and so on. Okay, so that is the significance of this one hot true. All right, and then we can check how the data is looking by displaying the data. And as I mentioned earlier, this is pretty much in the form of digital form, like numbers. So all these are like pixel values, so you will not really see an image in this format, but there is a way to visualize that image. I will show you in a bit. And this tells you how many images are there in each set. So the training, there are 55,000 images in training, and in the test set there are 10,000, and then validation there are 5,000. So altogether there are 70,000 images. All right, so let's move on, and we can view the actual image by using the matplotlib library, and this is how you can view. This is the code for viewing the images, and you can view them in color or you can view them in grayscale. So the CMap is what tells in what way we want to view it, and what are the maximum values and the minimum values of the pixel values. So these are the max and minimum values, so of the pixel values. So maximum is 1 because this is a scaled value. So 1 means it is white, and 0 means it is black, and in between is, it can be anywhere in between black and white. And the way to train the model, there is a certain way in which you write your TensorFlow code. And the first step is to create some placeholders, and then you create a model. In this case, we will use the softmax model, one of the simplest ones. And placeholders are primarily to get the data from outside into the neural network. So this is a very common mechanism that is used. And then, of course, you will have variables, which are you remember, these are your weights and biases. So in our case, there are 10 neurons, and each neuron actually has 784, because each neuron takes all the inputs. If we go back to our slide here, actually every neuron takes all the 784 inputs. Right? This is the first neuron. It receives all the 784. This is the second neuron. This also receives all the 780. So each of these inputs needs to be multiplied with a weight, and that's what we are talking about here. So this is a matrix of 784 values for each of the neurons, and so it is like a 10 by 784 matrix because there are 10 neurons. And similarly, there are biases. Now remember, I mentioned biases only one per neuron, so it is not one per input, unlike the weights. So therefore, there are only 10 biases because there are only 10 neurons in this case. So that is what we are creating a variable for biases. So this is something little new in TensorFlow. You will see, unlike our regular programming languages where everything is a variable, here the variables can be of three different types. You have placeholders, which are primarily used for feeding data. You have variables, which can change during the course of computation. And then a third type, which is not shown here, are constants. So these are like fixed numbers. All right. So in a regular programming language, you may have everything as variables, or at the most variables and constants. But in TensorFlow, you have three different types: placeholders, variables, and constants. And then you create what is known as a graph. So TensorFlow programming consists of graphs and tensors, as I mentioned earlier. So this can be considered ultimately as a tensor. And then the graph tells how to execute the whole implementation, so that the execution is stored in the form of a graph. And in this case, what we are doing is we are doing a multiplication. TF, you remember this TF was created as a TensorFlow object here. One more level, one more. So TF is available here. Now TensorFlow has what is known as a matrix multiplication, or matmul function. So that is what is being used here in this case. So we are using the matrix multiplication of TensorFlow so that you multiply your input values x with w, right? This is what we were doing, xw plus b. You're just adding b, and this is very similar to one of the earlier slides where we saw sigma xi wi. So that's what we are doing here. Matrix multiplication is multiplying all the input values with the corresponding weights and then adding the bias. So that is the graph we created. And then we need to define what is our loss function and what is our optimizer. So in this case, we again use the TensorFlow's APIs. So tf.nn softmax cross entropy with logits is the API that we will use. And reduce mean is what is like the mechanism whereby which says that you reduce the error. And optimizer for doing reduction of the error, what optimizer are we using? So we are using gradient descent optimizer. We discussed about this in a couple of slides earlier. And for that, you need to specify the learning rate. You remember we saw that there was a slide somewhat like this, and then you define what should be the learning rate, how fast you need to come down. That is the learning rate. And this again needs to be tested and tried, and to find out the optimum level of this learning rate. It shouldn't be very high, in which case it will not converge, or shouldn't be very low, because it will, in that case, it will take very long. So you define the optimizer, and then you call the method minimize for that optimizer, and that will kickstart the training process. And so far we've been creating the graph, and in order to actually execute that graph, we create what is known as a session, and then we run that session. And once the training is completed, we specify how many times, how many iterations we want it to run. So for example, in this case, we are saying 1000 steps. So that is a exit strategy in a way. So you specify the exit condition. So a training will run for 1000 iterations. And once that is done, we can then evaluate the model using some of the techniques shown here. So let us get into the code quickly and see how it works. So this is our cloud environment. Now you can install TensorFlow on your local machine as well. I'm showing this demo on our existing cloud, but you can also install TensorFlow on your local machine, and there is a separate video on how to set up your TensorFlow environment. You can watch that if you want to install your local environment. Or you can go for any cloud service, like for example Google Cloud, Amazon, or Cloud Labs. Any of these you can use and run and try the code. Okay, so it has got started. We will log in. Alright, so this is our deep learning tutorial code, and this is our TensorFlow environment. And so let's get started. We have seen a little bit of a code walkthrough in the slides as well. Now you will see the actual code in action. So the first thing we need to do is import TensorFlow, and then we will import the data. And we need to adjust the data in such a way that the one hot encoding is set to true, one hot encoding, right? As I explained earlier. So in this case, the label values will be shown appropriately. And if we just check what is the type of the data, so you can see that this is a data sets, Python data sets. And if we check the number of images, the way it looks, so this is how it looks. It is an array of type float 32. Similarly, the number, if you want to see what is the number of training images, there are 55,000, then there are test images 10,000, and then validation images 5,000. Now let's take a quick look at the data itself, visualization. So we will use matplotlib for this. And if we take a look at the shape, now shape gives us like the dimension of the tensors or the arrays, if you will. So in this case, the training data set, if we see the size of the training data set using the method shape, it says there are 55,000 and 55,000 by 784. So remember, the 784 is nothing but the 28 by 28, 28 into 28. So that is equal to 784. So that's what it is showing. Now we can take just one image and just see what is the first image and see what is the shape. So again, size, obviously it is only 784. Similarly, you can look at the image itself, the data of the first image itself. So this is how it shows. So large part of it will probably be zeros, because as you can imagine, in the image only certain areas are written, rest is blank. So that's why you will mostly see zeros, either it is black or white. But then there are these values so the values are actually, they are scaled, so their values are between 0 and 1. Okay, so this is what you're seeing. So certain locations there are some values, and then other locations there are zeros. So that is how the data is stored and loaded. If we want to actually see what is the value of the handwritten image, if you want to view it, this is how you view it. So you create, like, do this reshape, and matplotlib has this feature to show you these images. So we will actually use the function called imshow, and then if you pass this parameters appropriately, you will be able to see the different images. Now I can change the values in this position, so which image we are looking at, right? So we can say, if I want to see what is there in maybe 5,000, right? So 5,000 has 3. Similarly, you can just say 5. What is in 5? 5 has 8. What is in 50?
again 8. So basically, by the way, if you're wondering how I'm executing this code, Shift Enter, in case you're not familiar with Jupyter Notebooks, Shift Enter is how you execute each cell, individual cell. And if you want to execute the entire program, you can go here and say run all. So that is how this code gets executed. And here again we can check what is the maximum value and what is the minimum value of this pixel values. As I mentioned, it is scaled, so therefore it is between, the values lie between 1 and 0. Now this is where we create our model. The first thing is to create the required placeholders and variables, and that's what we are doing here as we have seen in the slides. So we create one placeholder and we create two variables, which is for the weights and biases. These two variables are actually matrices, so each variable has 784 by 10 actual values. Okay, so one for this 10 is for each neuron, there are 10 neurons, and 784 is for the pixel values inputs that are given, which is 28 into 28. And the biases, as I mentioned, one for each neuron, so there will be 10 biases. They are stored in a variable by the name B. And this is the graph, which is basically the multiplication of these matrix multiplication of X into W, and then the bias is added for each of the neurons. And the whole idea is to minimize the error. So let me just execute. I think this code is executed. Then we define what is the Y value is basically the label value. So this is another placeholder. We had X as one placeholder and Y underscore true as a second placeholder. And this will have values in the form of 10 digit arrays. And since we said one hot encoded, the position which has a 1 value indicates what is the label for that particular number. All right. Then we have cross entropy, which is nothing but the loss function. And we have the optimizer. We have chosen gradient descent as our optimizer. Then the training process itself. So the training process is nothing but to minimize the cross entropy, which is again nothing but the loss function. So we define all of this in the form of a graph. So up to here, remember what we have done is we have not exactly executed any TensorFlow code till now. We are just preparing the graph, the execution plan. That's how the TensorFlow code works. So the whole structure and format of this code will be completely different from how we normally do programming. So even with people with programming experience may find this a little difficult to understand it, and it needs quite a bit of practice. So you may want to view this video also maybe a couple of times to understand this flow, because the way TensorFlow programming is done is slightly different from the normal programming. Some of you who, let's say, have done maybe Spark programming to some extent will be able to easily understand this. But even in Spark, the programming, the code itself is pretty straightforward. Behind the scenes, the execution happens slightly differently. But in TensorFlow, even the code has to be written in a completely different way. So the code doesn't get executed in the same way as you have written. So that's something you need to understand, and a little bit of practice is needed for this. So far what we have done up to here is creating the variables and feeding the variables, and or rather not feeding but setting up the variables and the graph. That's all. Defining maybe the what kind of a network you want to use. For example, we want to use softmax and so on. So you have created the variables, how to load the data, loaded the data, viewed the data, and prepared everything, but you have not yet executed anything in TensorFlow. Now the next step is the execution in TensorFlow. So the first step for doing any execution in TensorFlow is to initialize the variables. So anytime you have any variables defined in your code, you have to run this piece of code
always. So you need to basically create what is known as a node for initializing. So this is a node. You still are not yet executing anything here. You just created a node for the initialization. So let us go ahead and create that. And here onwards is where you will actually execute your code in TensorFlow. And in order to execute the code, what you will need is a session, TensorFlow session. So tf.session will give you a session, and there are a couple of different ways in which you can do this, but one of the most common methods of doing this is with what is known as a with loop. So you have a with tf.session as ses and with a colon here, and this is like a block, starting of the block, and these indentations tell how far this block goes, and this session is valid till this block gets executed. So that is the purpose of creating this with block. This is known as a with block. So with tf.session as ses, you say ses.run init. Now ses.run will execute a node that is specified here. So for example, here we are saying ses.run. Ses is basically an instance of the session, right? So here we are saying tf.session. So an instance of the session gets created and we are calling that ses. And then we run a node within that, one of the nodes in the graph. So one of the nodes here is init. So we say run that particular node, and that is when the initialization of the variables happens. Now what this does is, if you have any variables in your code, in our case we have w is a variable and b is a variable. So any variables that we created, you have to run this code, you have to run the initialization of these variables, otherwise you will get an error. Okay, so that's what this is doing. Then we, within this with block, we specify a for loop, and we are saying we want the system to iterate for 1000 steps and perform the training. That's what this for loop does. Run training for 1000 iterations. And what it is doing basically is it is fetching the data or these images. Remember, there are about 50,000 images, but it cannot get all the images in one shot because it will take up a lot of memory and performance issues will be there. So this is a very common way of performing deep learning training. You always do in batches. So we have maybe 50,000 images, but you always do it in batches of 100 or maybe 500 depending on the size of your system and so on and so forth. So in this case we are saying, okay, get me 100 images at a time and get me only the training images. Remember, we use only the training data for training purpose, and then we use test data for test purpose. You must be familiar with machine learning, so you must be aware of this, but in case you are not, in machine learning also, this is not specific to deep learning, but in machine learning in general, you have what is known as training data set and test data set. Your available data, typically you will be splitting into two parts and using the training data set for training purpose, and then to see how well the model has been trained, you use the test data set to check or test the validity or the accuracy of the model. So that's what we are doing here. And you observe here that we are actually calling an mnist function here. So we are saying mnist train.next batch. Right? So this is the advantage of using MNIST database, because they have provided some very nice helper functions which are readily available. Otherwise, this activity itself, we would have had to write a piece of code to fetch this data in batches. That itself is a lengthy exercise. So we can avoid all that if we are using MNIST database, and that's why we use this for the initial learning phase. Okay, so when we say fetch, what it will do is it will fetch the images into X and the labels into Y, and then you use this batch of 100 images and you run the training. So ses.run, basically what we are doing here is we are running the training mechanism, which is nothing but it passes this through the neural network, passes the images through the neural network, finds out what is the output, and if the output, obviously initially it will be wrong, so all that feedback is given back to the neural network, and thereby all the W's and B's get updated till it reaches 1000 iterations. In this case, the exit criteria is 1000, but you can also specify probably accuracy rate or something like that for the as an exit criteria. So here it just says that, okay, this particular image was wrongly predicted, so you need to update your weights and biases. That's the feedback given to each neuron, and that is run for 1000 iterations. And typically by the end of this 1000 iterations, the model would have learned to recognize these handwritten images. Obviously it will not be 100% accurate. Okay, so once that is done, so this happens for 1000 iterations. Once that is done, you then test the accuracy of these models by using the test data set. Right? So this is what we are trying to do here. The code may appear a little complicated because if you're seeing this for the first time, you need to understand the various methods of TensorFlow and so on. But it is basically comparing the output with what is actually there. That's all it is doing. So you have your test data, and you're trying to find out what is the actual value and what is the predicted value, and seeing whether they are equal or not, tf.equal, right? And how many of them are correct, and so on and so forth. And based on that, the accuracy is calculated as well. So this is the accuracy, and that is what we are trying to see, how accurate the model is in predicting these numbers or these digits. Okay, so let us run this. This entire thing is in one cell, so we will have to just run it in one shot. It may take a little while. Let us see. And not bad. So it has finished the 1000 iterations, and what we see here as an output is the accuracy. So we see that the accuracy of this model is around 91%. Okay, now which is pretty good for such a short exercise. Within such a short time we got 90% accuracy. However, in real life this is probably not sufficient, so there are other ways to increase the accuracy. We will see probably in some of the later tutorials how to improve this accuracy, how to change maybe the hyperparameters like number of neurons or number of layers and so on and so forth, and so that this accuracy can be increased beyond 90%.
Hello and welcome to the TensorFlow Object Detection API tutorial. In this video, I will walk you through the TensorFlow code to perform object detection in a video. So let's get started. This part is basically you're importing all the libraries. We need a lot of these libraries, for example, NumPy, we need ImageIO, datetime, and pill, and so on and so forth, and of course matplotlib. So we import all these libraries, and then there are a bunch of variables which have some paths for the files and folders. So this is regular stuff. Let's keep moving. Then we import the matplotlib and make it inline, and a few more imports. All right. And then these are some warnings. We can just ignore them. So if I run this code once again, it will go away. All right. And then here onwards, we do the model preparation. Now what we're going to do is we are going to use an existing neural network model. So we are not going to train a new one because that really will take a long time, and it needs a lot of computation resources and so on, and it is really not required. There are already models that have been trained, and in this case it is the SSD with MobileNet. That's the model that we are going to use, and this model is trained to detect objects, and it is readily available as open source, so we can actually use this. And if you want to use other models, there are a few more models available, so you can click on this link here, and let me just take you there. There are a few more models, but we have chosen this particular one because this is faster. It may not be very accurate, but that is one of the faster models. But on this link you will see a lot of other models that are readily available. These are trained models. Some of them would take a little longer, but they may be more accurate and so on, so you can probably play around with these other models. Okay. Okay, so we will be using that model. So this piece of code, this line is basically importing that model, and this is also known as frozen model. The term we use is frozen model. So we import, download and import that, and then we will actually use that model in our code. Alright, so these two cells we have downloaded and imported the model, and then once it is available locally, we will then load this into our program. Alright, so we are loading this into memory, and you need to perform a couple of additional steps, which is basically we need to map the numbers to text. As you may be aware, when we actually build a model and when we run predictions, the model will not give a text. The output of the model is usually a number. So we need to map that to a text. So for example, if the network predicts that the output is 5, we know that 5 means it is an aeroplane. Things like that. So this mapping is done in this next cell. Alright, so let's keep moving. And then we have a helper code which will basically load the data or load the images and transform into NumPy arrays. This is also used in doing object detection in images. So we are actually going to reuse, because video is nothing but it consists of frames, which in turn are images. So we are going to pretty much reuse the same code which we used for doing object detection in images. So this is where the actual detection starts. So here, this is the path for where the images are stored. So this is here once again we are reusing the code which we wrote for detecting objects in an image. So this is the path where the images were stored, and this is the extension, and this was done for about 2 or 3 images. So we will continue to use this, and if we go down, I'll skip this section. So this is the cell where we are actually loading the video and converting it into frames, and then using frame by frame we are detecting the objects in the image. So in this code what we are doing basically is there are a few lines of code. What they do is basically once they find an object, a box will be drawn around those each of those objects, and the input file, the name of the input video file is traffic. It is the extension is MP4, and we have this video reader. It's an excellent object which is basically part of this class called image.io. So we can read and write videos using that, and the video that we are going to use is traffic.mp4. You can use any MP4 file, but in our case I picked up video which has like cars. So let me just show you. So this is in this object detection folder. I have this MP4 file. I'll just quickly play this video. It's a little slow. Yeah, okay. So here we go. This is the video. It's a short one, relatively small video, so that for this particular demo. And what it will do is once we run our code, it will detect each of these cars and it will annotate them as cars. So in this particular video we only have cars. We can later on see with another video. I think I have cat here, so we can also try with that, but let's first check with this traffic video. So let me go back. So we will be reading this frame by frame, and no, actually we will be reading the video file, but then we will be analyzing it frame by frame, and we will be reading them at 10 frames per second. That is the rate we are mentioning here, and analyzing it and then annotating and then writing it back. So you will see that we will have a video file named something like this, traffic_annotated, and we will see the annotated video. So let's go back and run through this piece of code, and then we will come back and see the annotated video. This might take a little while, so I will pause the video after running this particular cell and then come back to show you the results. Alright, so let's go ahead and run it. So it is running now, and it is also important that at the end you close the video writer, so that it is similar to a file pointer. When you open a file, you should also make sure you close it so that it doesn't hog the resources. So it's very similar. So at the end of it, the last piece or last line of code should be video_writer.close. Alright, so I'll pause and then I'll come back. Okay, so I will see you in a little bit. Alright, so now as you can see here, the processing is done, the hourglass has disappeared. That means the video has been processed. So let's go back and check the annotated video. We'll go back to my file manager. So this was the original traffic.mp4, and now you have here traffic underscore annotated mp4. So let's go and run this and see how it looks. You see here, it has got each of these cars are getting detected. Let me pause and show you. So we pause here. It says car 70%. Let us allow it to go a little further. It detects something on top. What is that? Truck. Okay. So I think because of the board on top, it somehow thinks there is a truck. Let's play some more and see if it detects anything else. So this is again a car, looks like. So let us, so this is a car, and it has confidence level of 69%. Okay, this is again a car. Alright, so basically till the end it goes and detects each and every car that is passing by. Now we can quickly repeat this process for another video. Let me just show you the other video, which is a cat. Again, there is this cat is not really moving or anything, but it is just standing there staring and moving a little slowly, and our application will, our network will detect that this is a cat, and even when the cat moves a little bit in the other direction, it will continue to detect and show that it is a cat. Okay, so so this is how the original video is. Let's go ahead and change our code to analyze this one and see if it detects, our network detects this cat. Close this, here we go, and I'll go back to my code. All we need to do is change this traffic to cat. The extension, it will automatically up because it is given here, and then it will run through. So very quickly, once again, what it is doing is this video underscore reader has a neat little feature or interface whereby you can say for frame in video underscore reader. So it will basically provide frame by frame. So you're in a loop frame by frame, and then you take that each frame that is given to you, you take it and analyze it as if it is an image, individual image. So that's the way it works. So it is very easy to handle this. Alright, so now let's once again run just this cell. The rest of the stuff remains the same. So I will run this cell again. It will take a little while, so the hourglasses come back. I will pause and then come back in a little while. Alright, so the processing is done. Let's go and check the annotated video. Go here. So we have cat annotated.mp4. Let's play this. Alright, so you can see here it is detecting the cat, and in the beginning you also saw it detected something else here. There looks like it detected one more object. So let's just go back and see what it has detected here. Let's see. Yes. So what is it trying to show here? It's too small, not able to see, but it is trying to detect something. I think it is saying it is a car. I don't know. Alright, okay, so in this video there's pretty much only one object, which is the cat, and let's wait for some time and see if it continues to detect it when the cat turns around and moves as well. Just in a little bit that's going to happen, and we will see. There we go. And in spite of turning the other way, I think our network is able to detect that it is a cat. So let me freeze and then show here it is actually still continues to detect it as a cat. Alright, so that's pretty much it. I think that's the only object that it detects in this particular video. Okay, so close this. So that's pretty much it. Thank you very much for watching this video, and you have a great day. And in case you have any questions, please put them below the video here, and we will be more than happy to get back to you. And make sure you put your email ID so that we can contact you in case you have any questions. Thank you once again. Bye-bye.
Today we're going to be covering the convolutional neural network tutorial. Do you know how deep learning recognizes the objects in an image? And really, this particular neural network is how image recognition works. It's very central, one of the biggest building blocks for image recognition. It does it using convolution neural network. And over here we have the basic picture of a hummingbird. Pixels of an image fed as input. You have your input layer coming in, so it takes that graphic and puts it into the input layer. You have all your hidden layers, and then you have your output layer, and your output layer, one of those is going to light up and say, oh, it's a bird. We're going to go into depth. We're going to actually go back and forth on this a number of times today. So if you're not catching all the image, don't worry, we're going to get into the details. So we have our input layer accepts the pixels of the image as input in the form of arrays. And you can see up here where they've actually labeled each block of the bird in different arrays. So we'll dive into deep as to how that looks like and how those matrices are set up. Your hidden layer carry out feature extraction by performing certain calculations and manipulation. So this is the part that kind of reorganizes that picture multiple ways until we get some data that's easy to read for the neural network. This layer uses a matrix filter and performs convolution operation to detect patterns in the image. And if you remember that convolution means to coil or to twist. So we're going to twist the data around and alter it and use that operation to detect a new pattern. There are multiple hidden layers like convolution layer. ReLU is how that is pronounced, and that's the rectified linear unit. That has to do with the activation function that's used. Pooling layer also uses multiple filters to detect edges, corners, eyes, feathers, beak, etc. And just like the term says, pooling is pooling information together. And we'll look into that a lot closer here. So if it's a little confusing now, we'll dig in deep and try to get you squared away with that. And then finally there is a fully connected layer that identifies the object in the image. So we have these different layers coming through in the hidden layers, and they come into the final area, and that's where we have, say, one node or one neural network entity that lights up that says it's a bird. What's in it for you? We're going to cover an introduction to the CNN. What is convolution neural network? How CNN recognizes images. We're going to dig deeper into that and really look at the individual layers in the convolutional neural network. And finally, we do a use case implementation using the CNN. We'll begin our introduction to the CNN by introducing the pioneer of convolutional neural network, Yann LeCun. He was the director of Facebook AI Research Group. Built the first convolutional neural network called LeNet in 1988. So these have been around for a while and have had a chance to mature over the years. It was used for character recognition tasks like reading zip code digits. Imagine processing mail and automating that process. CNN is a feed-forward neural network that is generally used to analyze visual images by producing data with a grid-like topology. A CNN is also known as a convnet. And very key to this is we are looking at images. That was what this was designed for, and you'll see the different layers as we dig in mirror some of them are actually now used since we're using TensorFlow and Keras in our code later on. You'll see that some of those layers appear in a lot of your other neural network frameworks. But in this case, this is very central to processing images and doing so in a variety that captures multiple images and really drills down into their different features. In this example here you see flowers of two varieties, orchid and a rose. I think the orchid is much more dainty and beautiful, and the rose smells quite beautiful. I have a couple rose bushes in my yard. They go into the input layer. That data is then sent to all the different nodes in the next layer, one of the hidden layers, based on its different weights and its setup. It then comes out and gives those a new value. Those values then are multiplied by their weights and go to the next hidden layer, and so on. And then you have the output layer, and one of those nodes comes out and says it's an orchid, and the other one comes out and says it's a rose, depending on how well it was trained. What separates the CNN, or the convolutional neural network, from other neural networks is a convolutional operation. Forms the basis of any convolutional neural network. In a CNN, every image is represented in the form of arrays of pixel values. So here we have a real image of the digit 8. That then gets put onto its pixel values, represented in the form of an array. In this case, you have a two-dimensional array. And then you can see in the final end form, we transform the digit 8 into its representational form of pixels of zeros and ones, where the ones represent, in this case, the black part of the 8, and the zeros represent the white background. To understand the convolution neural network, or how that convolutional operation works, we're going to take a sidestep and look at matrices. In this case, we're going to simplify it, and we're going to take two matrices, A and B, of one dimension. Now, kind of separate this from your thinking as we learn that you want to focus just on the matrix aspect of this. And then we'll bring that back together and see what that looks like when we put the pieces for the convolutional operation. Here we've set up two arrays. We have, in this case, they're a single dimension matrix. And we have A equals 5, 3, 7, 5, 9, 7. And we have B equals 1, 2, 3. So in the convolution, as it comes in there, it's going to look at these two, and we're going to start by multiplying them, A times B. And so we multiply the arrays element-wise, and we get 5, 6, 6, where 5 is the 5 times 1, 6 is 3 times 2, and then the other 6 is 2 times 3. And since the two arrays aren't the same size, they're not the same setup, we're going to just truncate the first one, and we're going to look at the second array multiplied just by the first 3 elements of the first array. Now that's going to be a little confusing. Remember, a computer gets to repeat these processes hundreds of times, so we're not going to just forget those other numbers later on. We'll bring those back in. And then we have the sum of the product. In this case, 5 plus 6 plus 6 equals 17. So in our A times B, our very first digit in that matrix of A times B is 17. And if you remember, I said we're not going to forget the other digits. So we now have 3, 2, 5. We move one set over, and we take 3, 2, 5, and we multiply that times B. And you'll see that 3 times 1 is 3, 2 times 2 is 4, and so on and so on. We sum it up, so now we have the second digit of our A times B product in the matrix. And we continue on with that same thing, so on and so on. So then we would go from 375 to 759 to 597. This short matrix that we have for A, we've now covered all the different entities in A that match 3 different levels of B. Now, in a little bit, we're going to cover where we use this math at, this multiplying of matrices and how that works. But it's important to understand that we're going through the matrix and multiplying the different parts to it to match the smaller matrix with the larger matrix. I know a lot of people get lost at is, what's going on here with these matrices? Ooh, scary math. Not really that scary when you break it down. We're looking at a section of A and we're comparing it to B. So when you break that down in your mind like that, you realize, okay, so I'm just taking these two matrices and comparing them, and I'm bringing the value down into one matrix, A times B. We're reducing that information in a way that will help the computer see different aspects. Let's go ahead and flip over again back to our images. Here we are back to our images. Talking about going to the most basic two-dimensional image you can get to. Consider the following two images. The image for the symbol backslash. When you press the backslash, the above image is processed. And you can see there for the image for the forward slash is the opposite. So when we click the forward slash button, that flips. Very basic. We have 4 pixels going in. Can't get any more basic than that. Here we have a little bit more complicated picture. We take a real image of a smiley face. Then we represent that in the form of black and white pixels. So if this was an image in the computer, it's black and white. And like we saw before, we convert this into the zeros and ones. So where the other one would have just been a matrix of just 4 dots, now we have a significantly larger image coming in. So don't worry, we're going to bring this all together here in just a little bit. Layers in convolutional neural network. When we're looking at this, we have our convolution layer. And that really is the central aspect of processing images in the convolutional neural network. That's why we have it. And then that's going to be feeding in. And you have your ReLU layer, which is, as we talked about, the rectified linear unit. We'll talk about that a little bit later. The ReLU is how that layer is activated, is the math behind it, what makes the neurons fire. You'll see that in a lot of other neural networks. When you're using it just by itself, it's for processing smaller amounts of data, where you use the atom activation feature for large data coming in. Now, because we're processing small amounts of data in each image, the ReLU layer works great. You have your pooling layer. That's where you're pooling the data together. Pooling is a neural network term. It's very commonly used. I like to use the term reduce. So if you're coming from the map and reduce side, you'll see that we're mapping all this data through all these networks, and then we're going to reduce it. We're going to pool it together. And then finally we have the fully connected layer. That's where our output's going to come out. So we have started to look at matrices. We've started to look at the convolutional layer and where it fits in and everything. We've taken a look at images. So we're going to focus more on the convolution layer, since this is a convolutional neural network. A convolution layer has a number of filters and perform convolution operation. Every image is considered as a matrix of pixel values. Consider the following 5x5 image whose pixel values are only 0 and 1. Now obviously when we're dealing with color, there's all kinds of things that come in on color processing, but we want to keep it simple and just keep it black and white. And so we have our image pixels, so we're sliding the filter matrix over the image and computing the dot product to detect the patterns. And right here, you're going to ask, where does this filter come from? This is a bit confusing because the filter is going to be derived later on. We build the filters when we program or train our model. So you don't need to worry what the filter actually is, but you do need to understand how a convolution layer works. Is what is the filter doing? Filter, and you'll have many filters. You don't have just one filter. You'll have lots of filters that are going to look for different aspects. And so the filter might be looking for just edges, it might be looking for different parts. We'll cover that in a little bit more detail in a minute. Right now we're just focusing on how the filter works as a matrix. Remember earlier we talked about multiplying matrices together? And here we have our two-dimensional matrix. And you can see we take the filter and we multiply it in the upper left image, and you can see right here 1 times 1, 1 times 0, 1 times 1. We multiply those all together, then sum them, and we end up with a convolved feature of 4. We're going to take that and sliding the filter matrix over the image and computing the dot product to detect patterns. So we're just going to slide this over. We're going to predict the first one and slide it over one notch, predict the second one, and so on all the way through until we have a new matrix. And this matrix, which is the same size as the filter, has reduced the image, and whatever filter, whatever that's filtering out, is going to be looking at just those features reduced down to a smaller matrix. So once the feature maps are extracted, the next step is to move them to the ReLU layer. So the ReLU layer, the next step, first is going to perform an element-wise operation. So each of those maps coming in, if there's negative pixels, so it sets all the negative pixels to 0. And you can see this nice graph where it just zeroes out the negatives, and then you have a value that goes from 0 up to whatever value is coming out of the matrix. This introduces nonlinearity to the network. So up until now, we say linearity. We're talking about the fact that the feature has a value. So it's a linear feature. This feature came up and it has, let's say the feature is the edge of the beak. It's like, or the backslash that we saw. It'll look at that and say, okay, this feature has a value from -10 to 10 in this case. If it was 1, it'd say, yeah, this might be a beak. It might not. It might be an edge right there. A -5 means, no, we're not even going to look at it. It's a 0. And so we end up with an output, and the output takes all these filtered features. Remember, we're not just running one filter on this, we're running a number of filters on this image. And so we end up with a rectified feature map that is looking at just the features coming through and how they weigh in from our filters. So here we have an input of it looks like a toucan bird. Very exotic looking. Real image is scanned in multiple convolution and the ReLU layers for locating features. And you can see up here, it's turned it into a black and white image. And in this case, we're looking in the upper right-hand corner for a feature, and that box scans over. A lot of times it doesn't scan 1 pixel at a time. A lot of times it will skip by 2 or 3 or 4 pixels to speed up the process. That's one of the ways you can compensate if you don't have enough resources on your computation for large images. And it's not just one filter that slowly goes across the image. You have multiple filters that have been programmed in there. So you're looking at a lot of different filters going over the different aspects of the image and just sliding across there and forming a new matrix. One more aspect to note about the ReLU layer is we're not just having one ReLU coming in. So not only do we have multiple features going through, but we're generating multiple ReLU layers for locating the features. That's very important to note. So we have quite a bundle. We have multiple filters, multiple ReLU, which brings us to the next step, forward propagation. Now we're going to look at the pooling layer. The rectified feature map now goes through a pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. That's all we're trying to do. We're trying to take a huge amount of information and reduce it down to a single answer. This is a specific kind of bird. This is an iris. This is a rose. So you have a rectified feature map. And you see here we have a rectified feature map coming in. We set the max pooling with a 2x2 filters and a stride of 2. And if you remember correctly, I talked about not going 1 pixel at a time. Well, that's where the stride comes in. We end up with a 2x2 pooled feature map, but instead of moving 1 over each time and looking at every possible combination, we skip a few there. We go by 2. We skip every other pixel. We just do every other one. And this reduces our rectified feature map, which as you can see over here, 16 by 16 to a 4 by 4. So we're continually trying to filter and reduce our data so that we can get to something we can manage. And over here you see that we have the max 3, 4, 1, and 2. And in the max pooling, we're looking for the max value. A little bit different than what we were looking at before. So coming from the rectified feature, we're now finding the max value and then we're pooling those features together. So instead of thinking of this as image of the map, think of this as how valuable is a feature in that area? How much of a feature value do we have? And we just want to find the best or the maximum feature for that area. They might have that one piece of the filter of the beak said, oh, I see a 1 in this beak in this image, and then it skips over and says, I see a 3 in this image, and it says, oh, this one is rated as a 4. We don't want to sum it together because then you might have like 5 1s and it'll say 5, but you might have 4 zeros and 1 10, and that 10 says, well, this is definitely a beak, where the 1s will say probably not a beak. A little strange analogy since we're looking at a bird, but you can see how that pooled feature map comes down, and we're just looking for the max value in each one of those matrices. Pooling layer uses different filters to identify different parts of the image, like edges, corners, body, feathers, eyes, beak, etc. I know I focus mainly on the beak, but obviously each feature could be a different part of the bird coming in. So let's take a look at what that looks like. Structure of a convolution neural network so far. This is where we're at right now. We have our input image coming in, and then we use our filters, and there's multiple filters on there that are being developed to kind of twist and change that data, and so we multiply the matrices. We take that little filter, maybe it's a 2 by 2, we multiply it by each piece of the image, and if we step 2, then it's every other piece of the image. That generates multiple convolution layers. So we have a number of convolution layers we have set up in there just looking at that data. We then take those convolution layers, we run them through the ReLU setup, and then once we've done through the ReLU setup, and we have multiple ReLUs going on, multiple layers that are ReLU, then we're going to take those multiple layers and we're going to be pooling them. So now we have the pooling layers, or multiple poolings going on. Up until this point, we're dealing with, sometimes it's multiple dimensions. You can have 3 dimensions. Some strange data setups that aren't doing images but looking at other things, they can have 4, 5, 6, 7 dimensions. So right now we're looking at 2D image dimensions coming into the pooling layer. So the next step is we want to reduce those dimensions, or flatten them. So flattening. Flattening is a process of converting all of the resultant 2-dimensional arrays from pooled feature map into a single long continuous linear vector. So over here you see where we have a pooled feature map, maybe that's the bird wing, and it has values 6, 8, 4, 7, and we want to just flatten this out and turn it into 6, 8, 4, 7, or a single linear vector. And we find out that not only do we do each of the pooled feature maps, we do all of them into one long linear vector. So now we've gone through our convolutional neural network part, and we have the input layer into the next setup. All we've done is taken all those different pooling layers and we've flattened them out and combined them into a single linear vector going in. So after we've done the flattening, we have just a quick recap because we've covered so much, so it's important to go back and take a look at each of the steps we've gone through. The structure of the network so far is we have our convolution where we twist it and we filter it and multiply the matrices. We end up with our convolutional layer, which uses the ReLU to figure out the values going out into the pooling. As you have numerous convolution layers that then create numerous pooling layers, pooling that data together, which is the max value, which one we want to send forward. We want to send the best value. And then we're going to take all of that from each of the pooling layers and we're going to flatten it. And we're going to combine them into a single input going into the final layer. Once you get to that step, you might be looking at that going, boy, that looks like the normal input to most neural network. And you're correct, it is. So once we have the flattened matrix from the pooling layer, that becomes our input. So the pooling layer is fed as an input to the fully connected layer to classify the image. And so you can see as our flattened matrix comes in this case we have the pixels from the flattened matrix fed as an input back to our toucan, or whatever that kind of bird that is. I need one of these to identify what kind of bird that is. It comes into our forward propagation network. And that will then have the different weights coming down across. And then finally it selects that that's a bird and that it's not a dog or a cat in this case. Even though it's not labeled, the final layer there in red is our output layer, our final output layer that says bird, cat, or dog. So, quick recap of everything we've covered so far. We have our input image, which is twisted and multiplied. The filters are multiplied times the two matrices multiplied all the filters to create our convolution layer. Our convolution layers, there's multiple layers in there, because it's all building multiple layers off the different filters. Then goes through the ReLU as its activation, and that creates our pooling. And so once we get into the pooling layer, we then on the pooling look for who's the best, what's the max value coming in from our convolution. And then we take that layer and we flatten it, and then it goes into a fully connected layer, our fully connected neural network, and then to the output. And here we can see the entire process, how the CNN recognizes a bird. This is kind of nice because it's showing the little pixels and where they're going. You can see the filter is generating this convolution network, and that filter shows up in the bottom part of the convolution network. And then based on that, it uses the ReLU for the pooling. The pooling then find out which one's the best, and so on, all the way to the fully connected layer at the end, or the classification and the output layer. So that'd be a classification neural network at the end. So we covered a lot of theory up till now, and you can imagine each one of these steps has to be broken down in code. So putting that together can be a little complicated. Not that each step of the process is overly complicated, but because we have so many steps. We have 1, 2, 3, 4, 5 different steps going on here with sub-steps in there. We're going to break that down and walk through that in code. So in our use case implementation using the CNN, we'll be using the CFAR10 dataset from Canadian Institute for Advanced Research for classifying images across 10 categories. Unfortunately, they don't let me know whether it's going to be a toucan or some other kind of bird, but we do get to find out whether it can categorize between a ship, a frog, deer, bird, airplane, automobile, cat, dog, horse, truck. So that's a lot of fun. And if you're looking anything in the news at all of our automated cars and everything else, you can see where this kind of processing is so important in today's world and very cutting edge as far as what's coming out in the commercial deployment. I mean, this is really cool stuff. We're starting to see this just about everywhere in industry. So a great time to be playing with this and figuring it all out. Let's go ahead and dive into the code and see what that looks like when we're actually writing our script. Before we go on, let's do one more quick look at what we have here. Let's just take a look at data batch 1 keys. And remember, in Jupyter Notebook, I can get by with not doing the print statement. If I put a variable down there, it'll just display the variable. And you can see under data batch 1 for the keys, since this is a dictionary, we have the batch 1 label, data, and file names. So you can actually see how it's broken up in our data set. So for the next step, or step 4 as we're calling it, we want to display the image using Matplotlib. There's many ways to display the images. You could even, well, there's other ways to drill into it, but Matplotlib is really good for this. And we'll also look at our first reshape setup, or shaping the data, so you can have a little glimpse into what that means. So we're going to start by importing our matplot, and of course, since I am doing Jupyter Notebook, I need to do the matplot inline command, so it shows up on my page. So here we go. We're going to import matplotlib.pyplot as PLT. And if you remember Matplotlib, the pyplot is like a canvas that we paint stuff onto. And there's my %sign matplotlib inline, so it's going to show up in my notebook. And then of course we're going to import numpy as np for our numbers Python array setup. And let's go ahead and set x equals to data batch 1. So this will pull in all the data going into the x value. And then, because this is just a long stream of binary data, we need to go a little bit of reshaping. So in here we have to go ahead and reshape the data. We have 10,000 images. Okay, that looks correct. And this is kind of an interesting thing. It took me a little bit I had to go research this myself to figure out what's going on with this data. And what it is it's a 32 by 32 picture. And let me do this. Let me go ahead and do a drawing pad on here. So we have 32 bits by 32 bits, and it's in color. So there's 3 bits of color. Now, I don't know why the data is particularly like this. It probably has to do with how they originally encoded it. But most pictures put the 3 afterward. So what we're doing here is we're going to take the shape, we're going to take the data, which is just a long stream of information, and we're going to break it up into 10,000 pieces, and those 10,000 pieces then are broken into 3 pieces each, and those 3 pieces then are 32 by 32. You can look at this like an old-fashioned projector where they have the red screen, or the red projector, the blue projector, and the green projector, and they add them all together, and each one of those is a 32 by 32 bit. So that's probably how this was originally formatted, was in that kind of ideal. Things have changed, so we're going to transpose it, and we're going to take the 3, which was here, and we're going to put it at the end. So the first part is reshaping the data from a single line of bit data, or whatever format it is, into 10,000 by 3 by 32 by 32, and then we're going to transpose the color factor to the last place. So it's the image, then the 32 by 32 in the middle. That's this part right here. And then finally, we're going to take this, which is 3 bits of data, and put it at the end. So it's more like we process images now. And then as type, this is really important that we're going to use an integer 8. You can come in here and you'll see a lot of these, they'll try to do this with a float or a float 64. What you got to remember though is a float uses a lot of memory. So once you switch this into something that's not integer 8, which goes up to 128, you are just going to, the amount of RAM, let me just put that in here, is going to go way up. The amount of RAM that it loads. So you want to go ahead and use this. You can try the other ones and see what happens if you have a lot of RAM on your computer. But for this exercise, this will work just fine. And let's go ahead and take that and run this. So now our X variable is all loaded and it has all the images in it from the batch 1, data batch 1. And just to show what we were talking about with the as type on there, if we go ahead and take X0 and just look for its max value, let me go ahead and run that. You'll see it doesn't, oops, I said 128, it's 255. You'll see it doesn't go over 255 because it's basically an ASCII character is what we're keeping that down to. We're keeping those values down. So they're only 255, 0 to 255 versus float value, which would bring this up exponentially in size. And since we're using the matplot library, we can do, oops, that's not what I wanted. Since we're using the matplot library, we can take our canvas and just do a plt.im for image show, and let's just take a look at what X0 looks like. And it comes in, I'm not sure what that is, but you can see it's a very low grade image broken down to the minimal pixels on there. And if we did the same thing, let's see what 1 looks like. Hopefully it's a little easier to see. Run on there, not enter. Let's hit the run on that. And we can see this is probably a semi-truck. That's a good guess on there. And I can just go back up here instead of typing the same line in over and over. And we'll look at 3. That looks like a dump truck unloading, and so on. You can do any of the 10,000 images. We can just jump to 55. Looks like some kind of animal looking at us there, probably a dog. And just for fun, let's do just one more run on there, and we can see a nice car for our image number 4. So you can see we paste through all the different images. It's very easy to look at them, and they've been reshaped to fit our view and what the matplot library uses for its format. So the next step is we're going to start creating some helper functions. We'll start by a one-hot encoder to help us when we're processing the data. Remember that your labels, they can't just be words. They have to switch it, and we use the one-hot encoder to do that. And then we'll also create a class CFAR helper, so it's going to have an init and a setup for the images. And then finally we'll go ahead and run that code so you can see what that looks like. And then we get into the fun part where we're actually going to start creating our model, our actual neural network model. So let's start by creating our one-hot encoder. We're going to create our own here, and it's going to return an out. And we'll have our vector coming in and our values equal 10. What this means is that we have the 10 values, the 10 possible labels. And remember, we don't look at the labels as a number, because a car isn't one more than a horse. That'd be just kind of bizarre to have horse equals 0, car equals 1, plane equals 2, cat equals 3. So a cat plus a car equals what? So instead, we create a NumPy array of zeros. And there's going to be 10 values, so we have 10 different values in there. So you have 0 or 1. 1 means it's a cat, 0 means it's not a cat. In the next line it might be that 1 means it's a car, 0 means it's not a car. So instead of having one output with a value of 0 to 10, you have 10 outputs with the values of 0 to 1. That's what the one-hot encoder is doing here. And we're going to utilize this in code in just a minute. So let's go ahead and take a look at the next helpers. We have a few of these helper functions we're going to build. And when you're working with a very complicated Python project, dividing it up into separate definitions and classes is very important. Otherwise, it just becomes really ungainly to work with. So let's go ahead and put in our next helper, which is a class. And there's a lot in this class, so we'll break it down here. And let's just start, oops, we can put a space right in there. There we go. Now this is a little bit more readable. Add a second space. So we're going to create our class, the Cipher Helper. And we'll start by initializing it. Now, there's a lot going on in here. So let's start with the init part. Self.I equals 0. That'll come in a little bit. We'll come back to that. in the lower part. We want to initialize our training batches. So when we went through this, there was like a meta batch. We don't need the meta batch, but we do need the data batch 1, 2, 3, 4, 5, and we do not want the testing batch in here. This is just the self all train batches. So we're going to make an array of all those different images. And then of course we left the test batch out, so we have our self.test batch. We're going to initialize the training images and the training labels, and also the test images and the test labels. So this is just to initialize these variables in here. Then we create another definition down here, and this is going to set up the images. And let's just take a look and see what's going on in there. Now we could have all just put this as part of the init part, since this is all just helper stuff, but breaking it up again makes it easier to read. It also makes it easier when we start executing the different pieces to see what's going on. So that way we have a nice print statement to say, hey, we're now running this and this is what's going on in here. We're going to set up the self-training images at this point, and that's going to go to a NumPy array VStack. And in there we're going to load up, in this case, the data for D and self all train batches. Again, that points right up to here. So we're going to go through each one of these files, or each one of these data sets, because they're not a file anymore. We've brought them in. Data batch 1 points to the actual data. And so our self-training images is going to stack them all into a NumPy array. And then it's always nice to get the training length, and that's just a total number of self-training images in there. And then we're going to take the self-training images. And let me switch marker colors, because I am getting a little too much on the markers up here. Oops, there we go. Bring down our marker change so we can see it a little better. And at this point, this should look familiar. Where did we see this? Well, when we wanted to look at this above, and we wanted to look at the images in the Matplot library, we had to reshape it. So we're doing the same thing here. We're taking our self-training images, and based on the training length, total number of images, because we stacked them all together, so now it's just one large file of images, we're going to take and look at it as our 3 video cameras that are each displaying 32 by 32, and we're going to switch that around so that now we have each of our images that stays the same place, and then we have our 32 by 32, and then by our 3. Our 3 different values for the color. And of course we want to go ahead and they run this where we say divide by 255. That was from earlier. It just brings all the data into 0 to 1. That's what this is doing. So we're turning this into a 0 to 1 array, which is all the pictures 32 by 32 by 3. And then we're going to take the self-training labels, and we're going to pump those through our one-hot encoder we just made, and we're going to stack them together. And again, we're converting this into an array that goes from, instead of having horse equals 1, dog equals 2, and then horse plus dog would equal 3, which would be cat. No, it's going to be an array of 10 where each one is 0 to 1. Then we want to go ahead and set up our test images and labels. And when we're doing this, you're going to see it's the same thing we just did with the rest of them. We just changed colors right here. This is no different than what we were doing up here with our training set. We're going to stack the different images. We're going to get the length of them so we know how many images are in there. You certainly could add them by hand, but it's nice to let the computer do it, especially if it ever changes on the other end and you're using other data. And again, we reshape them and transpose them, and we also do the one-hot encoder. Same thing we just did on our training images. So now our test images are in the same format. So now we have a definition which sets up all our images in there. And then the next step is to go ahead and batch them, or next batch. And let's do another breakout here for batches, because this is really important to understand. It tends to throw me for a little loop when I'm working with TensorFlow or Keras or a lot of these. We have our data coming in. If you remember, we had like 10,000 photos. Let me just put 10,000 down here. We don't want to run all 10,000 at once, so we want to break this up into batch sizes. And you also remember that we had the number of photos, in this case length of test or whatever number is in there. We also have 32 by 32 by 3. So when we're looking at the batch size, we want to change this from 10,000 to a batch of, in this case I think we're going to do batches of 100. So we want to look at just 100, the first 100 of the photos. And if you remember, we set self-I equal to 0. So what we're looking at here is we're going to create X We're going to get the next batch from the very initialized. We've already initialized it for 0. So we're going to look at x from 0 to batch size, which we set to 100. So just the first 100 images. And then we're going to reshape that into, and this is important to let the data know, that we're looking at 100 by 32 by 32 by 3. Now, we've already formatted it to the 32 by 32 by 3. This just sets everything up correctly so that X has the data in there in the correct order and the correct shape. And then the Y, just like the X, is our labels. So our training labels, again, they go from 0 to batch size. In this case, they do self I plus batch size because the self I is going to keep changing. And then finally, we increment the self I because we have 0. So the next time we call it, we're going to get the next batch size. And so basically, we have X and Y. X being the photograph data coming in and Y being the label. And that, of course, is labeled through one hot encoder. So if you remember correctly, if it was, say, horse is equal to 0, it would be 1 for the 0 position, since this is the horse, and then everything else would be 0 in here. Let me just put lines through there. There we go. There's our array. Hard to see that array. So let's go ahead and take that, and we're going to finish loading it, since this is our class. And now we're armed with all this, our setup over here. Let's go ahead and load that up. And so we're going to create a variable ch with the CFAR helper in it. And then we're going to do ch.setupImages. Now we could have just put all of the setup images under the init, but by breaking this up into 2 parts, it makes it much more readable. And also, if you're doing other work, there's reasons to do that as far as the setup. Let's go ahead and run that. And you can see where it says setting up training images and labels, setting up test images. And that's one of the reasons we broke it up, is so that if you're testing this out, you can actually have print statements in there telling you what's going on, which is really nice. They did a good job with this setup. I like the way that it was broken up in the back. And then one quick note, you want to remember that batch, to set up the next batch, since we have to run batch equals ch next batch of 100, because we're going to use the 100 size. But we'll come back to that. We're going to use that. Just remember that that's part of our code we're going to be using in a minute from the definition we just made. So now we're ready to create our model. First thing we want to do is we want to import our TensorFlow as TF. I'll just go ahead and run that so it's loaded up. And you can see we got a warning here. That's because they're making some changes. It's always growing, and they're going to be depreciating one of the values from float 64 to float type, or is treated as an NP float 64. Nothing to really worry about, because this doesn't even affect what we're working on, because we've set all of our stuff to a 255 value, or 0 to 1. And do keep in mind that 0 to 1 value that we converted to 255 is still a float value, but it'll easily work with either the NumPy float 64 or the NumPy D-type float. It doesn't matter which one it goes through, so the depreciation would not affect our code as we have it. And in our TensorFlow, we'll go ahead, let me just increase the size in there just a moment so you can get a better view of the what we're typing in. We're going to set a couple placeholders here. And so we're going to set x equals TF placeholder TF float 32. We just talked about the float 64 versus the NumPy float. We're actually just going to keep this at float 32. More than significant number of decimals for what we're working with. And since it's a placeholder, we're going to set the shape equal to, and we've set it equal to none, because at this point we're just holding the place on there. We'll be setting up as we run the batches. That's what that first value is. And then 32 by 32 by 3, that's what we reshaped our data to fit in. And then we have our y true equals placeholder TF float 32, and the shape equals none, comma 10. 10 is the 10 different labels we have, so it's an array of 10. And then let's create one more placeholder. We'll call this hold prob, or hold probability. And we're going to use this. We don't have to have a shape or anything for this. This placeholder is for what we call dropout. If you remember from our theory before, we drop out so many nodes is looking at, or the different values going through, which helps decrease bias. So we need to go ahead and put a placeholder for that also. And we'll run this, so it's all loaded up in there. So we have our 3 different placeholders. And since we're in TensorFlow, when you use Keras, it does some of this automatically, but we're in TensorFlow direct. Keras sits on TensorFlow. We're going to go ahead and create some more helper functions. We're going to create something to help us initialize the weights, initialize our bias. If you remember that each layer has to have a bias going in. we're going to go ahead and work on our convolutional 2D, our max pool. So we have our pooling layer, our convolutional layer, and then our normal full layer. So we're going to go ahead and put those all into definitions. And let's see what that looks like in code. And you can also grab some of these helper functions from the MNIST, the NIST setup. Let me just put that in there if you're under the TensorFlow. So a lot of these are already in there, but we're going to go ahead and do our own. And we're going to create our init weights. And one of the reasons we're doing this is so that you can actually start thinking about what's going on in the back end. So even though there's ways to do this with an automation, sometimes these have to be tweaked and you have to put in your own setup in here. Now we're not going to be doing that. We're just going to recreate them for our code. And let's take a look at this. We have our weights, and so what comes in is going to be the shape, and what comes out is going to be random numbers. So we're going to go ahead and just init some random numbers based on the shape with a standard deviation of 0.1. Kind of a fun way to do that. And then the TF variable, init random distribution. So we're just creating a random distribution on there. That's all that is for the weights. Now, you might change that. You might have a higher standard deviation. In some cases, you actually load preset weights. That's pretty rare. Usually you're testing that against another model or something like that, and you want to see how those weights configure with each other. Now remember, we have our bias, so we need to go ahead and initialize the bias with a constant. In this case, we're using 0.1. A lot of times the bias is just put in as 1, and then you have your weights to add on to that. But we're going to set this as 0.1. So we want to return a convolutional 2D, in this case a neural network. This is would be a layer on here. What's going on with the conv2D is we're taking our data coming in, we're going to filter it. Strides, if you remember correctly, strides came from, here's our image, and then we only look at this picture here, and then maybe we have a stride of 1, so we look at this picture here, and we continue to look at the different filters going on there. The other thing this does is that we have our data coming in as 32 by 32 by 3. And we want to change this so that it's just, this is 3 dimensions, and it's going to reformat this as just 2 dimensions. So it's going to take this number here and combine it with the 32 by 32. So this is a very important layer here because it's reducing our data down using different means. And it connects down, I'm just going to jump down one here. It goes with the convolutional layer. So you have your kind of your pre-formatting and the setup, and then you have your actual convolution layer that goes through on there. And you can see here we have init weights by the shape, init bias, shape of 3, because we have the 3 different, here's our 3 again. And then we return the TFNN ReLU with the convention 2D, so this convolutional has this feeding into it. Right there, it's using that as part of it. And of course the input is the XY plus B, the bias. So that's quite a mouthful, but these two are the keys here to creating the convolutional layers there. The convolutional 2D coming in, and then the convolutional layer, which then steps through and creates all those filters we saw. Then of course we have our pooling. So after each time we run it through the conventional layer, we want to pool the data. If you remember correctly on the pool side, and let me just get rid of all my marks, it's getting a little crazy there. And in fact, let's go ahead and jump back to that slide. Let's just take a look at that slide over here. So we have our image coming in. We create our convolutional layer with all the filters. Remember, the filters go, the filters coming in here, and it looks at these 4 boxes. And then if it's a step, let's say step 2, it then goes to these 4 boxes, and then the next step, and so on. So we have our convolutional layer that we generate, or convolutional layers. They use the ReLU function. There's other functions out there. For this, though, the ReLU is the one that works the best, at least so far. I'm sure that will change. And then we have our pooling. Now, if you remember correctly, the pooling was max. So if we had the filter coming in, and they did the multiplication on there, and we have a 1, and maybe a 2 here, and another 1 here, and a 3 here, 3 is the max. And so out of all of these, you then create an array that would be 3, and if the max is over here 2 or whatever it is, that's what goes into the pooling, and what's going on in our pooling. So again, we're reducing that data down. We're reducing it down as small as we can, and then finally we're going to flatten it out into a single array, and that goes into our fully connected layer. And you can see that here in the code. Right here we're going to create our normal full layer. So at some point we're going to take from our pooling layer, this will go into some kind of flattening process, and then that will be fed into the different layers going in down here. And so we have our input size. You'll see our input layer get shape, which is just going to get the shape for whatever's coming in. And then input size, initial weights is also based on the input layer coming in. And the input size down here is based on the input layer shape. So we're just going to already use the shape and already have our size coming in. And of course, you have to make sure you init the bias. Always put your bias on there. And we'll do that based on the size. So this will return tf.matmul input layer W plus B. This is just a normal full layer. That's what this means right down here. That's what we're going to return. So that was a lot of steps we went through. Let's go ahead and run that. So those are all loaded in there. And let's go ahead and create the layers. Let's see what that looks like. Now that we've done all the heavy lifting and everything, we get to do all the easy part. Let's go ahead and create our layers. We'll create a convolution layer 1 and 2 different convolutional layers, and then we'll take that and we'll flatten that out, create a reshape pooling in there for our reshape, and then we'll have our full layer at the end. So let's start by creating our first convolutional layer. Then we come in here, and let me just run that real quick. And I want you to notice on here the 3 and the 32. This is important because coming into this convolutional layer, we have 3 different channels and 32 pixels each. So that has to be in there. The 4 and 4 you can play with. This is your filter size. So if you remember, you have a filter and you have your image, and the filter slowly steps over and filters out this image depending on what your step is. For this particular setup, 4 is just fine. That should work pretty good for what we're doing and for the size of the image. And then of course at the end, once you have your convolutional layer set up, you also need to pool it, and you'll see that the pooling is automatically set up so that it would see the different shape based on what's coming in. So here we have max 2x2, and we put in the convolutional 1 that we just created, the convolutional layer we just created goes right back into it. And that right up here, as you can see, is the X. It's coming in from here, so notice to look at the first model and set the data accordingly. Set that up so it matches. And we went ahead and ran this already. I think I ran it. Let me go and run it again. And if we're going to do one layer, let's go ahead and do a second layer down here. And it's we'll call it Convo 2. It's also a convolutional layer on this. And you'll see that we're feeding convolutional 1 in, the pooling. So it goes from convolutional 1 into convolutional 1 pooling, from convolutional 1 pooling into convolutional 2, and then from convolutional 2 into convolutional 2 pooling. And we'll go ahead and take this and run this. So these variables are all loaded into memory. And for our flattened layer, let's go ahead and we'll do, since we have 64 coming out of here and we have 4x4 going in, let's do 8x8x64. So let's do 4096. This is going to be the flat layer. So that's how many bits are coming through on the flat layer. And we'll reshape this. So we'll reshape our Convo 2 pooling, and that will feed into here, the Convo 2 pooling, and then we're going to set it up as a single layer that's 4096 in size. That's what that means there. We'll go ahead and run this. So we've now created this variable, the Convo 2 flat, and then we have our first full layer. This is the final neural network where we have the flat layer going in. And we're going to again use the ReLU for our setup on there in a neural network for evaluation. And you'll notice that we're going to create our first full layer. Our normal full layer, that's our definition. So we created that. That's creating the normal full layer. And our input for the data comes right here from this goes right into it. The Convo 2 flat. So this tells it how big the data is. And we're going to have it come out. It's going to have 1024. That's how big the layer is coming out. We'll go ahead and run this. So now we have our full layer 1. And with the full layer 1, we want to also define the full 1 dropout to go with that. So our full layer 1 comes in, keep probability equals hold probability. Remember we created that earlier. And the full layer 1 is what's coming into it. And this is going backwards and training the data. We're not training every weight. We're only training a percentage of them each time, which helps get rid of the bias. So let me go ahead and run that. And finally, we'll go ahead and create a Y-predict, which is going to equal the normal full 1 dropout and 10, because we have 10 labels in there. Now, in this neural network, we could have added additional layers. That would be another option to play with. You can also play with, instead of 1024, you can use other numbers for the way that sets up on what's coming out and going into the next one. We're only going to do just the 1 layer and the 1 layer dropout. And you can see if we did another layer, it'd be real easy just to feed in the full 1 dropout into full layer 2. And then full layer 2 dropout would have full layer 2 feed into it. And then you'd switch that here for the Y prediction. For right now, this is great. This particular data set is tried and true, and we know that this will work on it. And if we just type in Y predict and we run that, we'll see that this is a tensor object, shape $10, D-type 32. A quick way to double check what we're working on. So now we've got all of our, we've done a setup all the way to the Y predict, which we just did. We want to go ahead and apply the loss function and make sure that's set up in there. Create the optimizer, and then train our optimizer, and create a variable to initialize all the global TF variables. So before we dive into the loss function, let me point out one quick thing, or just kind of a rehab over a couple things. And that is, when we're playing with these setups, we pointed out up here we can change the 4-4 and use different numbers there. They change your outcome. So depending on what numbers you use here will have a huge impact on how well your model fits. And that's the same here with the 1024 also. This is also another number that if you continue to raise that number, you'll get possibly a better fit. You might overfit. And if you lower that number, you'll use less resources. And generally, you want to use this in the exponential growth. And exponential being 2, 4, 8, 16. And in this case, the next one down would be 5, 12. You can use any number there, but those would be the ideal numbers when you look at this data. So the next step in all this is we need to also create a way of tracking how good our model is. And we're going to call this a loss function. And so we're going to create a cross-entropy loss function. And so before we discuss exactly what that is, let's take a look and see what we're feeding it. We're going to feed it our labels, and we have our true labels and our prediction labels. So coming in here is the two different variables we're sending in, or the two different probability distributions, is one that we know is true and what we think it's going to be. Now this function right here, when they talk about cross-entropy, in information theory, the cross-entropy between two probability distributions over the same underlying set of events measures the average number of bits needed to identify an event drawn from the set. That's a mouthful. Really, we're just looking at the amount of error in here. How many of these are correct and how many of these are incorrect? So how much of it matches? And we're going to look at that. We're just going to look at the average. That's what the mean, the reduced to the mean means here. So we're looking at the average error on this. And so the next step is we're going to take the error. We want to know our cross entropy, or our loss function, how much loss we have. That's going to be part of how we train the model. So when you know what the loss is and we're training it, you feed that back into the back propagation setup. And so we want to go ahead and optimize that. Here's our optimizer. We're going to create the optimizer using an atom optimizer. Remember, there's a lot of different ways of optimizing the data. Atom's the most popular used. So our optimizer is going to equal the TF train atom optimizer. If you don't remember what the learning rate is, let me just pop this back into here. Here's our learning rate. When you have your weights, you have all your weights in your different nodes that are coming out. Here's our node coming out, and it has all its weights. And then the error is being sent back through in reverse on our neural network. So we take this error and we adjust these weights based on the different formulas. In this case, the atom formula is what we're using. We don't want to just adjust them completely. We don't want to change this weight so it exactly fits the data coming through. Because if we made that kind of adjustment, it's going to be biased to whatever the last data we sent through is. Instead, we're going to multiply that by 0.001 and make a very small shift in this weight. So our delta W is only 0.001 of the actual delta W of the full change we're going to compute from the atom. And then we want to go ahead and train it. So our training, or set up a training variable or function. And this is going to equal our optimizer minimize cross entropy. And we make sure we go ahead and run this. So it's loaded in there. And then we're almost ready to train our model. But before we do that, we need to create one more variable in here. And we're going to create a variable to initialize all the global TF variables. And when we look at this, the TF global variable initializer, this is a TensorFlow object. It goes through there and it looks at all our different setup that we have going under our TensorFlow, and then initializes those variables. So it's kind of like a magic wand because it's all hidden in the back end of TensorFlow. All you need to know about this is that you have to have the initialization on there which is an operation, and you have to run that once you have your setup going. So we'll go ahead and run this piece of code, and then we're going to go ahead and train our data. So let me run this so it's loaded up there. And so now we're going to go ahead and run the model by creating a graph session. Graph session is a TensorFlow term. So you'll see that coming up. It's one of the things that throws me because I always think of GraphX and Spark and Graph as just general graphing, but they talk about a graph session. So we're going to go ahead and run the model, and let's go ahead and walk through this, what's going on here. And let's paste this data in here, and here we go. So we're going to start off with a TF session as ses. So that's our actual TF session that we've created. So we're right here with the TF session. Our session we're creating, we're going to run TF global variable initializer. So right off the bat, we're initializing our variables here. And then we have for I in range 500. So what's going on here, remember 500, we're going to break the data up and we're going to batch it in at 500 points each. We've created our session run, so we're going to do with TF session as session right here. We've created our variable session, and then we're going to run and we're going to go ahead and initialize it. So we have our TF global variables initializer that we created. That initializes our session in here. The next thing we're going to do is we're going to go for I in range of 500, batch equals ch.next batch. So if you remember correctly, this is loading up 100 pictures at a time. And this is going to loop through that 500 times. So we are literally doing, 500 times 100 is 50,000. So that's 50,000 pictures we're going to process right there. In the first process is we're going to do a session run. We're going to take our train. We created our train variable or optimizer in there. We're going to feed it the dictionary. We had our feed dictionary that we created, and we have x equals batch 0 coming in, y true, batch 1, hold the probability, 0.5. And then just so that we can keep track of what's going on, we're going to, every 100 steps, we're going to run a print. So currently on step, format, accuracy is, and we're going to look at matches equals tf argument y prediction 1, tf.arg max y true, comma 1. So we're going to look at this as how many matches it has. And here our ACC, all we're doing here is we're going to take the matches, how many matches they have, it generates a chart. We're going to convert that to float. That's what the TF cast does. And then we just want to know the average. We just want to know the average of the accuracy. And then we'll go ahead and print that out, print session run, accuracy, feed dictionary. So it takes all this and it prints out our accuracy on there. So let's go ahead and take this, oops, flip screens there. Let's go ahead and take this and let's run it. And this is going to take a little bit to run. So let's see what happens on my old laptop. And we'll see here that we have our current, we're currently on step 0. It takes a little bit to get through the accuracy. And this will take just a moment to run. We can see that on our step 0, it has an accuracy of 0.1 or 0.1028. And as it's running, we'll go ahead, you don't need to watch it run all the way, but this accuracy is going to change a little bit up and down. So we've actually lost some accuracy during our step 2. But we'll see how that comes out. Let's come back after we run it all the way through and see how the different steps come out. I was actually reading that backwards. The way this works is the closer we get to 1, the more accuracy we have. So you can see here we've gone from a 0.1 to a 0.39, and we'll go ahead and pause this and come back and see what happens when we're done with the full run. Alright, now that we've prepared the meal, got it in the oven, and pulled out my finished dish here, if you've ever watched any of the old cooking shows, let's discuss a little bit about this accuracy going on here, and how do you interpret that? We've done a couple things. First, we've defined accuracy. The reason I got it backwards before is you have loss or accuracy. And with loss, you'll get a graph that looks like this. It goes, oops, that's an S, by the way. There we go. You get a graph that curves down like this. And with accuracy, you get a graph that curves up. This is how good it's doing. Now, in this case, 1 is supposed to be really good accuracy. That means it gets close to 1, but it never crosses 1. So if you have an accuracy of 1, that is phenomenal. In fact, that's pretty much unheard of. And the same thing with loss. If you have a loss of 0, that's also unheard of. And the 0 is actually on this axis right here as we go in there. So how do we interpret that? Because, if I was looking at this and I go, oh, 0.51, that's 51%. You're doing 50-50. No, this is not percentage. Let me just put that in there. It is not percentage. This is logarithmic. What that means is that 0.2 is twice as good as 0.1. And when we see 0.4, that's twice as good as 0.2. Real way to convert this into a percentage. You really can't say this is a direct percentage conversion. What you can do, though, is in your head, if we were to give this a percentage, we might look at this as 50%, we're just guessing, equals 0.1. And if 50% roughly equals 0.1, that's where we started up here at the top. Remember at the top here, here's our 0.1028. The accuracy of 50%, then 75% is about 0.2, and so on and so on. Don't quote those numbers because that doesn't work that way. They say that if you have 0.95, that's pretty much saying 100%. And if you have anywhere between, you'd have to go look this up. Let me go ahead and remove all my drawings there. So the magic number is 0.5. We really want to be over a 0.5 in this whole thing. And we have both 0.5004. Remember, this is accuracy. If we were looking at loss, then we would be looking the other way. But 0.0, instead of how high it is, we want how low it is. But with accuracy, being over a 0.5 is pretty valid. That means this is pretty solid. And if you get to a 0.95, then it's a direct correlation. That's what we're looking for here in these numbers. You can see we finished with this model at 0.5135, so still good. And if we look at when they ran this in the other end, remember there's a lot of randomness that goes into it when we seed the weights. They got 0.5251, so a little better than ours. But that's fine. You'll find your own comes up a little bit better or worse depending on just that randomness. And so we've gone through the whole model. We trained the model, and we've also gone through on every 100th run to test the model to see how accurate it is. Welcome to the RNN tutorial. That's the recurrent neural network. So we talk about a feed-forward neural network. In a feed-forward neural network, information flows only in the forward direction, from the input nodes through the hidden layers, if any, and to the output nodes. There are no cycles or loops in the network. And so you can see here we have our input layer. I was talking about how it just goes straight forward into the hidden layers. So each one of those connects and then connects to the next hidden layer, connects to the output layer. And of course we have a nice simplified version where it has a predicted output, and they refer to the input as X a lot of times and the output as Y. Decisions are based on current input, no memory about the past, no future scope. Why recurrent neural network? Issues in feed-forward neural network. So one of the biggest issues is because it doesn't have a scope of memory or time, a feed-forward neural network doesn't know how to handle sequential data. It only considers only the current input. So if you have a series of things, and because 3 points back affects what's happening now, and what your output affects what's happening, that's very important. So whatever I put as an output is going to affect the next one. A feed-forward doesn't look at any of that. It just looks at this is what's coming in. And it cannot memorize previous inputs. So it doesn't have that list of inputs coming in. Solution to feed-forward neural network. You'll see here where it says recurrent neural network, and we have our X on the bottom going to H, going to Y. That's your feed forward. But right in the middle it has a value C, so there's a whole other process. So it's memorizing what's going on in the hidden layers, and the hidden layers, as they produce data, feed into the next one. So your hidden layer might have an output that goes off to Y, but that output goes back into the next prediction coming in. What this does is this allows it to handle sequential data. It considers the current input and also the previously received inputs. And if we're going to look at general drawings and solutions, we should also look at applications of the RNN. Image captioning. RNN is used to caption an image by analyzing the activities present in it. A dog catching a ball in midair. That's very tough. I mean, we have a lot of stuff that analyzes images of a dog and the image of a ball, but it's able to add one more feature in there that's actually catching the ball in midair. Time series prediction. Any time series problem like predicting the prices of stocks in a particular month can be solved using RNN. And we'll dive into that in our use case and actually take a look at some stock. One of the things you should know about analyzing stock today is that it is very difficult. And if you're analyzing the whole stock, the stock market at the New York Stock Exchange in the U.S. produces somewhere in the neighborhood, if you count all the individual trades and fluctuations by the second, it's like 3 terabytes a day of data. So we're only going to look at one stock. Just analyzing one stock is really tricky. In here, we'll give you a little jump on that, so that's exciting, but don't expect to get rich off of it immediately. Another application of the RNN is natural language processing. Text mining and sentiment analysis can be carried out using RNN for natural language processing. And you can see right here the term natural language processing, when you stream those three words together, is very different than if I said processing language naturally. So the time series is very important when we're analyzing sentiments. It can change the whole value of a sentence just by switching the words around. Or if you're just counting the words, you might get one sentiment where if you actually look at the order they're in, you get a completely different sentiment. When it rains, look for rainbows. When it's dark, look for stars. Both of these are positive sentiments, and they're based upon the order of which the sentence is going in. Machine translation. Given an input in one language, RNN can be used to translate the input into a different languages as output. I myself am very linguistically challenged. But if you study languages and you're good with languages, you know right away that if you're speaking English, you would say big cat. And if you're speaking Spanish, you would say cat big. So that translation is really important to get the right order, to get, there's all kinds of parts of speech that are important to know by the order of the words. Here this person is speaking in English and getting translated. And you can see here a person is speaking in English in this little diagram. I guess that's denoted by the flags. I have a flag. I own it. No. But they're speaking in English and it's getting translated into Chinese, Italian, French, German, and Spanish languages. Some of the tools coming out are just so cool. So somebody like myself who's very linguistically challenged, I can now travel into worlds I would never think of, because I can have something translate my English back and forth readily, and I'm not stuck with a communication gap. So let's dive into what is a recurrent neural network. Recurrent neural network works on the principle of saving the output of a layer and feeding this back to the input in order to predict the output of the layer. Sounds a little confusing. When we start breaking it down, it'll make more sense. And usually we have a propagation forward neural network with the input layers, the hidden layers, the output layer. With the recurrent neural network, we turn that on its side. So here it is, and now our X comes up from the bottom into the hidden layers into Y, and they usually draw it very simplified, X to H, with C as a loop, A to Y, where A, B, and C are the perimeters. A lot of times you'll see this kind of drawing in here, digging closer and closer into the H and how it works. Going from left to right, you'll see that the C goes in, and then the X goes in. So the X is going upward bound, and C is going to the right. A is going out. And C is also going out. That's where it gets a little confusing. So here we have X in, C in, and then we have Y out and C out. And C is based on HT minus 1. So our value is based on the Y and the H value are connected to each other. They're not necessarily the same value because H can be its own thing. And usually we draw this, or we represent it as a function. H of T equals a function of C, where H of T minus 1, that's the last H output, and X of T going in. So it's the last output of H combined with the new input of X, where HT is the new state, FC is a function with the parameters C, that's a common way of denoting it, HT minus 1 is the old state coming out, and then X of T is an input vector at time of step T. Well, we need to cover types of recurrent neural networks. And so the first one is the most common one, which is a one-to-one single output. One-to-one neural network is usually known as a vanilla neural network, used for regular machine learning problems. Why? Because vanilla is usually considered kind of just a real basic flavor. But because it's very basic, a lot of times they'll call it the vanilla neural network, which is not the common term, but it is, like kind of a slang term. People will know what you're talking about usually if you say that. Then we run one to many, so you have a single input, and you might have multiple outputs. In this case, image captioning, as we looked at earlier, where we have not just looking at it as a dog, but a dog catching a ball in the air. And then you have many-to-one network, takes in a sequence of inputs. Examples, sentiment analysis, where a given sentence can be classified as expressing positive or negative sentiments. And we looked at that as we were discussing, if it rains, look for a rainbow. So positive sentiment, where rain might be a negative sentiment if you were just adding up the words in there. And then, of course, if you're going to do a one-to-one, many-to-one, one-to-many, there's many-to-many networks, takes in a sequence of inputs and generates a sequence of outputs. Example, machine translation. So we have a lengthy sentence coming in English and then going out in all the different languages. Just a wonderful tool. Very complicated set of computations. If you're a translator, you realize just how difficult it is to translate into different languages. One of the biggest things you need to understand when we're working with this neural network is what's called the vanishing gradient problem. While training an RNN, your slope can be either too small or very large, and this makes training difficult. When the slope is too small, the problem is known as vanishing gradient. And you'll see here they have a nice image, loss of information through time. So if you're pushing not enough information forward, that information is lost, and then when you go to train it, you start losing the third word in the sentence or something like that, or it doesn't quite follow the full logic of what you're working on. Exploding gradient problem. Oh, this is one that runs into everybody. When you're working with this particular neural network, when the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. Issues in gradient problem: long training time, poor performance, bad accuracy. And I'll add one more in there. Your computer, if you're on a lower end computer testing out a model, will lock up and give you the memory error. Explaining gradient problem. Consider the following two examples to understand what should be the next word in the sequence. The person who took my bike and blank, a thief. The students who got into engineering with blank from Asia. And you can see in here we have our x value going in, we have the previous value going forward, and then you back propagate the error like you do with any neural network. And as we're looking for that missing word, maybe we'll have the person took my bike and blank was a thief. And the student who got into engineering with a blank were from Asia. Consider the following example, the person who took the bike. So we'll go back to the person who took the bike was blank a thief. In order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. So was a thief is singular. The student who got into engineering, well, in order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. And so you can see here the students who got into engineering with blank were from Asia. It might be sometimes difficult for the error to back propagate to the beginning of the sequence to predict what should be the output. So when you run into the gradient problem, we need a solution, the solution to the gradient problem. First, we're going to look at exploding gradient, where we have three different solutions depending on what's going on. One is identity initialization. So the first thing we want to do is see if we can find a way to minimize the identities coming in instead of having it identify everything, just the important information we're looking at. Next is to truncate the back propagation. So instead of having whatever information it's sending to the next series, we can truncate what it's sending. We can lower that particular set of layers, make those smaller. And finally is a gradient clipping. So when we're training it, we can clip what that gradient looks like and narrow the training model that we're using. When you have a vanishing gradient, the option problem, we can take a look at weight initialization, very similar to the identity, but we're going to add more weights in there so it can identify different aspects of what's coming in better. Choosing the right activation function. That's huge. So we might be activating based on one thing and we need to limit that. We haven't talked too much about activation functions, so we'll look at that just minimally. There's a lot of choices out there. And then finally there's long short-term memory networks, the LSTMs. And we can make adjustments to that. So just like we can clip the gradient as it comes out, we can also expand on that. We can increase the memory network, the size of it, so it handles more information. And one of the most common problems in today's setup is what they call long-term dependencies. Suppose we try to predict the last word in the text. The clouds are in the, and you probably said sky. Here we do not need any further context. It's pretty clear that the last word is going to be sky. Suppose we try to predict the last word in the text. I have been staying in Spain for the last 10 years. I can speak fluent. Maybe you said Portuguese or French. No, you probably said Spanish. The word we predict will depend on the previous few words in context. Here we need the context of Spain to predict the last word in the text. It's possible that the gap between the relevant information and the point where it is needed to become very large. LSTMs help us solve this problem. So the LSTMs are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. All recurrent neural networks have the form of a chain of repeating modules of neural network connections. In standard RNNs, this repeating module will have a very simple structure such as a single tangent H layer. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. LSTMS are a special kind of recurrent neural network, capable of learning long-term dependencies, remembering information for long periods of time as their default behavior. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. As you can see, the deeper we dig into this, the more complicated the graphs get. In here, I want you to note that you have x at t minus 1 coming in, you have x at t coming in, and you have x at t plus 1. And you have h at t minus 1, and h at t coming in, and h at t plus 1 going out. And of course, on the other side is the output A. In the middle, we have our tangent H, but it occurs in 2 different places. So not only when we're computing the x at t plus 1 are we getting the tangent H from x at t, but we're also getting that value coming in from the x at t minus 1. So the short of it is as you look at these layers, not only does the propagate through the first layer, goes into the second layer, back into itself, but it's also going into the third layer. So now we're kind of stacking those up. And this can get very complicated as you grow that in size. It also grows in memory too, and in the amount of resources it takes. But it's a very powerful tool to help us address the problem of complicated, long sequential information coming in, like we were just looking at in the sentence. And when we're looking at our long short-term memory network, there's 3 steps of processing in the LSTMS that we look at. The first one is we want to forget irrelevant parts of the previous state. A lot of times, like, is, as, in, a, unless we're trying to look at whether it's a plural noun or not, they don't really play a huge part in the language, so we want to get rid of them. Then selectively update cell state values. So we only want to update the cell state values that reflect what we're working on. And finally, we want to only output certain parts of the cell state. So whatever's coming out, we want to limit what's going out too. And let's dig a little deeper into this. Let's just see what this really looks like. So step 1 decides how much of the past it should remember. First step in the LSTM is to decide which information to be omitted from the cell in that particular time step. It is decided by the sigmoid function. It looks at the previous state, h at t minus 1, and the current input, x at t, and computes the function. So you can see over here we have a function of t equals the sigmoid function of the weight of f, the h at t minus 1, and then x at t, plus, of course, you have a bias in there with any of our neural networks, so we have a bias function. So f at t equals forget gate, decides which information to delete that is not important from the previous time step. Considering an LSTM is fed with the following inputs from the previous and present time step. Alice is good in physics. John, on the other hand, is good in chemistry. So, previous output. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our current input. So as we look at this, the first step is the forget gate realizes there might be a change in context after encountering the first full stop. Compares with the current input sentence of x at t. So we're looking at that full stop and then compares it with the input of the new sentence. The next sentence talks about John, so the information on Alice is deleted. Okay, that's important to know. So we have this input coming in, and if we're going to continue on with John, then that's going to be the primary information we're looking at. The position of the subject is vacated and is assigned to John. And so in this one, we've seen that we've weeded out a whole bunch of information, and we're only passing information on John, since that's now the new topic. So step 2 is then to decide how much should this unit add to the current state. In the second layer, there are 2 parts. One is the sigmoid function, and the other is the tangent h. In the sigmoid function, it decides which values to let through, 0 or 1. Tangent h function gives the weightage to the values which are passed, deciding their level of importance, -1 to 1. And you can see the 2 formulas that come up. The I of t equals the sigmoid of the weight of I, h at t minus 1, x at t plus the bias of I. And the c of t equals the tangent of h of the weight of c of h at t minus 1, x at t plus the bias of c. So our I of t equals the input gate, determines which information to let through based on its significance in the current time step. If this seems a little complicated, don't worry, because a lot of the programming is already done when we get to the case study. Understanding, though, that this is part of the program is important when you're trying to figure out what to set your settings at. You should also note when you're looking at this, it should have some semblance to your forward propagation neural networks, where we have a value assigned to a weight plus a bias. Very important steps in any of the neural network layers, whether we're propagating into the information from one to the next, or we're just doing a straightforward neural network propagation. Let's take a quick look at this, what it looks like from the human standpoint, as I step out of my suit again. Consider the current input at x of t. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our input. Input gate analyzes the important information. John plays football and he was a captain of his college team is important. He told me over the phone yesterday is less important, hence it is forgotten. This process of adding some new information can be done via the input gate. Now this example is as a human form, and we'll look at training this stuff in just a minute. But as a human being, if I wanted to get this information from a conversation, maybe it's a Google Voice listening in on you or something like that, how do we weed out the information that he was talking to me on the phone yesterday? Well, I don't want to memorize that he talked to me on the phone yesterday, or maybe that is important. But in this case, it's not. I want to know that he was the captain of the football team. I want to know that he served. I want to know that John plays football and he was the captain of the college football team. Those are the two things that I want to take away as a human being. Again, we measure a lot of this from the human viewpoint, and that's also how we try to train them so we can understand these neural networks. Finally, we get to step 3, decides what part of the current cell state makes it to the output. The third step is to decide what will be our output. First we run a sigmoid layer, which decides what parts of the cell state make it to the output. Then we put the cell state through the tangent h to push the values to be between -1 and 1, and multiply it by the output of the sigmoid gate. So when we talk about the output of t, we set that equal to the sigmoid of the weight of 0 of the h of t minus 1, back one step in time, by the x of t, plus of course the bias. The h of t equals the out of t times the tangent h of c of t. So our O of t equals the output gate, allows the passed in information to impact the output in the current time step. Let's consider the example to predicting the next word in the sentence. John played tremendously well against the opponent and won for his team. For his contributions, Brave blank was awarded player of the match. There could be a lot of choices for the empty space. Current input, Brave, is an adjective. Adjectives describe a noun. John could be the best output after Brave. Thumbs up for John, awarded player of the match. And if you were to pull just the nouns out of the sentence, team doesn't look right because that's not really the subject we're talking about. Contributions, brave contributions, or brave team, brave player, brave match. So you look at this and you can start to train this neural network. So it starts looking at it and goes, oh no, John is what we're talking about. So brave is an adjective. John's going to be the best output. And we give John a big thumbs up. And then of course we jump into my favorite part, a case study. Use case implementation of LSTM. Let's predict the prices of stocks using the LSTM network. Based on the stock price data between 2012 and 2016. We're going to try to predict the stock prices of 2017. And this will be a narrow set of data. We're not going to do the whole stock market. It turns out that the New York Stock Exchange generates roughly 3 terabytes of data per day. That's all the different trades up and down of all the different stocks going on. And each individual one second to second or nanosecond to nanosecond. But we're going to limit that to just some very basic fundamental information. So don't think you're going to get rich off this today. But at least you can give a step forward in how to start processing something like stock prices, a very valid use for machine learning in today's markets. Use case implementation of LSTM. Let's dive in. We're going to import our libraries. We're going to import the training set and get the scaling going. Now, if you watch any of our other tutorials, a lot of these pieces just start to look very familiar because it's a very similar setup. But let's take a look at that. And just a reminder, we're going to be using Anaconda, the Jupyter Notebook. So here I have my Anaconda Navigator. When we go under environments, I've actually set up a Keras Python 3.6. I'm in Python 3.6. And nice thing about Anaconda, especially the newer version, I remember a year ago messing with Anaconda in different versions of Python and different environments. Anaconda now has a nice interface And I have this installed both on a Ubuntu Linux machine and on Windows, so it works fine on there. You can go in here and open a terminal window, and then in here, once you're in the terminal window, this is where you're going to start installing using pip to install your different modules and everything. Now we've already pre-installed them, so we don't need to do that in here. But if you don't have them installed in your particular environment, you'll need to do that. And of course, you don't need to use the Anaconda or the Jupyter. You can use whatever favorite Python IDE you like. I'm just a big fan of this because it keeps all my stuff separate. You can see on this machine I have specifically installed one for Keras, since we're going to be working with Keras under TensorFlow. When we go back to home, I've gone up here to Application, and that's the environment I've loaded on here. And then we'll click on the Launch Jupyter Notebook. Now I've already, in my Jupyter Notebook, have set up a lot of stuff so that we're ready to go. Kind of like Martha Stewart's in the old cooking shows. We want to make sure we have all our tools for you so you're not waiting for them to load. And if we go up here to where it says New, you can see where you can create a new Python 3. That's what we did here underneath the setup, so it already has all the modules installed on it. And I'm actually renamed this. If you go under File, you can rename it. I'm calling it RNN Stock. And let's just take a look and start diving into the code. Let's get into the exciting part. Now we've looked at the tool, and of course you might be using a different tool, which is fine. Let's start putting that code in there and seeing what those imports and uploading everything looks like. Now, the first half is kind of boring when we hit the Run button, because we're going to be importing NumPy as NP. That's the number Python, which is your NumPy array, and the matplot library, because we're going to do some plotting at the end, and our pandas for our data set. Our pandas is PD. And when I hit Run, it really doesn't do anything except for load those modules. Just a quick note, let me just do a quick draw here. Oops, Shift-Alt, there we go. You'll notice when we're doing this setup, if I was to divide this up, oops, I'm going to actually, let's overlap these, here we go. This first part that we're going to do is our data prep. A lot of prepping involved. In fact, depending on what your system is, since we're using Keras, I put an overlap here, but you'll find that almost maybe even half of the code we do is all about the data prep. And the reason I overlap this with Keras, let me just put that down because that's what we're working in, is because Keras has like their own preset stuff, so it's already pre-built in, which is really nice. So there's a couple steps a lot of times that are in the Keras setup. We'll take a look at that to see what comes up in our code as we go through and look at stock. And then the last part is to evaluate. And if you're working with shareholders or classroom, whatever it is you're working with, the evaluate is the next biggest piece. So the actual code here, Keras is a little bit more, but when you're working with some of the other packages, you might have like 3 lines. That might be it. All your stuff is in your pre-processing and your data. Since Keras is cutting edge and you load the individual layers, you'll see that there's a few more lines here and Keras is a little bit more robust. And then you spend a lot of times, like I said, with the evaluate, you want to have something you present to everybody else and say, hey, this is what I did, this is what it looks like. So let's go through those steps. This is like a kind of just general overview. And let's just take a look and see what the next set of code looks like. And in here we have a dataset train, and it's going to be read using the PD, or pandas.readCSV, and it's the Google stock price train.csv. And so under this we have training set equals dataset train.iLocation, and we've kind of sorted out part of that. So what's going on here? Let's just take a look at let's look at the actual file and see what's going on there. Now if we look at this, ignore all the extra files on this, I already have a train and a test set where it's sorted out. This is important to notice because a lot of times we do that as part of the pre-processing of the data. We take 20% of the data out so we can test it, and then we train the rest of it. That's what we use to create our neural network. That way we can find out how good it is. But let's go ahead and just take a look and see what that looks like as far as the file itself. And I went ahead and just opened this up in a basic WordPad and text editor just so we can take a look at it. Certainly you can open up an Excel or any other kind of spreadsheet. And we note that this is a comma-separated variables. We have a date, open, high, low, close, volume. This is the standard stuff that we import into our stock, and we're the most basic set of information you can look at in stock. It's all free to download. In this case, we downloaded it from Google. That's why we call it the Google stock price. And it specifically is Google. This is the Google stock values from, as you can see here, we started off at 1/3/2012. So when we look at this first setup up here, we have a data set train equals PD underscore CSV. And if you noticed on the original frame, let me just go back there. They had it set to home Ubuntu downloads Google stock price train. I went ahead and changed that because we're in the same file where I'm running the code. So I've saved this particular Python code and I don't need to go through any special paths or have the full path on there. And then of course we want to take out certain values in here. And you're going to notice that we're using our data set, and we're now in pandas. So pandas, basically it looks like a spreadsheet. And in this case, we're going to do iLocation, which is going to get specific locations. The first value is going to show us that we're pulling all the rows in the data. And the second one is we're only going to look at columns 1 and 2. And if you remember here from our data, as we switch back on over, columns, we always start with 0, which is the date. And we're going to be looking at open and high, which would be 1 and 2. We'll just label that right there so you can see. Now, when you go back and do this, you certainly can extrapolate and do this on all the columns. But for the example, let's just limit a little bit here so that we can focus on just some key aspects of stock. And then we'll go up here and run the code. And again, I said the first half is very boring. Whenever you hit the run button, it doesn't do anything because we're still just loading the data and setting it up. Now that we've loaded our data, we want to go ahead and scale it. And we want to do what they call feature scaling. And in here, we're going to pull it up from the sklearn or the skKit preprocessing import min max scaler. And when you look at this, you got to remember that biases in our data, we want to get rid of that. So if you have something that's like a really high value, let's just draw a quick graph. And I have something here like maybe the stock has a value, one stock has a value of 100, and another stock has a value of 5. You start to get a bias between different stocks. And so when we do this, we go ahead and say, okay, 100 is going to be the max, and 5 is going to be the min, and then everything else goes, and then we change this, so we just squish it down. I like the word squish. So it's between 1 and 0. So 100 equals 1, or 1 equals 100, and 0 equals 5. And you can just multiply. It's usually just a simple multiplication we're using. Multiplication. So it's going to be minus 5 and then 100 divided, or 95 divided by 1. So, or whatever value is divided by 95. And once we've actually created our scale, we're telling it's going to be from 0 to 1. We want to take our training set and we're going to create a training set scaled. And we're going to use our scaler, SC, and we're going to fit. We're going to fit and transform the training set. So we can now use the SC, this particular object, we'll use it later on our testing set. Because remember, we have to also scale that when we go to test our model and see how it works. And we'll go ahead and click on the run. Again, it's not going to have any output yet because we're just setting up all the variables. Okay, so we paste the data in here, and we're going to create the data structure with the 60 time steps and output. First note, we're running 60 time steps, and that is where this value here also comes in. So the first thing we do is we create our xtrain and ytrain variables, and we set them to an empty Python array. Very important to remember what kind of array we're in and what we're working with. And then we're going to come in here, we're going to go for I in range 60 to 1258. There's our 60 time steps. And the reason we want to do this is as we're adding the data in, there's nothing below the 60. So if we're going to use 60 time steps, we have to start at point 60 because it includes everything underneath of it. Otherwise, you'll get a pointer error. And then we're going to take our xtrain and we're going to append training set scaled. This is the scaled value between 0 and 1. And then as I is equal to 60, this value is going to be 60 minus 60 is 0. So this actually is 0 to I. So it's going to be 0 to 60, 1 to 61. Let me just circle this part right here. 1 to 61, 2 to 62, and so on and so on. And if you remember, I said 0 to 60. That's incorrect because it does not count. Remember, it starts at 0, so this is a count of 60. So it's actually 59. Important to remember that as we're looking at this. And then the second part of this that we're looking at, so if you remember correctly, here we go from 0 to 59 of I, and then we have a comma, a 0 right here. And so finally, we're just going to look at the open value. Now, I know we did put it in there for 1 to 2. If you remember correctly, it doesn't count the second one, so it's just the open value we're looking at, just open. And then finally, we have ytrain.append training set I to 0. And if you remember correctly, I comma 0. If you remember correctly, this is 0 to 59, so there's 60 values in it. So when we do I down here, this is number 60. So what we're going to do this is we're creating an array, and we have 0 to 59. And over here we have number 60, which is going into the Y train. It's being appended on there. And then this just goes all the way up. So this is down here is 0 to 59, and we'll call it 60, since that's the value over here. And it goes all the way up to 1258. That's where this value here comes in. That's the length of the data we're loading. So we've loaded 2 arrays. We've loaded one array that has, which is filled with arrays from 0 to 59, and we loaded one array which is just the value. And what we're looking at, you want to think about this as a time sequence. Here's my open. What's the next one in the series? So we're looking at the Google stock, and each time it opens, we want to know what the next one, 0 through 59, what's 60? 1 through 60, what's 61? 2 through 62, what's 62? And so on going up. And then once we've loaded those in our for loop, we go ahead and take xtrain and ytrain equals np.array xtrain.nparray ytrain. We're just converting this back into a numpy array. That way we can use all the cool tools that we get with numpy array, including reshaping. So if we take a look and see what's going on here, we're going to take our xtrain, we're going to reshape it. Wow, what the heck does reshape mean? That means we have an array, if you remember correctly, so many numbers by 60. That's how wide it is. And so when you do xtrain.shape, that gets one of the shapes. And you get xtrain.shape of 1 gets the other shape. And we're just making sure the data is formatted correctly. And so you use this to pull the fact that it's 60 by, in this case, where's that value? 60 by 1199, 1258 minus 60, 1199, and we're making sure that that is shaped correctly, so the data is grouped into 1199 by 60 different arrays. And then the 1 on the end just means at the end, because when you're dealing with shapes and NumPy, they look at this as layers, and so the end layer needs to be 1 value. That's like the leaf of a tree, where this is the branch, and then it branches out some more, and then you get the leaf. np.reshape comes from and using the existing shapes to form it. We'll go ahead and run this piece of code. Again, there's no real output. And then we'll import our different Keras modules that we need. So from Keras models, we're going to import the sequential model. We're dealing with sequential data. We have our dense layers. We have actually 3 layers we're going to bring in. Our dense, our LSTM, which is what we're focusing on, and our dropout. And we'll discuss these 3 layers more in just a moment. But you do need with the LSTM, you do need the dropout, and then the final layer will be the dense. But let's go ahead and run this, and that'll import our modules. And you'll see we get an error on here. And if you read it closer, it's not actually an error, it's a warning. What does this warning mean? These things come up all the time when you're working with such cutting-edge modules that are completely being updated all the time. We're not going to worry too much about the warning. All it's saying is that the H5PY module, which is part of Keras, is going to be updated at some point. And if you're running new stuff on Keras and you start updating your Keras system, you better make sure that your H5Py is updated too, otherwise you're going to have an error later on. And you can actually just run an update on the H5Py now if you wanted to. Not a big deal. We're not going to worry about that today. And I said we were going to jump in and start looking at what those layers mean. I meant that. And we're going to start off with initializing the RNN, and then we'll start adding those layers in. And you'll see that we have the LSTM and then the dropout. LSTM, then dropout. LSTM, then dropout. What the heck is that doing? So let's explore that. We'll start by initializing the RNN, regressor equals sequential, because we're using the sequential model, and we'll run that and load that up. And then we're going to start adding our LSTM layer and some dropout regularization. And right there should be the Q, dropout regularization. And if we go back here and remember our exploding gradient, well, that's what we're talking about. The dropout drops out unnecessary data, so we're not just shifting huge amounts of data through the network. So we go in here. Let's just go ahead and add this in. I'll go ahead and run this. And we had 3 of them. So let me go ahead and put all 3 of them in, and then we can go back over them. There's the second one, and let's put 1 more in. Oops, put that in, and we'll go ahead and put 2 more in. I said 1 more in, but it's actually 2 more in. And then let's add 1 more after that. And as you can see, each time I run these, they don't actually have an output. So let's take a closer look and see what's going on here. So we're going to add our first LSTM layer in here. We're going to have units 50. The units is the positive integer, and it's the dimensionality of the output space. This is what's going out into the next layer. So we might have 60 coming in, but we have 50 going out. We have a return sequence, because it is a sequence data, so we want to keep that true. And then you have to tell it what shape it's in. Well, we already know the shape by just going in here and looking at xtrain shape. So input shape equals the xtrain shape of 1, 1. It makes it real easy. You don't have to remember all the numbers that put in 60 or whatever else is in there. You just let it tell the regressor what model to use. And so we follow our STM with a dropout layer. Now, understanding the dropout layer is kind of exciting because one of the things that happens is we can overtrain our network. That means that our neural network will memorize such specific data that it has trouble predicting anything that's not in that specific realm. To fix for that, each time we run through the training mode, we're going to take 0.2 or 20% of our neurons and just turn them off. So we're only going to train on the other ones. And it's going to be random. That way, each time we pass through this, we don't overtrain. These nodes come back in the next training cycle. We randomly pick a different 20. And finally, I see a big difference as we go from the first to the second and third and fourth. The first thing is we don't have to input the shape. Because the shape's already, the output units is 50 here, the next step automatically knows this layer is putting out 50, and because it's the next layer, it automatically sets that and says, oh, 50 is coming out from our last layer. It's coming out, goes into the regressor, and of course we have our dropout. And that's what's coming into this one, and so on, and so on. And so the next 3 layers, we don't have to let it know what the shape is. It automatically understands that. And we're going to keep the units the same. We're still going to do 50 units. It's still a sequence coming through, 50 units and a sequence. Now, the next piece of code is what brings it all together. Let's go ahead and take a look at that. And we come in here, we put the output layer, the dense layer. And if you remember up here, we had the 3 layers. We had LSTM, dropout, and dense. Dense just says we're going to bring this all down into one output. Instead of putting out a sequence, we just want to know the answer at this point. And let's go ahead and run that. And so in here, you notice all we're doing is setting things up, one step at a time. So far, we've brought in our, way up here, we brought in our data, we brought in our different modules, we formatted the data for training it, we set it up, we have our X train and our Y train. We have our source of data and the answers we know so far that we're going to put in there. We've reshaped that. We've come in and built our Keras. We've imported our different layers. And we have in here, if you look, we have 5 total layers. Now, Keras is a little different than a lot of other systems because a lot of other systems put this all in one line and do it automatic, but they don't give you the options of how those layers interface, and they don't give you the options of how the data comes in. Keras is cutting edge for this reason. So even though there's a lot of extra steps in building the model, this has a huge impact on the output and what we can do with these new models from Keras. So we brought in our dense, we have our full model put together, our regressor. So we need to go ahead and compile it, and then we're going to go ahead and fit the data. We're going to compile the pieces so they all come together, and then we're going to run our training data on there and actually recreate our regressor so it's ready to be used. So let's go ahead and compile that, and I can go ahead and run that. And if you've been looking at any of our other tutorials on neural networks, you'll see we're going to use the optimizer Atom. Atom is optimized for big data. There's a couple other optimizers out there beyond the scope of this tutorial, but certainly Atom will work pretty good for this. And loss equals mean squared value. So when we're training it, this is what we want to base the loss on. How bad is our error? Well, we're going to use the mean squared value for our error and the Atom optimizer for its differential equations. You don't have to know the math behind them, but certainly it helps to know what they're doing and where they fit into the bigger models. And then finally we're going to do our fitting the RNN to the training set. We have the regressor.fit, X-train, Y-train, epochs, and batch size. So we know where this is. This is our data coming in for the X-train. Our Y-train is the answer we're looking for of our data, our sequential input. Epochs is how many times we're going to go over the whole data set. We created a whole data set of X-train. So this is each of those rows, which includes a time sequence of 60. And batch size, another one of those things where Keras really shines, is if you were pulling this, say, from a large file, instead of trying to load it all into RAM, it can now pick smaller batches up and load those indirectly. We're not worried about pulling them off a file today because this isn't big enough to cause the computer too much of a problem to run, not too straining on the resources. But as we run this, you can imagine what would happen if I was doing a lot more than just one column in one set of stock, in this case Google stock. Imagine if I was doing this across all the stocks and I had, instead of just the open, I had open, close, high, low, and you can actually find yourself with about 13 different variables times 60 because it's a time sequence. Suddenly you find yourself with a gig of memory you're loading into your RAM, which will just completely, if you're not on multiple computers or cluster, you're going to start running into resource problems. But for this, we don't have to worry about that. So let's go ahead and run this, and this will actually take a little bit on my computer because it's an older laptop. And give it a second to kick in there. There we go. Alright, so we have Epic. So this is going to tell me it's running the first run through all the data. And as it's going through, it's batching them in 32 pieces. So 32 lines each time. And there's 1198. I think I said 1199 earlier, but it's 1198. I was off by 1. And each one of these is 13 seconds. So you can imagine this is roughly 20 to 30 minutes runtime on this computer. Like I said, it's an older laptop running at 0.9 gigahertz on a dual processor. And that's fine. What we'll do is I'll go ahead and stop, go get a drink of coffee, and come back, and let's see what happens at the end and where this takes us. And like any good cooking show, I've gotten my latte. I also had some other stuff running in the background, so you'll see these numbers jumped up to like 19 seconds, 15 seconds. But you can scroll through, and you can see we've run it through 100 steps, or 100 epochs. So the question is, what does all this mean? One of the first things you'll notice is that our loss is over here. It kind of stopped at 0.0014, but you can see it kind of goes down until we hit about 0.014 3 times in a row. So we guessed our epoch pretty close since our loss has remained the same on there. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And a real stock price, data set, test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. And you see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open. Stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And a real stock price, data set, test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. And you see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open. Stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data, because that's part of the next data, or it's actually the top 59. So that's what this first setup is over here, is where we're going in, we're doing the real stock price, and we're going to just take the data set test, and we're going to load that in, and then the real stock price is our data test location. So we're just looking at that first column, the open price. And then our data set total, we're going to take pandas and we're going to concat, and we're going to take our data set train for the open and our data set test open. And this is one way you can reference these columns. We've referenced them a couple different ways. We've referenced them up here with the 1, 2, but we know it's labeled as a panda set as open. So pandas is great that way. Lots of versatility there. And we'll go ahead and go back up here and run this. There we go. And you'll notice this is the same as what we did before. We have our open data set. We appended our concatenated our two data sets together. We have our inputs equals data set total length, data set total minus length of data set minus test minus 60 values. So we're going to run this over all of them. And you'll see why this works, because normally when you're running your test set versus your training set, you run them completely separate. But when we graph this, you'll see that we'll be looking at the part that we didn't train it with to see how well it graphs. And we have our inputs equals inputs dot reshape, so reshaping like we did before. We're transforming our inputs. So if you remember from the transform between 0 and 1. And finally, we want to go ahead and take our x test, and we're going to create that x test, and for I in range 60 to 80. So here's our x test, and we're appending our inputs I to 60, which remember is 0 to 59, and I comma 0 on the other side. So it's just the first column, which is our open column. And once again, we take our x test, we convert it to a numpy array. We do the same reshape we did before, and then we get down to the final 2 lines, and here we have something new. Right here on these last 2 lines, let me just highlight those or mark them. Predicted stock price equals regressor.predicts x test. So we're predicting all the stock, including both the training and the testing model here. And then we want to take this prediction and we want to inverse the transform. So remember, we put them between 0 and 1. Well, that's not going to mean very much to me to look at a float number between 0 and 1. I want the dollar amounts. I want to know what the cash value is. And we'll go ahead and run this, and you'll see it runs much quicker than the training. That's what's so wonderful about these neural networks. Once you put them together, it takes just a second to run the same neural network that took us, what, a half hour to train? Head and plot the data. We're going to plot what we think it's going to be, and we're going to plot it against the real data, what the Google stock actually did. So let's go ahead and take a look at that in code. And let's pull this code up. So we have our PLT. That's our, if you remember from the very beginning, let me just go back up to the top. We have our matplotlibary.pyplot as PLT. That's where that comes in. And we come down here, we're going to plot, and let me get my drawing thing out again. We're going to go ahead, and PLT is basically kind of like an object. It's one of the things that always threw me when I'm doing graphs in Python, because I always think you have to create an object, and then it loads that class in there. Well, in this case, PLT is like a canvas you're putting stuff on. So if you've done HTML5, you'll have the canvas object. This is the canvas. So we're going to plot the real stock price. That's what it actually is. And we're going to give that color red. So it's going to be in bright red, and we're going to label it real Google stock price. And then we're going to do our predicted stock, and we're going to do it in blue, and it's going to be labeled predicted. And we'll give it a title, because it's always nice to give a title to your graph, especially if you're going to present this to somebody, to your shareholders in the office. And the X label is going to be time, because it's a time series. And we didn't actually put the actual date and times on here, but that's fine. We just know they're incremented by time. And then, of course, the Y label is the actual stock price. PLT.legend tells us to build the legend on here so that the color red and real Google stock price show up on there. And then the plot shows us that actual graph. So let's go ahead and run this and see what that looks like. And you can see here we have a nice graph, and let's talk just a little bit about this graph before we wrap it up. Here's our legend I was telling you about. That's why we have the legend to show the prices. We have our title and everything. And you'll notice on the bottom we have a time sequence. We didn't put the actual time in here. Now we could have. We could have gone ahead and plotted the X, since we know what the dates are, and plotted this to dates. But we also know that it's only the last piece of data that we're looking at. So last piece of data, which ends somewhere probably around here on the graph, I think it's like about 20% of the data, probably less than that. We have the Google price, and the Google price has this little up jump and then down, and you'll see that the actual Google, instead of a turn down here, just didn't go up as high and didn't go down. So our prediction has the same pattern, but the overall value is pretty far off as far as stock. But then again, we're only looking at one column. We're only looking at the open price. We're not looking at how many volumes were traded. And like I was pointing out earlier, when we talk about stock, just right off the bat, there's 6 columns. There's open, high, low, close, volume. Then there's volume shares. Then there's the adjusted open, adjusted high, adjusted low, adjusted close. They have a special formula to predict exactly what it would really be worth based on the value of the stock. And then from there, there's all kinds of other stuff you can put in here. So we're only looking at one small aspect, the opening price of the stock. And as you can see here, we did a pretty good job. This curve follows the curve pretty well. It has like little jumps on it, bends. They don't quite match up. So this bend here does not quite match up with that bend there, but it's pretty darn close. We have the basic shape of it, and the prediction isn't too far off. And you can imagine that as we add more data in and look at different aspects in the specific domain of stock, we should be able to get a better representation each time we drill in deeper. Of course, this took a half hour for my computer to train, so you can imagine that if I was running it across all those different variables, it might take a little bit longer to train the data.
Today we are going to talk about Meta's new AI development called Llama 3.2, a new family of AI models designed for various tasks. And we will also see how to install Llama 3.2 and run it privately. The smaller models with 1B and 3B parameters are optimized for the mobile devices, handling tasks like text summarization and translation without draining your battery. The larger models, the 11B and 90B vision models, can process both text and image simultaneously, making them ideal for complex data analysis and industries like medical imaging. Llama 3.2 is multilingual out of the box, supporting 8 languages, including English, Spanish, and Hindi. Meta rigorously tested these models across 150 benchmarks and is releasing them as an open source, allowing developers to customize them to their needs, much like how Linux operates. In addition to AI models, Meta is advancing in augmented reality with its upcoming Orion glasses, aiming to overlay digital images onto the real world. While these are expected around 2027, their Ray-Ban Meta smart glasses are already popular, indicating a strong interest in wearable AI gadgets. Overall, Meta is pushing the boundaries of AI, AR, and VR technologies, making them more accessible and customizable for everyone. It's an exciting time for tech enthusiasts as these innovations shape our digital future. So without any further ado, let's jump into the demo part. So welcome to this demo part of how to install Llama 3.2 privately on your system locally. So first you will, I will give you this Llama link. All this the link I will give to you in the description, you can check. So first you have to install this Llama. Okay, you have to install Llama. So please select this OS. So my OS is Windows. I have already installed it, but again I'm telling you the steps. Okay, you can download it. Once this setup you install, I have already installed, so I'm pausing it. So once this setup installed, after that you come into this website. Okay, this is the step 2. Here you can see there are many Llama models, or you can see LLM models. Mistral is there, okay, and Code Llama is there, Command R is there, Llama 3.1 is there. The latest one is Llama 3.2, okay, with 1B and 3B models. Okay, these are the basics ones. So just click on this. So you will get this command, Llama run Llama 3.2. Just copy it, open your command prompt or PowerShell. I'm using PowerShell, just paste it. So this thing I have already installed. Okay, press enter. It will take some times. Okay, it will of like 2 GB or 4 GB something. So it will install. So I have already installed, so it will send a message. Okay, so I can write here, how are you? It will respond me. I'm just a language model, feeling our emotions like human do, these things and all. Okay, I will write exit, or I will write quit. Okay, so leave this. Okay, after this our Llama 3.2 is done. Okay, we have installed, but we will launch it with the Docker. Okay, So I'm closing this again. After that, come to this Docker. Okay, this is the docker.com. You come here, download Docker desktop app. So don't download this ARM64 as of now because it is in beta version. Okay, download this AMD64. Okay, so it's starting getting download. So again, my Docker desktop is also installed. Okay, so I will open it directly. So after installing, it will ask you for the email address and the password to sign in, not sign in, sign up, like this. So there, one option will be there, skip. So you can skip. See, I have also skipped. That is why it is asking for me sign in. Okay, after skipping, this thing will come. This dashboard, container, image, volumes, build, and Docker. So after this, don't close this Docker. Okay, just minimize it. After that, our last step is coming to this website, Open Web UI. I will give you the links. So here you can just copy this. If Llama is on your computer, Docker run this. Just copy this. Open your PowerShell. Paste it there. I have done this process as well, and enter. Okay, it's done. So when you will open your Docker, this will come. Okay, localhost. See, last started 5 seconds ago. So open this port. See, after opening that port, this will come. Sign in to Open Web UI. So here you can sign up. Okay, all right. See, after signing up, so this came. Again, you can see we are in local host. Okay, you can select a model. See, 3.1 and 3.2, the latest one. Okay, you can set as default. Okay, default model set. Here you can ask anything to Llama 3.2. Okay, any questions. Okay, here are some suggested, like, okay, give me ideas. What are the 5 creating things I could do with my kids art? Okay, press enter. So you can see Llama 3.2 latest. So there are 2 more models of this, 11B and 90B, which are multi-models which use for big things. Okay, so this is how you can run Llama locally into your systems. You can ask anything, you can create scripts. Okay, wait, I want to start my Instagram. Okay, I will write, I want to build community on Reddit. What should I do? Okay, it will give answer. So here you can see, gave me these things, these 5 creative things. Okay, it's thinking, I guess, or something it's doing. So this is how you can run Llama 3.2. See, it took time, I know, because we are running locally. That's why. See, building community on Reddit can be rewarding experience. For this is choose the right subreddit. And the second thing, create high quality content. So like this. So this is how you can run Llama 3.2. Okay, you can use Llama 3.2 in this terminal as well, but if you will run locally, deploy with Docker, so it will give you the good UI as well. See, good UI. Okay, you can sign out settings and these things. So what are confusion matrices and why do we need them? So in machine learning, classification is used to divide data into different categories. But after we have prepared the data and trained our model, how we can tell if the model is performing well? So there is where confusion matrix come in handy. So a confusion matrix is a tool that helps measure the performance of a classifier in detail. It goes beyond just giving an overall accuracy score. It shows exactly where the model is making mistake and how it is classifying each category. For example, if there is an imbalance in the data where one category has many more instances than other, the model might predict the majority category most of the time and still show a high accuracy. But this wouldn't be helpful
Because the model is not accurately predicting the minority categories, the confusion matrix helps visualize these outcomes by showing a table of all the predicted and the actual values, allowing users to see where the model is performing well and where it needs improvement. So moving forward, let's see confusion matrices parts or how to create 2 by 2 matrix. So we can get 4 different outcomes when comparing the predicted actual values from a classifier. The first one is true positive. This is when the model correctly predicts a positive outcome. You predicted positive and it was actually positive. The second one is false positive. This happens when the model incorrectly predicts a positive outcome for something that is actually negative, or a predicted positive but it was actually negative. The third one, true negative. This is when the model correctly predicts a negative outcome. You predicted negative and it was actually negative. And the fourth one, false negative. This occurs when the model incorrectly predicts a negative outcome for something that is actually positive. You predicted negative and but it was actually positive. So moving forward, let's see some matrices of confusion matrix. So this is a graph. So we know there are 4 parts: true positive, false negative, and true negative. So this one is true positive, this one is false positive, this one is false negative, this one is true negative. So just consider a confusion matrix made for a classifier that classify people based on whether they speak English or they speak Spanish. Okay, from this diagram you can see that. Fine. So these are some values: TP, FN, FP, TN. There is nothing true positive, true negative like this. Just from looking at the matrix, the performance of our model is not very clear. So to find out how accurate our model is, we use the following matrices. The first one is accuracy. So this is the formula of accuracy. TP means true positive, means this 86 value. So the accuracy is used to find the portion of correctly classified values. It tells us how often a classifier is right. It is the sum of all the true values divided by total values. So in this case, this is 88%. Okay, 86 plus 79, true positive plus true negative divided by this. It will come 88.23. Okay, and the second one is precision. So precision is used to calculate the model ability to classify positive value correctly. It is the true positive divided by the total number of predicted positive value. So this is the formula. It is true positive divided by true positive plus false positive. So in this case, the value will come 87.75%. Okay, and the third one is recall. So recall is used to calculate the model's ability to predict positive values. How often does the model predict the correct positive values? So it is true positives divided by the total number of actual positive values. So in this case, the value is 88.93. Okay, and the last one is F1 score. So it is the harmonic mean of recall and precision. It is useful when you need to take both precision and recall into an account. So in this case, the value is 88.77%. So now let's jump into the demo part and see how we can get these values: accuracy, precision, recall, and F1 score from our dataset using hands-on. So I'm performing this in Google Colab. So first I will rename it to confusion matrix. Okay, so yes, let's start. So first we will import some basic libraries of Python like NumPy and the pandas. So here I will like import NumPy as NP and import pandas as PD. Why I'm writing this NP and PD? Because I don't want to write again and again NumPy and pandas. Okay, this is a short form, NP. So everyone knows, I guess, NumPy and pandas because these are the basic library. So NumPy is used for mostly linear algebra stuff, and pandas is used for the creating data frames, data processing, or if you want to read files, CSV files like that. Okay, yeah. So now let's import our data. Okay, so data equals to pd dot read underscore CSV, then file name data.csv. So I will upload this file on the description box below. You guys can check out from there. Okay, yes. So okay, what is saying?
No such file or directory on data or CSV. I guess it's there. Okay, it's not. Let me import it. Okay. Yeah. Okay. Now file is there. So, yeah, it's working fine. So now let's check. Okay, 5 rows. Yeah, so this is our data. You can see we have columns with data dot columns. Okay, so we have this 32 columns in our data set: ID, diagnosis, radius means, texture means, parameter mean. So I just simply took this data. There is nothing related to confusion matrix and all. Okay, we can perform confusion matrix to any data. So head is used for displaying top 5 rows of our data set. Okay, if I will write data simply, you can see the full data, okay, with 33 columns and all the rows, right? So now we don't need this ID, and one is this unnamed data because there is no values. Okay, so what I will do, I will write data dot drop ID comma. Okay, let me copy it because I don't want any spelling mistake. Yeah, copy, paste here. Okay, let me write axis equals to 1, then comma, in place equals to true. Okay, let me run it. Okay, if you will check data dot head, now I guess there will be no ID and all. See, there is now no ID and all. Okay, this we remove that large column as well, unnamed 32. Okay, so now what I have to do, I will write here data dot diagnosis equals to 1 if each equals to m. Okay, else 0 for each in data dot diagnosis. Yeah, so if you can see, there is mmm value and there is other values as well. So for m I am putting 1, for the rest I will put 0. Okay, let's check again. Yeah, okay, you can see it's done. Replacement is done basically. Okay, so let's check the info of the data. So these are some basic functions of Python. So these are the column, these are the non-null values, these are the data type values. Okay, float we have or int we have. Okay, so we have only two type of data sets. So now what we will do normalization. Okay, y equals to data dot diagnosis dot values. Okay, so here I will write x underscore data equals to data dot drop diagnosis comma axis equals to 1. Okay, here I will write x equals to x underscore data minus np dot minimum value and the x underscore data and divided by, so I am using that formula if you guys know. Okay, divided by np, So what I'm finding is accuracy. Okay, I'm using that formula. NP dot max of x underscore data, then minus NP dot min value, then x underscore data. Okay, x's value is wrong. Sorry, spelling is wrong. Now fine. Yes, it's fine. So now we will do train test split. So what is train test split? Okay, so first let me write underscore selection import train test split. Okay, so what is train test split? So what we do, we split our data set into training and the testing. Mostly we train and the some part of data we test. Okay, so here I will set the ratio. So x underscore train comma x underscore test comma y underscore train comma y underscore test equals to train test split, then x comma y comma test underscore size equals to 0.15. Means 85% we are on the training and 15% we are on the testing part. Okay, comma random state equals to 42. Okay, let me run it. It's working fine. Yeah, it's working fine. So now let's see the accuracy from the random forest. So I will write from sklearn dot ensemble import random forest classifier. Okay, then rf equals to random forest classifier and n underscore estimators equals to 100, and here I will set random state to 1. Okay, then rf, this is a short form of random forest, dot fit x underscore train comma y underscore train, then print random forest score comma rf dot score, then x underscore test comma y underscore test. Okay, so now let's check how much the accuracy. So accuracy is coming 95%. Okay, which is very good. So now what I will do, I will create confusion matrix now. Y underscore prediction equals to rf dot predict x underscore test. Okay, then y underscore true equals to y underscore test. Okay, so here now let's create the array sklearn dot matrix import confusion matrix. Okay, then I will write CM, short form of confusion matrix. Here I will write y true comma y prediction. then confusion matrix. So this is our array. Okay, the true, positive, and this is false, negative, and this is false, positive, like this. Okay, so now let's create the visualization of confusion matrix. Okay, so here I will write import cborn as SNS, and import matplotlib dot pyplot as plt. plt means plot. Okay, the short form. F comma ax equals to plt dot subplots. Let's give the figure size equals to 5,5. Then SNS dot heat map, then confusion matrix comma n naught equals to true, then comma line width equals to 0.5, comma line color equals to, let's give red, then fmt equals to, I don't need any that decimal values, comma ax equals to ax. Okay, then plt dot x label y underscore prediction, then plt dot y label, then y underscore true. Add the, okay, forgot to add this braces, then plt dot show. Yeah, so as you can see, this is the y true values and this is the y prediction values. Okay, this is the heat map we have created. So this is how you can visualize your confusion matrix. Fine. So now what is RNN? RNN are a type of neural network that are designed to process sequential data. They can analyze data with temporal dimensions such as time series, speech, and text. RNN can do this by using a hidden state passed from one timestamp to the next. The next hidden state is updated at each other time step based on the input and the previous hidden state. RNN are able to capture short-term dependencies in sequential data, but they struggle with capturing long-term dependencies. Why the LSTMs are made? So moving forward, let's discuss types of LSTM gates. So LSTM models have three types of gates: the input gate, the forget gate, and the output gate. So let's first discuss the input gate. The input gate controls the flow of information into the memory cell, deciding what to store. The input gate determines which values from the input should be updated in the memory cell. It uses a sigmoid activation function to scale the values between 0 and 1, and then applies pointwise multiplication to decide what information to store. Next is forget gate. Controls the flow of information out of the memory cell, deciding what to discard. The forget gate decides what information should be discarded from the memory cell. It also uses a sigmoid activation function to scale the values between 0 and 1, followed by pointwise multiplication to determine what information to forget. The last one is output gate. Controls the flow of information out of the LSTMs, deciding what to use for the output. The output gate determines the output of the LSTM's unit. It uses a sigmoid activation function to scale the values from 0 to 1, then applies pointwise multiplication to produce the output of the LSTM unit. So these gates implemented using sigmoid function are trained using backpropagation. They open and close based on the input and the previous hidden state, allowing the LSTM to selectively retain or discard information, effectively capturing long-term dependencies. So now let's discuss application of LSTM. LSTM models are highly effective and used in various applications, including video analysis, analyzing video frames to identify action, object, and scenes. The second is language simulation, tasks like language modeling, machine translation, and text summarization. The third one is time series prediction. So predicting future values in a time series. The fourth is voice recognition. Tasks such as speech to text transcription and command recognition. The last one is sentiment analysis. Classifying text sentiment as positive, negative, or neutral. So there are many more examples of LSTM. So now let's move forward and understand LSTM model and how it works with example. Let's consider the task of predicting the next word in a sentence. This is a common application of LSTM networks in natural language processing. So I will break it down step by step using the analogy of remembering a story and deciding what comes next based on the context. So imagine you are reading a story. As you read, you need to remember what has happened so far to predict what might happen next. So let's illustrate with a simple example sentence. The cat sat on the dash. So you want to predict the next word, which could be mat or roof or something else. An LSTM network helps this make prediction by remembering important parts of the story and forgetting irrelevant details. So now let's dive into a step-by-step process. So step-by-step explanation using LSTM. The first one is reading the story, input sequence. As you read each word in the word sentence, you process it and store relevant information. For example, you understand it's a determiner. Cat, you know it's a noun and the subject of the sentence. Sat indicates the action performed by the subject. On, preposition indicating the relationship between the cat and the next noun. So this sequence diagram showing the words being read and processed. So second comes forget get. As you move through the sentence, you might decide that some details are no longer important. For instance, you might decide that knowing the is less important now that you have cat and said. So the word forget get helps discard this less important information. So this sequence diagram you can see on the screen showing how relevant information is discarded. So the third one, input get. When you read on, you need to decide how relevant this information is. So this sequence diagram in the screen is showing how new information is integrated with the last one. Okay, the fourth one is the cell state, memory part. So this is like your memory of the story so far. It carries information about the subject cat and the action sat on. So it updates the new information as you read each word. Okay, the cat sat on the, retaining the important context. So this sequence diagram showing how the memory is updated with the new information. So the last one is output get. When you need to predict the next word, the output get helps you decide based on the current memory, cell state. So it uses the context, the cat sat on the. So the predict the next word might be mat because cat and mat are often associated with the context. So it can predict anything. The cat sat on the table or on the sofa, anything. But mat, why I'm saying mat? Because cat and mat are often associated in the same context. So this diagram is showing the prediction of the next word based on the current memory. So there are many applications where you can use LSTM in predicting time series or next word in the sentence. So by the using of LSTM gates, input gate, forget gate, and output gate, and updating the cell state, the network can predict the next word in a sequence by maintaining relevant context and discarding unnecessary information. This step-by-step process allows LSTM network to effectively handle sequence and make accurate prediction based on the context.
So here's the OpenAI documentation, and you could see the new features introduced with the ChatGPT 4.0. So these are the improvements. One is the updated and interactive bar graphs or pie charts that you can create, and these are the features that you could see here. You could change the color, you could download it, and what we have is you could upload the latest file versions directly from Google Drive and Microsoft OneDrive. And we have the interaction with tables and charts in a new expandable view that I showed you here. That is here, you can expand it in the new window. And you can customize and download charts for presentations and documents. Moreover, you can create the presentation also. That we'll see in further. And here we have how data analysis works in ChatGPT. You could directly upload the files from Google Drive and Microsoft OneDrive. I will show you guys how we can do that and where this option is. And we can work on tables in real time. And there we have customized presentation ready charts. That is, you can create a presentation with all the charts based on a data provided by you. and moreover a comprehensive security and privacy feature. So with that guys, we'll move to ChatGPT, and here we have the ChatGPT 4.0 version. So before commencing guys, there's a quick info for you. If you're one of the aspiring data analysts looking for online training and graduating from the best universities, or a professional who elicits to switch careers with data analytics by learning from the experts, then try giving a shot to Simplilearn's Purdue postgraduate program in data analytics in collaboration with IBM. You can find the link in the description box and pinned comment. So let's get started with data analysis part. So this is the pin section or the insert section, where you can have the options to connect to Google Drive, connect to Microsoft OneDrive, and you can upload it from the computer. This option was already there, that is upload from computer, and you can upload at least or at max the 10 files. That could be around Excel files or documents. So the max limit is 10. And if you have connected to Google Drive, I'll show you guys. I'm not connecting you, but you guys can connect it too, and you could upload it from there also. And there's another cool update, that is ability to quote directly in your chat. So while chatting with ChatGPT, I'll show you guys how we can do that. And you could find some new changes, that is in the layout. So this is the profile section. It used to be at the left bottom, but now it's moved to the top right and making it more accessible than ever. So let's start with the data analysis part, and the first thing we need is data. So you can find it on Kaggle, or you could ask ChatGPT 4.0 to provide the data. I will show you guys. So this is the Kaggle website. You can sign in here and click on datasets. You can find all the datasets here. That would be around computer science, education, classification, computer vision. Or else you could move back to ChatGPT and you could ask the ChatGPT 4.0 model to generate a data and provide it in Excel format. So we'll ask him, we'll not ask him can you, we'll just ask him provide a data set that I can use for data analysis and provide in CSV format. So you could see that it has responded that I can provide a sample data set, and he has started generating the data set here. So you could see that he has provided only 10 rows, and he is saying that I will now generate this data set in CSV format. First he has provided the visual presentation on the screen, and now he is generating the CSV format. So if you want more data, like if you want 100 rows or 1000 rows, you could specify in the prompt and ChatGPT will generate that for you. So we already have the data. I will import that data. You could import it from here, or else you can import it from your Google Drive. So we have a sales data here. We will open it. So we have the sales data here. So the first step we need to do is data cleaning. So this is the crucial step to ensure that the accuracy of our analysis is at its best. So we can do that by handling missing values. That is, missing values can distort our analysis. And here ChatGPT 4 can suggest methods to impute these values, such as using the mean, median, or a sophisticated approach based on data patterns. And after handling the missing values, we will remove duplicates and outlier detection. So we'll ask ChatGPT, clean the data if needed. So we can just write a simple prompt that would be clean the data if needed. And this is also a new feature. You can see the visual presentation of the data here, that we have 100 rows here, and the columns provided, that is sales ID, date, product, category, quantity, and price per unit, and total sales. So this is also a new feature that, okay, we just headed back. We'll move back to our ChatGPT chat here. Okay, so here we are. So you could see that ChatGPT has cleaned the data, and he has provided that it has checked for missing values, checked for duplicates, and ensured consistent formatting. And he's saying, okay, so now we will ask him that execute these steps and provide the clean data. As ChatGPT has provided that these are the steps to clean the data, and let's see. So he has provided a new CSV file with the clean sales data. We will download it and ask him to use the same file only. Use this new cleaned sales data CSV file for further analysis. So you could see that he is providing what analysis we can do further. But once our data is clean, the next step is visualization. So visualizations help us understand the data better by providing a graphical representation. So the first thing we will do is we will create a prompt for generating the histograms, and we'll do that for the age distribution part. So we'll write a prompt that generate a histogram to visualize the distribution of customer ages. To visualize the distribution of customer ages. And what I was telling you guys is this code button. If you just select the text and you would find this reply section, just click on that and you could see that it has selected the text or what you want to get or the prompts started with ChatGPT. So we'll make it cross and you could see that it has provided the histogram here, and these are the new features here. And we could see that he is providing a notification that interactive charts of this type are not yet supported. That is, histogram don't have the color change option. I will show you the color change option in the bar chart section. So these features are also new. You can download the chart from here only, and this is the expand chart. If we click on that, you could see that you could expand the chart here and continue your chat with ChatGPT here. So this is the interactive section. So you could see that he has provided the histogram that is showing the distribution of customer ages, and the age range are from 18 to 70 years with the distribution visualized in 15 bins, that he has created 15 bins here. And now moving to another visualization that we'll do by sales by region. So before that, I will open the CSV file that is provided by the ChatGPT. So you guys can also see what data he has provided. So this is the clean sales data, and you could see that we have columns sales ID, date, product, category, quantity, price per item, total sales, region, and salesperson. So now moving back to ChatGPT. So now we will create a bar chart showing total sales by region. So we'll enter this prompt that create a bar chart showing total sales by region. So what we are doing here is we are creating bar charts or histogram charts, but we can do that for only 2 columns. If we want to create these data visualization charts, we need 2 columns to do so. So you could see that he has provided the response and created the bar chart here. And this is the interactive section. You could see that here's an option to switch to static chart. If we click on that, we can't, we are not getting any information if we scroll on that. And if I enable this option, you could see that I can visually see how many numbers this bar is indicating. And after that, we have the change color section. You can change the color of the data set provided. So we can change it to any color that is provided here, or you could just write the color code here. And similarly, we have other 2 options, that is download and another is the expand chart section. And if you need what code it has done to figure out this bar graph, so this is the code. You could use any ID to do so. If you don't want the presentations or the visualizations of the bar charts here, you could use your ID and use the Python language, and he will provide the code for you. Just take your data set and read it through pandas and generate the bar charts. So moving to next section, that is category wise sales section. So here we will generate a pie chart showing the proportion of sales for each product category. So for that we'll write a prompt, generate a pie chart showing the proportion of sales for each product category. So you could see that it has started generating the pie chart, and this is also an interactive section. If you click on that, you would be seeing a static pie chart, and if you want to change the color, you can change for any section. That could be clothing, electronics, furniture, or kitchen. And similarly, we have the download section and the expand chart section. So this is how this new ChatGPT 4 model is better than ChatGPT 4, that you could use a more interactive pie charts. You could change the colors for that, and you can just hover over these bar charts and found all the information according to them. So after this data visualization, now we'll move to statistical analysis. So this will help us uncover patterns and relationships in the data. So the first thing we'll do is correlation analysis, and for that we'll write the prompt, analyze the correlation between age and purchase amount. So this correlation analysis helps us understand the relationship between two variables. So this can indicate if older customers tend to spend more or less. So we'll find out that by analyzing the data, and we'll provide a prompt to ChatGPT that analyze the correlation between age and purchase amount. So let's see what it provides. So here's the response by ChatGPT. You could see a scatter plot that shows the relationship between customer age and total sales. That is with a calculated correlation coefficient of approximately 0.16. So this indicates a weak positive correlation between age and purchase amount, suggesting that as customer age increases, there's a slight tendency for total sales to increase as well. So you could just see the scatter plot here, that if the age increases, so it is not correlated to sales, as you could see an empty graph here. So till 40 to 50 years of age or the 70 years of age, you could find what amount they have spent here. That is the total sales accumulated by these ages. So now moving to sales trend. So here we will perform a time series analysis of purchase amount over the given dates. So what does this do is, time series analysis allows us to examine how sales amount changes over time, helping us identify trends and seasonal patterns. So for that we'll write a prompt, perform a time series analysis of purchase amount over given dates. So you could see that ChatGPT has provided us the response, and here is the time series plot showing total sales over the given dates, and each point on the plot represents the total sales for a particular day. So through this you can find out, and the businesses find out, which is the seasonal part of the year and where to stock up their stocks for these kind of dates. And after that you could also do customer segmentation. So what does this do is, so we can use clustering here to segment customers based on age, income, and purchase amount. So clustering groups customers into segments based on similarities. This is useful for targeted marketing and personalized services. And after that we have the advanced usage for data analysis. Here we can draw a predictive modeling table and do the market basket analysis and perform a customer lifetime value analysis. So we will see one of those, and what we'll do is we'll perform a market basket analysis and perform an association rule mining to find frequently bought together products. So the theory behind this is the association rule mining helps identify patterns of products that are often purchased together, aiding in inventory management and cross-selling strategies. So for that, we'll write a prompt that perform an association rule mining to find frequently bought together products. So for that, we'll write a prompt here, perform an association rule mining to find frequently bought products together. So let's see for this prompt, what does ChatGPT-4o respond to us? So you could see that he is providing a code here, but we don't need a code here. We need the analysis. Don't provide code. Do the market basket analysis and provide visualizations. So you could see that ChatGPT has provided the response that given the limitations in this environment, so he is not able to do the market basket analysis here. So but he can help us how we can perform this in an IDE. So he's providing, you can install the required libraries, then prepare the data, and here he is providing the example code. So you could see there are some limitations to ChatGPT-4 also, that he can't do advanced data analysis. So you could use the code in your IDE and do the market basket analysis there. So there are some limitations to ChatGPT-4 also. And now we'll ask ChatGPT, can you create a presentation based on the data set? And we'll provide a data set to it also. So we'll provide sample sales data. And we'll ask him, can you create a presentation or PowerPoint presentation based on this data set and only provide data visualization graphs. So you can see that ChatGPT-4o has started analyzing the data, and he is stating that, and he will start by creating a data visualization from the provided data set and compile them into a PowerPoint presentation. So you could see that ChatGPT-4o has provided us the response, and these are all the presentations or the bar graphs that he has created. And now we have downloaded the presentation here. We will open that, and here's the presentation that is created by ChatGPT-4o.
Today in this video, we are diving into a powerful machine learning algorithm that has made waves in the world of data science, AdaBoost. Whether you are a beginner or experienced data scientist, understanding AdaBoost is crucial for building robust and accurate predictive models. But what exactly is AdaBoost? AdaBoost, short for Adaptive Boosting, is an ensemble learning technique that combines multiple weak classifiers to form a strong classifier. Think of it as a term of experts working together, where each expert focuses on their areas where others might have made mistakes. So by the end of this video, you will clearly understand how AdaBoost works, why it is so effective, and how you can implement it in your projects. So we will start by breaking down the concept of boosting and how AdaBoost fits into this category. Then we will dive into how the algorithm adapts by assigning different weights to each instance, focusing more on mistakes made by a previous model. This unique approach helps us to reduce errors and improve model accuracy significantly. To make things even clearer, we will walk you through a practical example, showing you step by step how AdaBoost can be applied to solve real-world problems, whether you are working on classification problem or trying to improve your model's performance. AdaBoost is a technique you will want in your toolkit. So stay updated, and by the end of this video, you will not only understand AdaBoost, but also feel confident in using it to boost your own models. So without any further ado, let's get started. So what is boosting in machine learning? Boosting refers to the process of creating a strong learner from a collection of weak learners. A weak learner is a model that performs only slightly better than random guessing on the training data. By iteratively adjusting the weights of the training instances, boosting algorithms assign higher importance to misclassified instances, forcing subsequent weak learners to focus on these challenges samples. The final prediction is determined by aggregating the prediction of all weak learners with higher emphasis placed on those that demonstrate superior performance. So now move forward and see types of boosting in machine learning. Types of boosting algorithm. The first one is AdaBoost, adaptive boosting. AdaBoost is the most popular boosting algorithm. It assigns ways to train instances and adjusts these weights based on the performance of weak learners. It focuses on misclassified instances, allowing subsequent weak learners to concentrate on these samples. And the final prediction is determined by aggregating the prediction of all weak learners through a weighted majority vote. The second one is gradient boosting. Gradient boosting is a widely used boosting algorithm that builds an ensemble of decision learning. The third one is XGBoost algorithm, which is also known as extreme gradient boosting. XGBoost is an advanced boosting algorithm that combines gradient boosting with regularization techniques. The fourth one is Light GBM, Light Gradient Boosting Machine. Light GBM is a high-performance boosting algorithm that uses a leaf-wise approach to construct decision trees. So now let's see what is AdaBoost algorithm. So there are several machine learning algorithms available to address your problem statement, and AdaBoost is one of these powerful predictive modeling techniques known as adaptive boosting. So AdaBoost is an ensemble method in machine learning. It commonly uses decision tree with just one split, often called diffusion stumps, as its base estimator. In this approach, the model initially assigns equal weights to all the data points. It then increases the weight of the incorrectly classified points. In subsequent models, these points with higher weight are given more attention. The process continues, training new models until the overall error is minimized. So now let's see working of AdaBoost algorithm. So this image illustrates an example of AdaBoost algorithm using the dataset provided. Okay, so this is a classification problem. Since the targeted column is binary, initially each data point will be assigned an equal weight, as you can see 1 by 5. Okay, so the sample weights are calculated using this following formula. And here n denotes the total number of data points. Okay, in step 2, we will first assess how well gender classifies the samples, followed by evaluation of how the variables age and income perform in classifying the samples. For each feature, we will create a decision stump and calculate its Gini index. The tree with the data lowest Gini index will be selected as our first stump. Let's assume that in our data set, gender has the lowest Gini index, making it our first stump. So in step 3, using this approach, we will now determine the amount of say or importance or influence for this classifier and categories data points using this formula. Okay, here the total error is just the sum of misclassified data points sample weights. If there is one incorrect output in our data set, thus our total error is 1 by 5 and the alpha performance of the stump. Okay, using this. So now we will find out the performance of the stump. So using this formula, here 0 represent a flawless stump while 1 represent a bad stump. So according to this graph, where 0 is misclassification, there is no error. Hence the amount of say alpha, you can say, will be a huge value. Okay, when the classifier predicts half correctly and half incorrect, the total error is 0.5 and the classifier segment's amount of say equals to 0. Okay, and if all the samples were improperly categorized, the error will be quite large, about to 1, and our alpha value will be negative integer. Okay, negative integer, you can say -2. Okay, in step 4, you might be wondering why it's necessary to calculate a stumps, total error, and performance. The reason is straightforward. We need to update the weights because if the same weights are used in the next model, it will yield the same result as previous one. The weights of incorrectly predicted points will be increased while those of the correctly predicted points will be decreased. Okay, more emphasis will be placed on the points with higher weights. So after assessing the classifier significance, the total error we update weights using this formula. New sample weight equals to old weight multiplied by amount of say alpha. Okay, when the sample is successfully identified, the amount of say alpha will be negative, and when the sample is misclassified, the amount of alpha will be positive. You can say here plus and minus. There are 4 correctly categorized samples and 1 incorrectly classified sample. So in this case, the sample weight of the data point is 1/5 and the quantity of say performance of the gender stump is 0.69. Okay, so these are the following new sample weights. Okay, so this is the adjusted weight for incorrectly categorized. Okay, 0.398. So here the total sum of the weights must equal 1, but the updated weights add up to 0.8004. To normalize them, we divide each weight by 0.8004, making the total sum equals to 1. After normalization, the dataset weights now sum to 1. Okay, see, now sum to 1. So in step 5, we must know how to create a fresh dataset to see whether or not the mistake have decreased. To do this, we will delete the same weights and new sample weights column and then split our data points into buckets based on new sample weights. Okay, and in step 6, we are almost done here. The method now selects random values between 0 to 1. Since misclassified records have higher sample weights, so they are more likely to be selected. Let's say the algorithm randomly selects the number 0.38 or 0.26 or anything. Next, we will see where these random number falls within the weighted range and create our new dataset. So this is our new dataset. So in step 7, the new dataset will be used to repeat the previous steps. Start by assigning equal weights to each point, identifying this term, the best classify the sample of calculating the Gini index and selecting the one with the lowest value. So assume we have sequentially built 3 decision trees DT1, DT2 and DT3 using our dataset. Okay, so when we run our dataset through these trees, the class with the majority will be determined and we will make prediction based on that. Today we are talking about must-have Python AI projects and how to build them so that can really help you sharpen your skills and stand out in the growing field of artificial intelligence. So let's quickly see what is Python. Python is one of the most popular programming languages for AI because its simplicity and the powerful libraries it offers, like TensorFlow, Keras, and PyTorch. Building projects using Python is a great way to get started if you want to break into the AI industry. Whereas artificial intelligence is transforming industries like healthcare, finance, and even entertainment. Companies are now looking for experts who know how to apply AI to real-world problems. In this video, we will explore beginner level to advanced level projects. So these projects are designed to give you hands-on experience in building intelligent systems, analyzing data, and even automating tasks. So without any further ado, let's get started. So let's start with beginner level projects. So number 1, we have fake news detection using machine learning. So in today's world, fake news is a major concern, causing misinformation to spread rapidly across social media and news platforms. Detecting fake news is crucial to maintaining the integrity of the information we consume. So these projects aim to build a machine learning model that can identify fake news articles by analyzing their textual content, by learning from existing datasets of real and fake news. The model will be able to classify articles into these 2 categories, thus assisting media outlets and social media platforms in reducing the spread of misinformation. This project is perfect introduction to natural language processing, NLP, as it involves text data manipulation, feature extraction, and supervised learning. It can also be adapted for real-time use on website or social media platforms to flag suspicious articles and provide more reliable information to users. So now let's see how to build this. In this, first step is data collection. Use dataset like LIAR or fake news net that can contain label, real, and fake news articles. You can find dataset from the Kaggle. The second step is pre-processing. Clean the text by removing stop words, punctuation, and special character. Tokenize and stem words using NLTK or spacing. The third step is feature extraction. Use TF, IDF, or bag of words to convert the text into numerical data for machine learning models. The fourth step is model training. Train a classifier like Logistic Regression, naive Bayes, or random forest on the dataset. The fifth step is evaluation. Evaluate the model using accuracy, precision, recall, and F1 score metrics to determine how well it classifies fake and real news. Tools you can use is NLTK, Scikit-learn, and Pandas. Skills you will gain from this are text preprocessing, NLP, classification models. And if you want to make us video on this project, please comment down below. In number 2, we have image recognition using CNN. Image recognition is one of the core applications of deep learning and computer vision, used in a variety of industries ranging from healthcare to autonomous vehicles. This project will guide you through building an image classifier using CNNs, a deep learning architecture designed specifically for image recognition tasks. The goal is to create a model that can accurately classify images, such as differentiating between cats and dogs. By working on this project, you will gain a solid understanding of the fundamental concepts of CNNs, such as convolutional layers, pooling, and activation functions. This project not only introduces you to the basics of CNNs, but also teaches essential skills like image preprocessing, dataset handling, and model evaluation, which can be applied to more advanced computer vision projects in the future. So now let's see how to build this project. In this project, first you have to import dataset. So use a dataset like CIFAR10 or Kaggle cats versus dogs with labeled images. The second step is preprocessing. Resize, normalize, and augmented images using libraries like OpenCV or PIL to prepare the dataset. The third step is model architecture. Design a basic CNN model with convolutional, pooling, and fully connected layers using Keras or TensorFlow. The fourth step is training. Split the dataset into training and validation sets and train the CNN model to classify images. The fifth step is model evaluation. Use accuracy, precision, and confusion metrics to evaluate how well the model predicts the correct class label. Tools you will use in this project are Keras, TensorFlow, OpenCV, Pandas. Skills you will gain after doing these projects are image preprocessing, CNN architecture, model evaluation. And if you want to make us video on image recognition using CNN, please comment down below. Second, we have intermediate level projects. In this first, we have AI-based recipe recommendation system. Recommendation systems have become an integral part of modern digital platforms. From e-commerce websites suggesting product to users to streamlined services recommending shows and movies. So in this project, you will build a recipe recommendation system that suggests dishes based on the ingredients a user has on hand. This project demonstrates how recommendation algorithms such as content-based filtering and collaborative filtering can be used to provide personalized suggestions. You will also learn how to pre-process data and clean textual data, such as ingredient lists, and implement a machine learning algorithm to match user inputs with recipe databases. This is an excellent project for understanding how recommendation systems work and how they can be applied in various industries, from food tech to personalized content recommendations. So now let's see how to build this. In this project, first step is data collection. Use web scraping tools like Beautiful Soup to scrape recipes from websites, or use datasets like Recipe1M. The second step is pre-processing. Normalize and clean ingredient data by standardizing ingredient names and handling missing values. The third step is recommendation algorithms. Implement content-based filtering and collaborative filtering to recommend recipes. Content-based filtering matches ingredient list, while collaborative filtering uses user preferences model. Fourth step is model training. Use cosine similarity to match user-provided ingredients with recipe ingredient in the dataset. And the next step is interface and tools. So create a simple web interface using Flask where users can input ingredients and receive recipe recommendation. Tools you will use: Beautiful Soup, Pandas, Scikit-learn, and Flask. So you will gain skills like web scraping, data cleaning, recommendation systems using this project by doing this project. And if you want to make us video on this project, please comment down below. Number 4, we have chatbot with sentiment analysis. Chatbots have transformed how businesses and services interact with users, providing 24/7 support and personalized responses. In this project, you will build a conversational chatbot that can analyze the sentiment behind user inputs and respond accordingly. By incorporating sentiment analysis, the chatbot will not only understand the content of the user's messages, but also the emotional tone, such as whether the user is happy, frustrated, or neutral. This allows the chatbot to adjust its tone and responses to improve user satisfaction. For example, a chatbot could offer a more empathetic response if it detects a negative sentiment. This project will give you hands-on experience in building a conversational AI system while learning how to integrate machine learning techniques like sentiment analysis. The skills you develop in this project can be applied to customer service, healthcare, education, and more. So now let's see how to build this project. In this project, the first step is chatbot framework. Use tools like Dialogflow or Rasa to build a convolutional chatbot capable of handling various user intents. The second step is sentiment analysis. Integrate a sentiment analysis model using pre-trained models like VEDA or BERT. The third step is conversational flow. Adjust the chatbot's responses based on the sentiment, positive, negative, or neutral, detected in the user's input. The fourth step is integration and deployment. So build an interface, website, or messaging platform where users can interact with the chatbot in real time, and deploy the chatbot on a website or app, allowing user to engage with it and receive sentiment-aware responses. So you will use tools in this are Dialogflow, Rasa, Vader, Transformers, Flask, and you will gain skills like sentiment analysis, chatbot deployment, conversational AI. And if you want to make us video on this project, please comment down below. So now let's see some advanced level projects. In this we have AI-powered image colorization. Image colorization is a fascinating application of deep learning that transforms black and white images into color by predicting and applying realistic colors to grayscale images. This project explores how CNN and GANs can be used to learn mapping between grayscale and colored images. You will gather dataset of colored images, convert them into grayscale, and train the model generate color version. This project is especially useful in areas such as film restoration, photography, and artistic creation, where colorization can breathe new life into old black and white images. Moreover, it highlights the power of deep learning in understanding and generating complex visual data, giving you insight into how these models work for tasks like image generation, video prediction, and beyond. The skills you learn in this project will also be useful for other creative AI applications like style transfer and image synthesis. So now let's see how to build this project. So in this project, first step is data collection. Use dataset of colored image, convert them into grayscale, and use the grayscale images as inputs while training the model to output colorized version. The second step is pre-processing. Normalize images pixel values and resize them for training. The third step is model architecture. Implement a UNet model or generative adversarial network (GANs) which are well suited for image generation tasks like colorization. Fourth step is training and evaluation. Train the model on grayscale images as input and colored images as output using mean squared error method for guidance. Evaluate with visual inspection and peak signal to noise ratio. The last step is deployment. So create a web interface where user can upload black and white images and get them colorized. So you will use tools like TensorFlow, Keras, OpenCV, and Flask. So we'll gain skills like deep learning, CNNs, JNs, and image preprocessing. And if you want to make a video on AI-powered image colorization project, so please comment down below. And the last we have object detection using YOLO. You only look once. Object detection is one of the most popular computer vision applications, allowing machine to recognize and locate multiple objects within an image or video stream in real time. YOLO is a state-of-the-art object detection algorithm known for its speed and accuracy. This project involves building a real-time object detection system capable of identifying multiple objects in images or videos feeds by drawing bounding boxes around them. Object detection has widespread use in fields such as security surveillance, autonomous driving, and augmented reality, where systems need to understand and interact with their surroundings in real time. By working on this project, you will learn how to pre-process image data, format bounding box labels, and train a YOLO model using a dataset like Coco or Pascal. You will also gain a valuable experience in deploying object detection systems that process video streams, giving you the skills to build application in dynamic environment, from traffic monitoring to industrial robotics. So now let's see how to build this project. So in this project, we will first import dataset. So use a dataset like Coco or Pascal VOC, which contains label objects in images with bounding boxes. The second step is pre-processing. Resize image and normalize pixel values, ensuring bounding box labels are appropriately formatted. The third step is model architecture. Use the YOLO, you only look once architecture, which splits images into a grid and predicts bounding boxes and class probabilities for each object. The fourth step is training and evaluation. Train the YOLO model on labeled data using a framework like DarkNet. Evaluate the model using metrics like intersection over union and mean average precision. The last step is deployment. Develop a system that can process video streams in real time, detecting objects and drawing bounding boxes around them. Tool you will use OpenCV, TensorFlow, and DarkNet. You will gain skills like object detection, YOLO architecture, real-time video processing. And if you want to make videos on this project, please comment down below. So in conclusion, these Python AI projects not only help you build hands-on skills, but also provide a solid foundation for advancing your career in artificial intelligence. Whether you are working on fake news detection, image recognition, or developing advanced tools like chatbots and object detection systems, these projects offer real-world applications that companies are looking for. Start small, keep learning, and as you complete each project, you will get better prepared to take on the challenges in the growing AI field.
Did you know that you can easily build a website for free using AI? And that's not a trick. It's completely true. Thanks to the amazing new AI tools, anyone can create a website even without writing a single line of code. Even if you have no technical experience, you can set up a professional website quickly and easily. In this video, I'm going to show you how you can build a website without even writing a single line of code, using the power of AI and no-code tools. In today's video, we have split this video into two parts to make it more simple and easy to follow. So whether you are a complete beginner or a business owner or even a student, this is something anyone can do. In the first part, I'll guide you through how to build a website using Pantheon and WordPress. You don't need any coding skills for this. Plus, we will use Gravity Write, an AI tool that helps you generate content for your website, like About Us page or blog post. AI will take care of everything from writing to saving your time and also giving the maximum effort. In the second part, we look at some of the best AI website builders like Durable, Cleap AI, and Pineapple AI. These tools are actually free of cost and can build your website for you just in few seconds. You don't even have to worry about the design or content. AI will handle everything. It's fast, easy, and perfect for anyone who needs a website but doesn't want to struggle with coding. So if you're looking to create a website quickly and for free, you're in the right place. Stick around and I'll show you step by step how to get your website live using these top-notch code and AI-powered platforms. So let's get started and see how AI is making web design easier than ever. So let's move on to the demo part. Alright, so now that we know what we're going to cover, let's jump into the first part, which is building a website using Pantheon. And this is the Pantheon website we have logged in. And for this, you have to just click on Get Started. And then we will move on to the WordPress part. So here, as you can see, you have to just simply fill up your details. So I've filled up my details here and just click on Continue. Wait for a few seconds till the dashboard is being loaded. And then you have to just simply click on Create a Site. And then we will be selecting WordPress. So now, as you can see, we have successfully logged into our Pantheon account and we have also created our account. Now the next step will be installing this WordPress account and then deploying our website in Pantheon in WordPress. So we will just simply click on WordPress here. Okay, you have to enter your Pantheon site name. Suppose I want to keep my name as Urban Threads India and then just click on Continue here. So as you can see, the site name already exists. So we have to just change our name. We'll just put new over here. Let's see what it shows. New Urban Threads. And just click on Continue. So if this website name is not registered, it will successfully create my website using this particular name. So now the dashboard is being loaded. We just have to wait for a few seconds till it deploys our WordPress. Okay, so now that our WordPress is successfully deployed, we just have to click on Visit Your Pantheon Site Dashboard. And then it will load the dashboard. So now you have to click on Visit Development Site. And here you have to select the preferred language which you'll be using. So I've already selected my language, which is English here, and just click on Continue. And now as you can see that our WordPress installation is successfully done. So now I'll be just writing my title name, which is New Urban Threads. And write the username here, provide your name, and yeah, this password you can copy it or you can change your password accordingly. Just provide your email address here and click on discourage search engines from indexing this site and just select on Install WordPress. So now that our installation is completely done, we can log into our WordPress account, and here you have to provide your username and the email address which you have used in order to create this account. copy paste the password here and just click on login. So this is the WordPress interface here. Now, so this is the WordPress installation we have done, and now the next step will be building our website. So as you can see, we have successfully installed our WordPress, and this is the dashboard being shown. Now you have to click on plugins and just select add new plugin. And from here, you have to select plugin, which is a starter template, and just select enter. So this is the template which we will be using to create our website. So you have to install this template here, wait for a few seconds and then click on activate. So there are two ways of building our website here. The first one is using the AI website builder, which will be using features like zip-WP to help to build a website faster. And the second step, which is quite old and traditional, which is using the classic starter template. So using this method, you have to create a website, professionally designed templates to meet the requirements. I mean, you have to just select a template, already made website template, and from there you can customize and edit accordingly. But for the first step, I'll be showing you how to make using the AI website builder. So just simply click on build with AI. Okay, and here you have to select let's get started. So as you can see, we are building our website using zip-WP, which is an AI tool that can automatically create our website content and layout, and it makes our work super easy. So now, as you can see, we are connecting our zip-WP account with this website, Pantheon website, and then we will click on continue here. Okay, so as now you can see, we have logged into our zip-WP account, and from here you can select as per as your use. So for now, we will be going with the free version and just click on get started here. So this is the verification code it has sent to my email. We'll just wait for a few minutes. So now you have to give the name of your website which you're building, which was New Urban Threads, and you just have to provide the detail. What is this website used for? Is it for clothing, spa, gym, local business, non-profit, entrepreneur, agency? So here we will just click on entrepreneur and just click on next. So it's written describe your new urban threads in few words. So here you have to describe what your website, what your business is about in a few words. Or also here's an option like you can also write using the AI. So you can just simply click here, write using AI, and now you can see it has created a description for your Urban Threads website account. So it has already written what your website will be about. See, it's written it's an innovative fashion brand in San Francisco. Since we are in India, you can all modify here as per as your needs. So just provide Bengaluru and I'll just give your India. Okay, and whatever customization you have to do, you can do it. So it was founded 2001. I'll just put it 2024 and just click on next. So as you can see, it has already given a description for your website here, and now you have to provide your email address. You can also add your social media account if you want to, and just click on next here. Okay, so these are the images you want to pick. So just select on the images. Since it's my clothing online store, you can just select few images from here. You can select this. You can also just simply search here fashion or street style fashion. Okay, so as you can see, these are few images it has shown for us. I'll just select this also. You can also upload your images if you want to, and then we will click on next. So now since we have described our website and given our contact details and address and also uploaded the image here, the next step is choosing the design. So here from this templates given, you can choose your design, whatever you want your website to be displayed as. So these designs are actually premium. You can select, since we are using the free trial here, you can select the free version here. So whatever style it's looking good, you can just select that accordingly. Since I like this more, I'll just select this. And this is just a sneak peek of how our actual website will be. So just take a look, how will it look like. Alright, and from here you can actually upload your logo. So just click on select files. So this is our logo here, new urban threads. And you can also decrease the logo width accordingly. You can also change the font pair, whatever you want your website font to be in. So since I like this more, I'll just keep it this. You can change the color palette also. So I'll be selecting this as my color palette and I'll select continue. So also you can add features in your website, what features you want. Blog, contact form, automation integrations, video player, page builder, e-commerce, that cart, donations, free live chat. So I will just simply click on free live chat as I want this to be displayed as a feature in my website, and I'll just select start building. So we are preparing your website. You just have to wait for a few seconds till it prepares our website. So as you can see, our website is now ready and you can just click on this option. Okay, and now the next step will be editing our layout and the content in our website according to. Just simply click on edit page here. So from here you can just edit the home page, sustainable or okay. So this is the description here. You can add it accordingly, or you can also ask the AI to write it or make it more shorter here. You can also change the layout of this button, and from here click on content and the image icon you want it to be. So if you want this icon to be labeled, you have to just click on select here, and what style you want in your title plus your description. You can just change it accordingly. Since I want to keep it in white color, I'll just go with it. And okay, Alex turns journey to some sustainable fashion. These are the demo post 1 reviews. You can just simply click here and change if you want to. These are the testimonials of what our customers say here. And now if you want to stay in touch, you have to just enter your email address. To continue reading, you can just select here. So see, you can just customize it accordingly and edit your layout if you want to. And the best way I do it is using an AI tool known as Gravity Write. So you can just search your Gravity Write. This AI tool will help you to generate content for your website. I'll just show you how. So you have to just enter your email address here. Okay, so as you can see, it has got bundles and plenty of option here to provide you content for any of your thing, for booking management, course creator, music, website content. So since I want content for my website, see, you can even get some domain name ideas and create homepage, service page content using this AI tool, which is really amazing. So let's go back to our web page and we will just simply save this. So now we have finally viewed our page here. So this is how our actual page will look like. Our actual website, how it looks like. Isn't it really amazing? Just within few seconds, following few steps, you are now able to create an amazing website. So now that we have created a website, the next step is purchasing a domain name. For this, you can use one website which is called Web Space Kit or Hostinger. So I'll be showing you here. Just simply type Web Space Kit. And if you think you can buy a free domain, I don't think so it is possible to buy a free domain. It's obviously paid, but then you can use this website to actually buy a domain in lesser price, which is only 139 rupees per month. And you can just view the plans and simply buy. And the next website is Hostinger. So these services will let you buy a domain and host your website in a very small fee. So all the links will be added in the description box if you want to check out these websites and create and buy your domain for publishing it online in the internet. You can use either hosting it or WebSpace Kit. Also, one more thing. Now that we have decided to move our website for WebSpace Kit for hosting, you need to install a plugin on your Pantheon website, which is known as Migrate Guru. And using this plugin, you can actually, wait, I'll show you the plugin here. So you have to just simply click on add new plugin, and the plugin name is Migrate Guru. So we'll just search for Migrate Guru here. And using this, you have to just simply click on this. Now, why do we have to do it? I've already explained you. This will help you just have to install it on both your Pantheon site as well as your WebSpace, and it will help you to move everything over just within a few clicks. So we have now created a fully functional website using our AI. The second step was using the template version. You can also use the template version if you want to. So now that we have covered how to build a website using Pantheon, WordPress, so now we will discuss quickly the free AI tools which you can use to make your website even more faster. The first one on the list is Hookos AI. So you just have to simply click on Hookos AI Builder and it will create your website within just 5 minutes. So you have to just simply enter your email address and just click on Get Your AI Website here. As you can see, within just few steps, you have to just provide the details and the description of the website purpose. So suppose it's for travel, just simply write travel here and select categories like travel agent, equipment store. So it's a travel blog, so I'll just simply click on travel blog here. So you just can provide it accordingly what features you want to be included in your website here. So if I want to create a blog website for travel, just simply click on write a blog and just create a website. So as you can see, these are the steps here involved. So it's for my online business only. You can just simply provide business name here. Wander with me is my website name. So now you can see we're almost finished. So select the 3 unique aspects of your business, which is affordable prices, friendly, easy navigation, and just select on continue here. Just one more step and we will be done building our website. The second step is you can either what website visitors, how you want your website visitors to connect with you. So if you want your website visitors to connect via phone or contact form, I want them to connect via contact form and I'll just simply click on continue. So this is the layout they have generated for us for my travel blog website. Select the template you wanted. I like this one, so I'll just quickly click on this and select continue. So see, this is the website it has created for me here and it's really good. So I really like the layout it has generated for me here and also the font. You can just change, customize and edit your blog accordingly. If you want to keep it in pink color, you can also choose that and also edit the images if you want to. See, you can add your touch here and I like it in this font. If you like it in this font, you can just simply click here and create my website. So as you can see, our site is now created here. And this is really amazing. I mean, within just a few steps, you can create a fully functional website using this AI tool. Now let's discuss the second AI tool on the list, which is Leia AI. Just search your LEIA AI website builder. And this is also one of the amazing website builder you can create within just few seconds. You have to just click on get started here and just type, suppose I want a yoga studio website and just click on next here. Just build my site and click on continue. So it will not take even a minute to build this website. Just click on view it. And now you can see that a yoga studio website is functionally built here, like just within. And this is way more, I guess, faster than the previous AI website we have discussed before. I mean, you do not have to even provide description and it will just generate website for you. So from here, you can just simply replace the image, delete the element you want to, and add the content accordingly. So this was way more faster than the previous website, AI website we have generated. Now let's quickly dive into the third website tool, which is Pineapple AI. Just simply type Pineapple AI website builder and see. This is the website's interface, and here also you can just simply write your website you want. For example, you want a website for kindergarten school. You want to create a website for kindergarten school offering best education in town with all the modern technologies used to educate students. And just simply click on generate here. So see, you have to train your AI and just provide the business details you want to, and just simply click on next option to generate your website. So you can just simply click on the website template you want to. So if I like this one, I'll just simply click here and just click on AI customize, and see, it will generate a website for you. And from here you can add details to start generation. And like this, you can create a website. I mean, it is good, but I like the previous two AI tools more, which could create really amazing website within just a few seconds. This was the template we had selected, and from here you have to just simply click on each of the content you want to edit and just pick your design here. Alright, so let's move on to the next website, which is Cleep AI. Just simply search Cleep AI website builder, and let's see how this website is. So you can just simply click on try for free option here and search for business. If your business is related to health and beauty, just select that. If you're an entrepreneur, select entrepreneur. What name it should be? Fit India. What's your goal to make money online? Location you can set accordingly. With AI, add some information. For information, you can use either ChatGPT or your Gravity Rai to generate content. So just copy paste the content here from either ChatGPT or your this. You can also provide your logo and the picture of your choice, and just simply click on next here. You can choose any of the style you want, and now you can see that your AI is building your content. So as you can see, this website is being created using the Cleep AI tool. So this is a website. You can just click on the site settings and just change the template or the style you want, however you want to be. So let's talk about the final AI website builder, which is my personal favorite, which is Durable AI. So we just click on Durable AI and let's check how this AI will create content for us. We'll just select generate your website here. So what type of website are you building? It's we will use the same fashion online clothing store. Name of your business is Trendy Collections. Just click on generate websites. So you just have to wait for a few seconds and our website will be generated. So since I had provided my location, Bengaluru, so it has created my website called Bangaluru's latest collection website. You can check it now. So as you can see, our website is now ready and you can also edit your website accordingly. This tool creates websites in a matter of seconds. Just give some basic details and Durable AI generates a complete website including content, images and layout. If you're in a hurry, this is the perfect solution for you. I would highly recommend using this tool. And now you can see the pricing label and everything mentioned here. It's superb. I mean, the quality and the layout it has provided is really good. So now you can just click on edit section and edit accordingly. So guys, we have come to the end of our video. You know now how to build a no-code website using platforms like Pantheon and WordPress, as well as how quickly it generates website using AI-powered builders like ZipWP, Hookoo's AI, Clip AI, and my personal favorite, Durable AI. So whether you want full control over your website or fast AI-generated solutions, these tools are really game changers. So check out the link mentioned in the description box and you are good to go.
Imagine this, you are using a calculator app on your phone and it gives you an answer to be a complex math problem faster than you can blink. Pretty standard, right? But what if instead of just crunching numbers, that app could actually think through the problem, breaking it down like a human would, considering the best approach, and even explaining why it made certain decisions? Sound futuristic, doesn't it? Well, we are not too far from that reality. Today we are diving into OpenAI's latest project, codenamed Strawberry, a new AI model that pushing the boundaries of reasoning and problem solving. So in this video, we will break down what makes Strawberry special, how it works, and why it could change the game for AI systems moving forward. So first off, what exactly is Strawberry? According to recent report, OpenAI is preparing to release this new AI model in the next 2 weeks or in the couple of weeks. And it's set to improve on things like reasoning and problem solving. Previously known as Q or Q star, this model is designed to be much better at thinking through problems compared to what we have seen from previous versions. What makes Strawberry different from what we have used before? So now let's take a look. One of the coolest things about Strawberry is that it uses something called system 2 thinking. This idea came from the famous psychologist Daniel Kahneman, and it refers to a more careful and slow way of thinking. Like when you really focus on solving a tricky problem, instead of answering question instantly, Strawberry takes about 10 to 20 seconds to process its thought. This extra time helps it to avoid mistakes and gives more accurate answers. But the model doesn't just think slowly. It's got some really cool abilities that makes it stand out. Let's talk about those. Strawberry is built to handle advanced reasoning and solve mathematical problems. These are areas where AI systems struggles, but Strawberry is designed to be a lot better at breaking down complex problems step by step. And here is something interesting. It might even be added to future versions of ChatGPT, possibly as a model name called Orion or GPT-5. If that happens, it could mean ChatGPT will become more smarter and more reliable in solving tough problems. Now, here is where it gets really fascinating. There is some research that might help us understand how Strawberry improves its thinking. Let's check it out. You might have heard about something called STAR, which stands for Self-Taught Reasoner. This is a method where an AI can actually teach itself to think better. Here is how it works. STAR starts with a few examples where the AI is shown how to solve problems step by step. Then the AI tries solving their problem on its own, getting better as it goes. It keeps improving by looking at its mistakes and learning from them. This could be what's happening with Strawberry. It's using similar method to teach itself how to reason better and solve complex problems. But the AI doesn't just think better. It's also learning how to break down the problems in a very human-like way. So now let's explore that next. Strawberry uses something called chain of thought reasoning. Basically, when faced with a complex problem, it breaks it down into smaller, manageable steps. Kind of like how we do when we are solving a puzzle. Instead of just jumping on to an answer, it takes its time to go through each step, making the solution more understandable and accurate. So this is especially useful in math, where Strawberry is expected to be really strong. With all its potential, what does the future hold for AI models like Strawberry? So now let's wrap this thing with a look at what's next. So now what's next for OpenAI? Well, Strawberry is just the beginning. There is talk about a future model called Orion, which could be the next big version after GPT-4. or GPT-4o. It may even use that Strawberry learners to get better at solving problems. But here is the thing. Training these advanced models is expensive. Training GPT-4, for example, cost over 100 million, even though OpenAI CEO Sam Altman said the era of just making bigger models is coming to an end. It's clear that the models like Strawberry are focused on becoming smarter and more efficient. So what does all of this mean for the future of AI and how we use it? Strawberry could represent a huge leap in AI's ability to reason and solve complex problems. So with its focus on slower, more deliberate thinking and its potential connection to the STAR method, it's paving the way for smarter, more reliable AI system. And this is just the start. As we move forward, models like Orion, the possibilities are endless. And that's a wrap on OpenAI exciting new model Strawberry. It's clear that this AI could bring major advancement in reasoning and problem solving. And we can't see how it all unfolds. What are thoughts on your Strawberry? Do let us know in the comment section below.
So without any further ado, let's begin with top AI, ML and deep learning interview questions for 2023. Over to our experts.
We'll start with a very general concept of what is deep learning. This is where we take large volumes of data, in this case on cats and dogs or whatever. A lot of times you use a training setup to train your model. Remember, it's kind of like a magic black box going on there. Then we use that to extract features or extract information, and in this case classify the image of a cat and a dog. So the primary takeaway when we're talking about deep learning is it learns from large volumes of structured and even unstructured data and uses complex algorithms to train neural network. It also performs complex operations to extract hidden patterns and features. And if we're going to discuss deep learning in this very simplified overview, then we also have to go over what is a neural network. This is a common image you'll see of a drawing of a forward propagation neural network. And it's a human brain inspired system which replicate the way humans learn. So this is inspired how our own neurons in our brain fire, but at a much simplified level. Obviously it's not ready to take over the human population and be our leader yet, not for many years. It's very much in its infant stage. But it's inspired by how our brains work. And they use a lot of other inspirations. You can study brains of moths and other animals that they've used to figure out how to improve these neural networks. The most common one consists of 3 layers of network, and this is generally how you view these networks, is you have an input, you have a hidden layer, and an output. And the neural network is broken up into many pieces, but when we focus just on the neural network, it's always on the hidden layers that we're making all the adjustments and figuring out how to best set up those hidden layers for their functions to both train faster and to function better. When we look at this, of course, we have our input, hidden, and output. Each layer contains neurons called as nodes that perform various operations. And you can see here we have the list of the nodes. We have both our input nodes and our output nodes, and then our hidden layer nodes. And it's used in deep learning algorithms like CNN, RNN, GAN, etc. We'll address some of these models a little closer, at least the most common models, as we go down the list and we study the deep learning and the neural network framework. Let's start with what is a multi-layer perceptron, or MLP, a lot of time is referred to. And you'll see these abbreviations. I'll be honest, I have to write them down on a piece of paper and go through them because I never remember what they all mean, even though I play with them all the time. What is a multi-layer perceptron? Well, if you look at the image on the right, it's very similar to what we just looked at. You have your input layer, your hidden layer, and your output layer. And that's exactly what this is. It has the same structure of a single layer perceptron with one or more hidden layers, except the input layer. Each node in the other layers uses a nonlinear activation function. What that means is your input layer is your data coming in, and then your activation function is based upon all those nodes and weights being added together, and then it has the output. MLP uses supervised learning method called backpropagation for training the model. Very key word there is backpropagation. Single layer perceptron can classify only linear separable classes with binary output, 0, 1, but the MLP can classify nonlinear classes. So let's break this down just a little bit. The multi-layer perceptron with an input layer and a hidden layer and an output layer. As you see that it comes in there, it adds up all the numbers and weights depending on how your setup is, that then goes to the next layer, that then goes to the next hidden layer if you have multiple hidden layers, and finally to the output layer. The backpropagation takes the error that it sees. So whatever the output is, it says, hey, this has an error to it, it's wrong. And then sends that error backwards from where it came from. And there's a lot of different functions used to train this based on that error and how that error goes backwards in the nodes. So forward is you get your answers, backward is for training. You see this every day. Even my Google Pixel phone has this. They train the neural network, which takes a lot more data to train than it does to use. And then they load up that neural network into, in this case I have a Pixel 2, which actually has a built-in neural network for processing pictures. And so it's just the forward propagation I use when it processes my photos. But when they were training it, you use the back propagation to train it with the errors they had. We'll be coming back to different models that are used. For right now, though, multi-layer perceptron, MLP. Put that down as your vocabulary word. And, of course, back propagation. What is data normalization and why do we need it? This is so important. We spend so much time in normalizing our data and getting our data clean and setting it up. So when we talk about data, there's a pre-processing step to standardize the data. So whatever we have coming in, we don't want it to be a 1 gigabyte file here, a 2 gigabyte picture here, and a 3 kilobyte text there. Even as a human, I can't process those all in the same group. I have to reformat them in some way that loops them together so that it's standardized format. We use this data normalization in pre-processing to reduce it and eliminate data redundancy. A lot of times the data comes in and you end up with two of the same images or the same information in different formats. Then we want to rescale values to fit into a particular range for achieving better convergence. What this means is with most neural networks, they form a bias. We've seen this recently in attacks on neural networks where they light up one pixel or one piece of the view and it skews the whole answer. So suddenly, because one pixel is really bright, it doesn't know what to do. Well, when we start rescaling it, we put all the values between, say, -1 and 1, and we change them and refit them to those values. It helps get rid of that bias, helps fix for some of those problems. And then finally, we restructure the data and improve the integrity. We want to make sure that we're not missing values or we don't have partial data coming in. One way to look at this is bad data in, bad data out. So you want clean data in and you want good answers coming out. One of the most basic models used is a Boltzmann machine. So let's address what is a Boltzmann machine. And if you know, we just did the MLP, multi-layer perceptron. So now we're going to come into almost a simplified version of that. And in this we have our visible input layer and we have our hidden layer. The Boltzmann machines are almost always shallow. They're usually just two-layer neural nets that make stochastic decisions whether a neuron should be on or off, true, false, yes, no. First layer is the visible layer, and second layer is the hidden layer. Nodes are connected to each other across layers, but no two nodes of the same layer are connected. Hence it is also known as restricted Boltzmann machine. Now that we've covered a basic MLP or multi-layer perceptron, and we've gone over the Boltzmann machine, also known as the restricted Boltzmann machine, let's talk a little bit about activation formulas. And this is a huge topic that can get really complicated, but it also is automated, so it's very simple. So you have both a complicated and a simple at the same time. So what is the role of activation functions in a neural network? Activation function decides whether a neuron should be fired or not. That's the most basic one. And that actually changes a little bit because it's either whether it's fired or not, in this case activation function, or what value should come out when it's fired. But in these models we're looking at just the Boltzmann restricted layers. So this is what causes them to fire. Either they don't or they do. It's a yes or no, true, false, all or nothing. It accepts the weighted sum of the inputs, the bias, as input to any activation function. So whatever our activation function is, it needs to have the sum of the weights times the input. So each input, if you remember on that model, and let's just go back to that model real quick. And then you always have to add a bias. And you can look at the bias if you remember from your Euclidean geometry. You draw a straight line. Formula for that line has a y coordinate at the end. It's always cx plus m or something like that, where m is where it crosses the y coordinates if you're doing a straight line. With these weights, it's very similar, but a lot of times we just add it in as its own weight. We take it as a node of a one value coming in, and then we compute its new weight, and that's how we compute that bias, just like we compute all the other weights coming in. The node which gets fired depends on the y value, and then we have a step function. And the step function, this is where, remember I said it's going to get complicated and simple all at the same time? We have a lot of different step functions. We have the sigmoid function, we have just a standard step function, we have the ReLU is pronounced like ray, the ray from the sun, and lu, like a name. So ReLU function. And we have the tangent H function. And if you look at these, they all have something similar. They all either force it to be one value or the other. They force it to be, in the case of the first three, a 0 or a 1. And in the last one, it's either a -1 or a 1. And you can easily convert that to a 0, 1, yes, no, true, false. And on this, one of the most common ones is the step function itself, because there is no middle value. There is no discrepancy that says, well, I'm not quite sure. But as you get into different models, probably the most commonly used, used to be the sigmoid was most commonly used, but I see the ReLU used more often. Really, depending on what you're doing, you just have to play with these and find out which one works best, depending on the data in your output. The reason to have a non-0-1 answer or something kind of in the middle is when you're looking at this and it's coming out, you can actually process that middle ground as part of the answer into another neural network. So it might be that the ReLU function says, hey, this is only a 0.6, not a 1. And even though the 1 is what's going into the next neural network or the next hidden layer as an input, the 0.6 value might also be going in there to let you know, hey, this is not a straight up 1 or a straight up 0, it's someplace in the middle. This is a little uncertain what's coming out here. So it's a very powerful tool. But in the basic neural network, you usually just use the step function. It's yes or no. Let's take a big step back and take a kind of an overview. The next function is what is a cost function that we're going to cover. This is so important because this is your end result that you're going to do over and over again and use to decide whether the model is working or not, whether you need to try a different step function, whether you need to try a different activation, whether you need to try a fully different model used. So what is the cost function? Cost function is a measure to evaluate how good your model's performance is. It is also referred as loss or error, used to compute the error of the output layer during backpropagation. There's our backpropagation where we're training our model. That's one of our key words. Mean squared error is an example of a popular cost function. And so here we have the cost function C equals half of y minus y predicted, and then you square that. So the first thing is, real quick, if you haven't done statistics, this is not a percentage. It's not a percentage of how accurate it is. It's just a measurement of the error. And we take that error for training it, and we push that error backwards through the neural network, and we use that through the different training functions, depending on what model you're using, to train the neural network. So when you deploy the network, you're usually done training it because it takes a lot of computational force to train it. This is a very simple model. And so you deploy the trained one, but we want to know how your error is. And so how do we do that? Well, you split your data. Part of your data is for training and part of your data is for testing. And then we can also test the error on there. So it's very important. And then we're going to go one more step on this. We got to look at both the local and the global setup. It might work great to test your data on what you have on your computer, but that's different than in the field. So when we're talking about all these different tests in the error test, as far as your loss, you want to make sure that you're in a closed environment when you do initial testing, but you also want to open that up and make sure you follow up with the testing on the larger scale of data, because it will change. It might not fit the larger scale. There might be something in there in the way you brought the data in specifically, or the data group you used, or any of those could cause an error. So it's very important to remember that we're looking at both the local and the global context of our error. And just one other side note on a lot of the newer models of neural networks, by comparing the error we get on the data, our training data, with a portion of the test data, we can actually figure out how good the model is, whether it's overfitted or not. We'll go into that a little bit more as we go into some of the different models. So we have our output. We're able to figure out the error on it based on the square means usually, although there's other functions used. So we want to talk about what is gradient descent, another vocabulary word. Gradient descent is an optimization algorithm to minimize the cost function or to minimize the error. Aim is to find the local or global minima of a function. Determine the direction the model should take to reduce the error. So, as we're looking at this, we have our squared error that we just figured out based on the cost function. It says, how bad is my model fitting the data I just put through it? And then we want to reduce that error. So how do you figure out what direction to do that in? Well, it could be that you're looking at just that line of data coming in, so that would be a local minima. We want to know the error of that particular setup coming in. And then you have your global minima. We want to minimize it based on the overall data we're putting through it. And with With this, we can figure out the global minimum cost. We want to take all those local minimum costs of each piece of data coming in and figure out the global one. How are we going to adjust this model to fit all the data? We don't want it to be biased just on 3 or 4 lines of data coming in. We want it to kind of extrapolate a general answer for all the data coming in. But this, of course, we mentioned it briefly about back propagation. This is where it really comes in handy, is training our model. Neural network technique to minimize the cost function helps to improve the performance of the network, back propagates the error, and updates the weights to reduce the error. So as you can see here is a very nice depiction of a back propagation. We have our predicted y coming out, and then we have, since it's a training set, we already know the answer, and the answer comes back, and based on, in case of the square means was one of the functions we looked at, one of the activation functions based on cost function. That cost function then, depending on what you choose for your back propagation method, and there's a number of them, will change the weights. It will change the weight going to each of one of those nodes in the hidden layer, and then based upon the error that's still being carried back, it'll change the weights going to the next hidden layer. And then it computes an error level on that and sends that back up. And you're going to say, well, if it computes the error into the first hidden layer and fixes it, why would it stop there? Well, remember, we don't want to create a biased neural network. So we only make small adjustments on these weights. We don't make a big adjustment that changes everything right off the bat. So no matter how far back you go, you're always going to have a small amount of error, and that's still going to continue to go all the way back up the hidden layers. For right now, focus on the back propagation, is taking that error and moving it backwards on the neural network to change the weights and help program it so that it'll have the correct answers. So far, we've been talking about forward propagation neural networks. Everything goes forwards, goes left to right. But let's take a little detour and let's see what is the difference between a feed-forward neural network and a recurrent neural network. Now this is in the function, not when we're training it using the back propagation. So you've got new information coming in and you want to get the answer. And there's a couple different networks out there, and we want to know, we have a feed-forward neural network and we have a new vocabulary term, recurrent neural network. A feed-forward neural network. Signals travel in one direction from input to output. No feedback loops. Considers only the current input. Cannot memorize previous inputs. One example of one of these feed-forward neural networks, and we've covered a number of them, but one of the ones that has a big highlight nowadays is the CNN, a convolutional neural network. TensorFlow, the one put out by Google, is probably most known for their CNN, where the information goes forward. It first takes a picture, splits it apart, goes through the individual pixels on the picture, so it picks up a different reading, then calculates based on that, goes into a regular feed-forward neural network, and then gives your categorization on there. Now, we're not covering the CNN today, but we do have a video out that you can look up on YouTube, put out by Simplilearn, the convolutional neural network. Wonderful tutorial. Check that out and learn a lot more about the convolutional neural network. But you do need to know that the CNN is a forward propagation neural network only. So it's only moving in one direction. So we want to look at a recurrent neural network. Signals travel in both directions, making it a looped network. Considers the current input along with the previous received inputs for generating the output of a layer. Has the ability to memorize past data due to its internal memory. And you can see they have a nice image here. We have our input, and for some reason they always do the recurrent neural network in reverse from bottom up in the images. Kind of a standard, although I'm not sure why. Your X goes into your hidden layer, and your hidden layer, the answer for part of the answer from that it generates feeds back into the hidden layer. So now you have an input of both X and part of the hidden layer, and then that feeds into your output. Now if we go back to the forward, let me just go back a slide, and we're looking at our forward propagation network. One of the tricks you can do to use just a forward propagation network is if you're in a what they call a time sequence. That's a good term to remember, or a time series, meaning that it's sequential data. Each term comes after the other. You can trick this by creating your input nodes with the history. So if you know that you have values 1, 5, and 7 going in, and you know what the output is from what those outputs are, you can expand the input to include the history input. That's one of the ways to trick a forward propagation network into looking at that. But when you do it with a recurrent neural network, you let the hidden layer do that for you. It sends that data and reprocesses it back into itself. What are some of the applications of recurrent neural network? The RNN can be used for sentiment analysis and text mining. Getting up early in the morning is good for health. And it's a positive sentiment. One of the catches you really want to look at this when you're looking at the language is that I could switch this around and totally negate the meaning of what I'm doing, so it would no longer be positive. So when you're looking at a sentence, knowing the order of the words is as important as the meaning of the words. You can't just count how many good words there are versus bad words to get a positive sentiment. You now have to know what they're addressing. And there's lots of other different uses. Kids are playing football, or soccer as we call it in the US. RN can help you caption an image. So based on previous information coming in, it refeeds that back in and you have a image setter. And then time series problems like predicting the prices of stocks in a month or quarter or sale of products can be solved using an RNN. And this is a really good example. You have whatever your stocks were doing earlier this month will have a huge effect on what they're doing today if you're investing. So having an RNN model, a recurrent neural network, feeding into itself what was happening previously allows it to take that model and program in that whole series without having to put in the whole a month at a time of data. You can only put in one day at a time, but if you keep them in order, it will look back and say, oh, this is because of what happened yesterday. I need some information from that, and I'm going to use that to help predict today's, and so on and so on. We're going to go back to our activation functions. Remember I told you ReLU is one of the most common functions used? So let's talk a little bit more about ReLU and also softmax. Softmax is an activation function that generates the output between 0 and 1. It divides each output such that the total sum of the outputs is equal to 1. It is often used in the output layers. Softmax L of the n equals e to L of the n over the absolute value of e to the L. So what does this function mean? I mean, what is actually going on here? So we have our output nodes, and our output nodes are giving us, let's say they gave us 1.2, 0.9, and 0.4. As a human being, I look at that and I say, well, the greatest value is 1.2, so whatever category that is, if you have 3 different categories, maybe you're not just doing if it's a cat or it's a dog or, let's say it's a cow. Remember we had cats and dogs earlier. Why the cats and dogs are hanging out with a cow, I don't know. But we have a value, and it might say 1.2 is a cat, 0.9 is the dog, and 0.4 is a cow. For some reason it thinks that there's a chance of it being any one of these 3 items, and that's how it comes out of the output layer. Well, as a human, I can look at 1.2 and say this is definitely what it is. It's definitely a cat or whatever it is. Maybe it's looking at different kinds of cars. Might be a better, whether it's a car, truck, or a motorcycle. Maybe that'd be a better example. Well, from a computer standpoint, that might be a little confusing because they're just numbers waving at us. And so with the softmax, we want all those numbers to always add up to 1. So when I add 3 numbers together, I want the final output to be 1 on there. And so it goes through this formula, changes each of these numbers. In this case, it changes them to 0.46, 0.34, and 0.20. They all add up to 1. And that's a lot easier to register because it's very set. It's a set output. It's never going to be more than 1. It's never going to be less than 0. And so you can see here that there's probably a pretty high chance that it's the first one. So as a human being, we have no problem knowing that. But this output can then also go into, say, another input. So it might be an automated car that's picking up images, and it says that image in front of us is probably a big truck. We should deal with it like it's a big truck. It's probably not a motorcycle, or whatever those categories are. That's the softmax part of it. But now we have the ReLU. Well, where's the ReLU coming from? Well, the ReLU is what's generating the 1.2 and the 0.9 and the 0.4. And so if you remember, our ReLU stands for Rectified Linear Unit and is the most widely used activation function. We looked at a number of different activation functions, including tangent H, the step function. I remember I said the step function is really used if that's what your actual output is, because then you know it's a 0 or 1. But the ReLU, if you have that as your output, you now have a discrepancy in there. And if that's going into another neural network or another process, having that discrepancy is really important. And it gives an output of x if x is positive and 0 otherwise. So it says my x value is going to be somewhere between 0 or 1. And then the usually, unless it's really uncertain, the output's usually a 1 or 0. And then you have that little piece of uncertainty there that you can send forward to another network, or you can look at to know that there's uncertainty involved. And is often used in the hidden layers. This is what's coming out of the hidden layers into the output layer usually. Or as we referenced the convolutional neural network, the CNN, which you'd have to go to another video to review, the ReLU is the most common used for convolutional part of that network. It has a bunch of little pieces that are very simplified, looking at all the different images or different sections of the map, and the ReLU works really good for that. And like I said, there's other formulas used, but this is the most common one, and you'll see that in the hidden layers going maybe between one layer and the next layer. So just a quick recap, we have our softmax, which means that if you have numerous categories, only one of them is going to be picked, but you also want to have some value attached to it, how well it picked it. And you put that between 0 and 1, so it's very standardized. So we have our softmax. We looked at that. Let's go back one. We looked at that here, where it transforms the numbers. And then we have our ReLU function, which takes the information and the summation and puts it between a 0 and a 1, where it's either clearly a 0 or, depending on how confident our model is, it'll go between the 0 and 1 value. What are hyperparameters? Oh, this is a great interview question. Hyperparameters. When you are doing neural networks, this is what you're playing with most of the time once you've gotten the data formatted correctly. A hyperparameter is a parameter whose value is set before the learning process begins, determines how a network is trained and the structure of the network. This includes things like the number of hidden units. How many hidden layers are you going to have, and how many nodes in each layer? Learning rate. Learning rate is usually multiplied once you figured out the error and how much you want to change the weights. We talked about, or I mentioned it early just briefly, you don't want to just make a huge change, otherwise you're going to have a biased model. So you only take some little incremental changes, and that's what the learning rate is those small incremental changes. Epochs. How many times are you going to go through all the data in your training set? So one epoch is one trip through all the data. And there's a lot of other things depending on which model you're working with and which programming script you're working with. Like the Python sklearn package will have it slightly different than, say, Google's TensorFlow package, which will be a little bit different than the Spark machine learning package. So these are just some examples of the hyperparameters. And so you see in here we have a nice image of our data coming in, and we train our model, then we do a comparison to see how good our model is, and then we go back and we say, hey, this model's pretty good, but it's biased. So then we send it back and we change our hyperparameters to see if we can get an unbiased model, or we can have a better prediction on it that matches our data closer. What will happen if learning rate is set too low or too high? We have a nice couple graphs here. We have one over here that says the learning rate set too low. You can see that it slowly works its way down the curve. And on the right, you can see a learning rate set too high. It's just bouncing back and forth. When your learning rate is too low, that's what we studied at 2 slides ago, that's what the learning rate was, training of the model will progress very slowly as we are making very tiny updates to the weights. We'll take many updates before reaching the minimum point. So I just mentioned epoch, going through all the data. You might have to go through all the data 1,000 times instead of 500 times for it to train. Learning rate too high causes undesirable divergent behavior to the loss function due to drastic updates in weights. At times it may fail to converge or even diverge. So if you have your learning rate set too high and it's training too quickly, maybe you'll get lucky and it trains after one epoch run, but a lot of times it might never be able to train because the weights are changing too fast. They flip back and forth too easy. And you see down here we've introduced 2 new terms, converge and diverge. Converge means that our model has reached a point where it's able to give a fairly good answer for all the data we put in. All those weights have adjusted and it's minimized the error. Diverge means that the data is so chaotic that it can never manage to train to that data. The data is just too chaotic for it to train. So we have 2 new words there, converge and diverge are important to know also. What is dropout and batch normalization? Dropout is a technique of dropping out hidden and visible units of a network randomly to prevent overfitting of data. It doubles the number of iterations needed to converge the network. So here we have our standard neural network, and then after applying dropout. Now it doesn't mean we actually delete the node. The node is still there, and we're still going to use that node. What it means is that we're only going to work with a few of the nodes. A lot of times, I think the most common one right now used is 20%. So you'll drop out 20% of the nodes when you do your training. You reverse propagate your data, and then you'll randomly pick another 20 nodes the next time you go through an epoch data training. So each time you go through through one epoch, you will randomly pick 20 of those nodes not to mess with. And this allows for less overfitting of the data. So by randomly doing this, you create some, I guess it just kind of pulls some nodes off to the sides and says we're going to handle the data later on so we don't overfit. Batch normalization is a technique to improve the performance and stability of neural network. The idea is to normalize the inputs in every layer so that they have mean output and activation of 0 and standard deviation of 1. This question covers a lot of different things, which is great. It's a great interview question because it pulls in that you have to understand what the mean value is. So a mean output activation of 0, that means our average activation is 0. So when you normalize it, remember usually we're going between -1 and 1 on a lot of these. It's a very standard setup. So you have to be very aware that this is your mean output activation of 0. And then we have our standard deviation of 1. So we want to keep our error down to just a 1 value. The benefits of this doing a batch normalization is it provides regularization, it trains faster, higher learning rates, and weights are easier to initialize. What is the difference between batch gradient descent and stochastic gradient descent? Batch gradient descent. Batch gradient computes the gradient using the entire data set. It takes time to converge because the volume of data is huge and weights update slowly. So you can look at the batch as, a lot of times if you're using big data, batch the data in, but you still go through a full epoch. You still go through all the data on there. So batch gradient descent means you're going to use it to fit all the data and look for a convergence there. Stochastic gradient descent. Stochastic gradient computes the gradient using a single sample. It converges much faster than batch gradient because it updates weight more frequently. Explain overfitting and underfitting and how to combat them. Overfitting happens when a model learns the details and noise in the training data to the degree that it adversely impacts the execution of the model on the new information. It is more likely to occur with nonlinear models that have more flexibility when learning a target function. An example of this would be if you're looking at, say, cars and trucks and motorcycles, it might only recognize trucks that have a certain box-like shape. It might not be able to notice a flatbed truck unless it's only a specific kind of flatbed truck or only Ford trucks because that's what it saw on the training set. This means that your model performs great on your trained data and great on maybe a small test amount of data, but when you go to use it in the real world, it leaves out a lot and is not very functional outside of your small area, your small laboratory data coming in. Underfitting, doing the opposite when you underfit your data. Underfitting alludes to a model that is neither well trained on training data nor can generalize to new information. Usually happens when there is less and improper data to train a model, has a poor performance and accuracy. So if you're using underfitted data and you generate a model and you distribute that in a commercial zone, you'll have a lot of people unhappy with you because it's not going to give them very good answers. So we've explained overfitting and underfitting, so now we want to ask how to combat them. Combating overfitting and underfitting. Resampling the data to estimate the model accuracy, k-fold cross-validation. Having a validation data set to validate the model. So when we do the resampling, we're randomly going to be picking out data, and we'll run it a few times to see how that works, depending on our random data and how we sample the data to generate our model. And then we want to go ahead and validate the data set by having our training data and then keeping some data on the side, testing data to validate it. How are weights initialized in a network? Initializing all weights to 0. All the weights are set to 0. This makes your model similar to a linear model. So if you have linear data coming in, doing a basic setup like that might work. All the neurons in every layer perform the same operation given the same output and making the deep net useless. Right there is a key word. It's going to be useless if you initialize everything to 0. At that point, be looking into some other machine learning tools. Initializing all weights randomly. Here the weights are assigned randomly by initializing them very close to 0. It gives better accuracy to the model since every neuron performs different computations. And here we have the weights are set randomly. We have our input layer, the hidden layers, and the output layer. And W equals NP random, random N. Layer size L minus 1. This is the most commonly used, is to randomly generate your weights. What are the different layers in CNN? Convolutional neural network. First is the convolutional layer that performs a convolutional operation. We have our other video out if you want to explore that more, so we can go into detail exactly how the convolutional layer works in the CNN as far as creating a number of smaller picture windows that go over the data. The second step is as a ReLU layer. ReLU brings nonlinearity to the network and converts all the negative pixels to 0. Output is rectified feature map. So it goes into a mapping feature there. Pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. So we have all our ReLU layer, which is pulling all these little maps out of our convolutional layer. It's taking that picture and creating little tiny neural networks to look at different parts of the picture. Then we need to pool it together. And then finally, the fully connected layer. So we flatten our pooling layer out, and we have a fully connected layer recognizes and classifies the objects in the image. And that's actually your forward propagation, reverse propagation training model, usually. I mean, there's a number of different models out there, of course. What is pooling in CNN, and how does it work? Pooling, used to reduce the spatial dimensions of a CNN, performs downsampling operation to reduce the dimensionality, creates a pooled feature map by sliding a filter matrix over the input matrix. I mentioned that briefly on the previous slide. It's important to know that you have, if you see here, they have a rectified feature map. And so each one of those colors, like the yellow color, that might be one of a smaller little neural network using the ReLU. It'll just kind of go over the main picture and look at all the different areas on the main picture. So you might step 1, 2, 3, 4 spaces. And then you have another one that's also looking at features. And it has a 2, 7, 8, 5. Each one of those is a map. So it might be, the first one might be a map looking for cat ears, and the second one looking for human eyes. When it does this, you then have this rectified feature map looking at these different features. And the max pooling with the 2x2 filters and a stride of 2. Stride means instead of skipping every pixel, you're going to go every 2 pixels. You take the maximum values. And you can see over here, when we look at a pooled feature map, one of the features says, hey, I had a max value of 8, so somewhere in here we saw a human eye labeled as 8, pretty high label. And maybe 7 was a human hand, and maybe 4 was cat whiskers, or something that we thought might be cat whiskers. 4 is kind of a low number in this particular case compared to the other ones. So you have your full pooled feature map. You can see the process here as we have our stepping. We look for the max value, and then we create a pooled feature map of the maxed values. How does a LSTM network work? And that's long short-term memory. So the first thing to know is that an LSTMs are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. We did look at the RNN briefly, talked about how the hidden layer feeds back into itself. With the LSTM, it has a much more complicated feedback, and you can see here we have the hidden layer of t-1, and the hidden layer, that's what the H stands for, hidden layer of t, and the formula is going in. As we can see here, we have the hidden layers. We have t-1 and then h of t, where t stands for time. So this is a series. Remember, working with series, and we want to remember the past. And you can see you have your input of t, and that might be a frame in a video. As a frame comes in, they usually use in this one the tangent H activation formula, but you also see that it goes through a couple other formulas, the omega formula. And so when it combines these, that then goes into the next layer, your next hidden layer. That then goes into the data that's submitted to the next input. So you have your x of t plus 1. So when you have that coming in, then you have your h value that's coming forward from the last process. And depending on how many of these omega structures you put in there, depends on how long-term the memory gets. So it's important to remember this is more for your long-term recurrent neural networks. The 3 steps in an LSTM. Step 1 decides what to forget and what to remember. Step 2 selectively updates cell state values. So based on what we want to remember and forget, we want to update those cell values. And then decides what part of the current state make it to the output. So now we have to also have an output on there. What are vanishing and exploding gradients? This is a great question that affects all our neural networks. While training an RNN, your slope can become either too small or too large, and this makes the training difficult. When the slope is too small, the problem is known as vanishing gradient. So our slope, we have our change in x and our change in y. When the slope decreases gradually to a very small value, sometimes negative, and makes training difficult. When the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. The slope grows exponentially. You can see a nice graph of that here. Issues in gradient problem: long training time, poor performance, and low accuracy. What is the difference between epoch, batch, and iteration in deep learning? Epoch. An epoch represents one iteration over the entire data set. So that's everything you're going to go ahead and put into that training model. Batch. We cannot pass the entire data set into the neural network at once, so we divide the data set into a number of batches. And then iteration. If we have 10,000 images as data and a batch size of 200, then the epoch should run 10,000 times over 200. So that means we have our total number over the 200 equals 50 iterations. So in each epoch, we're running over all the data set, we're going to have 50 iterations. And each of those iterations includes a batch of 200 images in this case. Why TensorFlow is the most preferred library in deep learning? Well, first, TensorFlow provides both C++ and Python APIs that makes it easier to work on. Has a faster compilation time than other deep learning libraries like Keras and Torch. TensorFlow supports both CPUs and GPUs computing devices. So right now TensorFlow is at the top of the market because it's so easy to use for both programmer side and for hardware side and for the speed of getting something up and running. What do you mean by tensor in TensorFlow? Tensor is a mathematical object represented as arrays of higher dimension. These arrays of data with different dimensions and ranks that are fed as input to the neural network are called tensors. And you can see here we have a tensor of dimensions 5, 4. So it's a two-dimensional tensor coming in. You can look at an image like this, that each one of those pixels is a different value if it's a black and white. So it might be 0 and 1s, and then each one represents a black and white image. In a color photo, you might either find a different value system, or you might have a tensor value that has the XY coordinates as we see here, plus the colors. So you might have 3 more different dimensions for the 3 different images, the red, the blue, and the yellow coming in. And even as you go from one layer or one tensor to the next, these layers might change. We might flatten them, might bring in numerous, in the case of the convergence neural network, we have all those smaller different mappings of features that come in. So each one of those layers coming through is a tensor if it has multiple dimensions coming in and weights attached to it. What are the programming elements in TensorFlow? Well, we have our constants. Constants are parameters whose value does not change. To define a constant, we use tf.constant command. Example, a equals tf.constant 2.0 tf_float 32. So it's a tensor float value of 32. B equals tf constant 3.0. Print AB. If we did a print of AB, we'd have tf.constant, and then of course B is that instance of it. Variables. Variables allow us to add new trainable parameters to graph. To define a variable, we use tf.variable command and initialize them before running the graph in session. Example, w equals tf variable 0.3 dtype tf_float 32, or b equals the tf variable -3, dtype float 32. Placeholders. Placeholders allow us to feed data to a TensorFlow model from outside a model. It permits a value to be assigned later. To define a placeholder, we use tf_placeholder command. Example, a equals tf placeholder, b equals a times 2. With the tf session as SESS, result equals session run, b, feed dictionary equals a 3.0, print result. So we have a nice example there of a placeholder. Session. A session is run to evaluate the nodes. This is called as the TensorFlow runtime. So for example, you have a equals tf constant 2.0, b equals tf constant 4.0, c equals a plus b. And at this point, you'd go ahead and create a session equals tf session, and then you could evaluate the tensor c, print session run c. That would input C as an input into your session. What do you understand by a computational graph? Everything in TensorFlow is based on creating a computational graph. It has a network of nodes where each node performs an operation. Nodes represent mathematical operation and edges represent tensors. Since data flows in a form of a graph, it is also called a data flow graph. And we have a nice visual of this graph, or graphic image of a computational graph. And you can see here we have our input nodes, our add, multiply nodes, and our multiply node at the end. And then we have the edges where the data flows. So we have from A going to C, A going to D. You can see we have a 2 flowing, 4 flowing. Explain generative adversarial network along with an example. Suppose there is a wine shop that purchases wine from dealers, which they will resell later. So we have our dealer going to the wine, our shop owner that then sells it for a profit. But there are some malefactor dealers who sell fake wine. In this case, the shop owner should be able to distinguish between fake and authentic wine. The forger will try different techniques to sell fake wine and make sure certain techniques go past the shop owner's check. So here's our forger, fake wine, shop shop owner. The shop owner would probably get some feedback from the wine experts that some of the wine is not original. The owner would have to improve how he determines whether a wine is fake or authentic. Goal of forger, to create wines that are indistinguishable from the authentic ones. Goal of shop owner, to accurately tell if the wine is real or not. There are two main components of generative adversarial network. And we'll refer to it as a noise vector coming in, where we have our forger who's going to generate fake wine, and then we have our real authentic wine, and of course our shop owner who has to figure out whether it's real or fake. The generator is a CNN that keeps producing images that are closer in appearance to the real images, while the discriminator tries to determine the difference between real and fake images. The ultimate aim is to make the discriminator learn to identify real and fake images. What is an autoencoder? The network is trained to reconstruct its inputs. It is a neural network that has 3 layers. Here the input neurons are equal to the output neuron. The network's target outside is same as the input. It uses dimensionality reduction to restructure the input. Input image comes in, we have our Latin space representation, and then it goes back out reconstructing the image. It works by compressing the input to a Latin space representation and then reconstructing the output from this representation. What is bagging and boosting? Bagging and boosting are ensemble techniques where the idea is to train multiple models using the same learning algorithm and then take a call. So we have in here where we're bagging, we take a data set and we split it. We're going to have our training data and our test data. Very standard thing to do. Then we're going to randomly select data into the bags and train your model separately. So we might have bag 1, model 1, bag 2, model 2, bag 3, model 3, and so on. In boosting, the emphasis is to select the data points which give wrong output in order to improve the accuracy. So in boosting, we have our data set. Again, we split it to test data and train data. And we'll take bag 1 and we'll train the model. Data points with wrong predictions then go into bag 2, and we then train that model and repeat.
So if you are looking to try your hands on this field, then do check Simplilearn's postgraduate program in AI and machine learning. So hurry up and enroll now. Find the course link in the description box.
So one of the first questions that you may face is, what are the different types of machine learning? Now, what is the best way to respond to this? There are 3 types of machine learning. If you read any material, you will always be told there are 3 types of machine learning. But what is important is you would probably be better off emphasizing that there are actually 2 main types of machine learning, which is supervised and unsupervised. And then there is a third type, which is reinforcement learning. So supervised learning is where you have some historical data and then you feed that data to your model to learn. Now, you need to be aware of a keyword that they will be looking for, which is labeled data. Right? So if you just say past data or historical data, the impact may not be so much. You need to emphasize on labeled data. So what is labeled data? Basically, let's say if you're trying to train your model for classification, you need to be aware of, for your existing data, which class each of the observations belong to, right? So that is what is labeling. So it is nothing but a fancy name, you must be already aware, but just make it a point to throw in that keyword labeled, so that will have the right impact. Okay, so that is what is supervised learning, when you have existing labeled data which you then use to train your model. That is known as supervised learning. And unsupervised learning is when you don't have this labeled data. So you have data, it is not labeled. So the system has to figure out a way to do some analysis on this. Okay, so that is unsupervised learning. And you can then add a few things like what are the ways of performing supervised learning and unsupervised learning, or what are some of the techniques. So supervised learning, we perform, or we do regression and classification, and unsupervised learning we do clustering. Okay? And clustering can be of different types. Similarly, regression can be of different types, but you don't have to probably elaborate so much. If they are asking for just the different types, you can just mention these and just at a very high level you can. But if they want you to elaborate, give examples, then of course I think there is a different question for that. We will see that later. Then the third, so we have supervised, then we have unsupervised, and then reinforcement. You need to provide a little bit of information around that as well, because it is sometimes a little difficult to come up with a good definition for reinforcement learning. So you may have to a little bit elaborate on how reinforcement learning works.
right? So reinforcement learning works in such a way that it basically has two parts to it. One is the agent and the environment, and the agent basically is working inside of this environment, and it is given a target that it has to achieve, and every time it is moving in the direction of the target, so the agent basically has to take some action, and every time it takes an action which is moving the agent towards the target, right, towards a goal. A target is nothing but a goal, okay? Then it is rewarded, and every time it is going in a direction where it is away from the goal, then it is punished. So that is the way you can a little bit explain, and this is used primarily or very, very impactful for teaching the system to learn games and so on. Examples of this are basically used in AlphaGo. You can throw that as an example where AlphaGo used reinforcement learning to actually learn to play the game of Go, and finally it defeated the Go world champion. Right? This much of information that would be good enough. Okay. Then there could be a question on overfitting. So the question could be, what is overfitting and how can you avoid it? So what is overfitting? So let's first try to understand the concept, because sometimes overfitting may be a little difficult to understand. Overfitting is a situation where the model has kind of memorized the data. So this is an equivalent of memorizing the data. So we can draw an analogy so that it becomes easy to explain this. Now let's say you're teaching a child about recognizing some fruits or something like that. Okay? And you're teaching this child about recognizing, let's say, 3 fruits: apples, oranges, and pineapples. Okay, so this is a small child, and for the first time you're teaching the child to recognize fruits. Then, so what will happen? So this is very much like that is your training data set. So what you will do is you will take a basket of fruits which consists of apples, oranges, and pineapples. Okay, and you take this basket to this child, and there may be, let's say, hundreds of these fruits. So you take this basket to this child and keep showing each of this fruit, and then first time obviously the child will not know what it is. So you show an apple and you say, hey, this is apple. Then you show maybe an orange and say this is orange, and so on and so forth. And then again you keep repeating that, right? So till that basket is over. This is basically how training works. In machine learning also, that's how training works. So till the basket is completed, maybe 100 fruits, you keep showing this child. And then in the process, what has happened, the child has pretty much memorized these. So even before you finish that basket, right, by the time you are halfway through, the child has learnt about recognizing the apple, orange, and pineapple. Now what will happen after halfway through? Initially you remember it made mistakes in recognizing, but halfway through now it has learned. So every time you show a fruit, it will exactly 100% accurately it will identify. It will say, the child will say this is an apple, this is an orange, and if you show a pineapple, it will say this is a pineapple. Right? So that means it has kind of memorized this data. Now let's say you bring another basket of fruits, and it will have a mix of maybe apples, which were already there in the previous set, but it will also have, in addition to apple, it will probably have a banana or maybe another fruit like a jackfruit. Right? So this is an equivalent of your test data set, which the child has not seen before. Some parts of it probably has seen, like the apples it has seen, but this banana and jackfruit it has not seen. So then what will happen? In the first round, which is an equivalent of your training data set, towards the end it has 100% it was telling you what the fruits are. Right? Apple was accurately recognized, orange was accurately recognized, and pineapples were accurately recognized. Right? So that is like 100% accuracy. But now when you get a fresh set which were not a part of the original one, what will happen? All the apples maybe it will be able to recognize correctly, but all the others like the jackfruit or the banana will not be recognized by the child. Right? So this is an analogy, this is an equivalent of overfitting. So what has happened during the training process, it is able to recognize or reach 100% accuracy, maybe very high accuracy. Okay, and we call that as very low loss. Right? So that is the technical term. So the loss is pretty much 0 and accuracy is pretty much 100%. Whereas when you use testing, there will be a huge error, which means the loss will be pretty high and therefore the accuracy will be also low. Okay, this is known as overfitting. This is basically a process where training is done. Training process it goes very well, almost reaching 100% accuracy, but while testing, it really drops down. Now, how can you avoid it? So that is the extension of this question. There are multiple ways of avoiding overfitting. There are techniques like what you call regularization. That is the most common technique that is used for avoiding overfitting. And within regularization, there can be a few other subtypes like dropout in case of neural networks and a few other examples. But I think if you give example or if you give regularization as the technique, probably that should be sufficient. So there will be some questions where the interviewer will try to test your fundamentals and your knowledge and depth of knowledge and so on and so forth. And then there will be some questions which are more like trick questions that will be more to stump you. Okay, then the next question is around the methodology. So when we are performing machine learning training, we split the data into training and test, right? So this question is around that. So the question is, what is training set and test set in machine learning model, and how is the split done? So the question can be like that. So in machine learning, when we are trying to train the model, so we have a 3-step process. We train the model and then we test the model, and then once we are satisfied with the test, only then we deploy the model. So what happens in the train and test is that you remember the labeled data. So let's say you have 1,000 records with labeling information. Now, one way of doing it is you use all the 1,000 records for training, and then maybe, right, which means that you have exposed all these 1,000 records during the training process, and then you take a small set of the same data and then you say, okay, I will test it with this. Okay, and then you probably, what will happen, you may get some good results. Right? But there is a flaw there. What is the flaw? This is very similar to human beings. It is like you are showing this model the entire data as a part of training. Okay, so obviously it has become familiar with the entire data. So when you're taking a part of that again and you're saying that I want to test it, obviously you will get good results. So that is not a very accurate way of testing. So that is the reason what we do is we have the label data of this 1,000 records or whatever. We set aside, before starting the training process, we set aside a portion of that data and we call that test set, and the remaining we call as training set, and we use only this for training our model. Now, the training process, remember, is not just about passing one round of this data set. So let's say now your training set has 800 records. It is not just one time you pass this 800 records. What you normally do is you actually, as a part of the training, you may pass this data through the model multiple times. So this 1,000 records may go through the model maybe 10, 15, 20 times till the training is perfect, till the accuracy is high, till the errors are minimized. Okay, now, so which is fine, which means that that is what is known as the model has seen your data and gets familiar with your data. And now when you bring your test data, what will happen is this is like some new data, because that is where the real test is. Now you have trained the model and now you are testing the model with some data which is kind of new. That is like a situation, like a realistic situation, because when the model is deployed, that is what will happen. It will receive some new data, not the data that it has already seen, right? So this is a realistic test. So you put some new data. So this data which you have set aside is for the model, it is new. And if it is able to accurately predict the values, that means your training has worked. Okay, the model got trained properly. But let's say while you're testing this with this test data, you're getting a lot of errors. That means you need to probably either change your model or retrain with more data and things like that. Now, coming back to the question of how do you split this, what should be the ratio? There is no fixed number. Again, this is like individual preferences. Some people split it into 50-50, 50% test and 50% training. Some people prefer to have a larger amount for training and a smaller amount for test. So they can go by either 60-40 or 70-30, or some people even go with some odd numbers like 65-35 or 63.33 and 33, which is like 1/3 and 2/3. So there is no fixed rule that it has to be something, the ratio has to be this. You can go by your individual preferences. All right, then you may have questions around data handling, data manipulation, or what do you call data management or preparation. So these are all some questions around that area. There is again no one answer, one single good answer to this. It really varies from situation to situation, and depending on what exactly is the problem, what kind of data it is, how critical it is, what kind of data is missing, and what is the type of corruption. So there are a whole lot of things. This is a very generic question, and therefore you need to be a little careful about responding to this as well. So probably have to illustrate this again. If you have experience in doing this kind of work in handling data, you can illustrate with examples saying that I was on one project where I received this kind of data. These were the columns where data was not filled, or these were this many rows where the data was missing. That would be, in fact, a perfect way to respond to this question. But if you don't have that, obviously, if you have to provide some good answer, I think it really depends on what exactly the situation is. And there are multiple ways of handling the missing data or corrupt data. Now, let's take a few examples. Now, let's say you have data where some values in some of the columns are missing, and you have pretty much half of your data having these missing values in terms of number of rows. Okay, that could be one situation. Another situation could be that you have records or data missing, but when you do some initial calculation, how many records are corrupt or how many rows or observations, as we call it, has this missing data. Let's assume it is very minimal, like 10%. Okay. Now, between these two cases, how do we? So let's assume that this is not a mission critical situation, and in order to fix this 10% of the data, the effort that is required is much higher, and obviously effort means also time and money, right? So it is not so mission critical, and it is okay to, let's say, get rid of these records. So obviously one of the easiest ways of handling the data part or missing data is remove those records or remove those observations from your analysis. So that is the easiest way to do. But then the downside is, as I said, as in the first case, if let's say 50% of your data is like that, because some column or the other is missing. So it is not like in every place, in every row, the same column is missing, but you have in maybe 10% of the records, column 1 is missing, and another 10% column 2 is missing, another 10% column 3 is missing, and so on and so forth. So it adds up to maybe half of your data set. So you cannot completely remove half of your data set, then the whole purpose is lost. Okay, so then how do you handle? Then you need to come up with ways of filling up this data with some meaningful value, right? That is one way of handling. So when we say meaningful value, what is that meaningful value? Let's say for a particular column, you might want to take a mean value for that column and fill wherever the data is missing, fill up with that mean value, so that when you're doing the calculations, your analysis is not completely way off. So you have values which are not missing, first of all, so your system will work. Number two, these values are not so completely out of whack that your whole analysis goes for a toss. Right? There may be situations where if the missing values, instead of putting mean, maybe a good idea to fill it up with the minimum value or with a 0. So, or with a maximum value. Again, as I said, there are so many possibilities. So there is no like one correct answer for this. You need to basically talk around this and illustrate with your experience. As I said, that would be the best. Otherwise, this is how you need to handle this question. Okay, so then the next question can be, how can you choose a classifier based on a training set data size? So again, this is one of those questions where you probably do not have like a one-size-fits-all answer. First of all, you may not, let's say, decide your classifier based on the training set size. Maybe not the best way to decide the type of the classifier. And even if you have to, there are probably some thumb rules which we can use. But then again, every time, so in my opinion, the best way to respond to this question is you need to try out few classifiers irrespective of the size of the data, and you need to then decide on your particular situation which of these classifiers are the right ones. This is a very generic issue, so you will never be able to, just by if somebody defines a problem to you, and somebody, even if they show the data to you or tell you what is the data or even the size of the data, I don't think there is a way to really say that yes, this is the classifier that will work here.
No, that's not the right way. So you need to still, test it out, get the data, try out a couple of classifiers, and then only you will be in a position to decide which classifier to use. You try out multiple classifiers, see which one gives the best accuracy, and only then you can decide. Then you can have a question around confusion matrix. So the question can be explain confusion matrix, right? So confusion matrix, I think the best way to explain it is by taking an example and drawing like a small diagram. Otherwise it can really become tricky. So my suggestion is to take a piece of pen and paper and explain it by drawing a small matrix. And confusion matrix is about to find out, this is used especially in classification learning process, and when you get the results, when our model predicts the results, you compare it with the actual value and try to find out what is the accuracy. Okay, so in this case, let's say this is an example of a confusion matrix, and it is a binary matrix. So you have the actual values, which is the labeled data, right? And so you have how many yes and how many no. So you have that information, and you have the predicted values, how many yes and how many no, right? So the total actual values, the total yes is 12 plus 1, 13, and they are shown here. And the actual value no's are 9 plus 3, 12. Okay, so that is what this information here is. So this is about the actual and this is about the predicted. Similarly, the predicted values, there are yes are 12 plus 3, 15 yeses, and no are 1 plus 9, 10 no's. Okay, so this is the way to look at this confusion matrix. Okay, and out of this, what is the meaning conveyed here? So there are 2 or 3 things that needs to be explained outright. The first thing is, for a model to be accurate, the values across the diagonal should be high, like in this case, right? That is one. Number 2, the total sum of these values is equal to the total observations in the test data set. So in this case, for example, you have 12 plus 3, 15 plus 10, 25. So that means we have 25 observations in our test data set. Okay, so these are the 2 things you need to first explain, that the total sum in this matrix, the numbers, is equal to the size of the test data set, and the diagonal values indicate the accuracy. So by looking at it, you can probably have an idea about, is this an accurate model? Is the model being accurate? If they're all spread out equally in all these 4 boxes, that means probably the accuracy is not very good. Okay. Now, how do you calculate the accuracy itself, right? How do you calculate the accuracy itself? So it is a very simple mathematical calculation. You take sum of the diagonals, right? So in this case, it is 9 plus 12, 21, and divide it by the total. So in this case, what will it be? Let me take a pen. So your diagonal values is equal to, if I say D is equal to 12 plus 9, so that is 21, right? And the total data set is equal to, right, we just calculated, it is 25. So what is your accuracy? It is 21 by, so your accuracy is equal to 21 by 25. And this turns out to be about 85%. Right? So this is 85%. So that is our accuracy. Okay. So this is the way you need to explain, draw a diagram, give an example, and maybe it may be a good idea to be prepared with an example so that it becomes easy for you. You don't have to calculate those numbers on the fly, right? So a couple of hints are that you take some numbers which add up to 100. That is always a good idea, so you don't have to really do this complex calculations. So the total value will be 100, and then diagonal values you divide. Once you find the diagonal values, that is equal to your percentage. Okay. All right. So the next question can be a related question about false positive and false negative. So what is false positive and what is false negative? Now, once again, the best way to explain this is using a piece of paper and pen. Otherwise, it will be pretty difficult to explain this. So we use the same example of the confusion matrix, and we can explain that. So a confusion matrix looks somewhat like this, and when we just take looks somewhat like this, and we continue with the previous example where this is the actual value, this is the predicted value, and in the actual value we have 12 plus 1, 13 yeses, and 3 plus 9, 12 no's, and the predicted values, there are 12 plus 3, 15 yeses, and 1 plus 9, 10 no's. Okay. Now, in this particular case, which is the false positive. What is a false positive? First of all, the second word, which is positive, okay, is referring to the predicted value. So that means the system has predicted it as a positive, but the real value, so this is what the false comes from, but the real value is not positive. Okay, that is the way you should understand this term, false positive or even false negative. So false positive, so positive is what your system has predicted. So where is that system predicted? This is the one. Positive is what? Yes. So you basically consider this row. Okay, now if you consider this row, so this is all positive values. This entire row is positive values. Okay, now the false positive is the one where the actual value is negative. Predicted value is positive, but the actual value is negative. So this is a false positive, right? And here is a true positive. So the predicted value is positive and the actual value is also positive. Okay, I hope this is making sense. Now let's take a look at what is false negative. False negative. So negative is the second term. That means that is the predicted value that we need to look for. So which are the predicted negative values? This row corresponds to predicted negative values. All right. So this row corresponds to predicted negative values. And what they are asking for? False. So this is the row for predicted negative values and the actual value is this one, right? This is predicted negative and the actual value is also negative. Therefore, this is a true negative. So the false negative is this one. Predicted is negative, but actual is positive, right? So this is the false negative. So this is the way to explain and this is the way to look at false positive and false negative. Same way, there can be true positive and true negative as well. So again, positive, the second term you will need to use to identify the predicted row, right? So if we say true positive, we need to take for the predicted part. So predicted positive is here. Okay, and then the first term is for the actual. So true positive. So true in case of actual is yes, right? So true positive is this one. Okay, and then in case of actual, the negative. Now we are talking about, let's say, true negative. True negative. Negative is this one and the true comes from here. So this is true negative. Right? 9 is true negative. The actual value is also negative and the predicted value is also negative. Okay, so that is the way you need to explain this, the terms false positive, false negative, and true positive, true negative. Then you might have a question like, what are the steps involved in the machine learning process, or what are the 3 steps in the process of developing a machine learning model, right? So it is around the methodology that is applied. So basically, the way you can probably answer in your own words, but the way the model development of the machine learning model happens is like this. So first of all, you try to understand the problem and try to figure out whether it is a classification problem or a regression problem. Based on that, you select a few algorithms and then you start the process of training these models. Okay, so you can either do that, or you can, after due diligence, you can probably decide that there is one particular algorithm which is most suitable. Usually it happens through trial and error process, but at some point you will decide that, okay, this is the model we are going to use. Okay, so in that case, we have the model, algorithm and the model decided, and then you need to do the process of training the model and testing the model. And this is where, if it is supervised learning, you split your data, the labeled data, into training data set and test data set. And you use the training data set to train your model. And then you use the test data set to check the accuracy, whether it is working fine or not. So you test the model before you actually put it into production, right? So once you test the model, you're satisfied it's working fine, then you go to the next level, which is putting it for production. And then in production, obviously new data will come and the inference happens. So the model is readily available, and only thing that happens is new data comes and the model predicts the values, whether it is regression or classification. Now, so this can be an iterative process. So it is not a straightforward process where you do the training, do the testing, and then you move it to production. No. So during the training and test process, there may be a situation where, because of either overfitting or things like that, the test doesn't go through, which means that you need to put that back into the training process. So that can can be an iterative process. Not only that, even if the training and test goes through properly and you deploy the model in production, there can be a situation that the data that actually comes, real data that comes with that, this model is failing. So in which case you may have to once again go back to the drawing board, or initially it will be working fine, but over a period of time, maybe due to the change in the nature of the data, once again the accuracy will deteriorate. So that is again a recursive process. So once in a while you need to keep checking whether the model is working fine or not, and if required you need to tweak it and modify it and so on and so forth. So net, this is a continuous process of tweaking the model and testing it and making sure it is up to date. Then you might have question around deep learning. So because deep learning is now associated with AI, artificial intelligence and so on, so it can be as simple as what is deep learning. So I think the best way to respond to this could be deep learning is a part of machine learning. And then obviously the question would be, then what is the difference, right? So deep learning, you need to mention there are two key parts that interviewer will be looking for when you are defining deep learning. So first is, of course, deep learning is a subset of machine learning. So machine learning is still the bigger, let's say, scope, and deep learning is one part of it. So then what exactly is the difference? Deep learning is primarily when we are implementing these our algorithms, or when we are using neural networks for doing our training and classification and regression and all that, right? So when we use neural network, then it is considered as deep learning. And the term deep comes from the fact that you can have several layers of neural networks, and these are called deep neural networks, and therefore the term deep, deep learning. The other difference between machine learning and deep learning, which the interviewer may be wanting to hear, is that in case of machine learning, the feature engineering is done manually. What do we mean by feature engineering? Basically, when we are trying to train our model, we have our training data, right? So we have our training labeled data, and this data has several, let's say if it is a regular table, it has several columns. Now each of these columns actually has information about a feature, right? So if we are trying to predict height, weight, and so on and so forth, so these are all features of human beings. Let's say we have census data and we have all this. So those are the features. Now there may be probably 50 or 100, in some cases there may be 100 such features. Now all of them do not contribute to our model, right? So we as a data scientist, we have to decide whether we should take all of them, all the features, or we should throw away some of them, because again, if we take all of them, number one, of course, your accuracy will probably get affected, but also there is a computational part. So if you have so many features and then you have so much data, it becomes very tricky. So in case of machine learning, we manually take care of identifying the features that do not contribute to the learning process, and thereby we eliminate those features and so on, right? So this is known as feature engineering, and in machine learning we do that manually. Whereas in deep learning, where we use neural networks, the model will automatically determine which features to use and which to not use, and therefore feature engineering is also done automatically. So this is an explanation. These are two key things probably will add value to your response. All right, so the next question is, what is the difference between, or what are the differences between machine learning and deep learning? So here, this is a quick comparison table between machine learning and deep learning. And in machine learning enables machines to take decisions on their own based on past data. So here we are talking primarily of supervised learning. And it needs only a small amount of data for training, and then works well on low-end systems, so you don't need large machines. And most features need to be identified in advance and manually coded. So basically the feature engineering part is done manually, and the problem is divided into parts and solved individually and then combined. So that is about the machine learning part. In deep learning basically enables machines to take decisions with the help of artificial neural networks. So here in deep learning we use neural networks. So that is the key differentiator between machine learning and deep learning. And usually deep learning involves a large amount of data, and therefore the training also requires, usually the training process requires high-end machines because it needs a lot of computing power. And the machine learning features the feature engineering is done automatically. So the neural networks takes care of doing the feature engineering as well. And in case of deep learning, therefore, it is said that the problem is handled end to end. So this is a quick comparison between machine learning and deep learning in case you have that kind of a question. Then you might get a question around the uses of machine learning or some real life applications of machine learning in modern business. The question may be worded in different ways, but the meaning is how exactly is machine learning used, or actually supervised machine learning. It could be a very specific question around supervised machine learning. So this is like give examples of supervised machine learning, use of supervised machine learning in modern business. So that could be the next question. So there are quite a few examples or quite a few use cases, if you will, for supervised machine learning. The very common one is email spam detection. So you want to train your application or your system to detect between spam and non-spam. So this is a very common business application of supervised machine learning. So how does this work? The way it works is that you obviously have historical data of your emails, and they are categorized as spam and not spam. So that is what is the labeled information. And then you feed this information or all these emails as an input to your model, right? And the model will then get trained to detect which of the emails are to detect which is spam and which is not spam. So that is the training process. And this is supervised machine learning because you have labeled data. You already have emails which are tagged as spam or not spam. And then you use that to train your model, right? So this is one example. Now, there are a few industry-specific applications for supervised machine learning. One of the very common ones is in healthcare diagnostics. In healthcare diagnostics, you have these images and you want to train models to detect whether from a particular image, whether it can find out if the person is sick or not, whether a person has cancer or not. Right? So this is a very good example of supervised machine learning. Here, the way it works is that existing images, it could be X-ray images, it could be MRI or any of these images are available and they are tagged saying that, okay, this X-ray image is defective or the person has an illness, or it could be cancer, whichever illness, right? So it is tagged as defective or clear or good image and defective image, something like that. So we come up with a binary, or it could be multi-class as well, saying that this is defective to 10%, this is 25%, and so on. But let's keep it simple. You can give an example of just a binary classification, that would be good enough. So you can say that in healthcare diagnostics, using image, we need to detect whether a person is ill or whether a person is having cancer or not. So here, the way it works is you feed labeled images and you allow the model to learn from that, so that when new image is fed, it will be able to predict whether this person is having that illness or not, having cancer or not, right? So I think this would be a very good example for supervised machine learning in modern business. All right, then we can have a question like, so we've been talking about supervised and unsupervised, and so there can be a question around semi-supervised machine learning. So what is semi-supervised machine learning? Now, semi-supervised learning, as the name suggests, it falls between supervised learning and unsupervised learning, but for all practical purposes, it is considered as a part of supervised learning. And the reason this has come into existence is that in supervised learning, you need labeled data. So all your data for training your model has to be labeled. Now, this is a big problem in many industries or under many situations. Getting the labeled data is not that easy because there's a lot of effort in labeling this data. Let's take an example of the diagnostic images. We can just let's say take X-ray images. Now there are actually millions of X-ray images available all over the world, but the problem is they are not labeled. So their images are there, but whether it is defective or whether it is good, that information is not available along with it, right, in a form that it can be used by a machine, which means that somebody has to take a look at these images, and usually it should be like a doctor, and then say that, okay, yes, this image is clean and this image is cancerous and so on and so forth. Now that is a huge effort by itself. So this is where semi-supervised learning comes into play. So what happens is there is a large amount of data, maybe a part of it is labeled. Then we try some techniques to label the remaining part of the data so that we get completely labeled data, and then we train our model. So I know this is a little long winding explanation, but unfortunately there is no quick and easy definition for semi-supervised machine learning. This is the only way probably to explain this concept. We may have another question as what are unsupervised machine learning techniques, or what are some of the techniques used for performing unsupervised machine learning? So it can be worded in different ways. So how do we answer this question? So unsupervised learning, you can say that there are two types, clustering and association. And clustering is a technique where similar objects are put together. And there are different ways of finding similar objects. So their characteristics can be measured, and if they have, in most of the characteristics, if they are similar, then they can be put together. This is clustering. Then association, I think the best way to explain association is with an example. In case of association, you try to find out how the items are linked to each other. So for example, if somebody bought maybe a laptop, the person has also purchased a mouse. So this is more in an e-commerce scenario, for example. So you can give this as an example. So people who are buying laptops are also buying the mouse. So that means there is an association between laptops and mouse. Or maybe people who are buying bread are also buying butter. So that is a association that can be created. So this is unsupervised learning, one of the techniques. Okay. All right, then we have very fundamental question. What is the difference between supervised and unsupervised machine learning? So machine learning, these are the two main types of machine learning, supervised and unsupervised. And in case of supervised, and again here, probably the keyword that the person may be wanting to hear is labeled data. Now, very often people say, we have historical data, and if we run it, it is supervised, and if we don't have historical data, yes. But you may have historical data, but if it is not labeled, then you cannot use it for supervised learning. So it's very key to understand that we put in that keyword labeled. Okay. So when we have labeled data for training our model, then we can use supervised learning. And if we do not have labeled data, then we use unsupervised learning. And there are different algorithms available to perform both of these types of trainings. So there can be another question, a little bit more theoretical and conceptual in nature. This is about inductive machine learning and deductive machine learning. So the question can be, what is the difference between inductive machine learning and deductive machine learning, or somewhat in that manner, so that the exact phrase or exact question can vary. They can ask for examples and things like that, but that could be the question. So let's first understand what is inductive and deductive training. Inductive training is induced by somebody, and you can illustrate that with a small example. I think that always helps. So whenever you're doing some explanation, try as much as possible, as I said, to give examples from your work experience or give some analogies, and that will also help a lot in explaining as well, and for the interviewer also to understand. So here we'll take an example, or rather we will use an analogy. So inductive training is when we induce some knowledge or the learning process into a person without the person actually experiencing it. Okay, what can be an example? So we can probably tell the person or show a person a video that fire can burn his finger, or fire can cause damage. So what is happening here? This person has never probably seen a fire or never seen anything getting damaged by fire. But just because he has seen this video, he knows that, okay, fire is dangerous, and if fire can cause damage. Right? So this is inductive learning. Compared to that, what is deductive learning? So here you draw conclusion, or the person draws conclusion out of experience. So we will stick to the analogy. So compared to the showing a video, let's assume a person is allowed to play with fire. Right? And then he figures out that if he puts his finger, it's burning, or if he throws something into the fire, it burns. So he is learning through experience. So this is known as deductive learning. Okay, so you can have applications or models that can be trained using inductive learning or deductive learning. All right, I think probably that explanation will be sufficient. The next question is, are KNN and K-means clustering similar to one another, or are they same? Right, because the letter K is kind of common between them. Okay, so let us take a little while to understand what these two are. One is KNN, another is K-means. KNN stands for K nearest neighbors, and K means, of course, is the clustering mechanism. Now, these two are completely different, except for the letter K being common between them. KNN is completely different. K means clustering is completely different. KNN is a classification process, and therefore it comes under supervised learning, whereas K-means clustering is actually unsupervised. Okay, when you have KNN, when you want to implement KNN, which is basically K nearest neighbors, the value of K is a number. So you can say K is equal to 3. You want to implement KNN with K is equal to 3. So which means that it performs the classification in such a way that, how does it perform the classification? So it will take 3 nearest objects, and that's why it's called nearest neighbor. So basically, based on the distance, it will try to find out its nearest objects that are, let's say, 3 of the nearest objects, and then it will check whether the class they belong to which class, right? So if all 3 belong to one particular class, obviously this new object is also classified as that particular class. But it is possible that they may be from 2 or 3 different classes. Okay, so let's say they are from 2 classes, and then if they are from 2 classes, now usually you take an odd number, you assign an odd number to. So if there are 3 of them and 2 of them belong to one class and then 1 belongs to another class, so this new object is assigned to the class to which the 2 of them belong. Now, the value of K is sometimes tricky. Whether should you use 3, should you use 5, should you use 7? That can be tricky because the ultimate classification can also vary. So it's possible that if you're taking K as 3, the object is probably in one particular class, but if you take K is equal to 5, maybe the object will belong to a different class, because when you're taking 3 of them, probably 2 of them belong to class 1 and 1 belong to class 2. Whereas when you take 5 of them, it is possible that only 2 of them belong to class 1 and 3 of them belong to class 2. So which means that this object will belong to class 2, right? So you see that? So the class allocation can vary depending on the value of K. Now, K-means, on the other hand, is a clustering process, and it is unsupervised, where what it does is the system will basically identify how the objects are, how close the objects are with respect to some of their features. Okay, but the similarity, of course, is the letter K, and in case of K-means also we specify its value, and it could be 3 or 5 or 7. There is no technical limit as such, but it can be any number of clusters that you can create. Okay, so based on the value that you provide, the system will create that many clusters of similar objects. So there is a similarity to that extent that K is a number in both the cases, but actually these two are completely different processes. We have what is known as naive Bayes classifier, and people often get confused thinking that naive Bayes is the name of the person who found this classifier or who developed this classifier, which is not 100% true. Bayes is the name of the person, B-A-Y-E-S is the name of the person, but naive is not the name of the person, right? So naive is basically an English word, and that has been added here because of the nature of this particular classifier. Naive Bayes classifier is a probability based classifier, and it makes some assumptions that presence of one feature of a class is not related to the presence of any other feature of maybe other classes, right? So which is not a very strong or not a very, accurate assumption, because these features can be related and so on. But even if we go with this assumption, this whole algorithm works very well even with this assumption, and that is the good side of it. But the term comes from there, so that is the explanation that you can give. Then there can be question around reinforcement learning. It can be paraphrased in multiple ways. One could be, can you explain how a system can play a game of chess using reinforcement learning? Or it can be any game. So the best way to explain this is again to talk a little bit about what reinforcement learning is about and then elaborate on that to explain the process. So first of all, reinforcement learning has an environment and an agent, and the agent is basically performing some actions in order to achieve a certain goal. And these goals can be anything, either if it is related to game, then the goal could be that you have to score very high, score a high value, high number. Or it could be that your number of lives should be as high as possible. Don't lose lives. So these could be some of them. More advanced examples could be for driving. In the automotive industry, self-driving cars, they actually also make use of reinforcement learning to teach the car how to navigate through the roads and so on and so forth. That is also another example. Now, how does it work? So if the system is basically there is an agent and environment, and every time the agent takes a step or performs a task which is taking it towards the goal, the final goal, let's say to maximize the score or to minimize the number of lives and so on, or minimize the deaths, for example, it is rewarded. And every time it takes a step which goes against that goal, right, contrary or in the reverse direction, it is penalized. Okay, so it is like a carrot and stick system. Now, how do you use this to create a game of chess or to create a system to play a game of chess? Now, the way this works is, and this could probably go back to this AlphaGo example where AlphaGo defeated a human champion. So the way it works is in reinforcement learning, the system is allowed, for example, if in this case we are talking about chess, so we allow the system to first of all watch playing a game of chess. So it could be with a human being or it could be the system itself. There are computer games of chess, right? So either this new learning system has to watch that game or watch a human being play the game, because this is reinforcement learning is pretty much all visual. So when you're teaching the system to play a game, the system will not actually go behind the scenes to understand the logic of your software, of this game or anything like that. It is just visually watching the screen and then it learns. Okay, so reinforcement learning to a large extent works on that. So you need to create a mechanism whereby your model will be able to watch somebody playing the game, and then you allow the system also to start playing the game. So it pretty much starts from scratch. Okay. And as it moves forward, it's right at the beginning, the system really knows nothing about the game of chess. Okay, so initially it is a clean slate. It just starts by observing how you're playing. So it will make some random moves and keep losing badly. But then what happens is over a period of time, so you need to now allow the system, or you need to play with the system, not just 1, 2, 3, 4 or 5 times, but hundreds of times, thousands of times, maybe even hundreds of thousands of times. And that's exactly how AlphaGo has done. It played millions of games between itself and the system, right? So for the game of chess also, you need to do something like that. You need to allow the system to play chess and then learn on its own over a period of repetition. So I think you can probably explain it to this much, to this extent, and it should be sufficient. Now, this is another question which is again somewhat similar, but here the size is not coming into picture. So the question is, how will you know which machine learning algorithm to choose for your classification problem? Now, this is not only classification problem, it could be a regression problem. I would like to generalize this question. So if somebody asks you, how will you choose? How will you know which algorithm to use? The simple answer is there is no way you can decide exactly saying that this is the algorithm I'm going to use. In a variety of situations, there are some guidelines. Like for example, you will obviously, depending on the problem, you can say whether it is a classification problem or a regression problem. And then in that sense, you are kind of restricting yourself to, if it is a classification problem, you can only apply a classification algorithm, right? To that extent, you can probably, let's say, limit the number of algorithms. But now within the classification algorithms, you have decision trees, you have SVM, you have logistic regression. Is it possible to outright say, yes, so for this particular problem, since you have explained this, now this is the exact algorithm that you can use? That is not possible. Okay, so we have to try out a bunch of algorithms, see which one gives us the best performance and best accuracy, and then decide to go with that particular algorithm. So in machine learning, a lot of it happens through trial and error. There is no real possibility that anybody can, just by looking at the problem or understanding the problem, tell you that, okay, in this particular situation, this is exactly the algorithm that you should use. Then the questions may be around application of machine learning, and this question is specifically around how Amazon is able to recommend other things to buy. So this is around recommendation engine. How does it work? How does the recommendation engine work? So this is basically the question is all about. So the recommendation engine again works based on various inputs that are provided. Obviously something like Amazon, a website or e-commerce site like Amazon collects a lot of data around the customer behavior, who is purchasing what. And if somebody is buying a particular thing, they're also buying something else. So this kind of association, right? So this is the unsupervised learning we talked about. They use this to associate and link or relate items. And that is one part of it. So they kind of build association between items, saying that somebody buying this is also buying this. That is one part of it. Then they also profile the users, right? Based on their age, their gender, their geographic location. They will do some profiling, and then when somebody is logging in and when somebody is shopping, kind of the mapping of these two things are done. They try to identify, obviously if you have logged in, then they know who you are and your information is available, like for example your age, maybe your gender, and where you're located, what you purchased earlier, right? So all this is taken, and the recommendation engine basically uses all this information and comes up with recommendations for a particular user. So that is how the recommendation engine works. All right, then the question can be something very basic, like when will you go for classification versus regression, right? When do you do classification instead of regression, or when will you use classification instead of regression? Now, yes, so this is basically going back to the understanding of the basics of classification and regression. So classification is used when you have to identify or categorize things into discrete classes. So the best way to respond to this question is to take up some examples and use it. Otherwise, it can become a little tricky. The question may sound very simple, but explaining it can sometimes be very tricky. In case of regression, we use, of course, there will be some keywords that they will be looking for. So just you need to make sure you use those keywords. One is the discrete values, and other is the continuous values. So for regression, if we are trying to find some continuous values, you use regression. Whereas if you're trying to find some discrete values, you use classification. And then you need to illustrate. What are some of the examples? So classification is like, let's say there are images and you need to put them into classes like cat, dog, elephant, tiger, something like that. So that is a classification problem. Or it can be, that is a multi-class classification problem. It could be binary classification problem, like for example, whether a customer will buy or he will not buy. That is a classification, binary classification. It can be in the weather forecast area. Now, weather forecast is again combination of regression and classification, because on the one hand, you want to predict whether it's going to rain or not. That's a classification problem. That's a binary classification, right? Whether it's going to rain or not rain. However, you also have to predict what is going to be the temperature tomorrow, right? Now, temperature is a continuous value. You can't answer the temperature in a yes or no kind of a response, right? So what will be the temperature tomorrow? So you need to give a number, which can be like 20 degrees, 30 degrees or whatever. Right? So that is where you use regression. One more example is stock price prediction. So that is where again you will use regression. So these are the various examples. So you need to illustrate with examples and make sure you include those keywords like discrete and continuous. So the next question is more about a little bit of a design related question to understand your concepts and things like that. So it is, how will you design a spam filter? So how do you basically design or develop a spam filter? So I think the main thing here is he is looking at probably understanding your concepts in terms of what is the algorithm you will use, or what is your understanding about difference between classification and regression and things like that, right? And the process, of course. course, the methodology and the process. So the best way to go about responding to this is we say that, okay, this is a classification problem because we want to find out whether an email is a spam or not spam so that we can apply the filter accordingly. So first thing is to identify what type of a problem it is. So we have identified that it is a classification. Then the second step may be to find out what kind of algorithm to use. Now, since this is a binary classification problem, logistic regression is a very common algorithm. But however, right, as I said earlier also, we can never say that, okay, for this particular problem, this is exactly the algorithm that we can use. So we can also probably try decision trees or even support vector machines, for example, SVM. So we will kind of list down a few of these algorithms and we will say, okay, we would like to try out these algorithms. And then we go about taking your historical data, which is the labeled data, which are marked. So you will have a bunch of emails, and then you split that into training and test data sets. You use your training data set to train your model or your algorithm that you have used, or rather the model actually. So, and you actually will have three models. Let's say you are trying to test out three algorithms, so you will obviously have three models. So you need to try all three models and test them out as well, see which one gives the best accuracy, and then you decide that you will go with that model. Okay, so training and test will be done, and then you zero in on one particular model, and then you say, okay, this is the model we will use, and then go ahead and implement that or put that in production. So that is the way you design a spam filter. The next question is about random forest. So what is random forest? So this is a very straightforward question. However, the response, you need to be again a little careful. While we all know what is random forest, explaining this can sometimes be tricky. So one thing is, random forest is kind of, in one way, it is an extension of decision trees, because it is basically nothing but you have multiple decision trees, and trees will basically, we will use for doing, if it is classification, mostly it is classification, you will use the trees for classification, and then you use voting for finding the final class. So that is the underlying. But how will you explain this? How will you respond to this? So first thing, obviously, we will say that random forest is one of the algorithms, and the more important thing that you need to, probably the interviewer is waiting to hear, is ensemble learner, right? So this is one type of ensemble learner. What is ensemble learner? Ensemble learner is like a combination of algorithms. So it is a learner which consists of more than one algorithm or more than one maybe models. Okay, so in case of random forest, the algorithm is the same, but instead of using one instance of it, we use multiple instances of it, and we use. So in a way, that is a random forest is an ensemble learner. There are other types of ensemble learners where we have, like, we use different algorithms itself. So you have one maybe logistic regression and a decision tree combined together, and so on and so forth. Or there are other ways, like for example, splitting the data in a certain way, and so on. So that's all about ensemble. We will not go into that. But random forest itself, I think the interviewer will be happy to hear this word ensemble learner. And so then you go and explain how the random forest works. So if the random forest is used for classification, then we use what is known as a voting mechanism. So basically, how does it work? Let's say your random forest consists of 100 trees, okay, and each observation you pass through this forest, and each observation, let's say it is a classification problem, binary classification 0 or 1, and you have 100 trees. Now, if 90 trees say that it is a 0 and 10 of the trees say it is a 1, you take the majority. You may take a vote, and since 90 of them are saying 0, you classify this as 0. Then you take the next observation, and so on. So that is the way random forest works for classification. If it is a regression problem, it's somewhat similar, but only thing is, instead of vote, what we will do is, so in regression, remember what happens? You actually calculate a value. Right? So, for example, you're using regression to predict the temperature, and you have 100 trees, and each tree obviously will probably predict a different value of the temperature. They may be close to each other, but they may not be exactly the same value. So these 100 trees. So how do you now find the actual value, the output for the entire forest, right? So you have outputs of individual trees which are a part of this forest, but then you need to find the final output of the forest itself. So how do you do that? So in case of regression, you take like an average or the mean of all the 100 trees, right? So this is also a way of reducing the error. So maybe if you have only one tree and if that one tree makes a error, it is basically 100% wrong or 100% right? But if you have, on the other hand, if you have a bunch of trees, you are basically mitigating that error, reducing that error. Okay, so that is the way random forest works. So the next question is, considering the long list of machine learning algorithms, how will you decide on which one to use? So once again, here there is no way to outright say that this is the algorithm that we will use for a given data set. This is a very good question, but then the response has to be like, again, there will not be a one size fits all. So we need to, first of all, you can probably shorten the list in terms of by saying, okay, whether it is a classification problem or it is a regression problem. To that extent, you can probably shorten the list because you don't have to use all of them. If it is a classification problem, you only can pick from the classification algorithms, right? So for example, if it is a classification, you cannot use linear regression algorithm there. Or if it is a regression problem, you cannot use SVM, or maybe, no, you can use SVM, but maybe a logistic regression, right? So to that extent, you can probably shorten the list, but still you will not be able to 100% decide on saying that this is the exact algorithm that I'm going to use. So the way to go about is you choose a few algorithms based on what the problem is. You try out your data, you train some models of these algorithms, check which one gives you the lowest error or the highest accuracy, and based on that you choose that particular algorithm. Okay. All right. Then there can be questions around bias and variance. So the question can be, what is bias and variance in machine learning? So you just need to give out a definition for each of these. For example, bias in machine learning, it occurs when the predicted values are far away from the actual value. So that is a bias. Okay. And whereas they are all the values are probably, they are far off, but they are very near to each other though. The predicted values are close to each other, right? While they are far off from the actual value, but they are close to each other. You see the difference? So that is bias. And then the other part is your variance. Now variance is when the predicted values are all over the place, right? So if the variance is high, that means it may be close to the target, but it is kind of very scattered. So the predicted values are not close to each other, right? In case of bias, the predicted values are close to each other, but they are not close to the target. But here they may be close to the target, but they may not be close to each other. So they are a little bit more scattered. So that is what in case of a variance. Okay, then the next question is about, again, related to bias and variance. What is the trade-off between bias and variance? Yes, I think this is an interesting question because these two are heading in different directions. So for example, if you try to minimize the bias, variance will keep going high. And if you try to minimize the variance, bias will keep going high. And there is no way you can minimize both of them. So you need to have a trade-off saying that, okay, this is the level at which I will have my bias and this is the level at which I will have variance. So the trade-off is that pretty much that you decide what is the level you will tolerate for your bias and what is the level you will tolerate for variance, and a combination of these two in such a way that your final results are not way off. And having a trade-off will ensure that the results are consistent, right? So that is basically the output is consistent, and which means that they are close to each other and they are also accurate. That means they are as close to the target as possible, right? So if either of these is high, then one of them will go off the track. Define precision and recall. Now again, here I think it would be best to draw a diagram and take the confusion matrix, and it is very simple. The definition is like a formula. Your precision is true positive by true positive plus false positive, and your recall is true positive by true positive plus false negative. Okay, so that's, you can just show it in a mathematical way. That's pretty much that can be shown. That's the easiest way to define. So the next question can be about decision tree. What is decision tree pruning and why is it? So basically, decision trees are really simple to implement and understand, but one of the drawbacks of decision trees is that it can become highly complicated as it grows. Right? And the rules and the conditions can become very complicated, and this can also lead to overfitting, which is basically that during training you will get 100% accuracy, but when you're doing testing you will get a lot of errors. So that is the reason pruning needs to be done. So the purpose or the reason for doing decision tree pruning is to reduce overfitting or to cut down on overfitting. And what is decision tree pruning? It is basically that you reduce the number of branches, because as you may be aware, a tree consists of the root node, and then there are several internal nodes, and then you have the leaf nodes. Now, if there are too many of these internal nodes, that is when you face the problem of overfitting, and pruning is the process of reducing those internal nodes. Alright, so the next question can be, what is logistic regression? So basically, logistic regression is one of the techniques used for performing classification, especially binary classification. Now, there is something special about logistic regression, and there are a couple of things you need to be careful about. First of all, the name is a little confusing. It is called logistic regression, but it is used for classification. So this can be sometimes confusing. So you need to probably clarify that to the interviewer if it's really, if it is required. And they can also ask this like a trick question, right? So that is one part. Second thing is, the term logistic has nothing to do with the usual logistics that we talk about, but it is derived from log. So that the mathematical derivation involves log, and therefore the name logistic regression. So what is logistic regression and how is it used? So logistic regression is used for binary classification, and the output of a logistic regression is either a 0 or a 1, and it varies. So it's basically, it calculates a probability between 0 and 1, and we can set a threshold that can vary. Typically it is 0.5. So any value above 0.5 is considered as 1, and if the probability is below 0.5, it is considered as 0. So that is the way we calculate the probability, or the system calculates the probability, and based on the threshold it sets a value of 0 or 1, which is like a binary classification, 0 or 1. Okay, then we have a question around k nearest neighbor algorithm. So explain k nearest neighbor algorithm. So first of all, what is a k nearest neighbor algorithm? This is a classification algorithm. So that is the first thing we need to mention. And we also need to mention that the k is a number. It is an integer. And this is variable, and we can define what the value of k should be. It can be 2, 3, 5, 7, and usually it is an odd number. So that is something we need to mention. Technically, it can be even number also, but then typically it would be odd number, and we will see why that is. Okay. So based on that, we need to classify objects. Okay, we need to classify objects. So again, it will be very helpful to draw a diagram. If you're explaining, I think that will be the best way. So draw some diagram like this, and let's say we have 3 clusters or 3 classes existing, and now you want to find for a new item that has come, you want to find out which class this belongs to, right? So you go about, as the name suggests, you go about finding the nearest neighbors, right? The points which are closest to this, and how many of them you will find, that is what is defined by k. Now let's say our initial value of k was 5. Okay? So you will find the 5 nearest data points. So in this case, as it is illustrated, these are the 5 nearest data points. But then all 5 do not belong to the same class or cluster. So there are one belonging to this cluster 1, the second one belonging to this cluster 2, 3 of them belonging to this third cluster. Okay. So how do you decide? That's exactly the reason we should, as much as possible, try to assign an odd number so that it becomes easier to assign this. So in this case, you see that the majority, actually, if there are multiple classes, then you go with the majority. So since 3 of these items belong to this class, we assign, which is basically in this case, the green or the tennis or the third cluster, as I was talking about. right? So we assign it to this third class. So in this case, it is that's how it is decided. Okay, so k nearest neighbors. So first thing is to identify the number of neighbors that are mentioned as k. So in this case, it is k is equal to 5. So we find the 5 nearest points and then find out of these 5 which class has the maximum number in that. Okay, and then the new data point is assigned to that class. Okay, so that's pretty much how k nearest neighbors work.
Thanks for joining Simplilearn's course on machine learning. We hope you enjoyed learning about this powerful technology and its many uses. So if you found this video helpful, do appreciate it with a thumbs up and share with your fellow mates. Thanks for watching.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.